coming to operating systems, it is a systems course, and moreover it has a lot of theory in it. One is theory, another is problem. And in GATE, they mostly ask, so if you want to read some theory about operating systems, there are some good books. One book is coming to the way I teach operating systems. See, most of the theory will be provided. Operating system makes it easy and convenient for us to use the hardware. Without operating system, it is very difficult to use hardware, program, and other ways process. So I'll just differentiate between what these two are. The concept is like this: round robin algorithm. This is the most popular algorithm of all. So again, what is preemptive and what is non-preemptive is same. I have called the fork, and fork has created a new process. Based on this definition, 2 times GATE questions are asked. So it's simple. They have given various options. What is crystal section? See, coming to operating systems, it is a systems course, and moreover it has a lot of theory in it. One is theory, and other is problems. And in GATE, they mostly ask problems, and sometimes they even ask theory also. So if you want to read some theory about operating systems, there are some good books. One book is Galvin, Operating Systems by Galvin, and other book is Tenenbaum. And as William Stallings is also there, but I don't really suggest that you refer it. Galvin, Tenenbaum, and there is one by Dhamdere. Okay, so but the best 2 books are Galvin and Tenenbaum. So if you read these books, almost everything is there. Then I'll tell you, coming to the topics, whenever I teach any particular topic, at that point I'll tell you which textbook to read. Anyway, you need not read any textbooks. In case if you are interested in, if you have more time and if you are interested in learning more, yes, definitely you could go for textbooks, but then first priority should be given to my videos. Okay, and that is about operating systems. And then coming to the way I teach operating systems, see, most of the theory will be provided in the material which I am going to provide you, and whatever theory that is already there in the material, I'll just explain you orally. And if you want, you could just keep on pausing the videos and take the rough notes, or everything will be there in the material which I am going to provide you. Either you completely follow videos or you can read the materials, but then I suggest that you at least watch all the videos once and then read the material. That will be effective, because I will be covering more points in the videos than the mostly handouts. Okay, and then the way I teach it is, I'll take examples and then I'll explain the theory. Okay, so theory, I'll just not focus a lot of time on theory, only the essential parts I'll teach you. And for theory, just for theory, you might have to refer the books, textbooks, in case if you have time. Otherwise, just stick to my material and then videos, right? Yeah. Now see this operating system introduction, and this introduction you can find in every textbook, any textbook. There is nothing special about it, but still I'll just explain you a few points. First one is, operating system is the interface between user and hardware. So we have the hardware. Hardware means the CPU, memory, all these printers, all these are called hardware. Now there is hardware. We have the hardware, right? And then user is somewhere here. If you have to access the hardware directly, then user has to get into a lot of code. He has to write a lot of code even to execute a small function. For example, nowadays you are able to write a small C function using printf, right? If there is no operating system, if you have to directly interact with the hardware, then first of all you should write the program for everything. You cannot call printf, because printf internally makes a system call, right? And for the system call, operating system is going to provide you. Therefore, operating system makes it easy and convenient for us to use the hardware. See, without operating systems, many things, let us say you have to write 10 programs. In every program you should write the code which will enable you to access the hardware first and then give it some commands, right? But then having an operating system, you need not worry about how to interact with the hardware. You can just say what your program should do, and operating system will take those commands, and appropriately operating system will generate the system calls. Okay, what is the system call is? For example, in your program you have written printf, right? And the corresponding functionality of printf is not actually in printf. It is done by the operating system in the system called write, right? So if you don't have operating system, you are supposed to write the entire code which is actually written inside the write. So when many people need the same functionality, same kind of functionality, instead of asking everyone to implement it, operating system is going to provide it at one place, so that users can directly use that functionality and need not bother about their implementation. That is how system calls are going to help. Did you ever think about how write system call or read system call or at least printf is implemented? No, right? We just are guaranteed that you write this command and this action is guaranteed, right? So that kind of functionality is provided by operating system. You need not worry about the internal details. You just focus on your task, and everything else that you want is already provided by operating system. Therefore, it is a kind of interface, which means you need not do a lot of work in order to write a program. Most of the things which are required by this program are already implemented by the operating system, right? And now whenever you want to take any support from operating system, you are supposed to call something called as function call or system call. Okay, so here, okay, there is a difference between function calling and system calling. Anyway, we shall see it later, what is system call and what is functional call, and these things I'll talk about it later. But just remember that without operating system, it is very difficult to use hardware. People tried using it long back, but then every program has to write its own code so that it will interact with the hardware and then give it the commands. So obviously it is going to be a lot of time taking and inefficient. When many people need the same thing, why don't you implement it at one place and call it many times, right? So that is how operating system is going to be an interface. And next one is resource allocator. What is resource allocation is when we have many people sharing the computers, right? Or when we have many programs running simultaneously, we are supposed to allocate CPU to one of them and memory to some of them and printers to some of them. So that is called resource allocation. So how do I allocate one resource to one process? Sometimes some resources are not shareable, right? In that case, what you should do is you should allocate it to one and then take it out and then allocate it to other one. Sometimes resources are shareable, then we can allocate all of them simultaneously. So this resource allocation, resource means anything like CPU or memory or printers or any device or any file, that is resource. And allocation means giving these resources to the processes. And manager, it acts as a manager. Management means bookkeeping in the sense what is the resource allocated to which one and what are the free resources and what is the current capacity and how many people can I service further, everything. That is called management. Managing means they are going to manage the memory. Memory can be managed like how much memory you have, how much is allocated, how much is free. And processes. Process means every program that has to run. For every program there will be a process created, and then this process has to be managed, like what is the state, current state. States and all I'll tell you later. Shortly I'll talk about this process, leave it for now. And now files. So when we have many files, how are you going to see that the file system is consistent, which means even when many processes are accessing the same files, the data present in that should be consistent. And security, yes, security is important because when many people are accessing the same resources, some person will be allocated some resources and other people should not access this, or even at the level of processes also it is same, which means if a process is given some resource, then at that time someone else should not be able to access it, right? Therefore security also should be provided. Okay, and what are the main goals of this operating system is primary goal, which means main goal is convenience. So it is just to make it simple for the users to use it. So if you look at this DOS, disk operating system, convenience is not there, which means you might have to type everything. But if you look at this Macintosh systems, Apple, the convenience, their main focus is on convenience, which means it should be very easy for anyone to use it, right? So mainly operating systems, when you look at this mainframes and supercomputers, they need not go for convenience because people who use those systems are experts. In that case, efficiency will be used. Therefore, on mainframes and supercomputers, our main goal is efficiency. But then operating system is mainly used by the naive users at home computers or personal computers, where the main goal is convenience. So when I am talking about the personal computers, then the main goal is convenience and secondary goal is efficiency. We really don't want our computers to be efficient. I mean, we really don't need them to be efficient. If they could give us efficiency, it is fine. But then our main goal is make it simple to use the computer, because most of the people who use computers these days doesn't know much about hardware and software, right? They are just the end users. Then in that case, the main goal is convenience, secondary goal is efficiency. But in terms of these supercomputers and mainframes, the main goal is efficiency and the secondary goal is convenience, right? And there are various examples of operating systems which are used on various machines. Okay, now let's go to the types of operating systems. So the first operating system is batch operating system, batch OS. So what happened was, long back there used to be only a single computer to which everyone will be given access, and no, long back means in 1970s and 1980s the computers used to be very scarce. Then what happened is, they used to have one single computer which is called mainframe. Then everyone should give their programs to that mainframe, and in a queue they will put them all, and then the computer will pick up one after the other and execute them, and then later at some point of time users will come and pick them. Which means, see this, there used to be only one computer and all the jobs will be provided to this J1, J2, J3 like this, J4 by the users, and then they'll just not wait for the result, they'll just go away, and then after some point of time, after some amount of time, they are going to collect the results. For example, if people have given J1, J2, J3, J4, then computer will take first J1, this operating system, whatever I'm saying, batch operating system, and then finish it and then produce the results and save it at some place. Then the user who has given J1 will come after some time and collect the results and they will leave, right? Similarly, next J2, next J3, next J4, likewise it will be doing it, right? But the problem with this batch operating system was, if the job J1 which has to be serviced is going to take a lot of time, which means the first job is going to take 10 days, then for all these 10 days all the other jobs will starve, right? And second thing is, if the job J1 or any of the jobs require input output, which means assume that this J1, okay, first before going ahead, processes require two types of time. One is CPU time and other is IO time, which means sometimes they want to use the CPU and sometimes they want to use the input output devices like printers, right, scanners and all that. Now when you have CPU and IO times involved in a process, the process which has more CPU requirement will have more CPU time, and the process which has more IO requirement will have more IO time. Now if a job is here if a process requires less CPU time and more IO time, then what happens is, CPU will be executing this job J1. Let us say job J1 is the first process which requires only little amount of CPU time and more IO time. Then CPU will be taking this job J1 for some time, and after that it will push it to the IO device. Fine. And now while J1 is at the IO, CPU should have executed J2, J3, J4, but then according to the rules of batch processing, whoever gives their job first should finish it, then only other jobs will be taken up for processing. Therefore, even if the CPU is idle, even when the job which is selected is doing some IO work, even when CPU should have taken other jobs, it will not do that. That is why the efficiency is less, the throughput is less. So one thing is, there is starvation, and second thing is starvation provided that J1 is going to take a lot of time, and the next one is efficiency is very less, right? And now it is not even interactive also. Interactive means a user cannot submit a job and then wait for the response. For example, if you have some programs which will continuously ask for the user input, for example like press 1 to do this, press 2 to do this, and if you give it to the job processing, then what happens is, if the job which you require to interact, which you want to interact, happens to be, let us say J10, right, then until all these jobs are over, your J10 will never be processed, right? Therefore it is not really useful for interactive applications, right? So what happened is, people they used it, but then long back, currently no one is actually using batch operating system, Yes, they are using it, but really in the supercomputers and then the mainframes. So if you have any supercomputer which is having, like this, what I can tell you is, if you have a supercomputer in a college, and if many people wants to access it, then what they do is they'll get the accounts, and every account, using an account you can submit a job, but then your job is going to sit and wait in the queue, and therefore after all the jobs which are given ahead of you, after all of them are over, then your job will be taken. But then recently there have been modifications done in such a way that I'll talk about it. In the sense, the other things are used here, right? And next one is multi-programming. So multi-programming means it is just an extension to this batch processing. So here, whenever a job is wants IO, whenever it goes to the IO device, right, then CPU can actually take other job and process it. That is called multi-programming. So using multi-programming, CPU will be used efficiently as long as there are jobs which doesn't need any IO. CPU will always be busy. In the sense, if first job requires IO, it will go to the IO device, then it will pick up the second job, and if the second job also turns out to require IO, then the second job will go to the IO device and it will pick up the third job. So using multi-programming, the advantage is you need not actually keep the CPU idle. CPU will be busy all the time, right? So using this, efficiency has been improved, which was not there in the batch OS, right? And next one is multitasking operating system. Multitasking operating system is just an extension to multi-programming, where instead of providing access to one particular job and then finishing it off, multitasking does it. So there is actually a slight problem in the terminology. Some textbooks say what I am teaching you, and some textbooks say completely different thing. In some textbooks, multi-programming and multitasking both are same, and in some textbooks there is a slight difference, right? Anyway, they are not supposed to ask you the difference between these two in GATE, right? So I am following some textbooks in which they have discussed about these two separately. In some they are actually combined, right? But anyway, the difference what is mentioned by some authors is, it seems that multitasking means you could give J1, J2, J3, J4 like this, J1, J2, J3, J4 some processes, then CPU will choose J1 for some time, then again J2, then again J4, then again J5, which means CPU will be multiplexing among all the jobs without even completing anything, right? So that way interactiveness can be improved, which means if a user is waiting for the output to be produced, then user need not wait for a long time. The reason is his process will get a chance periodically, therefore it will be interactive. But earlier, now either you take batch operating system or multi-programming operating system, there is nothing like preemption. Preemption means when a job is already performing well in CPU time, they will not pull it out. But then in multitasking, the CPU will be pulled out using some constraint, and then it will be in a multiplexing order like round robin. We shall discuss about it, but then from now on, let's think that multitasking and multi-programming both are same, because in some textbooks they never talk about multitasking at all, and in some textbooks they combine them, right? So anyway, the main difference between batch operating system and the multiprocessing or multitasking is, in batch operating system there is no interactivity, and in the batch operating system there is starvation, and moreover a starvation is here itself, but then the main problem is CPU will be idle some of the time. Either you use multi-programming or multitasking, the CPU will not be idle. And multi-programming actually with preemption. Preemption means if you could allow the processor to stop a process forcefully and then start the other one, then that is called preemption. So if you have the preemption facility, multi-programming is nothing but multitasking, right? Fine. And from now on, instead of using multitasking term, I'll be using multi-programming, which actually contains even multitasking as well. Now this batch operating system is different and these two are similar, and the next one is called multi-processing. So multi-processing is again different, in the sense, instead of having one CPU, you will have lots of CPUs in the same computer, CPU 1, CPU 2, CPU 3, right? Now the advantage of having these many CPUs is many jobs can be processed simultaneously, which means parallelism is improved in multiprocessing. It is like this. Recently, okay, what is the difference between having multi-computers and multi-processing systems is, in a computer, in a single computer, if you have many CPUs, then that is called multi-processing environment. It is actually similar to having multi-computers, many computers, but then the concept is, this concept is less costly, in the sense you need not buy everything. You have to just buy the CPUs, and everything will combinedly use the memory and the file system, and everything will be shared. Therefore the cost of it is less, but the efficiency is more. At any time, in this case, if you have three processors, three jobs will be, three processors, you have three jobs which are executing parallelly, right? So what is the advantage of multiprocessing is, the throughput can be improved. Throughput means the number of jobs which are going to be finished per unit time. I'll talk about throughput again, but then here the point is, it will be faster in the sense, obviously you can see it, right? If the work is done by three parallelly, it will be fast, right? Fine. And then moreover, reliability is also increased. What is reliability? If one of them fails, the jobs will be scheduled onto the other CPUs. But then if you look at the other computers, other programming environments where you have only one CPU, if one of them fails, you cannot really access the other one, right? And recently, almost every computer is multi-core. Multi-core means, like you might have heard about it, dual core. Dual core means 2 CPUs, quad core 4 CPUs, octa core 8 CPUs, right? Therefore, this multi-processing is a popular environment now. Anyway, multi-processing can be combined with multi-programming, in the sense, even if you have many CPUs, each CPU can be used any way you like. Either you can use it as a batch processing system, or you can use it as a multiprocessing or multitasking system, which means the first CPU can be given many jobs parallelly, and each job can work at its own. It can process each job and then go to the next one, or it can go multiplex, right? Fine. And then there are real-time operating systems which are not really important for our GATE syllabus, for our coming to our GATE exam, but they just it is just worth knowing about them. Real-time means you will be given some jobs, and the jobs will be having some deadlines, and now you are supposed to finish the jobs in those deadlines. That is called real-time. So what is the main difference between others and this one is, here we have strict deadlines. You are supposed to finish the job at that. Otherwise, if you don't finish it, there will be a huge loss incurring, or even if you produce a result after that time, it will completely be useless. For example, in military applications, if you want to drop a missile, that missile has to be dropped exactly with a lot of precision, right? So even if you miss out of a beat, then it is going to be harmful, right? So like that, real-time applications use real-time operating systems where timing is everything, right? So anyway, we don't need it for GATE. So for GATE, the most important part is multi-programming. So which also includes, by multi-programming I mean multitasking as well. So what I mean to say is, there will be a single CPU to which many processes will be scheduled, and all these processes can be executed in any way, either with preemption or without preemption. I'll talk about it shortly, what is with preemption and without preemption. Okay, this is about the introduction to operating system. So in operating system, we have various topics like how is memory managed, and how are process managed. And by process management, and I mean there are various things, like when many processes want to communicate with each other, right? Then we need to synchronize them. That is called synchronization. So we have synchronization, and then we have file management, and then we have security, right? So they are the main important modules you might have to talk about operating system. So we shall discuss everything. So but then this is the brief overview of operating system. Okay, we shall look at the concepts, one by one. So when I'm teaching some concept, maybe you might not understand some of the words which I talk, but once you finish all the entire course, it will be very easy that everything will fall in place. So even if you don't understand anything when I'm teaching it, just keep on watching it, and act as if that video never happened, and just go ahead to the next one. So at some point I'll be talking about the terminology which I used in earlier videos. therefore everything will make sense by the end of the course. So even if you don't understand anything while I'm teaching, keep on going, don't stop watching, right? By the end of the course everything will make sense, even if it doesn't seem to be meaningful earlier. Okay, fine. Let's talk about process management. Before talking about process management, let's see what a process is. What do I really mean by process? There are two words which you must be listening for a long time. One is program and other is process. So I'll just differentiate between what these two are. So whenever you write any C program, it will look like this. For example, if you have written the C program example.c, right? And now this one will be given, this program will be given to the compiler, right? And what will compiler do? Compiler will just convert this high level language, generally your C program will be in the high level language, to a low level language, which is machine level language, which can be executed on the machine, right? So now see, operating system's task is not to take a high level language program and execute it on the machine. Before doing this, you should convert it to the machine level language, which operating system will understand, and then it will directly run on the hardware, right? So now compiler is going to generate something like, assume that a.out. So a.out is a file which contains executable code. Executable code means the machine code, right? So either this one or this one, these two are called programs only, program, right? And now this program is going to reside in the hard disk of your memory, hard disk of the computer, right? So hard disk means the secondary storage. See, I say that I generally use the terms primary memory, which means RAM, and hard disk, which means secondary memory. So secondary memory is generally the hard disk, and everything else is comes under primary memory. So we are mainly using, we even call it as main memory, secondary memory. Main memory is RAM and secondary memory is disk. Now this program will generally reside in the secondary memory, right? And now in order to execute it, operating system will take that program, right, and then put it in the main memory and then start executing it. So when it puts in the main memory, it will create some kind of structure, some data structure. So that data structure is going to look like this, and that is what we call it as a process. The process is something which is created by the operating system in order to execute a program. So before you execute a program, you are supposed to create the process, right? So the relationship between process and program is, you can take of it like this. A process is something which is real, and a program is something which is virtual, right? Or if you want to see this, a process is something which is like this body, and the program is the soul, right? So soul, you cannot actually, it is like a virtual concept, right? But then body, yes, it exists physically. So a process is body and program is soul. You can think of it that way, okay? And now see this. So whenever we want to execute the process, then the operating system will create something like this. It will create a structure like this. This structure will be created in the main memory, right? And your .exe code or executable code, whichever you wanted to execute, will be here, a.out. That is .exe file which you got, right? And above this, in your program, sometimes you have some variables which are called as static variables. Static variables means these variables will be created once, and then they are going to remain forever throughout the lifetime of the process, right? So they are called static variables, and global variables. Global variables are also kind of static variables which have to be given access to everything in the process. Okay, global variables, I'll talk about it later in some other subject, but now understand that these two variables, static as well as global, are supposed to be created once, and they are supposed to be existing forever. So they are going to be there forever, right? And then the remaining space is actually not divided, but then you can think of it like a not strict division, right? Something like this, where you could imagine it this way. In any program will contain a need for dynamic allocation. Dynamic allocation means like heap, right? So malloc, calloc, all these calls. The reason is we don't know what the requirement we might get, therefore we will not declare the data structures unless they are required. So therefore we have to have some space which will be used by the process later at some point of time whenever it is needed. For that reason, heap. So heap will be here, right? And then every process is supposed to contain something called as stack. So what is the advantage of stack? For the recursion calls, right? For the function calling we need stack. Therefore stack will be there. It is also called as function stack. Stack will be there, heap will be there, static variables, global variables, and then the executable code. Now after creating this, CPU will take one by one the lines available in the executable code and then keep on executing them. While executing them, it might sometimes have to refer the static variables which are present in the same program. That is why that will be present in the same process. This entire thing is called process boundaries, right? So everything that is required by this process will be in this, and operating system while executing this particular process should never cross the boundaries of this process, which means anything that you write here should access only this part. You should not write any access to the other part, then you will get segmentation fault in case if you try to access some other part. So this program is completely restricted in such a way that you are supposed to use only the elements present in this part. You are never supposed to go outside and refer something else, right? So now this part is static variables and global variables, and this part is heap, and this part is stack. One important thing about heap and stack is heap will grow upwards and stack will grow downwards. In this sense, they both will not grow upwards. The reason is if I grow both of them upwards, I don't know where to start each one of them, and I don't know, in some programs stack will take more space, and in some programs heap will take more space, and I don't know which one is going to take how much space before executing it. That is why I want to keep my options open. So whichever takes more space will occupy more space in this, and whichever needs less space will actually shrink down, right? That is how it can be taken advantage. It is like this: you are having a book in which from one side you are writing the TOC and other side you are writing the compiler design. Then you need not write TOC from half initial page and compiler from the mid page. You actually write it from the opposite sides, because you don't know which one is going to take more space and which one is going to occupy the complete book after some time, isn't it? Similarly, we don't know which one, therefore this is the kind of implementation we are using. So this entire thing is called a process. So this is the program either this one or this one is the program which will generally reside in the hard disk. And once we try to execute this, then for this particular program this entire thing will be created by the operating system, right? And now this one will be given for execution to the CPU. Now CPU will take each line from here and then refer to the elements here, or use this rough space and then try to finish the execution. So that is how it is done. So this is the body and this is the soul. This is the soul, right? And if it doesn't have any soul, CPU cannot execute it. It is as good as dead man, isn't it? If you don't have any instructions to execute, even if you give that entire structure to CPU, what will CPU do, right? Now, how can you identify process? See, given these many processes in the operating system like this, we have so many people in the world, right? Then how can you identify each one of them? We are going to use something called as identification cards, isn't it? Identification card is going to say, see, this is the ID number, maybe driving ID, and then this is the name, and then this is the age, and this is the status. Everything will be there, right? Similarly, when we have these many processes created in the memory randomly at any point of time, we are supposed to keep track of which process is what and how many processes are there, and what is the current state of the process, what is happening with it, is it running or is it blocked, or what should I do? So in order to identify everything, we are supposed to have some bookkeeping work. It is like this: every process will now be given an identity card, right? Now it is a newborn baby, right? It need not be newborn, it might have taken some time, and now it might have grown up already. Anyway, whenever anything is born, any process is born, operating system is going to give it some ID card, right? Now that ID card is going to look like this. That will contain all these attributes. One attribute is process ID. So process ID means every process will be given some number, right? That is called process ID. Why is it useful is we cannot obviously name a process, right, like how we name the people. So that is why it is a unique number which will be given to a process in a computer. Every process will get a different number, and coming to this process ID, it is not like port number. Port number is universal, everyone maintains the same port number, but here the process ID is actually different in the sense, it depending on the operating system, some operating systems will use 16 bit, some operating systems will use 32 bit, like that. Okay. And next one is program counter. Program counter means while you are executing a process, a program, here the process, you suddenly stopped the process and again you restarted it, then from which point should you actually start the execution? Which means, assume that we have like 10 instructions, I1, I2, I3, so on, I10, and say you stopped the execution after I6. You executed I6 and then after this you stopped the execution and then you removed this process and then you executed some other process and later again you started this process. Then after this instruction, what is the next instruction you are supposed to execute, right? So that is what we wanted. So for that reason we use something called as program counter. Program counter will contain what is the next instruction that has to be executed, right? So that you can keep on executing it without any repetition. That is just to maintain that. Now when we are talking about the context, okay, that PCB is also called as context. Everything about a process is called as context. Generally, what is its state, what is the program counter, general purpose registers, everything is called context. So this context is very important to be saved, so that later when you again schedule the process for running, this context is going to be very, very useful, right? And now let's talk about the states of the process. States of a process means, what I mean by saying states of the process is a process from its creation till its death. Death means the completion, creation till the completion. It will go through various states, and depending on its requirements, it will make the transitions. Sometimes depending on the nature of the process, the transitions will happen, and sometimes depending on the nature of the scheduling algorithm we use. Scheduling algorithm means, I'll tell you about it. We shall see that later, but for now think that either operating system will make a process forcefully change its state, or sometimes a process has its intrinsic characters that which will make a transition. Whatever it is, a process from its creation till the completion, it is going to go through various states. And now let's see what are the states, and later I'll show you what is the relationship between all these states. Okay. And now states of a process. First one is new state. So whenever any process is created, or generally when a process is about to be created, it will be in the secondary memory, and whenever we are going to pick up that process, we can call it as new. So the program which is present in the secondary memory, which is going to be picked up by operating system to create the process, is generally called as a new process, and it will be in the secondary memory. Strictly speaking, it should not be called a process set, it should not be called a new process set, because there it is not very clear, either it is created or about to be created. If it is about to be created, it is still a program. If it is created, it is a process. But anyway, that is standard terminology is, many people call it as new process, even though the program is in the main secondary memory hard disk, and even though we are going to pick it up, for some time we will call it as new process. And after that, ready. So ready state means, from the new, whenever you create a new process, that will be ready to run, right? Then we take all the processes and then put them in the ready state, which are ready to run, right? So whenever you create the process, that will directly enter the ready state. So maybe you can think of new as when the process is in the secondary memory, and you can think of this ready as when the process is in the main memory. Got it? Whenever it is created, it will directly come to the main memory, and now in the main memory there can be many processes which are ready to run, and it is up to you which one you are going to choose and which one are you going to execute. So depending on that, we have various types of multi-programming. See this? Multi-programming, the main meaning of multi-programming is when we have many processes which are ready to run, that is what is called multi-programming. When you have only one process which is ready to run, and that is not called as multi-programming. Okay, multi-programming means we have a choice, we have pool, we have lots of processes from which we could pick any process and we could run it. That is called multi-programming. And normally multi-programming is of two types. So with preemption and without preemption. So one is with preemption. Okay, what is preemption is when a process is still running, when a process is still having some let us say when a process still needs more time to run, at that point, at that particular time, we'll forcibly remove that process and we give the processor to the other process, which means assume that there is CPU and now the process P1 is running on the CPU, but it still needs it, it is not yet completed, but still what we do is we force it to leave, we force it to get out get out from the CPU, and then we try to get a other process to run now, right? So this is called as preemption. So preemption is nothing but we are trying to stop a process forcefully and then put the next process there, right? So this is also called as, with preemption, it is also called as sometimes multitasking. Multitasking means we are having, I told you, right, we are having many processes and we are going to share, right? Or it is also sometimes called as time sharing. Time sharing means we are not running only one process throughout the time, we are sharing the time among various processes, right? And therefore when you have these many processes in the ready state, you could pick any one of them depending on the strategy you are using. Let us say you have picked up a process P1. One thing is you need not, sometimes you will not force the process to leave until it finishes. That is called as without preemption. Without preemption means once you create it, you need not delete it. No, that is not the wrong. That is wrong definition. Without processing means once you give it to the CPU, you will not force it leave the CPU. That is called without preemption. With preemption means once you start it, you could even stop it in the middle and you could get some other process and again later it will resume, right? And for that we need the context to be saved. What is context? That PCB I told you, right? That entire thing is called context. And now. And moreover, when you pull out one process and send the next process, it is also called as context switching. I'll talk about this context switching again when I talk about the scheduling algorithms. For now, let's keep it simple. There is something called as context and we keep on switching it. Okay, what is that? We shall see it later. And now when these many processes are ready to run, right, one of the process has to be chosen and it will be given to the CPU which will run, right? And therefore if you have only one CPU, at any time only one process will be running, isn't it? So even when the process is running, it has to be in the main memory only, but then how many processes will be running at the simultaneously? Only one process if your system is one CPU, if your system has only one CPU. If you have n CPUs, then it is going to run n process simultaneously, right? So anyway, from ready there will be a transition to running, right? And when it is running, sometimes what happens is your process might need to read a file or write a file, which is nothing but it doesn't need anything to be any help from CPU. It just has to simply read or write, right? In that case, what happens is we are going to use a block or wait. Now how does this block or wait will work is, whenever any CPU requires a IO to be performed, then we are going to schedule it, pull it out and then put it in the block state or wait state until it finishes the IO. Once it finishes the IO, we'll again bring it back to the ready state, right? So this will be in the main memory itself, but the difference is it will, from running state, it will suddenly come to the block state, and from block or waiting state, it will again go to the ready state, not to the running state. Okay, anyway, I'll take the state transition diagram. There I'll tell you what is the relationship between all of them. Here it is very difficult for me to explain it, but for now consider that the processes which need some IO to be performed and which doesn't need CPU will actually go to the block state or wait state, and until they finish the whatever action they are doing, that IO, they'll stay there, and once they finish it, they can again come back and ask for the CPU. How they'll get into the ready state. And just that is keep that way. I'll show you the state transition diagram, which will be clear there. Okay, and next one is termination or completion. Okay, so once you are in running state, and once you have completed entire whatever you wanted to do, that job, then you can terminate it. It's like killing, right? So once the purpose is over, then it will be killed, and even its context will be deleted. Context means that PCB, right? So once a process finishes, even that PCB process control block, that will be also deleted, right? Therefore this is going to happen after running state, after everything is over, and every trace about the process will be deleted. Otherwise it is just a wastage of memory to save anything about it. So everything that was allocated for the process will be deallocated at this point, everything, including the process, PCB, and any trace of it. Okay, and next one is suspend or ready. So suspend ready means it is suspend ready. Suspend ready means sometimes what happens is there will be hundreds of processes in the main memory, and suddenly you would like to use main memory for some other process, which means let us say there are your main memory is able to hold only 10 processes, and all the 10 processes are there, and suddenly a new process came into existence and its priority is very high compared to all these 10 processes. Then we should definitely move one of the process in the ready to the backup. Backup means that secondary memory, and then make the room for the new one, right? So whenever this space is not sufficient, the main memory, and whenever we want to accommodate more important process, we just move the unimportant process to the out of your memory. And how do you decide that some process is unimportant? That is actually tricky here, in the sense the scheduling algorithms will decide it. I'll tell you about it. There is something called a scheduler which will decide which one is important and which one is not important. But anyway, once we know that some particular process is unimportant compared to the others, we just pull it out and throw it away, throw it into the secondary memory. Therefore, this particular suspend ready, or the set of states which were initially in the ready state, and now because of the lack of resources, mainly main memory, we are throwing them outside, right? And they will go and sit in the secondary memory until the resources again gets available. Once the resources get available, they can again come back. And next one is suspend wait or suspend block. It is also same as the suspend ready, but instead of suspending the processes which are ready, it is better that you suspend the processes which are blocked if you could make some room. The reason is already they are blocked and they are not using any CPU, so just move them to hard disk just for the time being, which means they are waiting for some IO to finish. Anyway, they are just waiting, so let them wait in the secondary memory. It is like this. See, assume that we have a conference room, and the conference room is very small, and then outside it there is lawn. Then what we do is we make as many people as possible to sit in the conference room. And now let us say suddenly an important guest has arrived and he has to be given the room. Then what we do is we ask someone to go and wait outside, isn't it? So it is better that when you ask someone to go and wait outside, you always choose someone who is sleeping, right? So waiting or block process is nothing but a person who is sleeping. He is useless, right? And if someone is active and if he is ready to ask some questions, when someone is active and if he is ready to learn or if he is active, then it is better you don't send him outside. So send some people who are sleeping outside so that you can accommodate more important people. Similarly here also, if a process is waiting for IO rather than CPU, then anyway it is waiting, it is useless. Therefore let it go out, right? So if you suspend or if you send a process which is in the block or wait state into the secondary memory, then it is called suspend or wait. Here also it is going to be secondary memory, right? Anyway, from these two states, once our resources become available, then we are going to get them back. One interesting thing is, see, if a process is in suspend wait and suddenly it has finished its IO, then it could make a transition to suspend ready. What is the difference? Okay, if a process is in suspend wait and when it could be brought back to main memory, it will come back to block or wait. And if a process is in suspend ready and if the memory is available, then it will come back to ready. But when the process is in the secondary memory waiting for the IO and its IO has been finished, then it could make a transition to suspend ready in the secondary memory itself, and later when the memory becomes available, it can directly come to the ready state. Anyway, I am going to show you all these transitions in a state diagram. Just wait for some time. Okay. And now coming to the operations on processes, we have various operations. One is creation. So first we create it. So once we create it, then the process will be ready and it will be in the main memory. And then we schedule it, which means when we have many processes in the ready queue, we are going to pick one of them, that is called scheduling, and give it to the CPU. Schedule it and then execute it. Executing means once we give it to the CPU, it will start executing. And then killing or delete. So killing or delete means whenever you are done with your work, you could simply kill it, right? I mean, whenever the process is over. So these are all the operations that the operating system will perform on a process. So fine, we shall see state diagram and we shall see other concepts which will make all this. See, right now what I am trying to do is I am just trying to put the dots here and there, and later I will connect all the dots, and once I connect them, it will all completely make sense. Till then there might be some doubt on your mind about what is this, what is that, but just keep watching it. Okay, don't give up, keep watching. Now let's see this state diagram. I already told you what are the states, and now let's see the relationship, which means what are the events that will trigger the transition from one state to the other state. So now if you look at the state diagram, first thing is you will be in the new state. New state means the process is not created, the process is about to be created. So new state is in the secondary memory, which means here you can call that process as a program itself, right? And once it is created, it will move to the ready state. So ready means it is ready to run, that is the meaning of it. And at any time, many number of processes can be in the ready. Now one thing you should decide is how many states can be in the ready at any time, right? That is a good decision, that is the actual decision you should take. The reason is, depending on the resources you have, you can get those many processes. Let us say you have 1000 processes available in the hard disk which want to run, but then the programs, right? But then you cannot run all the programs you cannot bring all of them into the main memory at the same time. Therefore, depending on your resources, you can decide about how many processes can be in the ready state at any time, right? So generally this depends on the memory. And once you are in ready state, you can schedule the process. Scheduling or dispatch means we are picking it up and then we are sending it, right? So and then run it. So scheduling it and running it is nothing but giving it to the CPU. So once the CPU takes the process, it will execute it, and if the process is completed, which means completion, then it will terminate. So the final state is termination. If everything happens smoothly, right, then this is the best thing that could happen. See this? New state, ready state, run state, and termination. Therefore, minimum number of states a process can go through is actually from here to here. How much? 4. I mean, at least you need to take 4 states. See, if this is the state diagram given, then the minimum state number of states which are required to go from here to here is 4. It is like this. Maybe you can compare it to a DFA where you have transitions. Then what is the smallest string that could be accepted by the DFA, right? Similarly, how many minimum number of states are required to go from ready state to termination state? Fine. And now once you are in ready state, there are various things that could happen. Okay, let's say you are in running state, which means you are given a process for running. Then first thing is, the process might contain, I told you that a process might contain 2 times. One is CPU time and other is IO time. If a process is having lot of CPU time to be performed, then it is called a CPU bound process. If it is having a lot of IO to perform, that is called IO bound process, right? There are 2 categories, CPU and IO. Now if you are in this run state, watch it, if you are in this run state and suddenly you get a IO request, which means a process is actually suddenly asking for a IO, right, input output. Then if you ask for it, then you are going to send it to the wait or block state, which means the process should not be again scheduled immediately. Why you should be sent to a different state, why not to the ready state is, if it is asking for IO, if you again put it back in the ready state, then again what happens is, you might again schedule it for running, and again it will ask for IO. Therefore, unless it will not, until its entire IO is over, and until you are sure that once you get it back to the running state, it will run smoothly without asking for IO, let it be there, right? So don't get it back. It is like this. You are just making sure that a process which will come to the running state will always be ready to run. It should not ask for IO at all. If you should make that happen, then let it go and wait in some other state until it finishes its IO, and next time again when it comes to the running state, it will run only on CPU without asking for IO. So that is why we are going to have this wait state. Got it? Wait or block. Now once the IO request is over, which means it has requested for this IO and IO is completed, maybe it wants to print something once its printing is over, or maybe it wants to read something. Once that reading is over, then we can again put it back to ready, because now it can again go to the CPU and run without any disturbance, without asking for any IO. And now once you are in running state, you could again go back to the ready state because of various parameters. One parameter is priority. What does it mean is, maybe you must be having a process which is running in the CPU, and suddenly a very high important process came into the picture. Then what you should do, you should stop it and then send it back to ready and schedule the high important process, right? That is one thing, which means priority will cause a process to get preempted. So because of this transition, this entire thing will be multi-program. Okay, is it multi-programming? Yes. The reason is there can be many processes in the ready state. That is why it is multi-programming. And now look at this transition. Because of this transition, we are stopping a process while it is running and sending it back to ready. Even if it is ready, I am not running it. I am again sending it back to wait in the ready state, right? Because of this transition, it is called preemption. It is multitasking or multi-programming with preemption, right? And what are the other events that will cause the preemption is, one is priority and other is time quantum. So whenever you decide that I give only this particular amount of time to each one, and after that time I want to keep on changing the process, you might decide about it, right? So whenever the time quantum expires, or whenever you need more priority, or whenever you get a process with higher priority, you are again going to send it back to the ready. Therefore this transition indicates preemption. Got it? Okay, so now these are the basically, these 5 are the basic states which are required in almost every operating system, which means it will be in the new, ready, running, termination and wait or block. And the other one is, depending on your requirement, resources, sometimes your resources will be too scarce that you want to suspend some process for some time, right? So for that reason, we are going to have one more state called as suspend wait and suspend ready. So what is the significance of this process? This state is, I told you, so whenever we have a process, some process in the main memory, and if you don't have memory for the new process, but the new process is very important that you should make a room for it, then we just push some of the processes outside to the secondary memory, then that is called as suspend ready. If the pushing is occurring from the ready state, then they will go to suspend ready. Similarly, if the pushing is occurring from the wait or block state, then they will go to the suspend wait. Either these two, suspend wait or suspend ready, these two are in the secondary memory. See, this is in the secondary memory, main memory that is not required, and wait or block is in the main memory, and these two are in secondary memory, right? And now once you decide that it has to be suspended, they will go there. And once you decide that, okay, I have the memory, I have the resources, then again you can resume, which means they will again come back. Similarly, once you decide that you should suspend it, they will be in the suspend state, and once you resume it, they will come back. And look at the relationship between these two states. Assume that you have pushed out a memory, process from main memory to secondary memory while it is doing some IO. One more thing. In order to do an IO, the process need not be in the main memory. It could be in the secondary memory also. Even when you push a process to the secondary memory, the IO which it has initiated will still continue without any interruption. Therefore, without any problem, the IO will continuously keep on happening, right? Therefore, once you are pushing in from here to here a process, that will keep continuing its IO work, and once its IO is over, it is actually ready now, isn't it? That is why we move it from suspend wait to suspend ready, so that next time it will directly come to ready, isn't it? If you let this state, the process be here itself, even after finishing its IO, then once we resume it, it will come to the block or wait state. That is why we just push it here, right? And from here it can directly come to the ready state. Got it? Now if you watch it, there are three kinds of decisions we are taking. One decision is how many processes to create, and once you decide about it, you have to live with it completely. Once you create a process, you should keep it in any of these states and then throw it out without doing, without finishing. You should not do anything, right? Therefore here, whenever you are creating the process, how many processes should you create it, that is a long-term decision, right? And this is taken by long-term scheduler. So first, there are three types of schedulers here. One is long-term scheduler, second is short-term scheduler, third is medium-term scheduler. So long-term scheduler makes the decisions about how many processes should be made. Once it has taken the decision is going to last for a long time. That is why it is called as long-term scheduler, right? And coming to the short-term scheduler, what it means is, now once you have a pool of process available ready for running, then we are going to pick one of them, isn't it? Then that is a short-term decision. The reason is that decision is not going to last forever. Only for that one process it is going to be valid, and once the process completes execution, or once it goes out to the wait block, it is going to be invalid, right? Therefore what is the meaning of this short term is, this decision will not last forever, and short term decision is made here, right? So short term is made by short term scheduler, and it is also called as dispatcher or short term scheduler. And second thing is, whenever your memory is full, you are going to suspend it, right? And either from here or here, right? Either you are going to suspend from here or suspend from here. That suspension decision is going to be made by medium term scheduler, because once you suspend it, it is not going to be there forever, or it is not going to be there for a small amount of time. That is why it is called medium term decision. It is called as medium term scheduler. Okay. Now let's see the parameters of process. These are all the times which are important. So what is arrival time? So whenever any process gets into the ready queue, then that is what we call it as arrival time, which means that is the time at which it is ready to be executed, right? So arrival time, you can think of it like this: the time at which a process enters the ready state is called arrival time. That is also called as ready queue, because all the process are going to wait in the ready queue. And next one is burst time. Burst time means the amount of time that is required by a process, that is CPU time. Okay, you please make a note of it. I'll be just dictating you the amount of time that is required by a process to finish, the amount of CPU time, right? So how much amount of CPU time should you dedicate to this process so that it could get finished? The problem is it would get completed, but the problem is, before running a process, actually saying this time exactly is really very hard. So many of the problems are based on this burst time. Many of the scheduling methods are based on the burst time, but we cannot implement them in reality. The reason is, we will not have anything called as burst time before we start it. Got it? So this is a bit confusing, because we are supposed to say the time required by a process before executing it, which means we are supposed to say how much time does it take to execute a process before even executing it. So it is tricky. And next one is completion time. Completion time is nothing but the time at which the process finishes, the process completes execution. It is going to arrive at some time and it is going to finish at some time. Then what is happening in the middle? It can be either with the CPU, which means it can be present in the running state. See this. Now the process is ready. The process has just entered this ready state, and now there is running state here, right? And then there is termination state here. Okay. Now between these two, which means the time taken by a process to the time at which the process arrives the termination state or the complete state, that finished state, is called completion time. Now if it is ready at this time at some point, and if it is come to finishing at some point, then what is happening in the middle? There are two things that will happen. One thing is it will spend lot of time in the ready queue itself, right, in the ready state, or it will spend some time in the running state. How much time will it spend in the running state? That depends on the burst time, right? Therefore, the entire time can be classified into two types, assuming that we are not involving any IO here. See, getting this IO time will complicate the things. So now the assumption is that a processor needs only the CPU time. Under that assumption, we are going to see all the problems. Okay, so I'm not going to consider anywhere that a process might need IO time. Without IO time, I'm just considering it. Okay, now without IO time means there is no way it is going to be blocked, right? So what happens now? It started at this point and it finished at this point. Then what happened in the meanwhile is, one thing is it will wait for the processor, that is called waiting time, and then it will execute it, that is called burst time, and then it will wait and then it will execute, right? So it need not happen all the time that for some time it waits, for some time it executes. That depends on the scheduling, which means is it preemptive or non-preemptive. I'm just taking a general case, which means a process might spend its time executing or it might spend its time waiting. Therefore, the difference between the arrival time and the completion time is equal to two things, isn't it? Completion time minus arrival time. See, one more thing is completion time and arrival time are points in time, okay? And waiting time and burst time are durations in time, right? So when I take the difference between 2 points in time, then I get the duration, isn't it? So completion time minus arrival time, which means the time at which it arrived and the time at which it completed. Let us say the difference is 1 hour. Then what would that process have done in this 1 hour? You would have done two things. One is either it executes or it is waiting in the ready queue, assuming that there is no blocking state here, right? So under that assumption, under the assumption that we have only new, ready, running and termination, that is where we are doing it, to keep the thing simple. Okay, it is equal to burst time plus waiting time, right? So depending on which you can compute even the other times as well, right? Now turnaround time, this is also called as turnaround time, which means the difference between the arrival time and completion time, the point at which a process has arrived initially and the point at which it completed. The difference is also called as turnaround time. Okay, and waiting time is nothing but out of this entire time, turnaround time, it has executed only for some time, right? And the remaining time it just waited for the CPU, that is called waiting time. So the relationship between waiting time, turnaround time and burst time is, you can say that waiting time equal to turnaround time minus burst time, which means if a process is in the system and it is not doing anything else, then obviously it is waiting, right? So waiting time is nothing but turnaround time minus burst time. It is either going to be in the burst time or in the waiting time. So if I take the difference between turnaround time and then burst time, I get the waiting time. Okay, and next one is response time. Response time is nothing but what is the first time at which the process hits the CPU, which means after it arrives, let us say it arrived here and then it waited in the queue, is called waiting time, and after that some point it is given for the processor to get executed. See, when I write that it is burst time, it doesn't mean that the entire burst time is over. You might get confused here. Whenever I say that it is waiting time, burst time, waiting time, burst time, it doesn't mean that the entire burst time is over. I mean to say that it executed only for some time and again it came back into the ready queue so that it can execute later. In case if this entire burst time is over, why will it ever wait? It will directly go and terminate, isn't it? Okay, now what I'm saying is, see, now a process has arrived here, let us say it is arrival time and this is waiting time for some time, not the entire waiting time, only for some duration, and then it has been taken up for processing at this point, right? So it is the first time a process is getting processed, which means that is the first time it will ever try to interact with the user. That is why it is called as response time. So what is the response time? So the first time at which a process gets scheduled minus arrival time, this is the response time. Got it? I'll show you with examples, it will be clear. Even if you don't understand anything right now, we are going to do hell a lot of problems and everything is going to be very, very clear once all the problems are over. Okay, so just go through this theory. I mean, don't stop watching, keep watching, everything will make sense by the end. Fine. See, CPU scheduling. CPU scheduling is nothing but picking up a process from the ready state, because in the ready state there will be many processes, picking up one of them and then giving it to the CPU. That is called CPU scheduling. And who will do that? The short-term scheduler. The short-term scheduler along with the dispatcher. Sometimes dispatcher is a part of this short-term scheduler, and sometimes both of them can be a different modules. So short-term scheduler, see this, if this is the pool of ready processes, now short-term scheduler will pick one of them and then give it to the CPU, right? So this entire thing is called as scheduling, CPU scheduling. But then there are various things. Sometimes short-term scheduler can limit itself to picking up a process, and then the actual scheduling will be, scheduling means changing the context. The actual context switching will be taken by dispatcher. That is one case, right? So anyway, who will do that is short-term scheduler. That is the module which initiates this, and then where from ready state to running state. And when will it happen is, there are various cases. Whenever a process moves from running to termination, it means that the process which you have given to the CPU has terminated and it does not need CPU anymore. Therefore CPU is free and it can be assigned to some other. It is a natural event, so it happens a lot of times. Whenever you give a process to the CPU, it gets executed, and therefore we can pick up the next one. And the second one is running state to wait state. This is the second one. So running state to wait state means when a process is in running, it might need the IO or some other event, something, either it might need IO or it might need some other resource which is not currently available. Then it is going to wait or block in which it is going to wait for that particular resource. And at that time you can pick one of the process from ready and you can schedule it. And the other one is, the process could go from run to ready. So why do you think that a process will go from run to ready? There are two ways. One is there is something called as timer. So that is also called as quantum time or timer. So every process, if we set it a time that it should only use for that much time and it should leave the CPU, therefore it is going to trigger that timeout event is going to trigger a transition. A process will move from running state to ready state, or depending on priorities also it will happen. So how does it happen because of priorities? See this, whenever a new process now suddenly join the ready queue, and if it is having a higher priority compared to the already existing processes, then this could happen, right? If already existing processes are having a less priority and suddenly a new process got created which is having high priority, then obviously we should pull out the less priority process from the CPU and give the higher priority process. If a process is already higher priority, then how could the lower priority process go to the CPU at the first place? Because that high priority process is not available till then. So whenever it came into availability, whenever it is available in ready queue, then this movement will be triggered, which means till now whatever are present here, among this we have picked up the best one, the highest priority, and we are running it, and suddenly a new priority has joined, a process has joined which is having higher priority than whatever you have picked up. Then we are going to remove it from the CPU, which means we are going to forcefully send it out and then put the new process there. And other one is if a process has done a transition from wait to ready, sometimes what happens is a higher priority process will go and wait for a resource, either for the IO or some resource, and it will wait in the waiting queue and the waiting state, right? Then what happens is, at that point the CPU becomes idle, and therefore you will schedule one of the next process which is having some priority. Then later, if the process which originally was in this waiting queue, that wait state, is now ready to execute, and which is having higher priority, which means, see this, I'll take an example. Let us say this is CPU, and now a process is having priority 10, highest priority, is now executing on the CPU, and suddenly it wants some resource. Therefore it gone to the waiting state. It is waiting state and it is ready state, right? Then what we do is, we take this process, process, and we put it in the waiting state, and then we take some other process and start running it. Let us say the process which got running is priority is 9, which means lower than this. So it is going to run as long as this process 10, the process with priority 10 is not available. But in case if the process with priority 10 now finishes its whatever requirement it has, IO requirement, and if it enters the ready queue, which means if it is now having a priority of let us say 10 and it is available in the ready queue, then definitely this one should be preempted. Preempted means pulled out. This is what happens when sometimes a process with moves from waiting state to ready state. But it does not mean that all the time whenever a process moves from waiting to ready you should actually schedule the CPU. No, that depends on the priority of the process. If it is having higher priority, then it should happen, right? So see this, whenever this one happens we should definitely schedule it, definitely, because CPU is idle, therefore CPU scheduling is required. And whenever this one happens we should definitely schedule it, because again CPU is idle, and here also we should definitely schedule it because CPU is idle, right? But whenever this thing happens, which means when a process is created from new to ready, you need not change the scheduling unless the newly created process is having higher priority. And the next one is wait to ready. So what does it mean? Whenever this example, right? So whenever any process moves from wait to ready, it does not mean that for every moment, every transition, for every process we are going to schedule it. No, we are going to do it only when the process which moved into the ready queue is having higher priority compared to the process which are inside the ready queue. I mean which are already running there. Okay. So this is how the CPU scheduling works. There are various types of scheduling algorithms. We shall look at them, and basically you can classify them as two types. One is preemptive and other is non-preemptive. Okay, we shall see all of them with examples. Now we have many scheduling algorithms, out of which the basic one or this simplest one is first come first serve. So here the model is, we are going to pick up a job. I mean, see, we are going to have, I'll just tell you this, we'll have lots of processes in the ready queue. It is ready. We'll have in this pool of processes, there will be lots of them, and now there is one CPU. My assumption is that there is only one CPU here. All the scheduling algorithms, we are going to use it only one CPU. Then we have to pick one of them and give it to the CPU. Then what is the criteria that you will be looking at? First come first serve. The name itself says that whoever comes first, they will get the first preference. Therefore, depending on the arrival time, we are going to pick a job and then give it. It is very simple and easy to implement also, and it is practical in the sense, even though okay, I'll just tell you what it is. Fine. And now arrival time is used, and then mode is non-preemptive. Non-preemptive means once you choose a job and once you give it to the CPU, we'll finish it. I mean, until it gets finished, we are not going to remove it. And second thing is, here I'm just assuming that every process requires only CPU time without any IO time. They are all CPU time oriented. Therefore, there is no need of using any block state. So a process will be created, it will be in the new state and it will go to the next state, which is ready running state, and then terminate, right? So if you look at the transition for this algorithm, it will look like this. It will be created newly, and then from there it will go to ready, and then from there it will go to running, and then from there it will terminate. So this is the only path that is possible. Now I am assuming that there is no IO time required, which means there is no need of a process going into the block state. And even I am assuming that there is no need of preemption, which means there is no need of these two. Got it? So only one path. Now which one are you going to choose? That depends on the arrival time. Got it? So I'll just take an example and explain you. And now we are going to use something called as Gantt chart. So Gantt chart is used, maybe if you remember it, I have used the Gantt chart even in job sequencing with deadlines. In algorithms, there is a concept called as job sequencing with deadlines. Even there I use the Gantt chart. Okay, let's see this. So these are the processes. This table says that we have 5 processes and the arrival times are like this. Process number 1 arrived at 0, process number 2 arrived at time. Okay, time 0 means what is the meaning of time 0 arrival time? It is not actual time, it is relative time. So using these numbers, the lower number indicates that it is the earliest time. So we are not actually using the real time. I mean, I'm not saying 10:30, 11:30 like that. It is just the relativeness. Relativeness means lower the number, earlier the process, like that. and then I'm going to assume that I start my CPU at time 0, and from there I am going to count the entire schedule, right? And now let's see how does it work. I'm assuming that I'm going to start counting everything from time t equal to 0, that is when I'm going to start it. So at time t equal to 0, what is the first one that has arrived? Arrival time of process number 1 is 0, which means process number 1 has arrived first. Therefore, I will give it for scheduling. Now this is the way the process are getting executed. Now, how much time does P1 require to finish its execution? If you see this, burst time is saying 4, which means after 4 it is going to finish its execution, right? And now at this point I am going to pick the next one. Why? Because you know that whenever a process finishes its execution, then we are supposed to pick up this one more process from ready state, and then we are supposed to schedule it, right? Now after P1 is over, see what is the time now? Time is 4. So by 4 all the others are available. So initially when you start it at time t equal to 0, there is only one process which is P1, and there is no option you have to pick it. Now by the time first one has executed, which means by the time 4 all the remaining processes are in the pool P2, P3, P4, P5. Now among these you have to pick one of them. So P1 is over already, right? So this is over, and next is you have to pick one of them, one of the remaining. What is the criteria? Criteria is again arrival time. In case if two processes have the same arrival time, then pick the process which is having lower process ID, which means if any two processes here show that their arrival time is 1 and 1, then you pick the one which is having the lower number, which means like 2 or something like that. Now what is the next process that has to be picked up? Obviously the arrival time is showing that the next process that has to be picked up is 2, isn't it? Therefore I am going to pick up the next process P2, and it is going to be scheduled at time t equal to 4, and it requires a time of 3 units. Therefore the total units required is 7. By time equal to 7 units, P2 gets finished, right? And then which one do you want to pick up? Obviously P3. How much time does P3 require? P3 require only 1 unit of time. Therefore from 7 to 8 we are going to give it to P3, right? And next one is obviously P1, P2, P3 is over. Next one is P4. So P4, when are you going to start? How much time does P4 require? Only 2 units, which means by 10 it is going to be finished. And what about P5? Arrival time is 4 and it requires 5 units, right? Therefore it is going to be 15. Understood this? So that is how the Gantt chart is prepared. And after preparing the Gantt chart, you could write the completion time. See, there can be various questions possible about it, like what is the turnaround time of each one, what is the completion time, what is the average turnaround time, all this. So I'll just tell you how it is going to be done. In the exam they are going to ask you for only one parameter, but here we shall see everything. Now completion time. Completion time is nothing but at what time the process is going to get completed. Watch it. What about P1? P1 got completed at 4, which means completion time of P1 is 4. P2 got completed at 7. P2 is 7. P3 is 8. P4 is 10. P5 is 15. So this is the times at which each one completed, right? And now we have started with this, and then we executed this much time, and this is the completion time. I told you that the time period between completion and arrival, right, is nothing but the turnaround time, which is nothing but the total amount of time spent by the process in the system is turnaround time. So once you have taken this, I'll just erase it. Now I'm interested in finding out the turnaround time. Turnaround time means the total amount of time that the process has actually spent in the system, right from its arrival till its completion. So the process 1 has arrived here and completed here, which means it has spent in the system a total time of 4 units. What about this? It arrived at P2 arrived at 1 and it completed at 7. Therefore it has spent a total of 6 units, right? And what about this? Arrived at 2 and completed at 8. Therefore it is 6. What about this one? Arrived at 3, completed 10. Therefore turnaround time is 7. What about this one? Arrived at 4 and completed 15. Therefore totally it is 11 units. Therefore this is the turnaround time. And once you know the turnaround time, then you can find out the waiting time. Right? I told you that waiting time is nothing but if a process, if it doesn't have any IO request, then whenever it is in the system, it is going to do only two things. One is it is going to be in the ready state waiting for the CPU. Other is it will be at the CPU in the running state and gets executed. Therefore, it has only two things to do: either wait or finish its burst time. One disadvantage of FCFS is there is something called as convoy effect. Convoy, you know that, right? When when a VIP is going, along with him 20-30 cars will be going with him, right? And what happens? So the time for which he is passing through some junction, for the entire time everyone else will be blocked. That is called as convoy effect, right? Now this convoy effect is severe in this FCFS, in the sense when a process is having a heavy burst time, then all the processes which are after it are going to starve. That is also called as starvation or convoy effect. Now let's see how it is possible here. I'll take the two cases to just study them, to study the effect. It will give you a clear understanding. See, I have three processes and the arrival times are 0, 1, 1 and then 20, 2 and 1 are the burst times, right? So let me schedule them first. Now I am assuming that I am going to start the scheduling at time 0. Which one is the first one that arrived? The first one that arrived is P1 at time 0. Therefore, I have to schedule P1. And what is the time for this? The burst time is 20. So it takes 20 units of time to finish P1 if I start from 0, right? And after that, what is that I could schedule? I could schedule, see, P2 and P3 are having same arrival times, and I told you that the one with the lower process ID is going to get the highest precedence, right? But then there is no relation between convoy effect and then process arriving at the same time. Here it so happened that the process are arriving at same time, but it doesn't have anything to do with the convoy effect. Convoy effect is independent of that, right? Now, so we see that P2 and P3 are arriving at the same time. Therefore, which one should you schedule first? The P2, right? So I am going to schedule P2 first. Fine. And what is the burst time? The burst time for P2 is 2 units. Therefore, the total time is 22. Got it? And then P3 will be scheduled. And what is the burst time for P3? It is 1 unit. Therefore, it is 23. So one thing you should observe is the total schedule, if it is going to start at 0, by the time the schedule ends, this is the schedule begin start time and this is the schedule end time, right? So by the time this total schedule, you can add all this and that should be equal to that, in case if it is starting with 0 and in case if there are no gaps. In case if there are gaps in the middle, it does not hold. Anyway, in this case, the schedule is taking a total time of 23 and even the burst time sum is 23. It happened here because there are no gaps here, which means CPU need not wait for any process because all the processes are available. By the end of one process, next one is available. By the end of second one, next one is available all the time. Now let's write everything. One is, what is completion time? So completion time for P1 is 20, P2 is 22, P3 is 23, right? Then what is turnaround time? So I told you that turnaround time is completion time minus arrival time. How much is it? 20 here, 21 here and 22 here, right? Isn't it? I'm just subtracting this one from this one, completion time minus arrival time. And after finding out this turnaround time, you could find out the waiting time. What is waiting time? Waiting time is turnaround time minus burst time. From this one you have to remove this, so which means 0 here and then 19 here and then 21 here, right? This is the waiting time. So how does this convoy effect is here is, if you find out the average waiting time of every process, average waiting time, you have to take all the waiting times and then you have to divide it with the number of processes, which is 0 plus 19 plus 21 by 3. This is the average waiting time. Now it is nothing but 40 divided by 3. This is the average waiting time for this example, for this schedule. Now let's do the same processes in a different order. If the arrival times are different in such a way that, see this here, what happened is the one with the largest burst time arrived first. That is why P1 got scheduled first. Now if the same three processes are arriving in such a way that the one with the largest burst time has arrived last, which means all the remaining processes have arrived early and this one arrived late. Now in this one what happens is, I'm just drawing the schedule here. So what is the first one that has to be executed? The process with arrival time 0. So we have two choices, P2 and P3. Which one should I choose? Obviously P2, because the one with the lesser process ID is going to take the higher precedence, right? Now if it starts at 0, burst time is going to be 2, isn't it? Then what is the next one? I have only one choice, P3. What is the burst time? 1, therefore it is going to be 3. Understood this? Why P2 and P3 is both are having the least arrival time, and out of them P2 is having the least process ID, that is why P2 first and then P3 next. And obviously the last one is P1, its arrival time is 1, that is why it is the last one, right? And then its burst time is 20, therefore it is going to be 23. Now the same thing, write the completion time and everything. So if I write the completion time, when it is going to complete, P1 is going to complete at 23, and P2 is going to complete at 2, and P3 is going to complete at 3. After that you have to write the turnaround time. So what is turnaround time? Turnaround time is completion time minus arrival time. How much is this? 22 here, 2 here and 3 here. And then what is the waiting time? Waiting time is turnaround time minus burst time, which means these two, right? Then what do we get? 22 minus 20 is 2 here, 0 here, and it is 2 here, right? Isn't it? The waiting time for P2 is 0 because it got scheduled immediately, and the waiting time for P3 is 2 because it arrived at 0 but it got scheduled at 2, and waiting for P3 is 2 because it arrived at 1 and it got scheduled at 3, right? Now in this case, what is the average waiting time? So if I write the average waiting time, so it is 4 by 3. 4 by 3 is the average waiting time, right? So here the average waiting time is 40 by 3. Here the average waiting time is 4 by 3, which means the processes are not waiting for a long time. So whenever you have a big process, the one with the burst time, very high burst time, whenever it arrives early in the initial phase, that is going to take a lot of time for it to finish, so that during at that entire time all the other processes are going to starve. This is called convoy effect. This is the disadvantage of FCFS, and so we are going to solve this problem by scheduling the processes which are having lower burst times initially. That is nothing but shortest job first. We shall see it later. Now let's see this shortest job first. So the name itself says that whichever is having the least burst time, we are going to schedule it first. That is why it is shortest job first, and it is of two variations. One is preemptive and the other one is non-preemptive. And coming to this one, here I am using non-preemptive, which means whenever any job is chosen, it will not stop until it finishes. That is why it is called non-preemptive. And the other one is the preemptive version is there, which is also called as shortest remaining job next. That one we shall see it. Okay, we shall see it later. But now we shall confine ourselves to the non-preemptive version. So what does it mean? Whenever you choose any process, you are going to run it till completion. Otherwise, you are not going to stop. Okay. Now let's see how to do this. First one is like this. First one is I am going to use the Gantt chart starting at 0. So at 0 is any process available. Arrival time is minimum is 1. Therefore, no process is actually available at 0. So until 1. So the first process which will be available will be at time 1. Therefore, from 0 to 1 CPU is idle. Now at time 1 the only process available is P1. Therefore, I am going to take P1 and run it till completion. The reason is it is non-preemptive version, right? So how much time does it take for it to complete? 7 units. Therefore, it is 1 plus 7 is 8. So now the time is 8. By the time 8, all the other processes are available. In case if they are not available, then you have to pick one of the available processes for the scheduling. Always remember this. Whenever you are trying to pick the next one, you see that you pick the next available process for scheduling, right? And now 1 to 8 is over. Therefore, you have to pick one from the available one, right? So from all these, which one is the least one? From all these, the least one is P3. See, P1 is over. Therefore, the least one is P3, which is having a burst time of 1. Therefore, I am going to take P3 next. P3, it is having a burst time of 1. Therefore, it is going to be running till 9, right? Now P3 is over. Then what is the next one with the least burst time, which is 2. Therefore P4, which is having a burst time of 2, therefore the completion time is 11, right? And now I have 3, one is 2 and other is 5. I think I have 2 process. 1, 3, 4 are over, 1, 3, 4 are over. I have 2 and 5, and in these two, which one is having the least burst time? If you watch it, the least burst time is at P2. Therefore I am going to take P2, and whose burst time is 5. Therefore 11 plus 5 is 16, and obviously only one is remaining, and it is already available at 16, right? P5, which is 8. Got it? So 16 plus 8 is how much? 24. Okay. Now if you observe it, even though it is shortest job first, when you have these many jobs, the question might be, given any schedule, given any random combination of process with random possible arrival times, our shortest job will always schedule the shortest job first. It is false. The reason is, it is actually scheduling among the available process the shortest job first, which means when you are standing at time 1, at this point of time 1, only process which is available is P1. That is why it is chosen, but it doesn't mean that P1 is the shortest job, right? Therefore shortest job works in such a way that among the available process it is going to take the shortest job. It doesn't guarantee that whatever is the arrival time, you are always going to start with the least job first. No, right? Therefore in this case it is 7. So what happens is, sometimes even shortest job first will also fall a victim to convoy effect. I mean, it is not mentioned in any of the textbooks, but then I observed this. The reason is, if the longest process, which means the process with the highest burst time, largest burst time, arrives earlier, a bit earlier compared to all others, right, then obviously you are going for this one, right? Therefore shortest job first is also a victim of convoy effect. The reason is, I'll just show this example. I think you understood this. Okay, let's finish it off. Then I'll show you what is the problem with this SJF, shortest job first, and then we can continue with the next algorithms. Okay, one more thing. How do you think that they implemented this? I mean, if you are trying to implement this program, you have to design the algorithm, right? Yes, algorithm works this way. Then what is the data structure which supports this algorithm? If you think about it. Now, among all the available processes, I might have to pick the least one, which means the one with the least burst time. Therefore the min heap is suitable data structure for this. The reason is, in min heap you can find the minimum as well as delete the minimum. Once you delete it, you need not again recheck it, right? So what we do is, as and when any process arrives, we are going to add it to the min heap, and the heap is maintaining the min property based on the burst time. Therefore always the root is going to be the process with the least burst time, and we are always going to remove it and then schedule it and then throw it out, right? That is why min heap is the best data structure here, right? And if you watch it in this one, in the min heap, one process will be added exactly once and deleted exactly once. Therefore for every process there will be one addition and one deletion. If addition is going to take log n time, adding an element in the min heap, and deletion is going to take log n time, right? Then n into 2 into log n. Therefore n log n is the time complexity for this. Okay, don't worry about that. Please refer to that algorithms, min heap, and then come back and watch it. If you didn't understand what I'm saying, you please go to the algorithms, watch it, and then come back. Now let's see about the completion time. When did each one complete? P1 completed at 8, and P2 completed at 16, P3 completed at 9, P4 completed at 11, P5 completed at 24, right? So after that you can find out the turnaround time. Then what is the turnaround time? I told you that turnaround time is completion time minus arrival time, the difference of these two, right? Then what is it? It is 7 here, and it is 14 here, and it is 6 here, and it is 7 here, and it is 19 here, right? It is the turnaround time. And after that you can find out the waiting time. So what is waiting time? I told you that waiting time is turnaround time minus burst time. Anyway, see, you can do all this very easily. These are the simple trivial things, right? Even though I am doing it, you can do it yourself. So for those who are not able to do it, I am just doing it. And 14 minus 5 is 9, 6 minus 1 is 5, 7 is 5, and if there are any mistakes in the numericals, you please use your good judgment. And it is 11. There is nothing like this, right? And then they will ask you what is the average turnaround time and what is the average waiting time. Got it? So that is how you can schedule it. So here also you should be careful that when you are standing at any point, just see what are the process available. Don't directly go and pick up the last, one with the lowest burst time. Right? I'll show you more examples on this also. Then you'll understand it. Now let's see this shortest remaining time first. The name itself says that it is actually, we are going to take the shortest jobs but in a different way, and it is actually based on burst times criteria, and the mode is preemptive, which means even when a process is running, we are going to stop it and then schedule the other one if the situations are like that. Okay, so let's see this example. With example it will be clear and easy to explain. So now watch it. So I am going to start at time t equal to 0, and at that time only one process is available, right? So which is nothing but P1. So at time 0 only P1 is available. I have no other option, therefore I am going to schedule P1. Fine. And now once I schedule P1, here I'll just be careful. I'll not directly completely run it to execution, completion. Then what I do is I stop it at every 1 unit of time and then check in meanwhile, which means during this time, if I got any other process, right? Which means I'm going to stop at this point when the time is 1, and then I'll just check in this time if any process got available and what is the time required for that. So one thing you should be careful is, you have already executed P1 for 1 unit, therefore the processing time here is going to be reduced to 6, right? And now we are going to check the next one. So what is it? It is nothing but I'm checking if any process is available by 1. So by the time we reach 1, the time 1, the process available will be P2. Therefore now I have P1 and P2 both available, and one is having a completion time of 6, remaining time of 6, and other is having a remaining time of 5. So you could choose any one of them, right? But then depending on the shortest burst time, I am supposed to choose P2. Therefore the next one which is chosen is P2, right? And now for P2, what is the burst time? It is actually 5, but then we don't run it to completion. We just run till 1 unit and then check it and then stop and see. So now I have did this P2 for 1. I executed P2 for 1 unit. Therefore the remaining time will be 4. Now the time is 2. By the time 2, when the arrival time, by the time 2, I'll see what are the process available. So one more process got available, which is P3. Now I have P1, P2 and P3 available, and the P3's burst time is 3. Therefore the shortest one among all these is P3. Therefore I'll take P3 and I'll schedule it. For how long? Just for 1 unit, and then I'll wait. So since I executed for 1 unit, therefore what is the time here? So the remaining time is 2, and now the time is 3. So when the time is 3, I have one more process arriving, which is P4. Therefore I have P1, P2, P3, P4, right? And now I am going to choose one of them. So which one is the minimum among P1, P2, P3, P4? P4 is the minimum. So P4 is going to be here, scheduled here. And anyway I'll run it for 1 unit. I don't have any other option. I have to run it for 1 minute only, because the burst time is 1 unit, and then stop it. Anyway it is going to be stopped. Now the time is 4, and what are the processes which are available? P1, P2, P3, P4, and then P5, but P4 is over, therefore you need not worry about it. P4 is not there, right? So among this P1, P2, P3, P5, you just check which one is having the least time. So which one is having the least time here? So we have two processes which are having the least remaining time. One is P3 and the other is P5. Yeah, P3 and P5. But you had to pick the one which is having the least arrival time. So which one is having the least arrival time? P3. Therefore you are supposed to pick P3 itself, right? And now P3 has to be run for 1 unit, which means till 5, and then you should stop it and check it. Since you have run P3 for 1 unit, the remaining time will be 1, and now you just check it if any process has arrived. Yes, one more process has arrived whose process ID is P6 and whose time is 1. So I have Now P1, P2, P3, P5, P6 except P4 I have all the process. In all these process you are not supposed to see, once you have all the process available completely, right, then you need not stop for every unit of time. The reason is now it is nothing but the shortest job first. Simple. Why are we stopping here after every unit of time is just to check if a new process with shorter time, shorter burst time has now become available. But once all of them have become available, then once I pick the least burst time, then there is no way after executing the least one for some time someone else will become the least. Why? Because if someone else is least, that would have been picked up earlier, right? Therefore in this case, once all the processes become available, then this algorithm is nothing but shortest job first. The reason is, the algorithm is nothing but you could execute it as if it is non-preemptive version, right? So now you could take the shortest one and you could keep on executing them one by one. So what is the next one that has to be executed? All of them are available. You can pick the least one. Least one is 1 and 1 here, but then the arrival time of P3 is less. Therefore I am going to schedule P3 itself, right? And now what is it? It is 1 unit 6 and it is 0. Therefore P3 is over. And next one will be P6. So P6 will be scheduled. It requires only 1 unit, therefore 7, and therefore it is going to be over. So P6 is over. And now I have 3 processes, P5, P1, P2. Then which one will be picked up first? P5 will be picked up, right? Then what is the time for the P5? It is 2 units, therefore it is 9, right? Yeah, and therefore P5 will be over, which means this will be 0, right? And then which one will be picked up next? The next one that will be picked up is after P5. Only one is okay. P1 and P2 are remaining. Among these two, the shortest one is P2. Yes, P2 will be picked up, whose time will be 9 plus 4, which is 13, right? Yeah, 9 plus 4, which is 13, right? And then the next one which will be picked up is P1, the last one. So this is also 0, and next finally this one will be picked up, which will be run for 6, therefore 19. So P1 takes 19. Got it? So this is how you could implement this shortest remaining time first. So the concept is like this: even though you are picking the best one, the shortest one, at some point, at some time, you just execute it for 1 unit and check if there is any better process available. If any better process is available which is having a burst time less than the remaining time of this process, then preempt it and continue with the other one. And then other one also you stop it and see. So till how long should I stop it? Until all the process become available. Once all the process become available, it will now become the non-preemptive version, which means we are not going to stop any process once we pick the least one. Got it? Now let's see the next algorithm, round robin algorithm. This is the most popular algorithm of all, and many of the operating systems at practice are using it, because one thing is it is going to provide you various advantages like this. First thing is it is practically implementable because it is not depending on burst time, and second thing is it doesn't require lots of data structures like heap and all. Using a queue we can implement it. And then the next thing is the response time, or there is nothing called as starvation here. The reason is okay, I'll tell you how it works. I'll tell you how it works and then we shall analyze it. So round robin works this way. It will take a particular process for execution and it will not execute it till completion, or it will not execute till next process arrives. Nothing like that. Whatever the process it is going to execute it only for some particular amount of time. That is called time quantum. And after executing that process for time quantum, whatever the process is, it will preempt it, and again the next process will get into the execution, and then it will get executed again for the time quantum. So every process will get executed only for small amount of time, which is called as time quantum, right? Therefore no process is going to wait forever for the CPU. So every process is going to get a chance after some amount of time, and every process will keep on getting the chance after some regular amounts of time. Therefore it is having very less starvation problem, and then it is very easy to implement, as I said. Now let's see the algorithm, and then I'll take an example and I'll explain you. Even if you don't understand anything here when I'm teaching it, don't worry, example will make it really clear, and I'll solve lots of examples on this. Watch it. Now initially you will be in the ready state, and then we pick a process, we select a process. After selecting a process, we check this one, whether the burst time of the process is less than the time quantum required. So what is time quantum? That is the fixed amount of time we fixed, so that any process that we pick up will be executed only for that much amount of time. Now it is like every process will be given this much time, that is called time quantum. And now I'm saying that if burst time is less than time quantum, what does it mean? The process does not need this much amount of time which you are planning to give. You are planning to give TQ, time quantum, but then process doesn't require really this much amount of time. Then what you could do is, you need not give it so much time, right? Then we will give it only the time which is required. It is like this, how can I say it? See, okay, I think you understood it, right? Okay, fine. So what I mean to say is, if you fixed up the time quantum, which means if you are willing to give 10 seconds, but then the process totally needs only 5 seconds, then why give it 10 seconds, right? That is the condition. So if the process requires less time than what you are willing to give it, then what it will do is, it will execute till completion. In other case, if the process requires more time than which is allocated for it, then it will execute only for a time quantum amount of time. And after executing it, we shall check whether the process execution is completed. So process exe means execution completes. Since I don't have space below this, that is why I am writing it. I have written the diamond shape like this. It is not an arrow, it is diamond only. Diamond is a condition checking. So after running a process for time quantum, we are going to check whether the process is completed. In case if the process is completed, then I am going to terminate, right? So otherwise, if the process is not completed, which means if it requires more time, then again it has to go back into the ready state and wait there. I don't know if you really understood this. I'll take an example and this will be very clear. So what you do is, you just note it down, and maybe after taking an example we shall come to this point. I mean, this will be, you can refer to this and it will be clear. Okay, let's see longest job first algorithm. It is just like shortest job first, where we have picked up the shortest jobs and scheduled them first. Here we are going to pick the longest jobs and schedule them. So what is the criteria again? Burst time. And the mode is non-preemptive, which means once we pick up a job, we are going to run it till completion. So otherwise we are not going to take it out, right? And similarly it will have a preemptive version as well. We shall see it too. First let's do this. At time 0, what are the processes that are available? Only one process is available, therefore I don't have any other choice. So I am going to pick up P1. I don't care whether it is the longest or shortest, I have no choice at all, right? And now by the time 3, these 3 become available, right? Isn't it? P2, P3, P4. Now among these remaining, I am going to pick the next longest. What is the longest? P4, right? So if I pick the P4, the next longest among the available, then it is going to run for 8 units. Therefore it is totally 5 units. Therefore it is totally 8 units. And P4 is going to be over, right? And then this one also becomes available by the time 8. So now P1 is over, P4 is over, P1 is over, P4 is over. Then in the remaining jobs, you pick the longest one first. So what is the longest one? P5. P5 is going to run for 6 units. Therefore 6 units is how much? 14 here. Right, P5 is over. Then what is remaining? P2 and P4. Then the next one is P4 is over, right? P4 is over. Okay, this is not over. P2, P3 is not over. Now the remaining jobs are P3 and P2. Therefore the longest one is P3 among them. Therefore P3 is going to run here till 18, and then P2. P2 is going to run for how much? I think it is P1. P1 is over, right? Then it is P2 only. So P2 is going to run for 2 units, then it is 20, right? Okay. Just see this. First one which got scheduled is the only one which is available at that time, which is P1. And then by the time the first one finished, the time is 3. Therefore all these are P1, P2, P3, P4 are available. And among them the longest one is P3, therefore scheduled it, P4, therefore scheduled it. And by the time it finishes, the time is 8. By that time even the P5 is also available, therefore all are available, but then 1 and 4 are over by then. 1 and 4 are over by then. Therefore in the remaining I am taking the longest one, which is nothing but 6 P5, which runs for 6 units, and then P1, P4, P5 are over. P1, P4, P5 are over. In the remaining two, P1 and P2, the longest one is P2, therefore the longest one is P3, therefore P3 is scheduled, and then the next longest one is P2, therefore P2 is scheduled. Got it? Now let's say I want to solve this question. The question is longest remaining time first. Just like shortest remaining time first, it is longest remaining time first. The difference is there we have been taking the shortest jobs, and then we'll stop after executing every job for some time, and then we'll see if there is any new job which is having a shorter burst time. Here we do the same thing. We start with some job and then execute it for some time, and then stop and see whether we got any new process which is having a longest remaining time or longest burst time, and then we could continue it that way. And now there is a chance that see the basic difference is like, maybe you could think of this longest remaining job first as like this. Let us say in your two hands you have two bread, and one bread is longer than the other one. Then maybe you'll bite the longer one first, and then you'll find it out that the other one is now the longer. Then you take it and bite it, and again you'll find out that this one is longer, bite it, find out that this one is longer, bite it, right? So that is how this is going to work. So whenever one process is longer, we are going to take it and then schedule it, but after executing for some time the other one becomes longer, and now we'll take the other one and execute it, and this keeps on happening, right? So now just watch it. So very simple, but then you should be really careful about the details. In the sense, you have to keep track of many things here. One is what are the process available, and what are their burst times, and then what are their arrival times. And one more thing, whenever two processes are having the same burst time, we shall pick the one with the lowest arrival time, right? So even though I start the Gantt chart at 0, I am not going to schedule anything till 1, right? So because 1 is the earliest arrival time, so I am going to take process P1 and run it for 1 unit, which means till 2. Therefore its burst time will now become 1. Now at time t equal to 2, we got one more process available, which is P2, and its burst time is 4. Now among these two burst times, 1 and 4, it is clear that 4 is longer. Therefore I am going to schedule 4 first. So P2 I am going to schedule it and run it for 1 more unit, and now its remaining burst time will become 3. Now the time is 3. Now by the time 3, P3 is also available, and now if you check it, 1, 2, 3, all the 3 processes are available, and the longest one is P3. Therefore P3 gets scheduled, and we shall run it for 1 unit, and now we shall check what is the time and what have arrived. Now the time is 4, and by this time 4, all of them have arrived, and among all of them the longest one is P4. Therefore I am going to schedule the P4 first, right? And I am going to run it for how long? When all the processes have arrived in the shortest job first, shortest remaining time first, what we did is we converted that to shortest job and we have finished it off. But then here the difference is, you cannot convert the algorithm now to longest job first, which means you cannot take this longest job and then finish it off. The reason is, after executing for some time this one, someone else will become longer. See, after executing 3 units of P4, then P3 will become 5 and P4 will become 5. Now there is nothing, now P4 is no longer the longest one, isn't it? Therefore the longest one, there is a tie. So what you should do is run a process until some other process becomes the longest one, right? So that is the method you should do. But anyway, I think it will be directly difficult for you to observe it. So let me go in step by step. It will take some time, but then in exam what you should do is, whenever you are scheduling this 8, you see that how long I should run it, so that some other process will become the longest. If I run it for 3 units, then the next process 5 will become the longest, right? Then I'll take this one and I'll alternate. Okay, fine. Let me do it first. You will understand it. With more examples, I'll make this point clear. Now I'll run it for 1 unit, only 1 unit, so that it will be easy for you to understand. Actually, I should have run it for more units, but then to make the thing simple, I'm running it for 1 unit, P4. Then what happens? This one will become 7. Now which one is the longest? Again P4. Therefore I'll again pick P4 and run it for 1 unit, right? then what is it? It is going to be 6. And again a longer one is P4. Let me pick P4 itself and run it for one more unit, so which is 6, 7 here, and now it will be 5. Interesting. Now watch it. Two processes have the same burst time which are both showing 5. Therefore both are longer. Then which one should I choose? I told you that whenever there is a tie between the burst times, the tie is going to be broken by considering the arrival times. So whichever has arrived early, that one I am going to take it. So there is a tie between P3 and P4 and the early process is P3. So I am going to take P3 here. P3 I am going to schedule it for one time, then this will become 4. Now which one has become longer? P4, right? So I am going to take P4 and schedule it for 1. Okay, it is 8 and it is 9, right? And now this one has become 4, right? And again which one has become longer now? P3, depending on the arrival time. Then I will schedule it for one more time and it is going to be 3, and again P4 becomes longer, so P4 I'll P3 or P4. Now P2 has also come into picture with the same time as P3. Therefore you should run P3, P4 and P2 and then P3 and then P4, and again the same thing will repeat, right? So I have to run P2, P3 and P4, right? So it is going to be 2, 2 and 2 now, isn't it? It will be 12, 13, 14. Again you run them for one more time. Now P2, P3, P4, because all the burst times are same and they are longest and they are all according to the arrival times. P2 is first, that is why P2 is scheduled, then P3, then P4, right? Therefore this one will become 1, 1 and 1, and this one will be 15, 16 and 17. Right? And now if you watch it, all the 4 processes are now having the same burst time, which is 1. Now what you should do is you should schedule them, all of them, one by one. So which one will get top priority? P1 because of arrival time, then P2, then P3, then P4, right? Therefore this is how all the process got completed, right? Then what is the finishing time of this? It is 18, 19, 20 and 21, right? So what is the advantage of this method is no process is going to complete until the longest process also approaches completion, right? It is not like any other algorithm. All the other algorithms, the shorter one, at least the shorter one will be finishing it early, right? But here, even though a process is very short, even though it requires only 2 units of time, it will be postponed till the other process will reach the same time, which means all the process will actually approximately finish at the same time. If you look at the completion time of P1, P2, P3, P4, they are very close, right? Because we are pushing all the process till the end. If a process is having longer burst time, then we are going to complete it first, but we are not going to completely finish it. We are going to just push all the process till the end, so that all of them are going to complete at the same time. Let's see highest response ratio next. The name itself says that we are going to find something called as response ratio, and now whichever process is having the highest of this, we are going to take it. So what is response ratio is waiting time plus service time by service time. So W means waiting time for a process so far, which means whenever you are standing at a point of time and till that point, whatever is the waiting time, that is called waiting time, W here. So W is not the final waiting time. W is what is the waiting time at the point of your computation. So whenever you are computing it, at that point you find out the waiting time, okay? That is W. And then S is service time or the burst time. So S is nothing but the service time. Now for every process, what we do is we find out this factor, and now among all the process, whichever is having this highest value, we are going to pick it up, right? So here we are not purely depending on the burst time, we are depending on the burst time as well as waiting time. So how are we depending is, see, whenever this burst time is less, see this, whenever this burst time is less, yes, that will be having the higher value, fine. But along with that, If a process has been waiting for a long time, then that one will get the higher value, isn't it? So it is tricky, but then understand this. So if the job is having the shortest burst time, that is going to get higher value. Along with that, if the process is waiting for a long time, that will also get the higher value. So what is the main difference between shortest job first and this one is, in shortest job we were always taking the shortest possible job, but here we are taking both the burst time as well as waiting time, which means if a longer job, if a job with lot of burst time has been waiting for a long time, then that will also get scheduled, right, like this. And S is the service time, which means this HRRN not only favors the shorter jobs. Why does it favor the shorter jobs? Because denominator, there is service time, therefore lesser the service time, higher the factor, therefore it favors the shorter jobs, but also limits the waiting time of longer jobs, which means it will not let a job wait for a long time, because because it is having a large burst time. With the examples it will be clear. Mode is non-preemptive. Non-preemptive means once we pick up a job, we are going to run to completion. So till a job completes, we are not going to let it go, right? So that is what it is. Now take this example and we shall see how to, how does this one works on this. Now at time 0, I am going to start it. At time 0, I am going to start the process P0 and I will be running it till completion. Why it is non-preemptive? Therefore at 3, now at 3 this process P0 gets completed. Now if you look at time 3, only one process has arrived by then, which is P1. Therefore I don't have any other choice, so I am just scheduling P1. And now what is it? So P1 is going to run for 6 units, therefore now the time is 9. Therefore by time 9, all the remaining 3 are available, 2, 3, 4 are available. Now which one should I pick among these? That depends on the response ratio, right? Now let's see the response ratio of each one. Response ratio of P2, process 2 is, what is the waiting time? It came at 4 and now the time is 5. Therefore what is the waiting time so far? 9 minus 4, which is nothing but 5, right? 5 plus, then what is this burst time? Burst time is 4 divided by 4, right, which is nothing but 9 by 4. I think you will get 2.25. okay, that is response ratio of P2. And now you can compute the response ratio of the process 3. So response ratio of process 3 is, waiting time is nothing but it came at 6 and now the time is 9, therefore it waited for 3, plus burst time is 5, therefore divided with burst time, right? Then what do we get? We get 8 by 5, right, which is 1.6. 1.6, yes. Okay. And the next one is response ratio of 4. You have to find out all the response ratios of the process remaining, right? And now it came at 8, therefore it waited for 1 because now the time is 9 and its burst time is 2, therefore 3 by 2 is 1.5. So these are the response ratios of second process, third process and fourth process. Which one is having the highest response ratio? This one, right? Therefore I am going to pick up the second process and schedule it. So P2 will be scheduled, and how long does it run? It will run for 4 units, which means till 13 it is going to run. Understood that? Okay, now the time is 13 and what are the process I have? 3 and 4. So now I should compute again the response ratios of 3 and 4. Response ratio of 3 is, it arrived at 6, now the time is 13, therefore it waited for 7 units, plus its burst time is 5, right, by 2. So which is nothing but 12 by 5. 12 by 5. So this is 2.5. 12 by 5. I think it is 2.5. Oh, 2.4. Yeah. And now response ratio of fourth process is here. It came at 8 and now the time is 13. Therefore it is 5 plus what is the burst time? Burst time is 2 divided by 2, which is 7 by 2, 3.5. So 3.5 is very much higher, right? So 3.5 is very much higher than this value. Therefore we are going to schedule P4 first, P4, and it is going to run till how much time? 5 units, therefore till 18, and then I am going to next schedule P3, that is the only job remaining. Now P3 needs how much time? P3 needs, if you observe it, 5 time, 5, right? Oh, P4 needs only 2 units, therefore it is from 13 it is going to run till only 15. Let me just check it. P0 requires 3 units, P1 requires 6 units, P2 requires 4 units, P4 requires 2 units, only 2 units, and then P3 requires 5 units, which means till 20, right? So this is how HRRN is going to schedule the process. Now let's see the priority algorithm. So here the process will be assigned some priority when they are created. So till now we have not seen any such type. So here what happens is, whenever a process is created by the scheduler, the long-term scheduler, whenever it enters the ready queue, it is going to come with a number associated with it, that is nothing but the priority, right? And now depending on the priority, whichever is having the highest priority, see, implementations they may vary, but then sometimes highest priority means the lower number and lowest priority means the higher number. But whatever it is, I am talking about the highest priority, whether you assign lower number or higher number, whatever you want. Now what we do is, among all the available processes, I'll pick up the one with the highest priority, right, and then run it. So the priority sometimes it will not change at all. So in the gate questions as of now, for whatever we are going to solve it, we assume that all the process will be given static priority, which means once a priority is assigned to a process, it is not going to change. That is what we assume. And sometimes priority might change, which means once the process might come in with some priority and suddenly its priority might increase, right? That might happen. So in our questions we are not considering this dynamic priority, we are considering only static priority. And based on this, the scheduling algorithms here, the priority scheduling algorithm can be classified into 2 types. One is preemptive and other is non-preemptive, like this. The scheduling algorithms can be classified like this. One is preemptive and other is non-preemptive. So again, what is preemptive and what is non-preemptive is same as the previous one. Till now we have seen preemptive and non-preemptive versions, right? But the only difference is here. So whenever non-preemptive means when we choose a process which is having the highest priority, we are going to run it till completion without stopping it. That is non-preemptive. And preemptive means we are going to choose a process which is having highest priority and we are going to run it until its completion, or if any process with higher priority is available suddenly, then we will stop it and run the other one. Okay, better I'll take some examples and explain you this concept. It is very simple, not much complex. And then sometimes what happens is 2 processes will have the same priority. In that case, arrival time is going to break the tie. Okay, if 2 processes are having the same priority, we take the one with the earlier arrival time. In case if the arrival times are also same, right, it doesn't happen because the time at which they join the queue is going to be different. At any time we are going to add one after the other, right? But in case if it happens, then again we are going to see the process ID P1, P2, P3 like that. Okay, the lower process ID will take the higher precedence. So now let's see some examples on that, using which I will explain you how does this preemptive and non-preemptive work. Now let's see the non-preemptive version of this priority. So here, once we take a schedule, take a process which is having the highest priority, we are going to run it till completion without any preemption. So now it is a priority based algorithm where we are going to see non-preemption. Okay, and then see one more thing, whenever priorities are given, you should always know which one is high priority and which one is low priority. Sometimes what happens is people will take the low number as high priority and high number as low priority. It might happen. Therefore here they have clearly mentioned that 12 is highest priority and 2 is lowest priority, right? Okay, and now we can start from first one. So I am going to start at time 0, and now at time 0 P1 has arrived, process P1 has arrived, and its priority is 2, and I don't have any other option now, so only one process is available, so I'm going to schedule it, process P1, and it is going to finish by burst time is 4, therefore 4, right? Yes, now by the time 4, actually till P5, till this point all the processes are available, 2, 3, 4, 5. Now among these 2, 3, 4, 5, I have to take the one with the highest priority, and in this algorithm they are saying that higher number is higher priority. Therefore 2, 3, 4, 5, the highest one is 4. Therefore I am going to schedule P4 next. Got it? Because that is having highest priority, and I could run it till P4 can be run till for 5, which means 9. Burst time of P4 is 5. So you can know what is the burst time of corresponding process this way. Okay, and now P4 is over, so P1 is over, and then P4 is over, completed, right? And now what is the time? 9. So by the time 9, all the processes are available. So other than 1 and 5, just see what are the priorities other than 1 and 5. Sorry, 1 and 4. 1 and 4 are over, right? So 4, 6, 8, 12 and 9. Obviously 12 is the highest priority, which is P6. Therefore next process is P6, and its burst time is 4. Therefore it is going to be finished by 13. So P6 is also over, right? So now this is over, and P4 is over, and then 1 is over. So in the remaining ones you pick up the one with the highest priority, which is now P7, right, which is having 9. Therefore P7 can be scheduled, which is having priority 9 and which is having a burst time of 6, which means by 19 it is going to be finished. And now next one is, among this you can pick the next maximum. So next maximum is 8, so I can pick 8. Therefore P5 is the priority, P5 is the process, and its burst time is 8. So 19 plus 8 is 27, right? Oh its burst time is not 9, its burst time is P5 is 1, which means by 20 it is over, right? And next one is among the available, next one is 6. Therefore I am going to take P3, and whose burst time is 3. Therefore by 23 it is over, and the only one remaining is P2. Finally P2 has to be scheduled, and its burst time is 2, therefore 25, right? So this is how we could schedule all the process. Maybe you could just cross verify it. See, P1 burst time is 4, therefore 4, and P4 burst time is 5, therefore 9, P6 burst time is 4, therefore 13, P7 burst time is 6, therefore 19, and P5 burst time is 1, therefore 20, and P3 burst time is 3, therefore 23, and P2 burst time is 2, therefore 25, right? So this is how we got to obtain all the process, and after this we can see the completion times. What is the completion time of each one? So we know that completion time can be obtained by looking at each of them, right? So completion time of P1 is 4, and P2 is 25, and P3 is 23, P4 is 9, P5 is 20, P6 is 13, and P7 is 19. This is the completion time. Therefore you can obtain the turnaround time and waiting time. So turnaround time and waiting time, and you can find out even the response time too, right? You can find out all these times, and you can find out the average of them. So you could do it anyway, but then let me just do it so that you can cross verify the solution. Now what is turnaround time? This completion time is arrival time, which is 4 here, which is 24 here, 21 here, and 6 here, 16 here, 8 here, 13 here. What about waiting time? Waiting time is turnaround time minus burst time. 0, 22, 18, 1, 15, 4, and it is 7. And what is response time? Response time is, see when it got initially scheduled for the first time and when it arrived. P1 got scheduled at 1 and it arrived at 0, therefore its response time is 0. It didn't wait for any time, right? And then P4 got arrived at 4 and it got first scheduled. P4 arrived at 4 and it got first scheduled at, sorry, P4 arrived at 3 and it got scheduled by at 4, therefore it is 1. Let's talk about P2 first. So P2 got scheduled at 23 and it arrived at 1, therefore its response time is 22. And one thing, if you observe, the response time and waiting time will be same in case of processes where the preemption is, it is non-preemptive. The reason is, if you think logically, if the schedule is non-preemptive means we are not going to pull out the process, then the response time is actually waiting time. The reason is, it is going to wait for only some amount of time, and once it waits that amount of time, it will completely run to execution. So whenever it is given for execution, it is going to complete it, and then leave the system. It is not going to wait any further. Therefore, if there is no preemption, waiting time and response time both will be same. In case if there is preemption, waiting time might be more compared to response time. Response time is when are you going to schedule it for the first time, and waiting time is depending on completely how much time it waited without getting executed. So in case if there is preemption, waiting time will come a lot of times in the middle compared to the burst time. Now next one is for the third one. So third one got scheduled at 20, but it arrived at 6, therefore it is but it arrived at 2, therefore it is 18. So you can check it. You can check everyone, it is going to be exactly the waiting time, nothing else, right? In case of preemption, then the response time and waiting time will be different. So anyway, you can find out what is the average turnaround time, what is the average waiting time, and what is the average response time. Okay, fine. Now let's see the non-preemptive version of this priority. So here, once we take a schedule, take a process which is having the highest priority, we are going to run it till completion without any preemption. So now it is a priority based algorithm where we are going to see non-preemption. Okay, and then see one more thing, whenever priorities are given, you should always know which one is high priority and which one is low priority. Sometimes what happens is, people will take the low number as high priority and high number as low priority. It might happen. Therefore, here they have clearly mentioned that 12 is highest priority and 2 is lowest priority, right? Okay. And now we can start from first one. So I'm going to start at time 0, and now at time 0 P1 has arrived, process P1 has arrived, and its priority is 2, and I don't have any other option now, so only one process is available, so I'm going to schedule it, process P1, and it is going to finish by first time is 4, therefore 4, right? Yes. Now by the time 4, actually till P5, till this point all the processes are available, 2, 3, 4, 5. Now among these 2, 3, 4, 5, I have to take the one with the highest priority, and in this algorithm they are saying that higher number is higher priority. Therefore 2, 3, 4, 5, the highest one is 4. Therefore I am going to schedule P4 next. Got it? Because that is having highest priority, and I could run it till P4 can be run till for 5, which means 9. Burst time of P4 is 5. So you can know what is the burst time of corresponding process this way. Okay, and now P4 is over. So P1 is over, and then P4 is over, completed, right? And now what is the time? 9. So by the time 9, all the processes are available. So other than 1 and 5, just see what are the priorities other than 1 and 5. Sorry, 1 and 4. 1 and 4 are over, right? So 4, 6, 8, 12 and 9. Obviously 12 is the highest priority, which is P6. Therefore next process is P6, and its burst time is 4. Therefore it is going to be finished by 13. So P6 is also over, right? So now this is over, and P4 is over, and then 1 is over. So in the remaining ones, you pick up the one with the highest priority, which is now P7, right, which is having 9. Therefore P7 can be scheduled, which is having priority 9 and which is having a burst time of 6, which means by 19 it is going to be finished. And now next one is, among this you can pick the next maximum. So next maximum is 8, so I can pick 8. therefore P5 is the priority, sorry, P5 is the process and its burst time is 8. So 19 plus 8 is 27, right? Oh, its burst time is not 9, its burst time is P5 is 1, which means by 20 it is over, right? And next one is among the available, next one is 6. Therefore I am going to take P3 and whose burst time is 3, therefore by 23 it is over, and the only one remaining is P2. Finally P2 has to be scheduled and its burst time is 2, therefore 25, right? So this is how we could schedule all the process. Maybe you could just cross verify it. See, P1 burst time is 4, therefore 4, and P4 burst time is 5, therefore 9, P6 burst time is 4, therefore 13, P7 burst time is 6, therefore 19, and P5 burst time is 1, therefore 20, and P3 burst time is 3, therefore 23, and P2 burst time is 2, therefore 25, right? So this is how we could obtain all the process, and after this we can see the completion times. What is the completion time of each one? So we know that completion time can be obtained by looking at each of them, right? So completion time of P1 is 4 and P2 is 25 and P3 is 23, P4 is 9, P5 is 20, P6 is 13 and P7 is 19. This is the completion time. Therefore you can obtain the turnaround time and waiting time. So turnaround time and waiting time, and you can find out even the response time too, right? You can find out all these times and you can find out the average of them. So you could do it anyway, but then let me just do it so that you can cross verify the solution. Now what is turnaround time? This completion time is arrival time, which is 4 here, which is 24 here, 21 here, and 6 here, 16 here, 8 here, 13 here. What about waiting time? Waiting time is turnaround time minus burst time. 0, 22, 18, 1, 15, 4, and it is 7. And what is response time? Response time is, see, when it got initially scheduled for the first time and when it arrived. P1 got scheduled at 1 and it arrived at 0, therefore its response time is 0. It didn't wait for any time, right? And then P4 got arrived at 4 and it got first scheduled. P4 arrived at 4 and it got first scheduled at P4 arrived at 3 and it got scheduled by at 4, therefore it is 1. Let's talk about P2 first. So P2 got scheduled at 23 and it arrived at 1, therefore its response time is 22. And one thing, if you observe, the response time and waiting time will be same in case of processes where the preemption is non-preemptive. The reason is, if you think logically, if the schedule is non-preemptive means we are not going to pull out the process, then the response time is actually waiting time. The reason is, it is going to wait for only some amount of time, and once it waits that amount of time, it will completely run to execution. So whenever it is given for execution, it is going to complete it. It is going to complete it and then leave the system. It is not going to wait any further. Therefore, if there is no preemption, waiting time and response time both will be same. In case if there is preemption, waiting time might be more compared to response time. Response time is when are you going to schedule it for the first time, and waiting time is depending on completely how much time it waited without getting executed. So in case if there is preemption, waiting time will come a lot of times in the middle compared to the burst time. Now next one is for the third one. So third one got scheduled at 20 but it arrived at 6, therefore it is but arrived at 2, therefore it is 18. So you can check it. You can check everyone, it is going to be exactly the waiting time, nothing else, right? In case of preemption, then the response time and waiting time will be different. So So anyway you can find out what is the average turnaround time, what is the average waiting time, and what is the average response time. Okay, fine. Now let's look at the this preemptive version of this priority based algorithm. So preemptive version means we are going to stop a process as and when a new process with high priority is available. That is called preemption. No preemption means we are not going to look at any other process. Once we have chosen a process with some priority, we are going to finish it off, right? So here you should be careful, I mean a bit careful. So let me just write this corresponding rows. It will be easy for us. Okay. Now the first one at time 0, if I start it, the first process which is available is process P1. I have no other choice. Therefore, I am going to run it till what point. You should just see what is the arrival time of the next one. So next one's arrival time is 1. So you can run it only till 1 because the next one arriving is having higher priority. Therefore, you preempt this and you put the next one. So what is next one process? Next process is P2, and now P2. How much should I run it till the next one is available? So next one is available at time 2 and it's having higher priority. Therefore run it for only one unit of time and then schedule the next one. And how long should I execute the next one? P3. So till the next one is available. The next process is available at 3. Therefore run it till 3 because the next process is having higher priority. In case if the next process is not having higher priority, you can keep executing the same one, right? But here it is next process is available at 10, therefore take it and schedule it. So P4, how long should I run it? Till the next one with higher priority is available. See this? So next one's priority is 8, but it is arriving at 4. You need not stop for it. The reason is, this is having higher priority compared to 8. Therefore you can run till 5 because only at 5 a process with higher priority 12 is available, right? Therefore run this one till 5, no problem. Right, and at this point we are going to schedule this P6 because it is having the highest priority. And now if you watch it, it is having the highest priority and it need not be stopped at all. It can be run till completion. So now to complete it, time taken is 4, therefore run till 9. And one more thing, whenever you are running a process and then preempting it, just keep track of its remaining burst time. Here the P1's burst time is 4 initially, but then it has run for 1 unit, therefore the remaining burst time is 3. And P2 burst time is 2 initially, it has run for 1 unit, therefore its remaining burst time is 1. And P3 is 3, it has run for 1 unit, therefore remaining burst time is 2. And P4 is actually 5 is the burst time, but it has run for 2 units, therefore remaining burst time is 3. And coming to this P5, it has not been scheduled yet, but P6 has run to completion, therefore P6 is over completely, right? This is over completely. Fine. And now the time is 9 and all the processes are available. Now it is up to you. You can choose the one with the highest priority, and from here on it will be non-preemptive version. The reason is once all the processes have arrived, now we are just going to see the priority, and whichever is having highest priority will take it directly, right? So now among all this, which one is having highest priority? The remaining one, 12 is over. So if you look at the numbers, next one is 10. Isn't it? Therefore P4 will be scheduled, and how long should it be run? It should be run for 3 units of time, right? Isn't it? Because that is the time remaining. So 3 units is nothing but 12. So 10 is over. Now after this, what is the next available process? The next available is 9. Highest process is 9, and it's if you schedule it, which is P7, it is going to run till completion till 6 units. Therefore 18, and it will be over, right? So this is over, and among the remaining, what is the next one? 8 is the next one, right? So you can take the P5, and what is its remaining burst time? Watch it, it has never been scheduled before, therefore its burst time is 1, and I am going to run it till completion, therefore till 19 I will run it, it will complete, right? And then the next one is in the remaining one, the next highest priority is 8. So if I take it and schedule, 8 is over, right? Yes, just now P5 is over. And in the remaining one, which one is highest? 6, 4 and 2. The 6 is highest and its remaining burst time is 2. Therefore, I am going to schedule P3 and run it for 2 units, and it is going to be finished. And what is its 2 units, right? Which means 21. Fine. and in the remaining one we have only two processes, one is 4 and other is 2. So I can take P2 and I can run it for how much time? The remaining burst time is 1, therefore I am going to run it for only 1 unit, and it is going to be over here, right? And then P1, its remaining burst time is 3, finally 25. Got it? So that is how this could be done. So only one thing you should be careful here is we are going to run a process till that point until which a process with higher priority becomes available. So whenever a process with higher priority becomes available, you are going to preempt this process and schedule that higher priority process, right? But then once all the processes become available, then you are going to pick the one with highest priority, and since no more process is going to arrive at later point, you can run it till completion. Therefore at some point this non-preemptive version, this preemptive version will convert to the non-preemptive version. At what point? When all the processes have arrived. It is exactly same as shortest job first. Even in shortest job, we are going to run a process until the next process with lower burst time is available. But then we are going to do this only until all the processes are available. Once all the processes are available, we can directly go in the increasing order of burst times, right? There is a correlation, right? One algorithm is converting to other algorithm after some point of time, isn't it? Now in case if all the processes arrive at the same time with all the priorities, right, which means arrival time is all same, 1 1 1 1 1 or 2 2 2 2, arrival time is same, then non-preemptive version and preemptive version will be exactly similar. The reason is you are going to pick the one with the highest priority and no other process is going to arrive at later point of time, therefore you are going to run that till completion. So it is exactly same as non-preemptive version, right? Even in shortest job first also, if all the process arrive at the same time, then non-preemptive and preemptive version will be same. The reason is we are not going to get a shorter process with lower burst time at later point of time, right? So just it is interesting to know it. Okay. And now let's finish this completion time and other stuff. This rough work. I just want to delete this rough work. See, one more thing, I am able to do this given this table, but in your examination what they give is, they'll give you a paper, this is online, they will not give you a paper. You have to see the question from the screen and then copy it on the paper and then solve it. So while you are copying the numbers from the screen onto the rough paper, be careful that you don't copy something wrong. If you copy anything wrong from there to the paper, then answer is going to turn out wrong. See, these questions are very simple and you should not do any calculation mistakes. It is very simple to get some calculation error here and there, but then just be careful, practice a lot. Now what about completion times? Since this is a preemptive version, you are supposed to check the completion times from the right end, right? So what is the completion time for P1? P1 got completed 25. And what about P2? P2 got completed 22. And P3 got completed 21, P4 got completed 12, P5 got completed at 19, P6 got completed at 9, and P7 got completed at 18, isn't it? Let me check it. P1 is 25, P2 is 22, P3 is 21, and P4 is 12, and P5 is 19, and P6 is 9 and P7 is 18, right? And after that we can find out the turnaround time. Turnaround time is difference of these two, right? Completion time minus arrival time. So here it is 25, 21, 19, 9, right? And what about this 15, and what about this 4, and what about this 12, right? Completion time minus arrival time. Fine. After finding the turnaround time, we can find out the waiting time and then the response time. See, in this case response time and waiting time will be different. I'll show you the difference why. See, earlier if you see P1 got scheduled only at one point, but now P1 got scheduled at 2 points. Therefore P1 is waiting for the entire duration, right? So for the entire duration between all this from here to here, P1 is waiting. Therefore waiting time is more and response time is less, isn't it? Response time is the point at which it gets scheduled first. That is the point on which response time depends on, but waiting time depends on the entire duration, right? Okay, now let's see what about the waiting time for P1. Waiting time is turnaround time minus burst time, this one minus this one, which is 21 here, and it is 19 here, and it is 16 here, 4 here, 14 here, 0 here. Waiting time of P6 is 0, fine. And then waiting time of this one is what is this, 7, right? Waiting time of this one is this one minus burst time, which is 6. Turnaround time minus burst time, which is 6. Okay. Now if you observe it, only process which is having 0 waiting time is the process having highest priority. So whenever you have a process with highest priority, you are going to complete it right from whenever it arrived. It will get the first priority and will get finished, then only other process will execute. That is why that only that process got the highest, this waiting time as 0. So in case if you have ever anytime you get a process with highest priority, always remember that in this scheduling, which means the scheduling is preemptive version. In preemptive version, it will get the waiting time of 0. In non-preemptive version, it might not get a waiting time of 0, because if there is some other process already running, we are not going to stop it for the high priority process. But here, whenever we have high priority process available, we are going to stop the other process which is running. That is why here we get a 0. And what about the response rate, response time? Now response time depends on when it arrived at the first time, right? Now see this, P1 is scheduled at 0 and it arrived at 0, therefore response time is 0. P2 has arrived at 1 and it got immediately scheduled at 1, therefore it is 0. And P3 got arrived at 2 and it got immediately scheduled at 2, therefore 0. And P4 arrived at 3 and it got scheduled at 3, therefore 0. And P5 arrived at 4 but it got scheduled at 18, therefore its response is 14, isn't it? Check that. And then P6 arrived at 5 and it got immediately scheduled at 5, therefore its waiting time is 0. And P7 arrived at 9 but P7 arrived at 9, P7 if you watch it, yes, it arrived at 9, it arrived at 6. P7 arrived at 6 but it got scheduled at 12, therefore its waiting time is 6, right? So only these two these two are having response time which is non-zero. And why is the response time of all these 0 is remaining process 0 is as and when they are available, they are the highest priority process available till then. That is how we got the process one by one. If you watch it, we got the process in an increasing order of priority. Therefore, as and when they are available, they are immediately scheduled until the next one gets available, next highest priority process gets available. Therefore, in this model, whenever the process which has arrived is higher than is having the priority which is higher than all the process which have already been present, then that is going to get a response time of 0, because it is going to be scheduled immediately, right? Okay, even if you didn't understand theory, whatever I was trying to say, right, whatever I have been speaking till now, if you understood this method, how to solve it, it is fine, it is perfectly fine. They will not ask you so much depth. Okay, and now you can find out what is the average turnaround time, what is the average waiting time, and what is the throughput. So what is the throughput of this? We started at 0 and we finished at 25, therefore the total schedule length is 25, and in this 25 units, how many processes did I finish? 7 units, right? 7 processes. Therefore throughput is 7 by 25, isn't it? So the throughput is number of processes which are finished per unit time. 7 processes got finished in 25 seconds, therefore 25 units, therefore throughput is 7 by 25. Okay. Now, as long as processes do not interfere with each other, and if they are just running independently, like process P1 runs and process P2 runs, there will be no problem at all, which means I told you how a process looks like. Right? There is something called as this code, and then static variables, and then there is stack, and then there is heap, like this, right? This is some process and this is other process. Now what will operating system try to do is, or what will operating system always provide is something called as security. which means any process which is running is just supposed to use only the memory allocated to this. If process P1 is running, it is never supposed to refer to any other element which is not present inside this. And if process P2 is running, it is also never supposed to use anything other than this, right? So as long as this is the case, if operating system is providing you with the protection, that is called protection, okay? As long as operating system protects your memory space from the other processes, there will be no problem at all. But then there can be some problem if two processes are trying to communicate with each other. So why communication is a problem is, okay, so one thing here, when I am talking about processes in operating system, we are mainly concerned about the process which are running in the same computer or in the same host. But when we talk about inter-process communication in computer networks, see, what is computer networks? Completely inter-process communication. Two processes want to communicate with each other when both of them, when these two processes are in different hosts, right? See, so in computer networks, it is like this. Two processes are present in two different hosts and they want to communicate with each other. There we have used the protocol stack ISO, SI, TCP, IP for this inter-process communication. Now in operating systems, what is the main difference is, in operating system we are not going to use different computers. In the same computers, two processes want to communicate. For example, there is process P1 and there is process P2. Both are present in the same computer and now they want to communicate with each other. Why do they really want to communicate with each other is, they want to cooperate or they want to compete for something. For example, maybe I have some task to do and I divided the task in such a way that P1 will do some work and then P2 will do some work, in such a way that P1 will finish its work and then P2 will take the output produced by P1 and work on it. And now when these two processes are running simultaneously, it will be a problem. Okay, again see this, P1 will produce some output and now P2 will take that output as input and produce the final output, right? And it occurs at many places, okay? And now if I have such a task, then both are cooperating to complete something, isn't it? Or sometimes they might compete for something, which means let us say P1 and P2 are two processes which are trying to access the printer. Both of them want to print something. In that case, P1 and P2 will simultaneously try to access the printer. That is called competing. So whenever they want to cooperate or they want to compete, they need to communicate, right? And whenever they communicate, they are going to do it with shared memory. Shared memory means like this. See, now we can say that P1, you please write the output here in some common space. Let us say this is shared memory. In the shared memory, P1 is going to write something, and now from that space P2 is going to read it and then run it. Now as long as they are not running parallelly, which means if this is written in such a way that P1 will finish its writing, then P2 will start reading. If that is the case, there will be no problem. But then if both of them are running simultaneously in such a way that P1 is still writing the output and P2 is reading the input from it, simultaneously if it is happening, there could be some problem. And similarly, if both of them want to write something to the printer, then it could be like this. Both of them can put their data here, which has to be printed, and now some other process will take this data and print it. Then what happens in that case? Both of them might write the data at the same time in this memory, and because of that one of the data might be overwritten and it will get lost, right? Anyway, whenever two processes are trying to cooperate or compete, they need to communicate using shared memory, and whenever they communicate using shared memory, there is a chance that there could be some inconsistency, which means data inconsistency, or there could be some other errors possible. So mainly here data inconsistency is very possible, right? So I'll just take a small example and explain you what happens because of this shared memory. Assume that there are two processes P1 and P2 which are running in the computer, two processes P1 and P2, and now both of them are using a common variable count. right? Both of them are using a common variable, which means you can think that these two variables, these two process P1 and P2 are having somewhere some shared memory to which both of them are given access by the operating system, and now both of them are communicating, right? And now assume that this is the variable count and its initial value is 5. In P1 the code is such a way that it wants to do like this. Let me say the code of P1 is like this. There is something here, and at some point P1 wants to do count plus plus, and now P2's code is such a way that P2 wants to do at some point in its program count minus minus. See, now the entire program they will not access the shared memory, only some part of the program they are going to access the shared memory or some variable or some resource. That part is called as critical section. So we shall see about it later. First let me finish this example. Now P1 wants to do increment the count in its code, and P2 wants to decrement the count in its code. That is how they want to access the common memory. One is incrementing it and other is decrementing it, right? And that is happening at some point in time in their programs, right? And now initially assume that the value of count is 5. Okay, this is the scenario. Now if you look at how this count minus minus and count plus plus will be converted to the assembly language code, I'm just writing it like this. So count plus plus might look like this. So it might contain 3 instructions at assembly language. First instruction may be we want to move count into some register or not, and second instruction may be after moving it maybe we want to increment the or not, and third instruction is we want to move or not back into count. Okay, so this is how the typical instructions look like when you are trying to increment a code. So there are some operating systems which are able to increment it atomically, but then most of the operating systems, most of the platforms, they support these 3 operations. So whenever you have this high level language code, one line, it is going to be converted into 3 assembly language lines, right? And similarly if you look at count minus minus, how does it look? So first thing is we want to move again count into some register. It need not be or not, or it can be or not. So whenever I'm talking about or not, it depends on the context, in the sense when some process is using or not here, and when it gets preempted and other process gets into running, then the or not value whichever this process was using will be saved in its memory. Okay, just not to confuse you, I don't want to confuse you here. So it can even be or not, the register or not, but I'm simply writing R1, right? So it doesn't change anything, it will just not create any confusion for you. And now second thing is decrement R1, and third thing is move R1 into count. So this is how count minus minus is going to be implemented, and this is how count plus plus is going to be incremented. In case if your operating system doesn't have, a platform that doesn't have increment or not command, you are going to say or not equal to or not plus 1. Here you are going to say or not equal to or not minus 1, right? Anyway these 3 instructions are going to be done. Now first one is nothing but reading, second one is nothing but changing or updating or changing, and then third one is nothing but updating. Reading, changing, updating, right? So when you have such a sequence of moves, what can go wrong is, now let's consider a scenario where we have this scheduling algorithms which are preemptive in nature. Preemptive means even when a process is executing, even if it didn't finish its execution, we are going to stop the process in the middle and then we are going to schedule a other process. Now in this scenario what happens is, I'll just take this example, see this. Now what did I say? Initially the value of count is 5 and we have these 3 instructions. Assume this sequence. For some time assume that P0 is scheduled, right? So what does P0 have? P0 have the P1 and P2, right? So assume that now the process P1 is scheduled, right? and now we are looking at P1, and we are assume that we are doing count plus plus, and so P1 is executing its line number 1, line number 2, line number 3 of this particular code, only count plus plus, right? Then what happens? Then we are going to move this count value into R0, therefore R0 will get 5 and increment R0, which means R0 will get 6, and then move this 6 to this, right? Then what happens if P0 gets 1, 2, 3, then this one is going to be incremented to 6, right? And then assume that P2 is got scheduled, and now P2 executed its 1, 2, 3 lines. Then what happens? Then we are going to read 6 into R1 and then decrement R1, which means it will be 5, and then R1 will be written back to count, which means this will be 5 again, right? Therefore, if these two sequences occur one after the other, P1 followed by P2 without any preemption in the middle, then what happens is all the process, everything that will get printed is consistent in the sense the value of count is actually 5, and after count plus plus and count minus minus it will remain 5 again, which is consistent, right? But there could be something wrong, something might go wrong if there is preemption in the middle. I'll just show you a sequence because of which there could be something wrong happening. Okay, why only that sequence is, okay, why should you believe that if there is such a sequence is possible is, Graham's law say that if something might go wrong, it will. Therefore, if there is a chance that this might happen, then definitely it will happen at some point. So you should handle that case and see that there is no chance of that being happening. Okay, now I'll just show you what could go wrong. Now if P1 executes line number 1 and let us say line number 2, then what happens here? So initially count equal to 5, and that count will be moved to R0, and now R0 will be incremented by 1, which means R0 will take 5 and now it is incremented by 1, which means now the value of R0 is 6. That is what has happened. Let us say at this point P1 got preempted and P2 got scheduled, right? And now P2, it has executed 1, 2 and 3, which means P2 will read 5 itself, right? Again move count to R1. It is interesting. See this? Even though P1, the value of count is incremented, whose value is 6, it is not yet written, which means the value of count still reflects 5. So whatever value you have incremented, that is not yet written onto the variable, right? So till this point, even though the value of count has to be 6, it is still showing as 5. At this point, the process P2, who's this whose code is count minus minus, will try to access. See, we are assuming that both are accessing these two codes, right? And now we'll try to access count now, which is going to get 5 into this R5. This is the mistake which might happen. See, even though we have incremented the count, value of count, we are not able to reflect it there, and in the meanwhile some other process came and it read the value which is wrong, which is inconsistent, right? And now the this one count minus minus means, but first we are going to read 5 into R1 and then decrement 5. Second line is decrement R1, which is nothing but now R1 will be 4, isn't it? And now move R1 to count. Finally 4 will be moved here. Got it? And then it got preempted, and finally P1 has came into existence, and finally P1 is running the line 3. So what is it? Move R0 to count, but according to P1, what is the value of R0 now? 6. Therefore 6 will be written, isn't it? Now check that. So because of this order of execution, so is this order of execution possible? Yes, it is possible, because if this kind of preemption happens, and preemption can happen at any instruction, isn't it? Therefore, if there is a chance that this sequence can happen, it will definitely happen in reality, right? At practice. Therefore, we should even handle it. So what happened? After executing count plus plus and count minus minus, the value of the count is supposed to remain at 5, but here the value of the count is showing 6, isn't it? Or let's say what happens if we do something like this. P1 is executing first line, second line, and then P2 is executing first line, second line, and then P1 is executing third line, and then P2 is executing third line. Let's see what happens with this sequence. So initially the value of count is 5. The value of count is 5. P1 is executing first line and second line. So P1 is this and P2 is this. So P1 is executing first line and second line. So what does it mean? P1 reads 5 into R0. Okay. 5 is here, and then P1 will increment 5, which means 6 is here. Fine. And now P2 is executing first line and second line, which means still P2 will also write 5, read 5, and then it decrements 5 and it will be 4. Now according to P1 the value present in R0 is 6, and according to P2 the value present in R0 is 4, right? And now if P1 first prints it, so if P1 first prints there the value, which means P1 is going to write R0 to count, it's not printing, it is storing. So P1 is writing R0 to count, then here it will be 6, and then P2 writes, if P2 writes R1 to count, then it will be 4, right? So now the value is going to be 4 finally. Earlier case, see, in this case count is going to be 6, and in this case count is going to be 4, right? And in this case count is going to be 5. So all these three values are possible depending on the order in which you are executing the instructions, isn't it? So if this particular execution takes place, which means if the preemption happens after this like this, then the order is going to be 5. Or even if the other kind of execution, which means P2 1 2 3, then P1 1 2 3, then also the value of count is going to be 5. If this happens, then the value is 6. If this happens, then the value is 4. This is called as race condition. Race condition means the final output depends on the order in which the processes are getting executed, right? Which is actually which should be avoided. The actual value has to be 5, which is the consistent value. Now the actual value that is going to be stored is inconsistent, right? Why do you think that this has happened? The reason is very simple. Two processes are trying to communicate with each other, sharing a memory, and now there is this preemption, right? There is reading, changing and updating, and in the middle there is preemption. And when you have more than one process updating the variable by reading it and then changing it and then updating it, then there is going to be a problem, right? And in fact this part of the code, the part of the code where the processes are using a common resource is called as critical section. Critical section. The terminology is important. Critical section. There are no theory questions on this. 1 or 2 are there. Mostly problems are there, but still you should know the theory so that we can solve the questions. Now what I am saying is the part of the code inside the process which will access the shared memory is called as critical section. Critical section means in that part of the code is actually accessing something common. Either it is a common resource or a common memory. For example, in these two programs the common resource is count variable, and this is the part of the code which is using the count variable in these two parts. Therefore this is the critical section in P1 and this is the critical section in P2, right? And now the final output is depending on the order in which the instructions are executed, which means depending on how you execute the instructions or how you preempt the process, or the which one wins. We call it race, right? So if P1 finishes first, see, if P1 finishes its execution first, which means here, then the value is going to be 4. If P2 finishes its execution first, then its value is going to be 6, which means there is a race between the processes. Whoever wins the race is going to define the value, which may not be right? Therefore this is called as race condition. Race condition means the output is depending on the order in which the process are executing the instructions, or the process whichever finishes first is going to decide the value of the output. In this case, if P2 finishes first, then the value is going to be 6. If P1 finishes first, then the value is going to be 4 in this particular order, right? So now there are going to be race conditions because of which the values are going to be inconsistent. Now what is the solution then? The solution is we should see that there should be some kind of synchronization. Synchronization means the entire process has arrived here. When one process is in its critical section, other process is also going into critical section. If you could see that only one process will access the critical section at any time without letting any other process access the same critical section during that time, we can see that we can actually stop this problem from happening. What I mean to say is, if either you let P1 to completely access the critical section and then allow P2, or either you let P2 to completely finish its work and then allow P1, that is called synchronization, right? And somehow if you could manage this, then such a problem will never occur, isn't it? Why? If P1 finishes it, then it is going to maybe increment the code, increment the value of count, and it will be 6. And then if P2 starts, then it will decrement the value, it will be 5. Or if P2 finishes it, then it is going to decrement the value, which will be 4. And then if P1 finishes it, it is going to increment it, then it is going to be 5. Which means you should see that one completely finishes, then the other will start accessing the critical section. If you can see that happening, if you can make sure that it happens, then that is called synchronization. Now we are going to see the solutions or synchronization techniques using which we will ensure that only one process enters the critical section, right? So I'll just show you how it is done. Fine. Now let's see the definition of critical section. It is a part of the program where shared resources are accessed by process. Based on this definition, 2 times gate questions are asked. So it's simple. They have given various options. What is critical section, right? So critical section is nothing but it is a part of the code where we are going to access the shared resources. For example, if the shared resource is a variable, then that part wherever you are going to use that shared resource, that is called as critical section. So if you write a program, now the program will contain like this. If you write any program, now that program will contain, for some part no critical resource will be used, then that is called as non-critical section, right? And for some part maybe you'll use the critical section, which means you will say here you will say count plus plus, count minus minus, and something you will use it, then this is called as critical section, this part wherever you are using the shared variables. And then again there will be some part where you don't use it, then that is called non-critical section. And again there will be some part where you will use the critical section, that will be called as critical shared resources, that is called critical section. Therefore you can divide the program into various sections and into 2 types of sections. One section is called critical section and another section is called non-critical section. Now why should we divide the program like this is, as long as a process is executing the code which is non-critical, which means which does not involve any shared resources, you need not worry about it at all. Only problem arises when a process is in the critical section and when it gets preempted, and some other process which is also having a critical section which is using the same resource gets into execution, then at that point it might lead to race conditions, right? So what is race condition? See this, the order of execution of instructions defines the results produced. It is also asked in gate. The question is like this, what is race condition, right? Or they ask this, right? If the speed of the processes define the output produced. Speed of the process means which process finishes first, right? If the speed of the process define the output produced, then it is called as race condition. Speed of the process means which one which finishes first. I told you in the previous example, if P1 finishes first, we are going to get some output. If P2 finishes first, we are going to get some output. That is called as race condition, right? Now if there are 2 processes, let us say this is process 1 and process 2, and 2 processes are having programs this way, and some part is having non-critical section and some part is having critical section, then the problem arises when one process is in critical section and it got preempted. Let us say this is critical section, this is critical section. One process P1 is in critical section and it suddenly got preempted, and other process P2 just entered the critical section, and both the critical sections are using the common variable something, count, right? Then what happens? It might lead to race condition. So just to avoid this, we are going to use something called as synchronization mechanisms. What is it? synchronization mechanisms, right? So what is the synchronization mechanism is, now you place some code, some piece of code, you write small piece of code and you put it just before you are going to enter the critical section, and then you put other piece of code after you come out of it, right? For every critical section you do it, which means here also we do something, we put a code here and here we put a small piece of code, and this is called as entry section and this is called as exit section, right? And here also I am going to put the code, this is called as entry section and this is called as exit section, right? And if I put some pieces of code here in such a way that this code will help us in stopping or in allowing only one process inside the critical section. If P1 has entered the critical section by crossing this entry point, then the other entry point should stop P2, or in case if P2 is inside the critical section, then this entry point should stop P1 from entering it. For every critical section we should do this, which means I don't care how many times we have critical sections in the program, for every critical section we are going to put a entry and then exit point. Now using this entry point and exit point, we are making sure that only one process will ever enter the critical section and the other process which will try to enter the critical section will be stopped by the entry point, right? So if you could somehow see that these pieces of code work that way as I defined now, then these are called as synchronization mechanisms. Now whenever you are designing the synchronization mechanisms, you should see that your solutions should follow some conditions, which means after designing the solutions you verify that these rules are followed by your solution. So there are 4 rules and 2 are very important and 2 are not very important, but then it is better if you have them. I mean, if your solution is having these 2 conditions as well. First one is, your solution should definitely provide mutual exclusion. That is why we are doing it. What is mutual exclusion? If one process is in the critical section, then the other process should not enter the critical section. That is mutual exclusion. It is like this. You can think of it like this. We have a room, and the room can be used only by one person at a time. Maybe you could think of it like a changing room, dressing room. Okay, let us say there is a dressing room, and now only one person can get into it, and at the same time 2 people can't get into it, right? Therefore what you should do is, you should come up with a solution in which you will allow only one person to get into that room, right, at any time, and once that person comes out, then only you can allow the other person into the dressing room, right? So that is called mutual exclusion. Therefore it is very important that your solution should definitely provide the mutual exclusion, otherwise there will be race conditions, right? And now second thing is, progress should be guaranteed. Progress is like this. You could think of it like this. Now you have a dressing room and there is no one who wants to get into the dressing room. And now if let us say there are 2 people and there is single dressing room, and person 1 doesn't want to get into the dressing room, then he should not stop person 2 from getting into the dressing room, which means, see this is the dressing room. So in our concept, critical section is nothing but the room. Okay, so this is the critical section, which is nothing but dressing room, and now there are 2 people, right? So what is mutual exclusion is, only one person should be inside the dressing room at any time. Only one process should be inside the critical section at any time. That is mutual exclusion, right? You cannot put 2 people at the same time, isn't it, in the dressing room, right? Then if that is the mutual exclusion, then what progress means is, let us assume that this person doesn't want to get into the dressing room. Now he should not stop other person who wants to get into the dressing room enter it, right? So if a process doesn't want to get into the critical section, then that process should definitely not stop other processes which are interested in getting into the dressing room. Which means, if this is the critical section and dressing room both are you can metaphors right here. Now what I mean to say is, if this person doesn't want to use the room, he should not stop other one from using the room, right? And these 2 are very important. Your solution should, whatever solutions you propose, your solution should always follow these 2 rules. and the other rules are like this. So if your solution is not providing these two, then we are not going to implement it anyway, because these are very important, and we'll search for other solutions which will provide us with this. And now other one is, second is bounded waiting. Bounded waiting means, if this is the room, right, you should not stop a person for a long time, which means if he enters the room and again she too wants to enter the room, once he comes out, she should be given the chance. Or at least you can say you enter one time and then you can enter one time, or you can say you enter two times and then you can enter one time, or you can say you can enter three times and you enter one time. But you cannot say that he can enter infinite times and then he can enter one time, she can enter one time. So if you say this, then it is nothing but there is no bounded waiting, right? Bounded waiting is nothing but you should be able to say after how many times at least you will get a chance. If you are able to say that, then the other person will happily wait. It is not that the other person will continuously be, one person will continuously be going into the critical section and the other process will wait forever, right? So bounded waiting should be guaranteed, and it is a secondary need. Even if you are not providing bounded waiting, there will be starvation. Okay, we are fine with that, right? Starvation means one process will wait forever, we are fine with that. So it is not primary requirement, it is secondary requirement. And the other one is portability or architectural neutrality. It means that you should not make any assumptions, right? Assumptions that this solution will run only on this operating system, or this solution will run only on this hardware. Sometimes what happens is, some solutions you propose will be so much dependent on the architecture, like they will depend on the operating system you are using, or they will depend on the hardware. For example, some solutions will require that your hardware supports some instructions, and if your solution is going to use the instructions provided by the hardware, then if you try to implement the same solution on some other hardware, it might fail because the other hardware might not have these instructions, right? Therefore it is very important that you should even keep this architectural neutrality. Whatever solution you propose, that should be able to run on all the platforms, but then it is not very important, right? Which means it is a secondary requirement. Understood this? Now let's see the simplest synchronization mechanism, which is lock variable. So even though the name says it is lock variable, it is not actually lock. Okay, let's see this first. Now it is a software mechanism, which means we don't need any support from the hardware, which is implemented in user mode. So what is user mode and kernel mode is, if you need any support from operating system, then we need to go into the operating system code, that is called kernel mode. And if you don't want any interference from operating system, then you can do it in the user mode. So user mode means we don't need anything from the operating system, we can write it in with our own code. So if you need any help from operating system code, that is called kernel mode. And now it is a busy waiting solution. So what did I say about busy waiting solution? The other person will keep on knocking, that is busy waiting solution. And it can be used even for more than two processes. Many of the solutions, they work for two processes, and some of the solutions they work for more than two processes, and it is such a solution where it will work for more than two processes. It works this way. See, what did I say about the mechanism? There will be critical section in the program, and above the critical section you are going to place the entry section, and after that you are going to place the exit section, right? And now if you watch it, above the critical section the entry section is like this. So okay, before going ahead, initially lock value will be 0. Lock value will be 0. So lock value 0 means the critical section is vacant, and lock value is 1 means the critical section is occupied. Okay, or lock value 0 means there is no one inside the critical section and you can enter it, and when lock value equal to 1, there is someone inside it, you should not enter it. Okay, so now watch it. While lock value is not equal to 0, which means as long as lock value is 1, there is someone inside, right? Therefore look at the semicolon here, it means you are going to be in infinite loop. As long as lock value equal to 1, you are going to be in infinite loop. You could even write it like this, as long as lock equal to 1, right? Because here we are going to use only two values, one is 0, other is 1. You need not write not equal to 0, you could even write equal to 1. then you are going to be in infinite loop. You are going to be here itself as long as lock value is 1. So that is why I am saying that it is busy waiting, right? And then when lock value equal to 1, then if lock value equal to 0, then what happens is this loop will break, and once you break the loop, then you are going to make lock value equal to 1, so that you are stopping others from entering. Got it? And then you will enter into the critical section, and once your work is done, you are again going to release the lock, right? Even though the name says lock, it is actually not going to lock the critical section. The critical section will still be open and anyone can enter it. Okay, let's see how it works. Let's go to our metaphor where I am comparing this critical section to a room. Now assume that critical section is again a dressing room, and there are not just one person. The solution is applicable for many people, right? So let us say there are 4 people. Okay, 2 girls and 2 boys, and now they want to use the dressing room, right? And dressing room is going to have a door. Okay, and now how does this one work is, it is not actually having a lock, right? So if this is the knob, the door knob, then to the door knob we are going to hang a tag. That's it, hang a tag. It is exactly similar to that your dressing rooms you might have seen in malls. So there you will see that if someone enters it, there it will show that it is occupied. If someone comes out, it will show that it is vacant, right? And sometimes the knob, that there will not be any lock, right? Maybe you can think of it as the dressing room in Zara showroom. If you have seen the Zara showroom, there they don't have any locks, they just have a curtain, right? You can think of it that way. So anyone can enter the dressing room while you are inside, right? So now see what happens here. So how does it work is, now you are just going to hang a tag. Initially the tag contains, this is the tag, not the lock, just the tag. I'm just hanging a tag to the knob. Initially it will be vacant, right? Then how does this mechanism works is, if this person wants to get into this room, then he will first check the knob and the tag whether it is vacant or not. Yes, how? He will check it whether it is 0 or not. If it is vacant, which means if the lock is 0, then he is going to replace it with the other tag. He will have one more tag and he will take out this tag and then replace it with the other tag, which will say occupied, which means lock equal to 1, and then he will enter the room. Yes, he is now inside the room, right? And now at this time, when anyone tries to enter the room, then now they will check that the knob contains the tag occupied, therefore they will stop themselves from entering. That is how this entire mechanism will work. But then the funny thing is, they will not enter it, but they'll keep on knocking it, right? So what does this knocking really mean is, maybe you can think of it this way. See this? Assume that process P1, let's put the line numbers here. It is line number 1, line number 2, line number 3. Okay. Now process P1 has checked for the lock, and initially assume that the lock is 0, which means process P1 is out of the while loop, and then it has locked it, lock equal to 1, and then it has entered the critical section. And at this time process P2 has come for execution. This got preempted. P1 got preempted, and now it's the turn for P2 to run. Now what will P2 do is, P2 will initially run line number 1, and now it is saying that if lock not equal to 0, yes, lock is not equal to 0, you be in the infinite loop. Therefore P2 is going to be in the infinite loop in line number 1 forever. And even though the CPU wants to execute P2, even though CPU is trying to execute P2, it will not be able to do anything else, which means P2 is still at the CPU, yes, but then it is not doing anything. It is simply in this loop. So CPU is busy, process is doing something, but it is not doing anything. It is simply waiting, right? So it will keep on being in this line number 1 forever until this P2 comes out. Now let us say, P1. Now P1 exited, which means P1 has executed the line number 4, and now it went out. And again, if P2, now if it gets a chance, now it will execute line number 1 and it will come out of it, breaking it, and therefore it will execute line number 2 here, right? And then enter into line number 3. Now if you watch it, this is what I am calling as the busy waiting. Why is it called busy waiting is, P2 is getting the CPU to get executed, but then it is not getting anything to execute. It is simply staying in the loop. So it is busy doing what? Waiting for what? For the other process to come out, right? That is called busy waiting. Got it? And P1 now that is why I am saying that it is a busy waiting solution, and it is implemented in user mode, right? And it can be implemented for any number of processes. Now look at this next approach. It is also called as strict alteration or turn variable. So it is like this. So we are going to have, okay, in terms of that room, I'll just explain you in terms of that room, dressing room, right? So assume that there is one dressing room, and now only one person can enter it, and it is locked, right? It is now locked. See, actually, even though it is turn variable, it is not lock variable. Actually, it will be locked. Earlier, you have seen that the lock variable is not actually a lock, isn't it? It is a kind of tag, and but here it is actually a kind of lock. And now, initially, the key it is only for two people, right? Now, initially, the key will be with one person, right? And only this person can go inside it. So, as long as he has the key, the other one cannot go inside. Even if he wants to go inside or not, he will keep the key. Now what happens is, he will open the door and he will enter it and he will use it and he will come out, and again he will lock it, and now he has to give the key to the next one, right? So what I mean to say is, see this, there are two people. First, one person is going to have the key with him, this fellow, and only he can enter the room. And if he doesn't want to enter the room, still he will have the key, and he will never give the key to him unless he uses it one time, right? And now he'll use it one time, comes out, locks it, and now he'll hand over the key to the other one, right? And now he can enter the room, and even if he doesn't want to enter the room, he can keep the key, and he will not return it unto the other one unless he finishes, he at least enters it once. That is called strict alternation, which means one person will enter, come out, give the lock to him and the key to him, and other person will enter, come out, give the key to him, right? That is why it is called as strict alteration. Now clearly you can understand one thing: when the key is with one person, and if he doesn't want to get into the room, if the other person wants to enter this room, still he cannot enter it because he doesn't have the key. Therefore, obviously, a person who is not interested in getting into the critical section is able to stop the other person, here in this case other process which wants to get into the critical section. Therefore, obviously there is no progress. It is like that dog and horse problem, isn't it? Now dog dog is guarding this door, but the horse wants to have the grass, right? But dog doesn't want to have the grass, still dog is stopping the horse, isn't it? So again the same problem. So there is no progress here, isn't it? Okay, anyway, let's look at this implementation, and again I'll explain you how the progress. And okay, what about the mutual exclusion? Is mutual exclusion there? Obviously yes. The reason is, it is only one person has the key and only he can enter it, other one can never enter it. Therefore mutual exclusion is definitely guaranteed because of the solution, but only thing is progress is not guaranteed, right? There is no progress. What about bounded waiting? Bounded waiting means, if he wants to enter the critical section, how much time should he wait? He should wait only for one time for this one for him to enter it, right? Which means, while a process which wants to get into the critical section is waiting, the other process cannot enter indefinitely, which means the other process can enter only for one time. Therefore there is a bound on the waiting. What is the bound? You wait for one time for this fellow to enter the room, and once he enters the room and comes out, you can definitely go inside the room, right? So therefore bounded waiting is definitely there. What about architecture neutrality? That we shall see in the implementation, right? Okay, first thing is, it is a software mechanism, which means we don't need any support from the hardware like in the previous interrupts. In interrupts we need the hardware mechanism, right? But here there is no need of hardware, only software mechanism is required, and we don't need any support from the operating system. Everything is implemented in the user mode itself, right? And it is a busy waiting solution. What is busy waiting solution? See, busy waiting solution means whenever the key is with him, which means he is supposed to get into it, and if this person wants to get into it, he will go and keep on knocking it. even though it is locked, he will keep on knocking it, right? Therefore it is busy waiting solution, and obviously every busy waiting solution is going to waste CPU time, isn't it? And now it is a two process solution. It can be implemented only for two processes. It cannot be implemented for more than two processes, right? Either you can call the process as P0 P1, or you call them as Pi Pj. It is simply a two process solution, right? Now for process P0, okay, watch it now. The code is like this. For process P0 the code is this, and for process P1 the code is this, right? And they both of them will share a global variable turn. It is a global variable turn which will be shared by both the processes, and assume that the turn value initially is 0. It can be anything. The turn value initially is 0. What does this turn value say is, this will say whose turn it is to enter into the critical section. If turn value equal to 0, then P0 can enter. If turn value equal to 1, then P1 can enter. Or if turn value equal to I, Pi can enter. If turn value equal to j, Pj can enter, right? So this turn will define who can enter the critical section and who has to wait. Now if turn value equal to 0, who can enter? P0 can enter, right? If turn equal to 1, P0 has to wait and P1 can enter, isn't it? Therefore now since the turn equal to 0, P1 can enter, but P0 can enter, but P1 has to wait. Just look at the code of P1. As long as you are in non-critical section, no permission is required. If you are not using any shared resource, if there is nothing shared between process, that is called non-critical section. Non-critical section is the part of the code where you access anything which is not shared, right? Which means it is private to your process. So you need not worry, you can access it as at your own will. And now whenever you want to access the critical section, you check whether it is your turn or not. If it is not your turn, which means if turn is not equal to 1, then you wait in a infinite loop. So this is an infinite loop, right? So it will keep on checking. The turn will be 1, isn't it? If the turn is not equal to 1, which means as long as turn is 0, it will keep on waiting here. It is nothing but knocking the door, isn't it? So whenever you schedule this process, and when this process tries to enter the critical section, and if the turn equal to 0, the CPU it will fall in infinite loop in this line, while loop, right? That is why it is busy waiting. And let's see the other one. Now as long as you are in non-critical section, you need not worry about the turn at all. And whenever you want to enter the critical section, now you have to check the turn variable. If turn variable is not equal to 0, you fall in infinite loop, but the turn variable here is 0. That is what we assumed, right? That is assumption. Now if the turn value equal to 0, it can obviously enter the critical section. Yes, it can enter the critical section and execute it, execute the critical section, and then make the turn equal to 1. Then what happens? The other one, now if the turn equal to 1, therefore this one will enter the critical section. So at any time, turn can take either two values, only two values, right? Turn can take either value 0 or 1. If it is 0, P0 can enter it, and if it is 1, P1 can enter it. Therefore there is mutual exclusion. At any time the turn can take only one value, therefore only one process can enter it, even if both of them look at the values at the same time. Earlier it didn't happen, because what happened is, with the lock variable, when the lock variable is 0, we are letting both P1 and P2 enter it, and when the lock value is 1, we are not letting anyone enter it. Now that was the problem. Earlier when both of them saw the value of lock as 0, both of them tried to enter. That is why mutual exclusion was not guaranteed there. But here it is not the case. Turn value is going to be either 0 or 1, and either it is 0 or 1, only one process is going to enter it. Therefore mutual exclusion is definitely guaranteed in turn. That is the difference between turn variable and lock variable. Fine. Now mutual exclusion is guaranteed. What about, that is the first one, right? The first condition that any the synchronization mechanism should satisfy is mutual exclusion, satisfied. What is the second condition that any method should satisfy? The second rule is as you remember, the second rule is progress. Progress means if a process doesn't want to enter the critical section, it should not stop the other process from entering it. But then it happens here that even though, let us say, turn equal to 0 and P0 is executing in its non-critical section and it doesn't want to get into critical section, still if P1 wants to get into critical section, it will get blocked here at this line, isn't it? Therefore a process which doesn't want to enter into its critical section is blocking other process which wants to enter into its critical section. So progress is not guaranteed. Fine. And what is the third condition? Bounded waiting. So bounded waiting means a process should not wait forever. You know, like this, if P0 wants to enter into the critical section, or let us say if P1 wants to enter into the critical section, if P1 wants to enter into the critical section, right, it should not so happen that P0 will enter into the critical section lots of times and there is no limit on how many times P0 will enter it. If that is the case, then it is called no bounded waiting. But in this solution, it so happened that if P1 wants to enter the critical section, then P0 can enter the critical section in case if it is P0's turn and if it is not P1's turn. But then once P0 finishes its execution, it should leave the control to P1, which means it should make the turn variable as 1, isn't it? See this. P0 will make the turn variable as 1, which means after its critical section is over, it will give the turn to P1. And similarly, P1 after its critical section is over, it will make the turn to 0, which means it will give the turn to P0, right? Therefore, P1 is not waiting forever. It is just waiting for P0 to get into the critical section one time, right? And after that, you will get the control, isn't it? P1. Therefore, you need not worry about it at all. So there is bounded waiting. So there is a bound on the waiting. What is the bound? One time. You just let the other process get into the critical section once, then you can use the critical section, isn't it? And then the fourth condition is architecture neutrality, right? So actually we don't need any support from either the software or the hardware, which means we don't have any assumptions about the platform on which we are running it. This can be implemented on any platform. Therefore, it is architecture neutral. So the only problem with this is progress. Progress is not guaranteed. Now see this. Using this lock variable, what we did was, if lock variable is 0, both P1 or let us say P0 and P1, they are the two processes. It is, any number of processes can use this. But let us say P0 and P1, only two processes are there. Both of them can enter, and if it is 1, no one can enter. And then we use the turn variable. Using the turn variable, if turn is 0, then P0 can enter. If turn is 1, then P1 can enter. Right? So here there is a chance that there could not be any mutual exclusion. But here there is a chance that there is mutual exclusion but no progress. Right? Now, why is there no progress is, if the other process is not interested, still you are stopping one process, even the other process is not interested. Therefore, now I want to use a new, instead of using one variable, I want to use two variables, like this. Interested of 0 and interested of 1. So if any process wants to get into the critical section, it should say that it is interested, right? Otherwise, it should say that it is not interested. So before entering the critical section, you say that you are interested, so that other party will know that, oh, you are interested in entering the critical section, so that will wait, right? Maybe now using this, see here the difference is, till now we are using only one variable, here I use two variables, right? So using two variables, then 0 process P0 will use this and process P1 will use this. So I am even increasing the space at which they will compete. So earlier they are competing at the same value, they are competing at different values. Now they are competing at different variables. Now let's see how to write the solution for this, the synchronization mechanism, and we shall analyze it. Okay. Now P0, as long as it is in non-critical section, fine. And if it wants to enter the critical section, I am talking about the entry section here. It should say that interested of 0, which means the variable for 0, interest of 0 equal to true, which means I am interested in entering it, and then it should even check the other one, right? While interested of 1, the process 1 is equal to true, which means if the other one is also interested, then it should hold. because other one is actually interested, therefore you should not enter it. Got it? And then after that entry section, you are going to enter the critical section and then exit. So when you are going to exit, so when you are going to exit, you can write it as you are not interested anymore. Interest of 0 equal to false, right? And similarly in P1 also we could do the same thing, right? In P1 what we can say is, if you are in non-critical section, be there as long as possible, I mean as you wish, and then once you are entering the critical section, if you want to enter the critical section, then what you do is you show your interest, which means interested of 1 equal to, let us say you are interested in entering it, therefore interested of 1 equal to true, and even you check the other one. If other one is interested, the chances are that the other one might be already in the critical section, or it has already shown its interest first, well ahead of you, therefore give it the chance. So while interested of 0 equal to true, then you wait here for the other one to go into the critical section, right? And once the other one comes out of the critical section, it is going to say, you can enter the critical section and then you can say interest of 1 equal to false, right? This is the exit. So this is how you can implement one more synchronization mechanism. Now let's see if mutual exclusion is possible, which means is it possible that both the process can enter the critical section simultaneously. Observe this, let's see this. Now interested of 0 initially is false, and interested of 1, int is not integer, it is interested, right? And it is false. Now when P0 wants to enter the critical section, now it will make the interested as interest of 0 as true, and it will see that other one is not interested, therefore it can enter the critical section. Let us say P0 is in the critical section, then what happens? Obviously interest of 0 will be true, right? And then now P1 tries to enter the critical section. What it will do is it will make interest of 1 as true, right? But then it will find out here that 0 is already interested, which means the chances are that 0 might already have entered the critical section. In this case it is true, therefore it is going to hold here, it is going to stop there, right? And until what point? Until this one comes out. So you are going to stop P1 at this loop until P0 comes out. Once P0 comes out, it is going to make it as false. Now next time when P1 gets the chance, this while loop will break, because interest of 0 is not true now, it is false. Therefore this one will break and it will enter this critical section. Like that it will execute. Got it? Therefore mutual exclusion is guaranteed. The reason is simple. Even if both the process watch the interested first, whoever enters this, whoever passes this while loop first, right, they are going to get into this. So therefore using this solution, mutual exclusion is guaranteed. What about progress? Mutual exclusion is guaranteed, I'm sure. I mean just check it, because only one process can enter it at any time. Mutual exclusion will not be guaranteed only if we are letting two processes or more processes enter into the critical section on the same condition, like L equal to 0. But here they are not entering the critical section on the same condition, they are entering the critical section on a different condition. Here we are setting interest of, this is checking interest of 1 and that is checking interest of 0. So both of them are different. See, if you have any doubt, just analyze this a bit more. See, now let us say this is interest of 0 variable and interest of 1 variable. What are the four cases? Interest of 0, both of them can be true, 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 false, false, true, false, false, right? So in this case no one is interested, therefore there is no problem with this. In this case only I1 is interested, therefore who will get the chance? P1. So I1 is having true value, therefore it means that P1 is interested and other one is never interested, therefore P1 can enter the critical section. In this case P2 can enter the critical section, I0 can enter the critical section, because only that is interested. In this case, which means if both are interested, then there is a problem. If both I0 and I1 are interested, then who will enter the critical section? The one which has set its interest first and the one which has entered this. But then there is a problem here. Okay, I'll show you that problem. But anyway, here only one process, either P0 will enter or P1 will enter. That depends on who has actually passed this while loop first, isn't it? If P0 has passed the while loop first, these two executed first, then P0 will enter it and P1 will hold there, even though both are having interested equal to true. Let's say there is a problem there. I know you got it, but let's hold on. Let's go step by step. First one is mutual exclusion, it is guaranteed. And next one is progress. Progress is guaranteed. The reason is, see, if one process is not interested, it can never stop the other process which is interested. Why? Because we are clearly checking if the other one is interested or not, isn't it? If the other one is not interested, it can never stop it. And then what about the next one? Bounded waiting. What is bounded waiting? Anyway, it is a two process solution, right? So bounded waiting means if one process wants to get into it, the other process, like this, it would happen like this, P0 and then P1 and then P0, something like this, right? So let's see if bounded waiting is possible or not. If P0 wants to get into the critical section, let us say it got blocked, right? Then what happens? The other one which got the permission, see this, let me write it here. See, initially assume that both interested equal to interest of I0 equal to false and interest of I1 equal to false, right? And P0 wants to enter the critical section, and therefore P0 will make I0 equal to true, right? And then it will enter the critical section, and it is there in the critical section. At that point, P1 wants to enter the critical section, therefore it made I1 equal to true, right? Then what happens? If when it made I1 equal to true, right, and it will get stuck in the while loop. In the while loop it will get stuck. The reason is other one is still interested. So next time P0 comes out of the critical section and then it will make interest equal to false, right? Let us say after some time again P0 only wants to enter the critical section, which means let us say this is in a while loop. It is not just over in one time, it is in a while loop. It will continuously happen, right? And here also everyone wants to enter the critical section continuously. They want to come out of it and again enter it, right? Then let's consider this scenario. P0 came out of the critical section and showed that it is not interested. Again it want to enter it, which means it immediately made I0 equal to true. Now if it wants to enter it, it will just check the interested, right? While interest of other equal to true, yes, interest of other equal to true, therefore this time it is going to wait in a while loop. And now what happens to the other one? P1 again it will try to execute, then again it will be in the while loop showing that other one is interested. Now both of them are interested and both of them will be in the while loop. So it is not just bounded waiting, it is a deadlock. So deadlock is possible. The reason is when both of them show that their interest is true, and both of them get preempted, which means P0 has executed this line, got preempted. Then P1 has executed this line, got preempted. Then P0 will come and check that the other one is interested, it will be in the while loop. And P1 is also come, it will check that the other one is interested, it will be in the while loop. Therefore, there is a deadlock. Whenever there is deadlock, there is no bounded waiting, isn't it? Deadlock is more severe than bounded waiting. The process are going to wait forever. They are never going to get out of it. So the problem with this is deadlock. Even though there is no assumption about the architecture, it is architecture neutral. Fine. The problem with this one is deadlock. Now let's watch it. See, it is Peterson's method. Till now, whatever we have seen, either lock or turn or interested or any other methods like disabling that interrupts, all these methods have one disadvantage or the other. I mean, if you look at the four conditions, none of these methods have really satisfied all of these four conditions, right? But this is the first method which is proposed by Peterson, which is a combination of two variables, turn and interested. I'll show you how. And this is the first method which is used at the user mode. User mode means we don't need any support from the operating system. Therefore, it is platform independent, which means it can run on any operating system because we are not taking any support from operating system. And then it is a busy waiting solution and it is applicable for two processes, right? So this is the method using which, the first method using which we are able to implement a synchronization mechanism with all the four conditions being satisfied. It is very simple, and everything executes at user mode. Therefore, there is nothing overhead, no overhead for the operating systems. We don't expect anything from operating systems. Okay, I'll just explain you this algorithm, and then I'll take two processes and I'll trace out what happens to this algorithm if if two processes are going to run at parallelly. Now let's see this. The algorithm is like this. This is the entry section. I think you remember this. So whenever you want to enter into the critical section, you have to first write the entry and then write the exit, isn't it? So entry section, we are going to write it first and then enter the critical section and then exit section. This is what is the synchronization mechanism. Now in this algorithm, we are going to show what should be this entry section and what should be the exit section and what should each process. Here I am assuming that there are two processes, and the two processes are like this, P0 and P1, which means one process ID is 0 and other process ID is 1, right? So now I'll show you what should each process execute before they enter into the critical section, which means the entry section, and what should they do after they exit the critical section, right? Let's see this. Hash define n as 2. It means that the number of processes which could use this solution is 2. That is what the meaning of it. And hash define true as 1. These are all the constants. Hash defines are nothing but the preprocessor directives which are used to define the constants, which means wherever you see n now, it is always you assume that it is 2, and wherever you see true, it is nothing but 1, like that. Now I am saying that number of process n is 2 and true is defined as 1 and false is defined as 0. Int interested of n equal to false. It means that I am assuming that all the processes are initially not interested. So what is interested of n? Interested of 2, isn't it? Which means interested is an array which is having two variables, two elements, interested of 0 and interested of 1, because n is 2 and both are initialized to false. What does it mean? Initially no process is interested in getting into the critical section. That is the meaning of it. And then in turn, so turn is not set, turn is a random number here. Initially it is not initialized. In turn means turn means that whose turn it is to enter the critical section. We are not going to define it at all. We are going to leave it free. Now void entry section of int process. So if this function is executed by, let us say, P0, the process P0, then this process will take 0. This int process will take 0. In case if it is executed by P1, then it takes 1, right? Int other means if it is called by P0, then process ID will be 0, and what will be the other process? Other process will be 1 minus 0, which is nothing but 1. So the concept of the process and other works like this. If the process is P0, then the process which is calling this function is P0, then the process number will be 0, and therefore the other process number will be 1 minus 0, which is nothing but 1. That is how it works. Are you understanding this? See, the beauty of this concept is, if P0 calls it, then process number will be 0. Then what about the other? Other will be 1 minus 0, which is 1. Similarly, if P1 calls that function entry section, then process this with the integer will be 1 and the other will be 1 minus 1, which is 0, right? Therefore either P0 or P1, whoever calls this entry section, they will be able to figure out who is the other process, right? If it is 0 is calling it, then the other will be 1. 1 is calling it, then the other will be 0, right? That is the beauty of this line. Simple line, right? And next one is, since you want to get into the critical section, just say that you are interested, which means interested of process equal to true. In case if it is called by P0, then interested of 0 will be true, which means it is showing that P0, P0 is telling that I am interested in getting into the critical section. And then it is funny. See, turn equal to process. See, earlier what happened is, we have decided the turn, and that is how a process enters the critical section. But here a process which is interested in getting into the critical section, it itself is declaring that it is my turn to get into it, isn't it? So it is funny here. See this, now it is saying that turn equal to process. It means that it is saying it is my turn to get into the critical section, right? Okay, how does it work? I'll show you how it works. Initially we are saying that I am interested, and then we are declaring that it is my turn to get into the critical section, right? And then it is cautious in such a way that if other one is also interested, then maybe that process might be in the critical section, then I'll wait. Okay, see this. What it will do is, while interested of other is true, which means if the other one is also interested, which means if the other process has also run this line, which means other process also has tried to enter the critical section. Therefore there are two choices, two chances or two possibilities. When the other process is interested, either it is already in the critical section or it is still somewhere here, isn't it? So which means other process has just crossed this line, which means either the other process is there somewhere here or it crossed it and it is inside the critical section. Then what I do is, safely I assume that the other process might already be in the critical section, therefore I will wait. So see this, while interested of other equal to true, which means other one is interested, and turn equal to process. Turn equal to process means I am the last one to set the turn value. Okay, I'll again explain you with an example, right? So don't worry, I'm just trying to explain this algorithm. Even if you don't understand it, I'll take examples and I'll make it very clear. So for now, understand that this process, one particular process, is just thinking that other process is already interested, and turn equal to my ID, which means other process has already set the interested value as true, and then it might have made turn equal to process, or I don't know, but then I am the last one to have updated the turn. Then I'll wait. Why? Because the chances are that when the other process is interested, that process might have already crossed this entire part and it might be in the critical section. Therefore I'll wait in a infinite loop. Till what time? Till the other process comes out and makes its value as false, which means, see this, but how long are you going to wait? We are going to wait till exit section is exit of in process. The other, exit is nothing but you should show that I'm not interested anymore, which means once you are reached here, you should say that I'm not interested, you can get in. See, till now we have seen various solutions like lock variable, turn variable, TSL, Peterson's. All the solutions have one common disadvantage, or let's forget about lock variable and turn variable, they are out of race. Peterson's solution and TSL, these two are perfect. I mean, they are better, they are good, right? They are working. But the problem with these two solutions is, whenever you implement any synchronization mechanisms, they have this problem of busy waiting, which means whenever the entry section, it doesn't allow you to get into the critical section, then what the process are doing is they are following an infinite loop in the entry section itself, right? And because of which, the time that has been allocated by the scheduler for the process to run on the CPU, that complete time is wasted. The reason is CPU will continuously execute it because it doesn't understand that the process is doing nothing, but the process will continuously be in the loop, right? That is called busy waiting, right? And that is completely a waste of time, first thing. And second thing is, moreover, this might lead to a problem of priority inversion. What priority inversion is? If a process with high priority is inside the it has not yet come, and if a process with low priority is inside the critical section, I already told you this if you remember it. See this, assume that there is the entry section and there is critical section and there is exit here, okay? And now a process with priority low priority L is inside the critical section, it is here, right? And suddenly a process with high priority came into the system. Therefore this process will be scheduled first, and this process will be preempted. And when this process gets preempted, the process with low priority which got preempted, and the process with high priority, when it enters the entry section, this high priority process will fall in the infinite loop at the entry section, and the low priority process will not leave the critical section because it never gets a chance, right? Therefore both of them will get struck. High priority process will get struck in the entry section, and low priority process which is already there in the critical section will never get a chance to execute, right? Therefore it is called as priority inversion problem, and this problem is possible in all the solutions which we have discussed till now, whatever it is, either Peterson or all of them, the process with busy waiting, right? Then what is the other solution is, it is like this. If you go to that example that I have been talking about, the one with dressing room, that trial room example. If one person is already in the trial room, right, other person is seeing that the other person is in the trial room, fine, he shouldn't have disturbed him, but this other person will continuously be knocking on the door, right, saying that I want to get inside, and the other person, the one who is inside it, he will not come out, and the outside people, they will be continuously be knocking, right, and that is the problem. Now what is the solution for that? Instead of continuously knocking the door, why don't you go and sleep, so that the process which comes outside the trial room, he will come outside and he will come to you and he will wake up, isn't it? That is a better solution, right? So it is called as sleep and wake up, right? It is also nothing but mutual exclusion is provided without busy waiting. Now we are going to look at some solutions where busy waiting is not there. Simply one process, if it sees that other process is in the critical section, the process will go and sleep, and the process which comes out of the critical section should go and wake up one process and again send it to the critical section. This way CPU will never get blocked, first thing. I mean, CPU will never get what can I say, idle, first thing. And second thing is the priority inversion problem will never occur. The reason is, whenever any process with a lower priority is in the critical section, right, that will be pulled out and that will be kept to sleep, right, and then the higher priority process can obviously get inside, right. So now using this procedure, we can solve the priority inversion problem as well as the CPU wastage, right. So for that, we are going to see something called as sleep and wake up. Sleep means if any process wants a resource or critical section, and if it is not available, that process will go and sleep, and as soon as the other process which is using critical section finishes its usage, it is going to go and wake up the one which is sleeping. So using sleep and wake up, we can solve the problem of CPU wastage, right. This is the best method possible, and let's see with examples. Okay, I'll show you with examples how it works. So we have seen that in sleep and wake up, whenever a process is sleeping and when other process is trying to wake it up, that wake up signal is going to get lost if the process is not actually sleeping, right. So instead of using that, this Dijkstra has proposed that don't directly send the wake up signal to them to the sleeping process. You just write the signal in a variable so that it will be stored and it will be there, and anyone can use it whenever they want it, right. So semaphores provide a way using which we can store the wake up calls. So this variable will contain all the wake up calls. So any process before going to sleep, it can just check if some other process has already given a wake up, and if it is true, then it need not go to sleep. That is how this semaphores will work, right. And that is how semaphores will work. That is the main use. But then the problem with semaphores is, if they are implemented at the user level, then at the same time someone will try to store a wake up signal in the semaphore, and someone will try to use the wake up signal at the same time, and the same inconsistency problem will happen because of the race conditions, just like I have shown you in the first example in the video of need for synchronization. When two processes are trying to access the same variable like count, the value of count is getting inconsistent, right. I have shown you with an example. So similarly, if I use this semaphore at the user mode, then again the same problem arises. See, this concept is simple. Okay, let me not use my hands, I'll just write it down and I'll explain you. See, now the concept is, let's go to the producer consumer problem, or if there is a producer and if there is a consumer, if producer is directly giving a wake up signal to consumer, and if consumer is not sleeping, then this wake up signal is going to be lost. So semaphore solution helps us in such a way that you need not directly give a signal to that. You please store the signal in a variable, right? And later, and this variable is going to be there forever, right? And later, whenever consumer wants to sleep, it will just check that variable and see if already producer has given a wake up call, so that it need not go to sleep. That is how this variable is going to be useful as semaphore. But now the problem is, since this semaphore is a shared resource, isn't it? It is a shared resource, and the code which accesses the semaphore will now become the critical section, right? And then what happens if two processes are trying to add a value to this and remove a value to this? See, one process will try to add it, which means he is trying to wake up, right? Another process is going to remove it, which means he is trying to use it up so that he need not sleep, right? And now when two processes are trying to access the same variable, again the same problems will arise. What is that? Inconsistency, right? Therefore, implementing semaphores at the user level is dangerous and it will be inefficient. So most of the operating systems will provide some of the primitives, which means the function calls, which will be which are used to access the semaphores atomically, which means whenever anyone is reading it, all the others will be stopped from using it. So read, modify and update, which means read the value, change it and then update the value, all these are going to be taking place atomically, right? So that is called as atomicity, right? So atomically, when we implement all these operations, right, on a shared variable, then that is how this can be used in order to store the wake up calls and then consume it later. So it is a solution which requires help from the operating system. It cannot be implemented at the user mode. So at user mode we will use it, but then not implement it. It is actually implemented at the kernel mode, right? Anything by operating system is called kernel mode. Now let's see what are the various things on this. First one is variables on which read, modify and wake up happens atomically in the kernel mode. So it is going to happen in the kernel mode. Next thing is there are two types of semaphores. One is called counting semaphore and other is called binary semaphore. So counting semaphore means, okay, I'll tell you about these two by taking examples, or you can, if you can understand it, okay, I'll take examples and tell you what is counting semaphore and what is binary semaphore. So for now understand that there are two types of semaphores. One is called counting and other is called binary semaphores. So why these two are required is sometimes there will be some resources which have to be used in a mutually exclusive manner, which means while you are using it, no one should use it. And sometimes there will be some resources which can be used parallelly by many processes. For example, assume that we have a variable and that variable can be used at any time by only one process. Then in that case we use this binary semaphore. Binary semaphore supports mutual exclusion, which means if you use a binary semaphore at the entry section, only one process can enter the critical section. And other one is counting semaphore. Counting semaphore advantage is if you use counting semaphore at the critical section, it will allow more than one process to enter the critical section and all of them can exist inside the critical section parallelly. In case if your critical section supports more than one process operation at the same time, then go for this counting semaphore. Okay, I'll take examples and explain you what is counting semaphore and what is binary semaphore and what are the operations on it. We shall see the code, everything. Okay. Now let's look at the counting semaphores. The counting semaphore will be a structure like this. Watch it. Struct semaphore. It will have an integer value, right? And then it will have a queue. So what is this integer value means? Every semaphore, especially the counting semaphore, will have some integer value. It means that how many processes can enter into the critical section at the same time. That is called, that is the meaning of this integer value. So semaphore is going to have initially some value. That value will determine how many processes can simultaneously get into the critical section. Some critical sections might allow more processes to get into this. For example, if you have 4 instances of a printer, then at any time 4 processes can access the printers at the same time. Why? They have four instances, right? So like that, if a resource is allowed to be shared by some particular number of by some n number of processes, but not more than that, then always you can go with the counting semaphores. So at any time, if value of the semaphore is positive, it means that these many processes can enter into the critical section. And in case if the value of the semaphore is negative, then it means that you cannot already some processes are blocked based on that value. Okay, I'll just tell you what that means. I'll just tell you, don't worry. And next one is queue. There is a queue which is called L. So L means this. L will contain set of all processes which are blocked whenever they try to enter the critical section because they didn't get the permission. Okay, I don't know if you understood this or not. Okay, let me take an example. I'll just explain you with this example. Watch it. Assume that we have a critical section and we have the entry code here and we have the exit here. Fine. Now our critical section is in such a way that at any time 3 processes can enter the critical section, right? Then what I do is I'll have a counting semaphore in the entry section in such a way that counting semaphore is initially initialized to 3, right? And whenever any process tries to enter the critical section, it will try to decrement it and then enter it. So let us say P0 has first come and it wants to enter the critical section, then what P0 will do is it will decrement it. Now the value of counting semaphore is 2. It means that P0 has made the value as 2 and still it is a positive number, so P0 will enter it. So how many more processes can enter now? 2 more processes. Let us say P1 has come. Now P1 has P1 also wants to enter the critical section. Then it will decrement it to 1 and still it is greater than 0, right? Therefore it will also enter it, P1. And now let us say P2, the next process has come for execution and it will make it as 0, right? And still it is not less than 0, therefore it will also enter it. So P0, P2 and P1, all the three are simultaneously inside the critical section, right, or simultaneously executing the critical section, and now the semaphore value has become 0, right? And if any new process comes, let us say P3, and if it tries to enter the critical section, then what happens is the value of this will now become -1. We are decrementing it each time, right? Then what happens with this value of what does it indicate is it is not supposed to enter the critical section, and moreover this particular process will be added to the list of waiting process will contain P3. Now if P4 comes, then what happens is again it will be decremented and its value will be -2, right? And therefore again it will be added to the list, right? So if the value is negative for a semaphore, these values indicate -2 indicates that 2 processes are waiting for the have tried to enter the critical section but failed, and so they are waiting in the queue, right? They are blocked. So these negative values indicate how many processes are blocked, and the positive value indicates how many processes can enter into the critical section, right? And this is applied only for the this counting semaphore. Counting semaphore can take both the values, positive values or 0 or negative values. Whenever it is positive, it means that even more process can enter. The positive number indicates how many process can enter the critical section, and 0 indicates no more process can enter the critical section. In case if any process tries to enter, it is going to get blocked, and negative number indicates how many process have got blocked when they try to enter the critical section. Therefore that is how you could interpret these numbers of a counting semaphore. Now what happens is in the exit section, whenever any process comes out, let us say the process P0 comes out, so whenever it comes out, it is going to increment the value of this. So after incrementing the value, its value will be -1. So whenever it is less than 0, it will understand that some processes are already in the queue waiting, which have got blocked, and therefore it will go and wake them up, right? It is going to wake them. So P3 will get unblocked. So P3 will get unblocked, and P3 can get into the critical section, right? So any process which tries to get inside the critical section should decrement the value of semaphore, and if the value of semaphore is less than 0, it should go and sleep in the list. It should sleep and then put its number in the list. And any process which tries to get out of the critical section should increment the semaphore value, and in case if the semaphore value is less than 0, then it can understand that some processes are less than or equal to 0, then it can understand that some processes are already in the waiting list, and it is supposed to awake one of the process and then get out of the list. So that is how we are going to use these counting semaphores. Therefore counting semaphores should have some integer value, positive or negative, indicates how many processes can get into it and how many processes are blocked. And second thing is you should have a list which contains how many processes are already blocked, right? And then next operations are whenever they try to enter, we should have some facility using which they could decrement the value of semaphore, right? And now that decrementing should be in a atomic fashion, atomic way. Atomicity means when one process is trying to decrement the value of the semaphore, at the same time some other process should not do it, otherwise there will be inconsistency, isn't it? Therefore we want some functions which are going to be implemented atomically at the kernel, right? Those functions are nothing but here we need decrementing and here we need incrementing, and while decrementing we should check what is the new value, and depending on which we should know whether to allow a process inside it or whether to block it there, right? and while incrementing the value we should check whether there are already some process waiting, can we let them inside, or we can directly come out. So one more thing is, in this case, we don't want mutual exclusion. It is not actually mutual exclusion, isn't it? When these many processes are present in the critical section, it is not actually mutual exclusion. In case if you want mutual exclusion, then set this initial value of semaphore as 1. So whenever initial value of semaphore is 1, only one process will be allowed to get into the critical section, and all the other process which will try to get into the critical section while one process is inside will all get blocked, right? And later what we do is, all those blocked processes will be in the list and they can be woken up one by one and they can be added into the critical section. And one more thing, the way we, if you use a queue here, that is always better. The reason is, if P3, P4, P5 got blocked in this order, then they will be woken up in that order, so that even bounded waiting can be guaranteed, which means the order in which the process get blocked, you are going to unblock them in the same order. Therefore no process will wait forever, so bounded waiting will be guaranteed. In case if you want mutual exclusion, that will be guaranteed, and then progress will also be guaranteed, because if no one is going to enter this critical section, then anyone who wants it can enter it, isn't it? So mutual exclusion is guaranteed in case if you set the value of semaphore as 1. In counting semaphores, we generally have value of semaphore greater than 1, which means we don't really want mutual exclusion. But in case if you want mutual exclusion, then you can set the semaphore value as something as 1, and therefore mutual exclusion is guaranteed, progress is guaranteed, and even bounded waiting is there. Bounded waiting in the sense, you understood this, right? The order in which the process get blocked, they get unblocked in the same way, because they are all going to be added to the queue, and queue is a first in first out. So anything which got blocked first will get unblocked first, right? And but then everything, if you want to implement this, you need the support from operating system. Operating system should provide you with this atomic operations for decrementing the value and incrementing the value, right? And generally this decrementing and incrementing, these have some specific names. So when they were first used by Dijkstra, okay, watch it. So we want to decrement the value or increment the value, right? So here I am going to use decrementing is as down and incrementing as up. But then when Dijkstra implemented them in his research paper in 1965, he has used the letters. For decrementing, I think he used P, and for incrementing he used V. These symbols he used, right? And some people will use for decrementing, they will say wait, and for incrementing they will say signal. Anyway, whatever they are using, these are the standard terminology: down, up, PV, wait, signal. Here I am using down and up. Anyway, in the exam they will clearly say what is that they mean by saying these symbols. Okay, let's see this. Now watch this one. I think I made the example clear. Now let's watch this one. So you understood this, right? Structure contains some integer value which will take positive or negative or 0. Positive values indicate that these many processes can be allowed, and negative values indicate that these many processes are blocked, right? And Q contains the number of all the PCBs. This PCB is nothing, you know that, right? Process control block, the entire information about a process. This Q contains what are all the processes which are blocked and waiting in the blocked state, and what is their information, so that you can wake them up. And now down, watch it. So down is like this: s dot value equal to s dot value minus 1. So whenever you want to perform the down on a semaphore, we are simply decrementing the value, right? And then if s dot value is less than 0, so it means that in case if you want when you try to decrement it, and if it is going less than 0, it means that the earlier value is already 0 or some negative value. Then you don't have any permission to enter it. I think I told you this. See this? See here, assume that initial value of the semaphore is 4, then P0 has entered, then it's okay, let's say 3 only. I already told you this. P0 has entered, its value will become 2, and P1 has entered, its value become 1, and P2 has entered and its value will become 0. Since the value is 3, only 3 processes can enter and all the other processes are supposed to get blocked. See, since the value is 3, only 3 processes have entered. Now the value is 0. Now if P3 tries to enter, then what happens is it will decrease the value. Yes, it decremented the value, and now the value got less than 0, isn't it? Now the value becomes, after decrementing, it is -1. Therefore, now the value is this. So whenever it is less than 0, then put the process PCB in list, which means you put that inside the list here somewhere, L, in the list L, you put that I am waiting. The process is P3, and you go and sleep happily in the block state, and later someone will wake you up. That is the meaning of it. Got it? Now the value is -1. It means that if the value is -1, it means that one process is sleeping, right? That is how down is implemented. Now let's look at up. So up means generally when will down be implemented is whenever any process is trying to get inside the critical section, it is supposed to apply down, and whenever any process is trying to come out of critical section, it is supposed to apply up. Now let's see what happens if I apply up. If I apply up, it is up UP, right? Let us say P0 wants to come out of the critical section. Then what it will do is, P0 is trying to come out of the critical section. What it will do is, it will increment the S dot value. Now if it increments the S dot value, the new value becomes 0. If S dot value is less than or equal to 0, which means after incrementing the value of S, if it is less than or equal to 0, then what do you think will be its value before incrementing? Definitely a negative number, which means definitely some process is blocked in the block state and is waiting for someone to come out. Just think about it, is logical. See, now I incremented the value, and after incrementing the value, if the value is negative, then definitely before incrementing it, it is negative. Then what does negative value mean? It means that some processes are waiting, isn't it? Therefore, in that case, which means if S dot value is less than 0, which means some process is already waiting. I don't know how many, at least one process will be waiting, right? And now select a process from L. So it is better that you select them in, first out, so that progress will be, bounded waiting will be implemented. Or it is not a rule. You can select any process, that is up to you. If many processes are waiting, you choose one of them, right? Select a process and wake up. Wake up means put it in the ready queue. Sleep means put it in the block queue. Wake up means put it in the ready queue, so that next time it will run and will get a chance to enter the critical section, right? So that is how this is going to done. In case if it is not less than 0, then it simply we increment it and we leave. Nothing is required. Got it? See this. Next time what happens? Watch it. Let us say P1 comes out. So when P1 comes out, it is going to increment 0 by 1, which means it will be now 1, right? What does it mean? Watch it. S dot value equal to S dot value plus 1, but S dot value, new value, is not less than or equal to 1. It is now actually, not less than or equal to 0. It is greater than 0. If the value is greater than 0 after incrementing by 1, then what could be its value before incrementing? Either it could be 0 or some positive value, which means there is no process which is waiting. That is why we don't do anything. Got it? So only when the value is less than or equal to 0, we try to do something like pulling out a process and then scheduling it. Otherwise, we just leave it as it is. Now what is the new value for this? 1. What does it mean? Next time one process can enter without getting blocked. Got it? Now let's see deadlocks. Deadlock is nothing but a set of processes will be waiting for each other. I think you have already seen the deadlock in the concept of this semaphores. So if one semaphore is taken by one process, and if the other process is taking other semaphore, and if these two processes wait for each other, that is deadlock. Or in general, if you want to see any metaphor, let me say this. Let us say you are asking your dad to buy you a bike, right? A bike, and now your dad is saying that you learn it first, then I'll buy it. But then you are saying that you buy it, then I'll learn it, right? Then it will be a deadlock, isn't it? Now your dad will be waiting for you to learn, and you will be waiting for your dad to buy, and then so that you will learn. Therefore, it is a deadlock, isn't it? The set of process waiting for some event, so that other one will perform the event, so that you will continue. And this one, it is like this. Your dad is waiting for you, right? to perform, to learn the bike, and you are waiting for your dad to buy the bike, and both of the process are waiting for each other so that you could continue, right? And now that will be an infinite loop, and this is called infinite starvation, right? So what is deadlock is, if you get blocked for an infinite time, which means there is no one who is going to get you out of that infinite waiting, then that is a kind of deadlock. So the definition is like this. See this: a set of processes are said to be in deadlock if they wait for the happening of an event caused by the others in the same set. Which means there are, let us say, 3-4 processes are in one set, and each process is waiting for the other one to do something, right? And then the other one is also waiting for someone else in the same set to do something, and everyone has got blocked, and these events will never occur, right? Then that is called as deadlock. I'll take examples and explain you. And anyway, starvation is nothing but long waiting, and deadlock is nothing but infinite waiting. That is the main difference between starvation and deadlock. And every deadlock is also a starvation, but every starvation need not be a deadlock. The reason is, after some time, maybe process will come out of starvation and they will get executed, right? Therefore, every starvation need not be a deadlock, but every deadlock is a starvation. And if you want to see how the process will react with the operating system and how they get the resources and release the resources. Okay, one more thing, there is something called as a resource. So a resource can either be a file or a variable or a semaphore or register or CPU, anything. Everything in the computer is called as a resource, right? And now a process will like to use some of the resources in order to complete its execution. And whenever it wants a resource, then it is going to ask the operating system. And if the resource is available with the operating system, it will give it to the process, and process will use it and then release it and complete its execution. But sometimes what happens is, let us assume that first watch this one. A process will request operating system for a resource, and in case if the resource is available, the operating system will immediately grant the resource, and the process will use the resource and then release the resource and then return it back to the operating system. That is what happens if everything is smooth. But sometimes what happens is, the resource which you asked might not be available right now with the operating system because someone else is using it. For example, the semaphore. If it is a mutex, and if someone has already performed a down on mutex, that semaphore will not be available for you, right? You are supposed to wait until the semaphore becomes available, kind of it. Or let us say there is only one printer to your computer, and now you wanted to print something, and now you are asking for a printer. But if already someone is using the printer, that cannot be given to you. So until that other process finishes using the printer, you are going to wait for some time, right? That is what happens here. In case if the resource is not available with the operating system is going to delay the process of giving you the resource, and for that delay you are going to wait in a block state. You are going to go into the block state and wait for some time. And in case if you wait in the block state only for some time, then that is called as starvation. In case if you wait in the block state forever, right, then that is called as deadlock. So either deadlock or starvation, you will be in the blocked state. Got it? The main difference between starvation and deadlock is the amount of time. In starvation, you will eventually come out of the block state and you will run after some time. But in deadlock, you will never come out of the block state. Okay. Now, if this is the scenario, now assume that. So now you understood that a process will do 3 types of things. One is it will request for a resource, and again it will get the resource, and therefore it will use the resource and then release it. So request, use and release it, right? These 3 steps are performed by a process on the resource. Now assume that there are 3 processes like this: P1, P2, P3, and there are 3 resources like this: R1, R2, R3. These 3 resources can be printers, or they can be anything, registers or files or whatever you could think of in a computer. Now let us say P1 asked for R1 and it got assigned, which means R1 is with P1, and now P1 and R2, P2 wants R2 and it got it, and P3 wants R3 and it got it, right? And now P1, after some time, if it is asking for R2 and R2 is under the control of P1, P2, then P1 is going to wait until R2 is available, right? And at the same time, after some time, let us say R2 is with P2 and P2 now wants R3. R3 is already with the P3, right? Then what happens to P2? It is supposed to wait for some time. And at the same time, if P3 wants R1, right, and R1 is with P1, so every process has taken some resources and they are waiting for some other resources so that they can complete the execution, but the other process is not going to leave it. And if you observe it, there is a cycle, isn't it? Therefore this kind of waiting is called as deadlock. In case, okay, I cannot directly declare that there is a deadlock unless you observe, we examine what types of resources are R1, R2 and R3. We shall examine them first. So, let's not call it as deadlock as of now. Let me explain some few points. Now, necessary conditions for deadlock. If deadlock has to happen, there has to be 4 conditions which have to be true always. If you have to have a deadlock. First thing is mutual exclusion. Mutual exclusion means the resources which you are talking about should not allow multiple processes to access them at the same time. For example, printer. If one process is already printing something using the printer, at the same time if some other process also starts printing, then there will be interleaving of both the files, isn't it? That will be chaos. So that kind of resources is what we are talking about, and we are not talking about some resources which can be shared. For example, if there is a file and if many processes want to read it, then they need not use any mutual exclusion, right? They can all read simultaneously. In that case, there will be no deadlock. So if there has to be deadlock, then there has to be mutual exclusion, which means only if there is mutual exclusion, then only there could be deadlock. Simple, the reason is simple. Deadlock is a condition in which many processes want the same resources, and since they are not able to get them, they are going to be blocked, right? In case if the resource can be used by many processes, obviously everyone can use it, and they can come out of the deadlock. They need not starve at all if they can access the resource simultaneously. And the second condition is hold and wait. Hold and wait means like this: one process is taking up one resource and then it is waiting for other resource, right? P2 has taken up R2 and it is waiting for R3. So this is the condition for deadlock. The second condition, which means if one process is going to hold some resources and then wait for other resources, then what happens is it is not going to leave the resources which it is holding, and for this resource someone else might be fighting, right? And now this wants something else. That is how hold and wait is a necessary condition for deadlock. And the next one is no preemption. No preemption means while some process is using the resource, you are not supposed to pull that resource out, which means while some process is printing the file, you are not supposed to stop the process and get the printer and give it to the other process, right? If that could be done, then deadlock can be resolved easily, isn't it? You pull out one of the resource from one process and give it to the other one. Now other one will use all the resources and finish it and then release all the resources, and that can be used by other process, right? So no preemption should exist for the deadlock to happen. And finally, circular wait. Circular wait means, see this here, P1 is waiting for P2, P1 is waiting for R2 in fact, and R2 is with P2. Therefore P1 is waiting for P2, isn't it? And P2 is waiting for R3 and R3 is with P3. Therefore P2 is waiting for P3, and P3 is waiting for R1 and R1 is with P1. Therefore P3 is waiting for P1. So there is a circle here. P1 is waiting for P2 and P2 is waiting for P3, and again P3 is waiting for P1. Therefore there is a circle. So it is a circular wait, and therefore these 4 conditions are the necessary conditions for deadlock. Understood this? So let me do one thing. I'll explain you with problems. This will be very easy if I take problems to explain. Maybe then we shall see the questions, the other theory questions. Okay, fine. Deadlocks are really a true condition, and they really exist, and so we are supposed to deal with them. So we are supposed to handle them. So what are the various deadlock handling mechanisms that are right now used at practice? Or first, the simplest one is deadlock ignorance, and this is the most popular one, and it is used by Windows and Linux. So both Windows and Unix, they are going to use this method of ignorance. Ignorance means we act as if there is no deadlock at all. Even though it is true that deadlocks are possible, we act as if it is never possible, right? and what happens because of that? There will definitely be deadlock in your system, and because of which your system will halt. Then users, they will wait for some time, and then they don't understand what is going on in the system, and simply they will restart it and they will go ahead with that. And why such a mechanism used is this ignorance. The reason is, in order to use any other handling techniques, we need to write lot of code, and then we need to spend a lot of time on dealing with these problems with lots of restrictions, and moreover, and all of this is going to hurt the performance. And as a user, I mean, if it is not a mission critical job, and if you are doing if you are a normal user who wants your computer to just for browsing and then doing some personal stuff, then you will not be too much worried about the deadlocks, which means you will be happy if your system runs faster compared to your system runs safer, right? So there is a trade-off. Mathematicians argue that deadlock should be handled, but engineers argue that since deadlock is a rare condition, which means once in 5 years people will come across this problem, therefore we'll handle the other problems, like if every day some problem is going to arise, right, then we'll handle that problem first rather than handling a problem which occurs once in 5 years in a computer, right? So that is how many of the practical operating systems, the end user operating system these days, they are just ignoring the deadlock. I'll tell you an example. Let us assume that we have 10 process in our computer, and each process requires that they fork 10 sub processes. Therefore 10 running process wants to produce 10 sub process each, and totally combined it is going to be, I think 110 processes. That is what the system requirement is. Let us assume that at some point in time 10 processes are running, and each of these 10 processes want to start 10 sub processes, and therefore the total number of processes that can be present in the system at maximum are 110, right? And now at this point, assume that we need 110 processes to be present in the system, so that all these processes will get complete their execution. But then assume that our process table, I'll tell you later what the process table is. The process table will contain one entry for each process that is going to be present in your computer. The process table is big enough so that it can handle only 100 processes. Now I need 110 processes to finish my job, but I have only space to hold 100 processes. Assume a scenario where all of these 10 processes have produced 9 sub processes each, and therefore 90 plus 10, original 10 plus 90 sub processes, totally 100 processes are now completely present, and they have taken all the space slots. Now all these processes, all these 10 original processes, in order to finish their execution, they need to have one more process, right? Because each one needs 10 processes, which means we need 10 extra slots, and every process needs one extra slot. Therefore they all will be waiting for the extra slots, and they all will go into the deadlock. How can you ensure that such a deadlock will not occur? Only thing is, you should restrict the process in such a way that at any time only one process can apply the fork. If more than one process applies the fork, then what happens is, I mean, if two processes are allowed to use the fork, then what happens is two processes will keep on filling up the process table slot, right? And suddenly what happens, there will be no space, and therefore these two processes will wait for each other to finish their jobs, and therefore they will get into deadlock. Now restricting that at any time only one process uses the fork is a very high restriction, very big restriction, right? And it is going to hurt the performance, because many of the systems, many of the processes want to apply the fork randomly. We cannot say that at any time only one process can apply the fork. Even in order to do that, you have to maintain lots of data structures, and you have to keep track of what are the processes running and what is the code they are using, and in case if they try to apply the fork, you should block the process. It is all going to be a headache, and this deadlock is a very rare condition in normal users in such a way that if you experimentally, it has been found out that it is a condition which occurs once in 5 years. Now in order to handle that case once in 5 years, you have to write a lot of code, and you have to create a lot of inconvenience to the users. Instead of that, what many engineers did is they simply ignored it. That is how Windows and Unix, they don't handle it at all. They just ignore it. They act as if nothing is going to happen. I mean, there is no deadlock at all. And sometimes this method is also called as ostrich approach. Ostrich is a bird, you know that, right? The ostrich is a bird with long neck and which cannot fly. I think the biggest bird in the world. I think yes, right? And how will this ostrich, attack this problem of this sandstorm? Is whenever there are sandstorms in the deserts, this ostrich will just stick its head into the sand. It will put its head into the sand, and it will close its eyes and act as if there is no sandstorm, right? That is why it is, it is comparable to this deadlock approach. So it is also called as ostrich approach, which means we act as if there is no problem. Like the same way how ostrich is acting as if there is no sandstorm, we are acting as if there is no problem at all, right? But the actual case is, deadlock is real, we have to handle it. But then, there is always a trade-off, correctness versus performance. So we are going to prefer performance, not the correctness, right? So at some point of time, definitely users will get struck, some process will get struck and no work will get done. Then what is that users will do is again restart. They shut down the system and restart it, right? So that is how the deadlock ignorance is going to work. And then the deadlock prevention method is prevention. You know this, prevention is better than cure. We'll see that deadlock will never occur in our system at the first place. How could that be done? Now, if you want to make sure that something doesn't happen, just disable all the necessary conditions, or at least one of the necessary conditions. For example, I've shown you that there are 4 necessary conditions for deadlock. Now we shall take those 4 necessary conditions and then we shall try to disable at least one of the necessary conditions. If you could disable at least one of them, then definitely deadlock will never occur, right? So if the deadlock is not occurring at the first place, you need not deal with it at all, right? So one way to handle the deadlock is don't let it happen at the first place. That is called as deadlock prevention method. And next one is deadlock avoidance. So deadlock avoidance is we'll try to avoid it, in the sense there is a chance of getting the deadlock, but then we'll at every step we try to avoid it. How it is possible is, in order to do that, we distinguish the states of the systems between 2 things. One is safe state, other is unsafe state. So I'll again show you this, but just I'm trying to introduce you here. So deadlock avoidance, in order to do this, I'll try to find out whether this system is in the safe state or unsafe state. I mean to say safe, S-A-F-E, safe state or unsafe state. So safe state means now the system could, all the process could somehow run with the available resources to the completion. Unsafe state means there is no safety, which means the process which are present in the system, there is no way you could allocate the resources so that it will run to completion. They will run to completion. Now we'll always see that our system will never go out of the safe state. Okay, forget it. I don't think that you understood it now. I'll take example and explain it. Okay, so forget it. So what I mean to say by deadlock avoidance is, at every step, whenever we allocate the resources to a process, we'll just be sure that this allocation will not lead to the deadlock. That is what I mean, right? So whenever you try to allocate resources to the process, we just see that this allocation will not lead to the deadlock. Got it? And next one is deadlock detection and recovery. See, deadlock ignorance is the most widely used method. And then deadlock prevention is possible, but then it has got some glitches. And deadlock avoidance also has got some glitches, in the sense, I'll tell you that. But then deadlock detection and recovery is the next most popular method, which means we let the process get into deadlock, and then once they get into deadlock, we periodically try to detect the deadlocks, and then we shall try to do some methods to recover from them. So that is what. So now the main challenge in this is, how are you going to detect the deadlock, right? See, here you need not do anything, deadlock ignorance, just ignore it. And deadlock prevention, yes, we need to do some work, like how can we disable the 4 necessary conditions, one of the 4 necessary conditions. And deadlock avoidance, here the main challenge is, how are you going to find out what is the system state, which means is this a safe state or unsafe state? Depending on that, we shall allocate the resources. But the problem is, predicting the requirement of the process well before they run is a problem here. So that is a glitch. Okay, I'll talk about it later. And deadlock detection is I can say is the most practical method, which means let them go inside and then get into deadlock, and then I'll see that they are in deadlock, and then I'll do some of the methods, recovery methods, right? Now let's see this deadlock prevention method. So in order to know what is prevention is, see, for a deadlock to happen, there are 4 necessary conditions, and if all these necessary conditions hold together, all of them, then only deadlock would be possible. Right now, if you could disable at least one of the condition, then we can completely avoid the deadlock. It is like this: deadlock is a chair or a table standing on 4 legs, right? And all these 4 legs should be there if the table has to stand, and if you could pull one of the legs, then the deadlock will fall. So that is how you could fail the deadlock, or that is how you could prevent the deadlock, right? So what are the 4 conditions? If you remember it, I told you that there are 4 necessary conditions for a deadlock to happen, right? So first necessary condition is mutual exclusion, which means the main reason why the deadlock will happen is because a resource will not lend itself to be used by more than one process. Then what happens? When this resource is currently being held by one process, other process will try to access this resource, and that is how these 2 processes will fall in the deadlock. Are you getting this? See, how will the deadlock happen is, there will be some resource, right, and there will be some process. Now this resource will be taken by this process, and which means while this process is using this resource will not lend itself to be used by some other process, and that is how the deadlock will be causing, right? So which means some other process P2 might ask for the access to this resource, but this resource is saying that I am already being used by P1 and you cannot use me again, right? And now at the same time, this P2 might be holding some resource R2, and which also doesn't lend itself to be used by more than one process, and P1 wants it, right? Therefore there is a cycle here, right? And if this is the case, that is how the cycle is possible. If you see this, that is the case how the cycle is possible. The main culprit here is the resource. Resource is saying that more than one process cannot use me at the same time. Now if you could somehow disable that requirement, that if you could make every resource to be used by more than one process at the same time, maybe deadlock will never happen, right? Why? Because if these 2 processes want this resource, just give it to both of them and they'll finish their execution. But what is the problem with that? Just think about this scenario. Let us say we have a printer, and it can be used at any time by only one process, and at the same time if you give 2 processes, right, and the printer is being used by 2 processes, now one process will be trying to print something on the printer, and suddenly it gets preempted and the second process will start printing. Therefore your output printed on the paper will be a combination of the results produced by P1 as well as P2, 2 processes, right, which is nothing but a chaos, right? So we don't want that situation. So disabling this one is really difficult. So disabling mutual exclusion, which means making a resource which has to be accessed in a mutual exclusion manner, disabling that is really dangerous. I mean, it is not physically possible, it is not feasible at all. Then what is the solution is, if you have any device like a printer, you can use pooling methods. Pooling method is, if you want the printer, let us say this is the printer, right, then you just say what you want to do with the printer. You just write the job there, you just give the job to the printer as a process, and you go and you just leave the place, and next process will come and then it will give the job to the printer, and then next process will come and will give the job to the printer, and they will leave, they will not worry about it, right? And later at some point of time, the printer daemon, right, there will be daemon process. This daemon process will take the jobs one by one and then it will start printing. Therefore the processes are not actually printing, competing for printer, they will be competing for the spool memory, right? This is called spooling. So they will just drop their jobs in this spool, and then later printer daemon will take each job and then print it. Therefore now only one process, even though we have so many processes which wants to access the printer, now we resolved everything, or we combined all the process in such a way that there will be only one process which will now compete for the printer. That is nothing but the printer daemon. Now this printer daemon will take the jobs one by one and it will schedule them to the printer. Therefore at any time only one process will be accessing the printer. That is how you could some way, I mean for some of the resources you could use this solution and avoid the deadlock. But the problem is this is not a feasible solution for all the resources, and in fact even it is not feasible for the printer also. Even though process are now not computing for the printer, they will now compute for this memory, isn't it? Now many process will try to write the jobs in this memory, and this memory will get full, the disk space will get full, and therefore again the process have to wait for this one, right? So it cannot be completely avoided, or you cannot use this as a solution. Disabling mutual exclusion as a solution in order to prevent the deadlock, it is not physically possible. To some extent yes, but 100% no, which means you cannot using this solution, you cannot completely solve the problem. To some extent yes. And next one is hold and wait. So if you want to if you want processes not to hold one resource and then wait for other resource, see, like this, hold and wait is like this. This process is holding this resource and then waiting for this resource, right? So this is one more necessary condition. If you have to disable this, then what should happen is, the solution is request all the resources initially. So if you want the resources R1 and R2 as P1, then you request them initially, and in case if you don't get both of them simultaneously, then never start it at all, right? Then what happens? This one will not be started, then only one process will be started, because at least one process will get all the resources. That is how we can avoid it, right? See, what I mean to say is, watch it, I want to disable hold and wait, right? Which means I don't want hold and wait. Then what should happen? I should not hold or I should not wait, isn't it? Now if you don't want to wait, then hold, get all the resources at the beginning, right? So which means if this process wants 2 resources, you are supposed to ask them before execution. If both of them are available, then only you are supposed to run, otherwise don't run, right? And what about not hold? Not hold means, in case if you found out that you need one more resource, now you have started, and in case this is second strategy. See, one strategy is this: get all the resources, then only you start. If you don't get, don't start. That is nothing but requesting all the resources initially. And the other strategy is don't hold. Don't hold means, if you want to make a request for a new resource, you release all the resources you are holding, and then you make the request for all the resources together. That is a better thing. Either you don't hold or you don't wait, right? So if you can do this, the second condition can be this second condition does not hold, and therefore deadlock prevention is possible. But the problem with this approach is, there is a small glitch here. The problem is, before you start running, a process starts running, how can it say what are all the resources it might need during the execution? That is very difficult thing, right? Because while the process is running, at some point of time it will contain an instruction which will demand a resource. Therefore we cannot predict well ahead how many resources we need and what resources we need. So that is the problem. Therefore disabling this condition practically is a problem, because in order to guess the requirement, it is very difficult. In case if you could have a mechanism using which you could guess the requirement, then there are various different methods, better methods, which will work better than this prevention. They are avoidance method, which means if a process has the capacity to give you all the resources, to mention all the resources that it might need, then you will never go for this method at all. The best method possible will be deadlock avoidance. Even deadlock avoidance will also have the same problem. The problem is, a process will not be able to declare its need well ahead of its execution. During the execution it can say that I need it, but then before execution it cannot say that I need it. So that is a problem here, right? So hold and wait disabling is somewhat, I can say, I don't really suggest that. See, so this is practically not possible, and this is also practically not possible because of the restriction that process will not be able to declare its need well ahead of execution, right? And so next one is no preemption. So what is no preemption? No preemption says that while a process is using a resource, we are not supposed to pull it away forcefully, right? That is no preemption. Now if I have to break this condition, it is nothing but preemption, right? Which means take resources away, right? It is obviously not a good approach. while some resource is being used by a process, if you take it away, then completely whatever the process has been running till now, it cannot continue further. For example, if a printer has been printing something, and if you have pulled out the printer away and if you have directly given it to the other one, the results which are produced by the process one, will become inconsistent, and again you cannot restart from the place where you have pulled it out, right? Therefore, again, no preemption is also not a practical condition to be implemented. So now all these three conditions cannot be disabled practically. So now out of no choice, we are left with only one option. What is it? Disable the circular wait. So how to disable the circular wait is, now what is circular wait is, see, so what they say is, you number all the resources and then you ask for the resources only in the increasing order. So whenever you ask for a resource, if a process wants to ask for a resource, it should ask for a resource which is great. Okay, like this. I'll just use it diagram and I'll show you. And let us say all the resources are numbered like this: R1, R2, R3, R4, so on, right? And now a process P1 is supposed to request, if it requested process number, resource number R2, and if it got it, then it should not ask for R1 again. It should ask for something greater than this, right? And if other process, let us say P2 has requested for R2, it should not ask for again less than this. It should only ask for something greater than this, like this. So if every process is going to ask for the resources in the increasing order, then obviously no process will again come back and ask for the lower number. Therefore, there will not be any cycle, isn't it? See this here. How did this deadlock happen? Because R1 is being, P1 is holding R1 and it could request for R2, it is fine. But then P2 is holding R2, but it is coming back and requesting for R1. In case if it doesn't request it, if it is supposed to request only higher numbers, right? Then this, in the first place, it will not happen. So if it requests R1 and R2, let it ask for R1 first and then R2, depending on the increasing order of the resources, right? If you can make sure that such a thing happens, then we can avoid this circular wait, right? So the procedure is number all the resources, give them some ordering, and then a process should be restricted in such a way that it should ask only for the resources in the increasing order. In case at any point of execution, if it requires any resource which is lower than the resources which it already holds, then it is supposed to release all the resources it is holding, then only it can make the request for the lower one. If we can enable this, then the problem can be solved, and this is the only problem which can be implemented practically, and all the other these conditions cannot be implemented practically here, because we don't need a process to declare its need way ahead of its execution. As and when it wants a resource, it is just supposed to see whether the resource number is in the increasing order. If it is in the increasing order, it can place the request. If it has to ask for a resource which is at a lower number than the resources which it already holds, it is supposed to release all the resources and again start from the beginning, right? So using which we can disable this circular wait, which means order the resources numerically and then keep on ordering them in the increasing order. Therefore, this cycle will not occur, the circular wait will not occur, right? So this is one of the methods which is generally used in the real-time systems, where if you really want no deadlock to happen, and if you don't want a lot of time wasting in detecting the deadlock and then recovering from it, then go for it. So it will completely prevent it. Understood this? So this is how the deadlock can be prevented. Now let's see the lost handling method. Deadlock handling method is deadlock detection and recovery. See, we have seen all the four. Now it is the fourth one. One handling method is deadlock avoidance. Ignorance. Deadlock ignorance means the ostrich method. We'll act as if there is no deadlock at all. And the second method was deadlock prevention, which means we try to somehow avoid one of the necessary conditions, right? And the next one is deadlock avoidance, which is Banger's algorithm, right? And now we are going to see the last one, where we don't do any prevention or any avoidance. Therefore, deadlock is definitely going to occur. And what operating system will do is, it will periodically keep checking the system for any presence of deadlock. In case if it detects any deadlock because of this, at any time, then it is going to recover from the deadlock, right? So first thing is, first challenge for the operating system in such a case is, how is it going to detect the deadlock? So let's talk about the detection first. Now how are we going to detect the deadlock? So as you know that resources are of two types. One is resources can be of single instance type, other is resources can be of multi instance type. So in single instance resource types, the deadlock can be detected by detecting the cycle, right? And you know how to detect a cycle in a graph, that we shall discuss it in the algorithms, right? So using a traversal method, we can find out that a cycle is present inside the deadlock order of E. So that is straightforward. Therefore, in case of single instance resource types, detecting a deadlock is straightforward. How can you detect it? By detecting the cycle, isn't it? Then if you see a cycle in single instance resource allocation graph, then there is a deadlock. That is why your operating system is going to detect a cycle in case of single instance resources, right? And the other one is multi-instance resource types. If each resource is going to have multiple instances, then in that case you are going to detect, in that case you are going to, you have to detect the this deadlock, but then cycle will not imply the deadlock, which means cycle is just a necessary condition, as cycle implies the deadlock, but then cycle is just a necessary condition but not the sufficient condition, right? So in this case what we do is we run that safety algorithm which we have seen already, right? So in case of this banker's algorithm, we have already seen the safety algorithm, right? So we are going to run the same method here, right? So using safety algorithm, we can find out that there is a deadlock in case of multi-instance. So either you use this cycle method here or safety algorithm here, we can somehow detect the deadlock. Therefore your operating system can detect the deadlock. And after detecting the deadlock, what your operating system should do is, it should take some measures so that this deadlock can be resolved somehow, right? That is called as recovery. Now let's talk about recovery methods. How can you recover from the deadlock is, you can follow two approaches. One approach is you can do some actions on the resources, right? And then you can recover from the deadlock. One is preempt the resources. Preempt the resources means whatever resources you have been using, you pull one of the resource from its user, from the owner, and give it to the others in a hope that the other one will finish using this and eventually release it, and therefore again you can give it back. But then this method really requires manual intervention, because you cannot write an algorithm to decide which resource has to be picked up, right? So manually we have to choose one of the resource and pull it out and then give it to the others. It is a headache, right? And the other one is roll back. So we will roll back to where some resources were not allocated. So right now you are going to see, for rolling back what we need is checkpointing. So while execution, we shall maintain various checkpoints, and then whenever there is a problem of deadlock, we shall go to the previous checkpoint or the system state where it was safe, right? See, let us say you are in state Sn, right? How did you reach there? You might have started from state S0 and from there S1, from there S2, so on here, right? And every state is going to be recorded, right? Every state is going to be recorded, right? And what we do is, whenever there is a deadlock in some state, we roll back to some state where it was known that it was safe, right? And that is called as rollbacking, right? When you roll back, then the resources will be released, some resources will be released, and then again will be in some state, and again we continue with the allocation of the resources, right? So anyway, you could either preempt one resource or two resources or n resources, or you could go back to a state where some of the resources will be completely released, where the system was safe. And now the other method is other method of recovery is, other than this resources, dealing with the processes. Fine. Now let's deal with the process. So there are two ways to deal with the process. One way is kill a process, and other way is kill all processes. right? If you kill all processes and then again restart them, definitely that method will work, isn't it? Why? All the processes are going to be deleted and again they are going to be created. But then the problem is you might have to again do all the work, right? Some processes might have worked for hours together and now you kill them and again you restart it, and therefore they are going to run for even more hours, right? Therefore it is a waste of time. But instead of that, if you could kill one process at a time and then see if that process, if it is removed from the system, is going to resolve the deadlock, right? If you are lucky, you'll be able to kill only few processes and then resolve the system to the safety, right? But then selecting that one process is going to be a big deal. I mean, it is going to be difficult. Why? One thing is sometimes you have to choose one of the process which is present in the loop, so that if you remove it, then the loop will be broken. Or the other way is you have to select a process which is not in the loop but then holding a resource which is present inside the loop, right? And now how to choose a process? It is always better that you choose a process which has done least amount of work, or which is not very important. So there are various strategies that are being followed, right? Anyway, killing the process is one of the solution. Understood this? So this is the last resort, which means we will not do anything about prevention or avoidance, then definitely there will be deadlock, and therefore it is the responsibility of the operating system to detect it and then recover it. Okay, so that is how this method works. Fine. CPU can directly access, if you have CPU, it can directly access registers and main memory, maybe cache, if cache is present, right? So these are the three main important memory elements in which you can put either the data or instructions, and CPU can access only this. But the problem is all these components are costly. So if you look at registers, they are very costly compared to cache, and if you look at cache, it is costly compared to main memory, right? And main memory is costlier compared to the hard disk, or let us say secondary memory. So main memory is nothing but RAM and secondary memory is nothing but the hard disk, right? So now what I mean to say is when CPU has only the access to these memory parts directly, only these memory parts, but the problem is you cannot go for very large amounts of main memory or very large amounts of register or cache, because your system cost is going to be very, very high, right? And then how much main memory you should really buy, that is one thing. Depending on the main memory, you are supposed to have the system cost also, right? So on your budget, depending on your budget, you are supposed to allocate something to the main memory. How much do you want to allocate? That depends on how much efficiency you want. Okay, what is the relationship between the main memory and the efficiency of CPU is, if you have a bigger main memory, then I could load more process. If I could load more process, if I load more process, then what happens is I could run more processes without stopping. I mean, I'll just take an example and I show you. See, what I mean to say is, if you have more main memory, then the CPU utilization is going to be high. But then I don't really say that CPU utilization is going to be 100% if the main memory is infinite. And that is not what I really mean to say. But then there is some correlation. Just watch it. See, now let us say I have a main memory of 16 MB and a process size of 4 MB, right? Now if I run only one process, if I have only one process, or assume that main memory is 4 MB and a process size is 4 MB, just forget about the operating system. Assume that operating system is already separately present in above the main memory in some other element, and my main memory is 4 MB completely available for the process which contains 4 MB. Then how many processes can I run? Only one process, right? Now if the process, this particular process, spends a fraction of p time doing IO, which means if you schedule the process, it will just spend a fraction of p time doing the IO, then what will be the CPU utilization? Then CPU utilization is equal to See, what is CPU utilization? The amount of time that you are going to use CPU running the program, right? But the program is saying that I need only 1 minus p fraction of time doing the CPU and the other p fraction of the time doing IO. Therefore, in that case, CPU utilization is going to be 1 minus p. Got it? What I mean to say is, if you have only one process in the main memory, or if the main memory is having a space to hold only one process, this is the process size. If the main memory is having space to hold only one process, then the problem with such a kind of arrangement is, if the process is going to take p fraction of time doing IO, then CPU utilization is going to be 1 minus p, isn't it? Now, if this p fraction is going to be 80%, which means if the process is going to spend 80% of the time doing IO, then what is CPU utilization? Just 20%, right? When p equal to 80%, isn't it? So there is a problem. Now CPU utilization is directly linked to the number of processes that can be present in this. Now let us say I am going to increase the main memory size to 16 MB. Then each process size is 4 MB. This is the main memory size and this is the process size. Then how many processes can I put? I can put 4 processes, isn't it? Now again, if each process is going to spend p fraction of time doing the IO, right, then what is the probability that all the processes will do IO at the same time? If p is the fraction of time each one is doing IO, then the fraction of time, the probability that all of them will do IO simultaneously is p power 4, right? And what is the fraction of time that CPU will be busy? 1 minus p power 4. In this case, CPU utilization is going to be this much, right? If I increase the number of processes which are present in the main memory, then the CPU, what it will do is, whenever one process goes for IO, it can choose the other process, right? The probability that all of them will be waiting for the IO is p power 4. Therefore, the CPU utilization in this case is equal to 1 minus this one. So if you assume that the fraction of time each process waits is 80%, then this is roughly equal to 60%. So with 4 processes in the main memory, I have increased the we are getting a utilization of 60%. Now let's see if I still try to increase it. Let us say from 16 I increase it to 32 MB, right? And each process is of size 4 MB. Then how many processes can I get? I can get 8 processes. 8 processes, and assume that the same p fraction of time each one is waiting for IO, then CPU utilization in this case, CPU utilization is going to be 1 minus p power 8, right? And it is roughly going to be 83%. Got it? So as I increase the main memory size, the number of processes that are going to be present in the main memory are increasing, and hence the CPU utilization is increasing, right? Will it happen like this? I mean, when I double the number of this process, it is going to be like this. So let us say I just want to examine one more. Let us say the main memory is now 48 MB and each process size is 4 MB. This is main memory size and this is the process size, and each process is waiting for p fraction of time for IO. Then how many processes can be present? 12 processes can be present in the main memory at the same time. Then what is the probability that all the 12 processes will go for IO? P power 12. Then what is CPU utilization in that case? In that case, CPU utilization is going to be 1 minus p power 12. So if you put 80%, if p equal to 80% of the fraction of the time it is waiting for IO, then we are going to get 93% roughly, right? So if you look at this gain, if it is 16 MB, then it is 60%. If I increase it by 16 MB, then gain is 23%. But if I increase it by one more 16 MB, the gain is not 23%, it is roughly 10%. Therefore, the gain is not going to increase linearly with the increase of the main memory. In fact, you can think of the CPU utilization like this. CPU utilization is 1 minus p power n, where P is on average the fraction of time every process is waiting for IO, assuming that n is the total number of processes in the main memory. I told you what is n? The number of processes that can be present in main memory at any time is nothing but the degree of multi-programming, isn't it? Therefore, CPU utilization is directly depending on, or somehow it is depending on, degree of multi-programming. If you increase the degree of multi-programming, CPU utilization is going to increase, right? So if I want CPU utilization to be 100%, see what is P? P is the fraction of time for which it is going to go for IO, and P is obviously a number between 0 and 1. It is a fraction, isn't it? Then what happens is, if I increase the degree of this multi-programming, if I say limit n tends to infinity, which means if I increase the number of processes that are present in the main memory to infinity, then CPU utilization is going to be, can you guess it? If this n tends to infinity, it is a fraction, it is a number less than 1, then this number will tend to 0, then CPU utilization will become 100% or 1, isn't it? So if you have to get 100% CPU utilization, this formula says that have as many processes as possible in the main memory. But how is that possible? Only if you have lot of main memory, then only you can have lots of processes, right? But then the problem is, if I have infinite main memory, it is obviously not possible, right? The reason is it is going to be very, very costly. So having finite amount of memory, we should try to increase the degree of multi-programming. How is that possible? Use the memory in such a way that it mimics or it acts as if it is infinite. Got it? Which means even though I have a finite amount of memory, I'll try to use it as if there are infinite number of processes or lots of processes in this finite amount of memory by using memory management techniques, right? So memory management is all about that. How could you increase the CPU utilization? By putting as many processes in the main memory as possible, right? But now it is going to lead to many problems. The problem is this: when you have only one process in the main memory, you can directly take the process, put it in the main memory, execute it, pull it out, fine. But when you have more than one process present in the memory simultaneously, then lots of issues will come into picture. How much memory are you going to allocate to each process? And how are you going to allocate it? How are you going to deallocate it, right? And how are you going to provide the protection among various processes? These are all the various things which you might have to look at it, right? Therefore, memory manager is not just responsible for allocating the memory and deallocating the memory. It is also responsible for providing security, right? There are various things that the memory manager has to look at. So one of the earliest techniques used in memory management is when you have lots of processes which have to be loaded in the main memory. The first technique used is this contiguous. So contiguous memory allocation is, so it is like this. There are two types. One is, if you have the main memory like this, main memory, right? And now what people did is, okay, one part of the main memory is always going to contain operating system, no doubt about it, and in the remaining part we could put as many processes as possible, right? So one technique what they did is they divided the remaining part into equal sized partitions, or fixed size partitions, we can say fixed size partitions, and then they decided that a process, if it has to run, it should be loaded in only one partition and it should be contiguously present in one partition, then only it can run. So using this method, it is called as fixed partitioning. Fixed partitioning means the memory is divided into partitions. In this case, let us assume that the memory is divided like this, and the size of this partition is, let us say, 2 MB, and size of this partition is 4 MB, 4 MB, and let us say 10 MB, something like this. And all the partitions can be of equal sizes or different sizes. Then what happens is, whenever we want to load any process and run, we are supposed to load the process in only one particular part, one particular partition, and the process is not supposed to span over many partitions. So using such a kind of architecture, there are some few problems here. So one problem is called internal fragmentation. So internal fragmentation means, let's say this, let us say one process has come and its requirement is 1 MB, the process size is 1 MB, right? So what is the smallest fragment that smallest partition that you could assign in case if 2 MB is freely available, I mean if it is not occupied by any process, then definitely you could assign 1 MB there, right? So what happens is the 1 MB process will be kept there completely and 1 MB will be wasted. So this 1 MB cannot be allocated to any other process. This problem is called as internal fragmentation. What is it? Internal fragmentation. So what is internal fragmentation is whenever you have a partition and in that partition if you try to put a process and if that partition is going to have some extra free space, then you cannot fill that free space with any other process, isn't it? Therefore this problem is called as internal fragmentation. So one problem with this fixed partitioning is internal fragmentation. Then there is other problem. The other problem is what is the maximum size of the process that could be run in this architecture. If a process is less than or equal to 10 MB, it can be assigned in this partition and it can be run. If the process is more than 10 MB, there is no partition which can hold it. Therefore, it may not be able to run in this architecture unless we use virtual memory. Virtual memory concept, we shall see it later, right? Therefore, other limitation is maximum size of a process may be limited by the size of the partition if we don't use either overlays or virtual memory concept, right? So one is internal fragmentation is there, and then there is limitation on process size, right? And other disadvantages is that there is something called as external fragmentation. So external fragmentation happens this way. Watch it. Let us assume that in this 2 MB 1 MB is kept and 1 MB is free, and is 4 MB, let us say 3 MB is filled up and 1 MB is free, and here also 3 MB is filled up because the process size is 3 MB and 1 MB is free, and let us say here 9 MB is filled up, right? So 1 MB is remaining here, 1 MB is remaining here, 1 MB is remaining here, and 1 MB is remaining here. All the free space put together, we have a total free space of 4 MB, right? And now even if a new process comes and if its requirement is 4 MB, even though we have 4 MB space freely available, we will not be able to allocate that 4 MB to this, isn't it? That is called as external fragmentation. So what is external fragmentation? Even though we have total free space available, we will not be able to assign it to a process because of the requirement that the process has to be contiguous. We are not allowing a process to fill up 1 MB here, 1 MB here, 1 MB here, 1 MB here. Our requirement is that if a process is present, it has to be contiguously present. It cannot be present in parts. That is the main concept of this contiguous memory allocation. So as long as we have contiguous memory allocation, there will be a chance of external fragmentation, right? So external fragmentation is there, isn't it? And the other disadvantage of this model is, one more disadvantage is the degree of multi-programming is limited, isn't it? If you watch it, at any time, at maximum only 4 processes can be present because we have only 4 partitions, right? Therefore, the other disadvantage is degree of multi-programming is limited or fixed. Limited means fixed. It doesn't vary, right? So depending on the size of the process, or the size of the memory, nothing, it is not going to vary, it is going to be static like this. So these are all the disadvantages we have. So with these many disadvantages, people rarely use this. In 1950s they used to use this in mainframes, but later they moved on to other architectures. So even though we have this, this is called as fixed partitions, right? Partitioning with fixed partitions, right? So in this method we have so many disadvantages. So we are not using it now, and we used it very long back. So I'm not going to discuss anything further about it, like how the process are allocated or anything. I'm not interested in discussing because it is never used, and definitely there are no questions on gate also. Okay. Now let's see dynamic partitioning or variable partitioning. It has got some advantages over fixed partitioning, and it is the next to this static partitioning, that fixed partitioning, dynamic partitioning is widely used. So just watch it, I'll tell you what it means. So till now we have seen this static partitioning, right? So in static partitioning what happened was, see, if this is the memory and some part of it is already dedicated to OS, then what we did is we have partitioned the remaining space like this, maybe 2 KB, 4 KB, 16 KB, something like this, 32 KB, something, right? And now any process which wants to come into the main memory, we are going to put it in one of the partitions. But the problem there was, if a partition size is 4 KB, let us say 2 KB, right? And if the process which has come is 1 KB, then I am going to put the process in 1 KB here, and 1 KB is going to be remaining, right? And because of that, this 1 KB is wasted. See, the main rule is this: either in dynamic partitioning or static partitioning, the rule is always a process has to take one partition completely, and it cannot span over two partitions, or we cannot put two processes in the same partition. So even though 1 KB of space is remaining here, that we cannot use. That is called internal fragmentation. Maybe if you could think of a cake example, let us say we have a cake, okay, and now we have already cut it into pieces like this, right? So anyone who wants to have the cake should take one piece, that is the rule, right? But then what happens is, someone might be on diet and he might not want to have the full cake. Maybe someone would be trying for a 6-pack, okay? In computer science we should not try for 6-pack, we should try for 8-pack, isn't it? Why? Because 8 is a power of 2, isn't it? In computer science everything has to be a power of 2, 2 power 3 is 8. Isn't it? So let us say you cannot take the big piece because you are trying for 8-pack, and even if you take this entire piece, you will just have a bite and waste it all. Then what is the other solution? Leave the cake as it is, like this, right? And let the user, whoever wants the cake, let him cut it. So you don't decide about this size, so just hand him over the knife, and whatever piece he wants, he will cut it. If you want a small piece, he will cut it like that. Got it? And that is the main difference between fixed partitioning and dynamic partitioning. This is fixed partitioning, which means the sizes of partitions are already fixed, and either you like it or not, you have to take one partition, right? Even if it is big for you, right? And sometimes what happens is, the problem here is some people might want bigger than this, but then the rule is anyone can take only one piece. Because of that, they might fall short. So the dynamic partitioning is, if you want a smaller one, you can take it. If you want a large one, yes, you can take it, right? So if you want this piece, you take it. If you want this piece, you take it, right? That is how dynamic partitioning works. So what I mean to say is, if you have the memory like this, and one part of it is for operating system that we are not going to touch, the remaining space, which is also called as user area or user space, right? So this entire part we are not going to make it into partitions. Let the process come, then I am going to create a partition. Now the partition will be equal to the process need. Then what happens? There is no wastage at all. Let us say now a process has come, its requirement is 1 KB, fine, good. I'll just create new one partition whose size is equal to 1 KB, and I'll put it completely there, right? Therefore there is no internal fragmentation, right? Very important. So if I go for dynamic partitioning, there is no internal fragmentation, which means you can completely fill up this space without any wastage, right? So there is some confusion here, right? What is external fragmentation? Generally, one definition is one definition. I am talking about one definition. External fragmentation is because of internal fragmentation. If there is some wastage in the memory, and if all the wastage put together is making up some size, right? I told you there. So let us say here 1 KB is wasted here, 1 KB, 1 KB, 1 KB, 1 KB. If in all the partitions, let us assume that 1 KB is wasted because of internal fragmentation, then how much is total wastage? 1, 2, 3, 4, 5. 5 KB is the total wastage, right? So External fragmentation is, even though we have 5 KB memory available at different places, we will not be able to use it because we had a rule that the process has to be contiguous, right? And process cannot be kept 1 KB here, 1 KB here, 1 KB here, 1 KB here, and moreover one partition can hold only one process, right? So if there is internal fragmentation, there is definitely external fragmentation, isn't it? If there is internal fragmentation, there is definitely external fragmentation, right? Are you following it? I think you got the reason, right? Whenever there is internal fragmentation, we will not be able to use that space even though the space is available. That is external fragmentation, right? But then if there is no internal fragmentation, you cannot say that there is no external fragmentation. That is very important. I'll just show you how it is possible, right? See, what I mean to say is, now whenever a process arrives, I am going to dedicate it the partition, or I am going to create a partition whose size is equal to that process, and therefore I am saying that the process is there is no wastage inside the partition, so there is no internal fragmentation. Fine. Now what happens? Assume that here it has, a process has taken 1 KB, right, and next process has come and it has taken 2 KB, and next process has come and it has taken 3 KB, something like this, and next process wanted 5 KB and we dedicated this 5 KB to this, right? And now assume that, and at some point this 1 KB process has run to completion, and therefore we have freed it up, which means we have removed the 1 KB process from this, and now 1 KB is available, this block is available, right? And this 3 KB is also freed up, and therefore this 3 KB is also vacated. This process which is there is pulled back, and therefore these two partitions are available now. So 1 KB is available and 3 KB is available. Are you following it? See, initially I have given the process 4 processes like this, and 2 processes have run to completion, and therefore I pull them back, right? Now there are empty spaces. One space is equal to 1 KB and other space is equal to 3 KB, right? Therefore what is the total space available now? 4 KB. 4 KB of free space is available. Now even if a process with 4 KB comes into play, and even if it wants the 4 KB, we will not be able to dedicate, or we will not be able to give 4 KB for it because it is not contiguous, right? So here also there is external fragmentation. Why? Because we have free space available at 2 points, as 2 parts, and since they are not contiguous, we are not able to dedicate it to, assign it to any process. That is called external fragmentation. Even though there is no internal fragmentation, there can be external fragmentation. So what is the reason for external fragmentation? So the main reason for external fragmentation is your rule saying that a process has to be contiguous, right? It cannot occupy various places. So if you have to have no external fragmentation, change your rule, or you say that a process need not be present contiguously. That is called paging. We shall see it later. Okay, so the main reason for external fragmentation is not internal fragmentation. People think that because of internal fragmentation there is external fragmentation. No, that is not true. But then if there is internal fragmentation, there will be external fragmentation. That is fine. But even if there is no internal fragmentation, here there is external fragmentation. And how are you going to what is the main culprit here? The rule that a process has to be contiguous, right? So if you can break that rule, if you can say that a process can be present as parts in various partitions, then you can say that there will be no external fragmentation, and that is what where we are going to use paging. But before going to paging, maybe we could try to solve it in some other manner. Watch it. Maybe before going to that paging, let's try to solve it this way. There is a gap here and there is a gap here, and these two gaps are not being dedicated to any a process of 4 KB because it has to be contiguous. Then what I do is I apply a method called as compaction. Compaction means pulling all the occupied parts together and pulling all the free parts together, right? So if this 2 KB and 5 KB are occupied, I am going to pull 2 KB and 5 KB together, and I am going to pull 1 KB and 3 KB together. Therefore if I do that, if I pull them, then the free space will be available at one place. So what is compaction? It is called as compaction. or some textbooks they even call it as defragmentation. So both are the names, but anyway the process is like this. You pull the occupied spaces together and you pull the free spaces together, so that the entire free space will come as one big block, and that could be dedicated to any process, because now it is contiguous, right? So that is the method, that is the solution for now, as of now. Later we have paging will solve this. In paging there is no compaction required, right? But then as of now we can solve it using compaction, but compaction has got its own disadvantages. So one disadvantage is when you are moving these processes around, which means when you are pulling this, like this, when you are moving the process up and then free space down, the entire procedure, all the processes have to be stopped for some time, because you are doing some work, isn't it? And now that is actually a copying operation in memory. We are going to copy the memory bits, right? I mean the data in memory from one place to the other place. So if you think that, let us say the problem is, in order to copy 4 bytes, if we need 4 nanoseconds, or let us say in order to copy 1 byte, if we need 4 nanoseconds, right? Then if the total memory is 256 MB, right, then it nearly takes how many? You can just multiply with this. 256 into m is, let us for now assume that m is 2 power something, 2 power 20, into 4 into nano is 10 power minus 9, right? So it is going to be a considerable amount of time. So what I mean to say is, whenever you have any memory like this, a very large memory, in order to do compaction, it is going to take some time, which is not very small, which will be in seconds, not in nanoseconds or milliseconds, right? So all that time the CPU is going to be idle, therefore the efficiency of the system is going to come down because of compaction. So even external fragmentation is not a good solution either. Internal fragmentation has many limitations, like the static fragmentation or fixed partition has many limitations, like internal fragmentation, external fragmentation, and limiting the degree of multi-programming and all this, right? And therefore we are using external fragmentation, but external fragmentation also has got one limitation, which means this compaction, right? So as even though it has got some limitations, it has got some advantages as well. Let's see the advantages of this external fragment, this dynamic partitioning. So dynamic partitioning or variable partitioning has got some advantages. One advantage is it is flexible, in the sense the degree of multi-programming is not fixed, isn't it? So degree of multi-programming, what is degree of multi-programming? The number of processes that can be present in the system at any time, right? It is not fixed, it is dynamic. So depending on the sizes of the processes, right, at every time, at every point of time, the number of processes that can be present in the memory are going to change. That is dynamic, right? And moreover, there is no limitation on size of the process, right? So size of the process is not limited by size of a partition, isn't it? Earlier, if a partition was of some size, you are supposed to use only one partition, therefore your process size is limited. But now it is not limited by the size of the process, it is limited by the total available free space, isn't it? So these are the advantages when we go for dynamic. So number of processes that can be present and the size of each process, they are going to be varying, and degree of multi-programming is going to be varying, and there is a lot of flexibility. Any process can be loaded at any point, isn't it? But along with this flexibility, right, we get lot of problems as well. The problem is earlier when it was static partitioning or fixed partitioning, there is only one list of partitions, and that list doesn't change. Let us say we had this 2, 4, 16, 32, 64. This list was there like that, and it never changed. But now using this dynamic partitioning, the list of free spaces and the list of used spaces both are going to continuously going to vary, right? For example, see this, watch it. So initially we have completely one free okay, the problem is this. Why should we do this is, I'm talking about disadvantages. Disadvantages of this dynamic partition is allocation and deallocation. Allocation and deallocation of memory is complex. It is going to be very complex. The reason is initially there is one contiguous free space available, right, a big free space, and later when we fill them up with these processes and the processes are moving out, they are going to create some holes. The terminology is holes. What is a hole is whenever a process is occupying a particular amount of memory and then suddenly it moves out, that particular slot is going to be a hole. I mean, that is a vacant slot, right? So because of this vacant slot, the problem is that, you know, when we are having, let us say a process is here occupying 1 KB, and when we pull it out, there is going to be a hole created, right? So because of that hole, you know, the management is going to be very difficult, because as a period of as we you know go as we have you know done this process for, let us say, for some time, the number of holes created will be very high, and now the managing all the holes is going to be a headache, right? So here how many holes are there, or how many partitions are there? 1 2 3 4 5. So managing five partitions is very easy, right? Maybe you could have an array containing 5 elements, and each array will say whether it is occupied or free, and therefore it is very easy, right? But then here management is going to be very difficult, in the sense as the time grows, you know, the number of partitions, they keep on changing dynamically, and the number of holes will get created and some holes will get managed, and therefore the management is going to be really a headache, right? And after managing it, see, keeping track of what are the holes and what are the processes is one thing, fine. And the second important thing is how are you going to allocate and deallocate, which means what are you going to do whenever you are going to, you know, assign a hole to a process, and whenever a process vacates, right? Either it will lead to creating a new process or creating a new hole, isn't it? Therefore it is going to be really headache. So there are various data structures which are used in order to keep track of what are the holes and what are the use spaces, first thing. And then there are various algorithms used on these data structures in order to allocate and deallocate the memory. Now let's see what are the various algorithms that are used on the linked list that I have shown you just now, that you know, linked list, in order to find out a hole and allocate it to the process. And these methods can be applied even for the fixed partitioning or static partitioning. Let's talk about variable partitioning. Okay. So first one is first fit. First fit means whenever you require, you are required to add any okay, let's take this example and I'll show you. I'll better use an example here. Let us say I have a memory like this, operating system, and then there are 4 blocks, and one block is a hole and its address is 0 to 100, and other block is a process, its address is 100 to 199, let us say it is 0 to 99, and other block is a hole, address is 200 to 299, and other is a process, address is 300 to 399, right? And this is the organization I had. So there are 2 holes and there are 2 processes, and if you look at the linked list for this representation, it will have like this, right? Hole and starting address is 0, ending address is 99, right? And then a process, starting address is 100 and then 199, right? And then a hole, starting address is 200 and ending address is 299, and then a process, starting address is 300 and ending address is 399, right? And it is a linked list. As I told you, it is a double linked list, right? And it is the head. Fine. And now what does this first fit say is scan the entire list, right? Whenever you want to allocate any memory to a process, scan the entire list and then see whenever you find a process, the first process which is big enough to hold the first hole which is big enough to hold a process. Let us say I got a request from a process and it needs 50 bytes. This is the request I got. Then how does this first fit algorithm work is, it starts from the beginning and it scans the list and it will find out what are all the holes, and it will find out and it will stop whenever it comes across the first hole which is big enough to hold this 50 bytes, right? Let's see this. Now when it is scanning the entire list, first thing is it comes across this hole, right? And the size of this hole is 100 bytes, isn't it? So 100 is less than 50, 100 is greater than 50, and it is the first hole which is big enough to hold this 50 bytes, then it will allocate it. That is first fit. So what is first fit is, scan the entire list from the beginning, and whenever you come across any hole, what can I say, a hole which is big enough to hold the process, you give it away. Then what are the implications here? Whenever you give a hole to a process, then you have to break the hole into two parts: how much it is occupied and how much it is free. That is the beauty of this dynamic allocation, remember. So in fixed allocation, whenever you allocate a process to a block, you cannot allocate the remaining space to other one, right? But here whatever is remaining, that will form a new hole, right? So which means now if you allocate this 50 bytes here, which means if you allocate a new process here in this place, right, then what happens here is, this hole will get broken into two parts. One part will say now a process is present from 0 to 49, and then the hole is from 50 to 99, right? So because of now you understood. So whenever you create any process, then the number of elements in the list are going to increase because they are going to split up, right? A process and whole, like that, right? And whenever you take a whole and allocate it to a process, it is going to split up, and it is always going to happen. And whenever you delete a process, it might merge with the other process, or it might merge with the other holes, or it might merge with or it might create a hole there. I'll just tell you what happens, right? So this is how it is happening. And then in order to implement this, we are going to maintain the list in the increasing order of the starting addresses. Now let us say after some time this process, this one got freed up, which means 100 to 199 got freed up. Then how is this algorithm going to work? See, in the PCB, if you look at, if you know that, remember that PCB, process control block. From that PCB, whenever you free up a process, whenever a process is over, there will be an entry from the PCB to the node which contains the entry in this list, right? So somehow you could directly come to the node in the list for which you have to free up the memory. How is that possible? In that PCB, we can even maintain a pointer saying that see, this process was holding this memory. So whenever you try to release that process from the PCB, or whenever you are trying to stop a process and kill a process, then you can even go to this list, directly come to that point where it was allocated, it was holding some memory, and you can free up there. Which means, see, you can directly come here, right? And you can now see what is adjacent. So adjacent, there are two holes, right? So whenever you try to free it up, you can create a new hole, new bigger hole, because two sides it is hole, right? So now it is a new bigger hole. It is starting from 50 and ending with 299, right? So and now you can have the adjustments like this, right? And you can delete all this, right? Therefore first fit is really very efficient. In the sense, it is faster to find out a node which is free to a hole which is free to hold the process. That is first thing. And second advantage is maintaining it is easy, in the sense whenever we free up any process, it is very easy to merge the holes together, right? And first fit is the most widely used algorithm among all this. And then even in malloc, so if you remember that in C there is a memory allocation function, right, malloc, that is used to allocate the free space from the heap. And even heap is a kind of dynamic allocation, right? Dynamic partitioning. Whenever you ask for a memory element, it is going to be dynamically created in the heap, right? So even in that dynamic allocation part inside the heap, the first fit algorithm is going to be used. Now next one is next fit. Next fit says that earlier, let us say you have allocated a process here, right? So wherever you have scanned, whatever part you have scanned earlier, you start scanning from there. So what is the difference between first fit and next fit is, next fit is exactly first fit, but then we'll start scanning the list exactly at the point where we left it earlier. Let us say we have a very big list like this, and last time we allocated a hole here. Then next fit says that don't scan from the beginning, scan from this part. So next fit, the idea behind next fit is, since we have already scanned the list once, the probability of finding a hole will be better if you start from that point. But then simulations have shown that next fit is not better than first fit. So after doing this, after proposing this next fit and implementing it in some of the systems, later when they found out using simulations means we tried some experimentations and we shall see which one is better. So simulations have shown us that next fit is not really better than first fit. So first fit is better. So next fit is not really used these days. And next one is best fit. Best fit is among all the holes which are possible present, you find the smallest hole which can accommodate the process. Which means, assume, let's say I have many holes in my list like this. Let us say there are many holes in the list, and each hole is, let's say this is a process and this is a hole whose size is 20, maybe 20 MB, right? And again there is a process and there is a hole whose size is 10 MB. There is a process, there is a hole whose size is 5 MB, and there is a process like this. If you have this process, then what happens is this best fit will try to search for all the holes. Among all the holes, it will choose the smallest hole possible and will allocate it will allocate it to the process. Let us say I got a process request of 4 MB, which means now a process wants 4 MB space. Then what will best fit do is, it will search all the holes. One hole is 20 MB, 10 MB and 50 MB, right? Then it will allocate the process with the smallest hole possible, which means it will allocate the process with 5 MB, right? So what will first fit do? First fit would have allocated 20 MB, but best fit would allocate 5 MB. The idea behind it is, if you allocate the smallest hole possible, then it will not waste a lot of space. That is what the idea behind it. But the problem with this best fit is, even though we could find a hole early, we are supposed to search the entire list. Therefore it is going to take order of n time, right? So we have to search and scan the entire list and then decide which one is smaller. So one thing is, it is slower because of this searching, and second thing is, when we try to allocate a smallest hole to a process, the remaining space, the remaining hole is going to be very small, that it will become really useless next. The reason is, it will create very small holes, and this small hole cannot be allocated to any big process or any process on average, right? So two disadvantages of this best fit is, it is slower compared to first fit, and second thing is, it will create very small holes, and so best fit is not actually best. Best fit is not a practical one. So the better one is first fit. So the first fit is faster, and second thing is, whenever we allocate by simulations we found out that whenever we allocate any hole using first fit, on average the hole created next because of this allocation will be larger than the hole created by the best fit, and therefore that larger hole can be used for some other process. Getting this? See, in this case first fit would have created a hole of 15 MB, I think 16 MB. If I allocate 4 MB here the whole remaining new hole created will be 16 MB, and here the new hole created will be 1 MB, and 1 MB is a smaller hole, and therefore it might not be taken up by any process. But if you create a bigger hole, larger hole, then it will be having a good impact later, right? Later a process can take it. So again, even compared with the best fit, again first fit is better. Even though name says it is best, it is not actually best. Using simulations we found out that it is not really best, it is worst. The reason is, it is taking up a lot of time to search for the best one, and second thing, it is creating very small hole. And next one is worst fit. Worst fit says the same thing. You scan the entire list, and then you find that is scanning is same, but then you find the biggest biggest hole possible, and then you assign the process, right? So in worst fit, let us say this is 100 MB, not 10 MB, it is 100 MB. Then what will worst fit do is, if you have to allocate 4 MB, it will scan the entire list, See, according to first fit, this is allocated, right? And according to best fit, it is allocated. Now, according to worst fit, it will take the largest hole, which is 100 MB, and it will try to allocate it. So when you try to allocate this 100 MB hole, what is the problem there? We get the largest hole possible, but the problem is searching for the worst case or the largest hole is again going to be a problem, isn't it? So even this worst fit is also not better than first fit, because search time is going to be very high. See, yes, the hole produced will be larger, but then the search time itself is going to be very high, right? So again, compared to worst fit, first fit turned out to be better. So next fit or best fit or worst fit, first fit turned out to be the better one, right? And then there is one more modification which is called as quick fit. Quick fit says that there are normally some sizes, some process sizes which are most frequently used. Therefore, it says that for all the most frequently used sizes, you maintain a linked list, which means it says that maintain a linked list which will contain most frequently used sizes. Let us say most frequently used size is 2 MB, then this list will contain all the holes which are having size 2 MB, or all the holes which are having size 4 MB, all these holes which are having 8 MB. Like this, if you maintain individual lists of holes which have this capacity, then allocating them will be easy. That is what this quick fit says. Quick fit says that maintain different lists for frequently used sizes, but it is not really practical. Yes, it can be practical, but it is a waste in the sense we might have to maintain different lists, and then whenever you try to free up a process, then that is going to take a lot of time, because you have to go to the process and then find out what are the adjacent lists, and you might have to expand the whole, and it is going to be a very hectic thing. Yeah, it is quick, but then it is not very fast. In the sense, allocation is quick, but deallocation is going to take up a lot of time. And see, all these assumptions, whatever analysis I did till now, it is all based on the assumption that the list is maintained in the increasing order of the start addresses, and then it is a double linked list. But then you could do, if you are very much inclined towards implementing one particular kind of algorithm, then you might have to modify the list in such a way that this data structure will help you in implementing that algorithm fast. See this, many times the running time of algorithms depend on the data structures you are using, isn't it? So maybe you could modify the list in such a way that it will support some of the algorithms. For example, for first fit you need not do anything, the increasing order of this one is going to be enough. For next fit also nothing is required, but for the best fit it will be better if you sort out the if you sort out the list in the increasing order of the sizes of the holes, which means if you sort it out in such a way that the smallest hole comes earlier and the largest hole comes at the last, if you sort it out like that, then best fit will have the same performance as the first fit, because the first one, which is a fit, is nothing but the best fit, isn't it? But it is going to have some, see what I'm trying to say is, see, let us say I have a process, a hole of size 50, and a process, a hole of size let's say 100, and a process and a hole of size 10, right? Now what is that we could do is, we could separate out the holes from the processes, and these holes could be sorted out on the increasing order of their sizes, which means the hole with capacity 10 will come first, and then the hole with capacity 50 will come next, and then the hole with capacity 100 will come next. If I do this kind of sorting, right, and now if I search this list for the smallest fit possible, the best fit possible, here the first fit is going to act as the best fit. But then separating out the holes and then sorting them in the increasing order is going to have lot of impact when you are trying to free up the process. Now when we try to free up the process, they are no longer present in a way where this combining is possible. Earlier they are present in a way in which the combining, the merging of neighbors to form a bigger whole was possible, but now here the combining is not possible, isn't it? So anyway, it is going to be inefficient. And overall, the reason is why many of the algorithms are inefficient even if you try to change the data structures is allocation is going to happen, as well as deallocation is also going to happen frequently, as frequent as allocation is going to happen, isn't it? A process will arrive as well as a process will leave. So even though you try to optimize the allocation time, the deallocation time may be very high. So overall, the bottom line is first fit is the best one, and many of the existing systems wherever this contiguous allocation with dynamic partitioning is used, first fit is used, and no other algorithm is actually beating this first fit. People have tried various variations, and they are trying to optimize one kind of either allocation or deallocation, but then not both of them. First fit is working fine, right? So in C, malloc, we shall again see it in the C programming language, but remember that in C, malloc function is going to use first fit algorithm, and it is faster compared to any other algorithms, right? Fine. So sometimes what happens is, compared to the size of the biggest partition, the size of the program will be even more. Then in that case, what should we do is we should go with overlays. So overlays based on the concept that the program will not use all the entire code or all the sections at the same time. It might use only a part of it at any time, right? So the best example is assembler. So assembler, let us say assembler has two pass. Two pass means at any time it will be doing only one thing, either the first pass or the second pass, which means it will finish the first pass first and then the second pass. So now the code is like this. When it is in the first pass, it wants the code of 70 KB, which means it wants a space of 70 KB, and then along with that it needs the symbol table and common routines. So when it is in first pass, the total memory required is 70 plus 30 plus 20, and in the second pass it will not use the first pass memory anymore, and it will use 80 KB, and then it will use symbol table and common routines, right? So if you look at the process at a whole as the as one entity, it will contain the first pass requirement, second pass requirement, symbol table and common routines, and all of them put together is going to be 200 KB. Therefore, if you don't have the concept of overlays, you are supposed to have a partition which is going to hold 200 KB. But in case if your memory, it is not the case now, earlier long back, if your memory doesn't have a capacity to support more than 200, more than some 150, let us say 150 KB, or even the longest partition is not able to give you the provision of 200 KB, then what are you supposed to do is use the overlays, right? Then what is that they are saying is, at any time only one pass will be in use, which means either first pass or second pass, and both the passes will always need symbol table and common routines, which means symbol table and common routines is a must, right? Then if the overlay driver is 10 KB, what is overlay driver is? It is the user responsibility to take care of overlay. Operating system will not provide you anything, which means it is user should write even what part is required in first pass, and once the first pass is over, user should write the code to pull out the pass 1 and load the pass 2, and again once the pass 2 is over, he can pull out the pass 2 and then maybe pass 1 if required, right? So that is what is the responsibility of the user. So that is called as overlay driver. Overlay driver will just help us in moving out and moving in the various parts of the code, right? If the overlay driver is 10 KB, then what is the minimum partition size required? Then if this is the case, they are asking how much minimum partition do you want. Now let's analyze this. Now in pass 1, we need 70 KB plus symbol table and common routines, right? So symbol table, in pass 1 we definitely need this memory because they are saying that it is required in pass 1, and then symbol table is definitely required, and then this one, right, common routines. And then in pass 2, how much memory do you need? 80 KB plus 30 plus 20, right? So either you are in pass 1 or in pass 2, you are supposed to use the driver, right? And the driver size is going to be 10 kb, right? And then 10 kb. Now add all this, 70 plus 30, 100, 100 plus 20, 120 and 130. So pass 1 requires 130 kb and pass 2, 80 plus 30, 110, 20 and then 10. Right, 140 is it? 140 kb, right? Therefore you need so how much is this? 70 plus 30, it is 130 and then 140, yes. So therefore how much memory do you need? So in total you need either 130 or 140. So if you have a if you have this partition which is big enough to hold 140 kb, then you can comfortably finish running this, right? So even though the total memory required is 200 kb, you don't need it at the same time, right? Given this amount of memory, using the concept of overlays, you could finish your program. That is the advantage of overlaying, right? Fine. See, what is the main disadvantage of this partitioning? External fragmentation. Internal fragmentation has been completely removed by dynamic partitioning, but still external fragmentation is going to be there. And other than this compaction, the only method using which you can remove the external fragmentation is by letting the process be non-contiguous, which means like this. Watch it. Let us say we have the memory like this, and some part of it is taken by operating system and the remaining part is occupied by various processes. And in a course of time, what happens is there will be some holes forming. Let us assume that there is a process from here to here, and again there is a hole, and there is a process from here to here, right? So let us say there is a hole here of 1 MB and there is a hole here of 1 MB, right? Fine. Now a new process of size 2 MB has come, and now it is asking for the memory. The new process, this is the process of size 2 MB, right? This is the process. Now we cannot allocate this process either here or here completely, and therefore it is leading to external fragmentation in case of contiguous allocation. Now if you remove that restriction and say that a process can even be present non-contiguously, then you can happily run it, isn't it? Then what I'll do is I'll try to divide this process into two parts, right? And then maybe put one part here, 1 MB, and put other part here, and then run it. But the problem here is this division is going to be a headache. The reason is here you got 1 MB, 1 MB, and sometimes you might get 1 MB, 2 MB, 3 MB, like that. Holes will be created randomly, right? So dividing a process according to the holes is going to take a lot of analysis, and a lot of code has to go into it in the operating system, right? So better than this, they have come up with another solution. What they did is, we could expect that at any time the process would have to be might have to be divided. Then what is that they are proposing is, so if there is a process, you don't wait till the point where it might have to be divided, you just divide it right away. They want to divide the process into small parts, and then they want to divide the memory also into small parts, many parts like this, right? In such a way that each part is able to hold one part of this, and this part, the small parts in which the process is divided, this is called as a page, and the small parts in which main memory is divided, these are called as frames. And the names are so chosen in such a way that it is logical. A frame is going to hold a page, right? And a page is going to go and sit there. Now whenever you have these frames in a non-contiguous manner, you can directly take some pages and you place them in a non-contiguous manner without worrying about how to divide them. If it is already divided, then operating system need not worry about it, right? And I think you understood this, right? So why we need it is, we don't want to divide it randomly whenever the requirement has come. We are going to initially divide it and then use it. So maybe so now you understood this. This is a page. Page is nothing but dividing the process into small parts. Then each part in a process is called as page, and dividing the memory into small parts, each part in the memory is called a frame, in such a way that the division is happening in such a way that the page size and the frame size both are same, which means a main memory frame will be able to hold a process page. That is the concept. So what is the advantage of this paging is, now let's see this. I'll just show you how it works really and what we should be doing about this. Now let us say our main memory is having 16 KB. Let us say this is the main memory, right? And main memory is having 16 KB, and assume that I am having 16 KB, and assume that I am having pages in such a way that each page is of size 1 KB. Then how many pages? Okay, it is frames. I am having frames in such a way that each frame is of size 1 KB. Then how many frames will be present in this main memory? 16 frames, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16 frames, right? So let me number the frames. Frame number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 0 to 15 is 16 frames, right? And now say I have 4 processes running or 4 processes in use, and each process is again divided into pages in such a way that the page size is also 1 KB. I told you the page size and the frame size both have to be same, so that you need not divide it, we can directly place it there. Now let us say I have 4 processes, P1 which contains 4 pages and each page is 1 KB again, right? And then P2 which contains 4 pages, and then P3 which contains 4 pages, and then P4 which contains 4 pages. Assume that the process P1 has to be loaded into the main memory and it has to run. Initially, when all the pages or when all the frames are free, you need not go for non-contiguous allocation. That is madness. Whenever you have a chance to load the process at one place, load it, right? Since you have the liberty to load it at random places, I mean non-contiguously, you need not take it and put it at various places, right? So initially, when you have the chance to run it put it at the contiguous places, put it. So now let us say process P1 has been occupying all the 4 frames of the memory, and then process P1, and then assume that process P2 has come for execution, and then we are going to allocate it 4 frames, right? So process P2 has 4 pages and all the 4 pages are loaded into 4 frames. Similarly, process P3 is again loaded into 4 frames, and process P4 is loaded into 4 frames, right? And say now the process P2 and P4, which are now in the main memory, which means in the ready queue, wants to perform some IO operation, and so they have to be taken out. The reason is, if once I take out these process which are waiting for IO, I could put in that place some other process which are willing to run. So assume that I have pulled out P2 and P4, which means during the course of the execution either P2 and P4 got completed or P2 and P4 got blocked because of some event, and therefore I am going to take them out and then put them back in the hard disk, so that I can take other process and put it in the main memory so that it could run. So now I am going to take it out, P2 and P4, and when I pull out P2 and P4, right, now there are gaps in the main memory, right? So in case if there is no this paging concept, then you could think of this as a gap, isn't it? These are holes. In case if this is contiguous allocation of dynamic allocation, then these can be compared as holes, right? And these 2 holes might not be useful later if a process wants to use them completely, but because of the paging, the advantage is this. Now let us say we have a process P5, right, which has 8 pages, 1, 2, 3, 4, 5, 6, 7, 8 pages. Then if the requirement of P5 is 8 pages, even though the 8 pages are not contiguous, 8 frames are not contiguous, you can take 8 pages of P5 and you can allocate them in the non-contiguous region. So this is how external fragmentation can be eliminated. So now P5 can be loaded here. P5, 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 right? So that is how P5 can be loaded. Fine, understood this concept? Now using this concept, you can, I'm saying that you can avoid the external fragmentation completely, right? So even though the memory is at, without any compaction, we are going to use the memory which is not contiguous. But then it is going to present us with more challenges. Here the problem is, how are you going to map the addresses? In this sense, according to CPU, right, a CPU doesn't know that your process is actually partitioned and then split up across many parts, right? So CPU is going to generate an address asking for something belonging to a process, and that address we call it as logical address, right? So here the problem is this: since we are going to put a process and then again pull it out and again put a new process, I cannot go for load time binding. Load time binding means I cannot ask a loader to convert the that relocatable addresses to absolute addresses. If that is done by the loader, then we will not be able to pull one process out and again put it back, and again let us say next time P2 might have to be kept in some other location. We cannot do that. When the processes have to be moved around even after loading once, then we need runtime binding. So whenever we need runtime binding, we are not going to convert that relocatable addresses to absolute addresses during the load time, and this has to be done during the runtime, which means whenever any process CPU asks for an address on the go, this address has to be converted to the actual address, that is called physical address. Now we need something in the middle which is called as memory manager, right, or memory management unit, which will take the address generated by CPU and then it should convert it into the actual address. I'll take an example and explain you. Watch it. Now let us say CPU is running the process P5 and it wants some address from the P5, from this one of P5, and it doesn't know that P5 is actually present in parts like that in the main memory. Then it will think that P5, CPU will generate the addresses as if they are relocatable, which means CPU will generate the addresses assuming that the process is starting at address 0 and it will count like this 0, 1, 2, 3 like this, but then they are relocatable addresses which are not absolute addresses. Therefore there has to be some method of conversion. Do you remember how we converted in case of partitioning? We had a register which is called as relocatable register, which is going to contain the base address, and to that base we are going to add something and then we are going to get the physical address, isn't it? Please go back to that relocation. There you have got it. There I explained it clearly. Now here also we need something like this, using which we'll be able to convert this logical address, which means CPU is thinking that the process is running from 0, 1, 2, 3 like this, but then process is not running like that. Process is at some other point, right? Now whenever some logic address is generated by CPU, it has to be converted to the physical address, and therefore that physical address should point to the exact location, isn't it? So we need something called as memory management unit or memory manager. Now how that memory management should perform is, see this, assume that CPU is asking for, it is running P5 and it is 0 and 1. So from the page number 1, this is page number 0, page number 1, from page number 1 of P5, let us say it wants the 10th word. From page number 1, it wants the 10th word. That is what CPU wants. And now if you watch it, the page number 1 of P5 is loaded in page number 5, frame number 5 of main memory. Therefore the 10th word in first page of P5 is equal to 10th word of 5th frame in the main memory, isn't it? So whatever address is given, you have to split it first into two parts. What is the page number it is asking and what is the offset? Let us say the page number is, are you understanding it? I'll take an example and I'll explain you, don't worry. So whatever address CPU is asking, we have to split it into two parts. One is what is the page number and other is what is the offset. right? So let us say it is asking for page number 1 and the word number 10, right? Then word is nothing but a byte. So in this case, okay, don't worry about it, word and byte, I'll explain that concept later. For now, understand that it is a byte. Okay, let's not use the word, it is byte, which means in page number 1 I want the 10th byte. That is what I want from the CPU. So CPU's address, right? So CPU's address has been broken down in such a way that from page number 1 I want the word number 10, right? And whenever this is generated, the corresponding logical address should be mapped to the physical address. So where is page number 1 present? Page number 1 is present in frame number 5. Therefore, this has to be taken by this memory management unit, and it has to be converted like this. What is the frame number in the main memory and what is the offset, right? So the frame number here is 5, isn't it? Because zeroth page is loaded here and first page is loaded here, right? So the page number 1 of P5 is present in frame number 5 of the main memory, right? And the offset is remains same. So the offset we are going to leave it as same, but the page number has to be converted to the frame number. Therefore, the entire purpose of memory management unit or memory manager in case of this MMU, in case of this paging, is converting the page number into the frame number. So yes, eventually we have to convert the logical address into physical address. In order to convert the logical address into physical address, we are going to convert the page number into the frame number. I think I have given you the conceptual view of the concept, but then let me get into the details and I'll show you how it is done. Okay, anyway, what I mean to say is whatever address CPU is going to generate, that is nothing but the relocatable address. Relocatable address means CPU assumes that the process has been loaded from address number 0, which is not true. And now that relocatable address has to be converted to the physical address. Physical address means where is the process actually running. Therefore, whenever CPU asks for address, when it is running some process, it is not actually the address that you should fetch from the main memory. You should convert it into the physical address. So logical address has to be mapped to physical address. That mapping is done using the memory management unit. And for that mapping, it converts the logical address into page number and offset, and then using the page number it will try to get the frame number. Now frame number when concatenated with the offset is going to be the actual physical address. So once the memory management unit generates the physical address, then it will put that physical address in the memory address register. I'll talk about memory address register later in CO. Okay, or you can think of it like this. Once we get the physical address, we'll present the physical address to the main memory, and main memory will take that physical address and take the word or the byte which is present there and will give it to the CPU. That is the entire procedure. Now the basic of this, the smallest addressable unit in a computer is called as a word. So what is it? Word. You might have heard about this one, right? Word. So even though there are bytes, we rarely have byte as the basic addressable unit, which means we count the memory in terms of the words, and we count everything in terms of the words, size of the entire memory or size of the page or size of the process. What is a word is the smallest addressable unit in a computer is called as word. And why are we interested in words? Because depending on the number of words we have, the addresses are going to depend on that, and depending on the addresses we need, the address size in bits is going to depend on that, right? So what is a word? The smallest addressable unit in a computer, right? And how does this concept of word come into picture is, maybe if you remember this RAM, the concept of RAM, right? There is a decoder, and decoder is going to be given some input. You please refer to the digital where I have discussed about the concept of RAM there, right? And it is, let us assume that it is a 4/16 decoder. So what is RAM? It is a combination of maybe let's talk about, instead of talking about RAM, let's talk about ROM first, right? What is a ROM? ROM is a combination of this this decoder and then this one, right? And then the matrix, isn't it? So let us say 4/6. Now this this entire part is nothing but the data, and this entire part is nothing but the address, right? So whenever you give it some address, one of the line is going to be activated, and whenever you activate one of the line, how many bits will come out, that will depend on number of the vertical lines. You please refer to the digital and again come back here, only the ROM concept. What I mean to say is, whenever you give the memory unit some address, it is going to give you as output some number of bits. It is not just going to give you 1 byte. It might give you sometimes 2 bytes, sometimes 4 bytes, or sometimes just 1 byte. So in that case, one address is going to give you those many bits, right? And all those bits are collectively going to form as word, which means there is no way you can read anything less than that, because your system is configured in such a way that you give it some address, it is going to give you some fixed number of bits, and that is called as word. Got it? And sometimes what happens is, the number of bits that comes out will be 8 bits, then it is nothing but one word equal to 1 byte. And sometimes 16 bits will come out, in that case one word equal to 2 bytes. Sometimes 32 bits will come out, then one word equal to 4 bytes. So depending on how many bits are going to come out, whenever you give it some address as input, we are going to define a word, and the word size can be anything, right? And now once you define the word, then you can define the addresses, right? Let us assume that we have the main memory here, which is RAM, which is made of flip-flops. We have main memory, and in the main memory we have 128 words. If 128 words are there, then in order to address each one of them, how many bits are required? Log 128 base 2, which is nothing but 7 bits. Got it? So depending on the number of words, we are going to derive the number of bits required in the address. So I think you understood the concept of words. Now let's go back to the concept of paging, right? So before going ahead, now there are some terminologies which you should be knowing about. So one is called as physical address space. The physical address space is nothing but size of the main memory. So generally they will give it in words, right? In case if they don't give it in words, it is better that you convert it into words. So sometimes they'll say that the physical address space is let us say 128 KB, 128 kilobytes, right? Then how much is this? 2 power 7 into 2 power 10 into bytes, right? So what is it? 2 power 17 bytes. This is what they are given. And now they might say that word size is 4 bytes, right? Then how much is this? 2 power 2 bytes. Then if this is the case, then what is the size of the physical address space in words? Physical address space in words equal to 2 power 17 divided by 2 power 2, which is nothing but 2 power 15 words. Got it? And once you find out the number of words, then you can find out the number of bits required in order to address each word, right? If I have 2 power 15 words, then how many bits are required to address each one of them? 15 bits, isn't it? Then in that case, physical address, this is called physical address. Physical address is going to be 15 bits. Got it? So always find out the physical address space in terms of words, and once you find out the physical address space in terms of words, then you can find out the number of bits required in the physical address, right? So in general, if physical address space is going to be, let us say m words, right? Then physical address, which means number of bits required in the physical address, is going to be log m base 2 bits, right? This is the physical address, right? And similarly, there is one more concept which is called as logical address space. So logical address space is nothing but the size of the process. So what is physical address space? Size of the memory, main memory. Logical address space is size of the process. Why is it important? Because sometimes your space, your process might be smaller than your physical address, or your process process might be larger than the physical address, right? And we have to take care of both of them. So next one is called as logical address space. So what is logical address space is equal to size of a process, and this number varies from process to process because every process can be of different sizes, right? So let us say logical address space is equal to 256 MB megabytes, and now you find out the word size. Word size will be given already, right? So what is 256 MB? 256 is 2 power 8 and M is 2 power 20 and bytes, so which is nothing but 2 power 28 bytes, right? And then you can find out the word. Let us say word size is given as the same thing, 4 bytes, right, which is nothing but 2 power 2 bytes, right? Then what is logical address space in terms of words? 2 power 28 divided by 2 power 2, which is nothing but 2 power 26 words, right? So once you find out the logical address space in words, then you can define the logical address. Logical address is nothing but number of bits required to address the logical address, right? Now logical address is number of bits required to address these many words, right? Then how are you going to find it out? And then if 2 power 26 is number of the words, then obviously it is going to be 26 bits. So 26 bits is going to be required in order to address the logical address. Understood this? So in general, if logical address space is equal to let us say L words, then what is logical address? The size of logical address is going to be log L base 2 bits. Got it? So what is the relationship between logical address and physical address? Actually there is no relationship. That is the size of the memory and this is the size of the process, right? So earlier what used to happen is we used to always have programs or processes whose size is less than the main memory. Then what happened was the entire process could be loaded in the main memory and it could run. But later what happened is the size of the process have become so large that they are not able to fit in the main memory, right? So watch it. What happens here? If the physical memory is only 128 KB, but if the process size is, what is logical address space? Process size. Process size is 256 MB. Obviously we cannot place it in the main memory completely, right? Then the concept of virtual memory has come into picture. So what is virtual memory is, you can run a process even without having the process completely in the main memory. You can have only partial part of, which means only some part of process you can have it in the main memory and still you could be able to run it. That concept is called as virtual memory. And when is it going to be useful? This is going to be very useful whenever the size of the process is very much higher than the main memory, right? That is how the virtual memory concept has been introduced. So what is virtual memory? The concept is simple. Whenever you can make a note of it, whenever the size of the process is larger than the size of the main memory, we are going to put only a part, which means partial amount of process in the main memory, and we will be able to run it. That is called as virtual memory. So initially it has been proposed in order to handle the cases where the size of the process is very much higher than the size of the memory available. But later it has been used to take the advantage of increasing the the degree of multi-programming. Now even though the processes sizes are less than the size of the main memory available, still we try to accommodate as many processes as possible in the available space by putting only the partial amount of each process. So now virtual memory concept has been implemented to increase the degree of multi-programming. I don't know whether you are following it or not. Just watch it. Here I'll explain you. See, why was this virtual memory concept was introduced is, initially in the earlier days, whenever you have main memory size like this and the process size like this is the process, and obviously process size is greater than main memory size, and we will not be able to place entire process into the main memory to run it. But then at any point of time we require only a part of the process, not the entire process, right? and therefore we are taking a part of the process and then we are loading it into the memory and we are running it. So this concept is called virtual memory. Virtual memory is having a part of the process in the main memory, not the entire process, to start running. That is called virtual memory. Till now we have never seen anything like this, as we have seen it in overlays, and overlays is handled by user, not by the operating system. Now virtual memory concept is implemented by the operating system. You need not know about it, which means a programmer will get a illusion that lot of memory is available at his disposal. So according to programmer, he can think that infinite amount of memory is available and he can write the program of any length. And operating system will take care of the limitation. If the physical memory is less than what is the memory given available for a process, then operating system is going to implement the virtual memory concept. Got it? And later what happened is, even though the process is able to fit in the main memory, see right now maybe you have seen that even in a mobile phone, in a small mobile phone, the RAM available is 128 GB, isn't it? So like that the processors are having the computers are having the technology so big, technology is developing so fast that the size of the RAM available in the devices is going to increase, right? Therefore the main memory sizes are increasing. So there is now the main memories are going to be larger than the process sizes, but still virtual memory concept has been implemented. Why is it used is, now even though the process size is let us say this is main memory and these are the process, even though the process's size is less than what the main memory size is, we are still having a part of the processes run in the main memory or load in the main memory at any point of time, because by doing this we can have as many processes as possible inside the main memory. Then what is the advantage? We can increase the CPU utilization by increasing the degree of multi-programming. Got it? So virtual memory concept can be used either when the process size is bigger than the main memory or when the process size is smaller than the main memory. Whatever it is, the advantage that we get is we can have many processes present in the main memory at the same time, and so increasing the degree of multi-programming and therefore the CPU utilization. Understood this? So that is how this virtual memory has been implemented. Now in the light of this virtual memory, what happened is, sometimes this logical address space is also called as virtual address space. Virtual address space, and this logical address is also called as virtual address, and these two words are now in use interchangeably. Strictly speaking, they should be different, but the computers have evolved so much that they are using virtual address at all the places, virtual address space at all the places, irrespective of the sizes of physical address and logical address. In general, the strict concept should be like this: whenever the logical address space is greater than physical address space, then we should call it as virtual address space, and the logical address should be called as virtual address, right? But since we are going to apply this virtual memory concept everywhere now, irrespective of the size of the main memory and the process size, these two names are actually used interchangeably. So now from now on, either I say virtual address space or logical address space, virtual address or logical address, you should think that everything is same. Got it? Fine. Now you know about a process size now and the main memory size. Then the next concept that comes into picture is, what is a page size or a frame size. Now I told you that already page size or frame size are same, isn't it? So now we are going to divide the main memory into many small parts, and each part is called as a frame, and we are going to divide the process into many small parts, and each part is called as a page, in such a way that page size is equal to frame size, right? Now let us assume that page size is equal to frame size is equal to p words. If these many words are present in the page or frame, right, then how many bits are required to address each word? So number of bits are required to address each word within a page is log p base 2, right? These many bits are required in order to address a bit in each page. This is also called as page offset. Page offset. Page offset is nothing but in order to address each word in a page uniquely, how many bits you should be using. That is called as page offset. So in this case, the page offset is nothing but log p base 2 bits. See, to take a small example and explain you, let us assume that page size is 1k words, right? Or you know, in terms of bytes and then words, generally they will give directly in words, but then I just want to make it clear what is the difference between words and bytes. Let us say page size is 4 kilobytes, right? And the word size is 4 bytes. Then how many words will be present per page? Then page size in words will be 1 kilo words, right? Which is nothing but 2 power 10 words, right? Then how many bits are required in order to address each word? So in order to address each word, the number of bits required will be 10 bits, right? Therefore that one I call it as offset, word offset or page offset, right? So okay, generally the concept is page offset. Let's use page offset because word offset is sometimes used in order to find out a byte within a word, right? So let's make it page offset only. Page offset, right? Or sometimes frame offset. Both are same. Let's keep it as page offset. Here the page offset is 10 bits, which means 10 bits are required in order to address each word in a page uniquely. Got it? Now let's put it all together about what is the main memory, logical address and physical page size. Let's put everything together now. Okay. Assume that capital M is instead of saying capital M, let us say physical address space is equal to main memory size, isn't it? I'll not say this again and again, but it is the last time. Physical address size is equal to main memory size, and let us say it is M words. So capital M words represent the physical address space, which is equal to the main memory. And now logical address space is equal to process size, right? Process size, let us say this is equal to capital L words, right? And let us say page size is equal to p words. Fine. If this is the case, right? If this is scenario, then how many words, what will be the size of the physical address? See, physical address size means the size of the total memory, and physical address means number of bits which are used to access the physical memory. Both are different, right? And physical address will be log M base 2 seal. Actually we need not put seal, right? But then you know the reason why we need not put this seal is always capital M will be a power of 2, and whenever I take any logarithm for any power of 2 with base 2, I'll not get any fractions, right? I'll get a whole number. But then why am I putting this seal is, it is just for the conventional sake. Nowhere you are going to see that main memory is 100 bytes. No one is going to say that. It will be either 128 or 250 or something like this. Okay. Anyway, let's go with the conventions. Got it? And let me write it as small m bits. So small m bits are required for physical address, and logical address is nothing but number of bits required to address the process, which will be log L base 2 seal, and let me write it as small l bits. Okay. And now page size. So if page size is going to be p words, then how many bits are required in order to identify a word within a page? Are you following it? If page size is p words, then how many bits are required to identify a word within the page? That is what I am asking here. Then I'll call it as page offset. Page offset is nothing but if I want to identify a word within a page, then how many bits are required. So page offset can be obtained by putting log p base to c. Let me call it as p bits, right? So if you want to know what all these bits mean, let's take a small example and I'll tell you this. Let us say physical address space equal to 128 MB, right? And logical address space equal to 1 MB and page size equal to 4 KB, right? So what do you understand? Total main memory I have is 128 MB and the size of each process is going to be 1 MB and page size is going to be 4 MB, right? So if this is the scenario, then let's analyze all these numbers. Now in order to identify, okay, here whenever they say that the memory or everything is in bytes, and if they don't mention anything about words, think that each word is 1 byte. Got it? Sometimes they will not talk anything about the words, right? In case if they give you about the words, like each word is 4 bytes or something, convert everything to words and then solve the question. If they don't mention anything about the words, best thing is to assume that a word is equal to 1 byte, right? So you can leave it just like this in terms of bytes and you can compute it, or you can replace bytes with words because nothing is given and you can go ahead with the question. Now if this is the scenario, then what is the physical address? So if you have to identify all this, convert them into powers of 2's. What is 128? 2 power 7. What is m? 2 power 20. Therefore this entirely is going to be 2 power 27 bytes. And what about 1 MB? 2 power 20 bytes. And what is 4 KB? 4 is 2 power 2, K is 2 power 10. Therefore it is going to be 2 power 12 bytes, isn't it? Then if this is the case, if I have 2 power 27 bytes, in order to identify each byte within a within the physical address space, how many bits are required? Let's say logical address space is this. Let's say the process size is bigger, or okay, let's leave it this way, no problem. Physical address space, right? Okay. See, I want to extend this question a bit further. So if I take other representation, it will be better. Let us say logical address space is this and physical address space is this. If you observe this, logical address space means size of the process is 128 MB. Physical address space means the main memory available is just 1 MB. So if you observe this question, the process size is very much bigger than the main memory, right? Then what is this? Then the concept of virtual memory has to be used. Then logical address can also be called as virtual address. But anyway, people are using both the names simultaneously, which means sometimes they say virtual address, sometimes they say logical address. So don't get confused in that. Okay. Fine. Now, if the logical address space is 2 power 27 bytes, then how many bits are required in order to identify a byte within this logical address is? So logical address is going to be 27 bits, isn't it? Then what about physical address? How many bits are required to identify a byte within 2 power 20 bytes? 20 bits, right? With 20 bits I can get 2 power 20 addresses, and each address can be associated with 1 byte. Got it? And what about this page offset? If page size is 2 power 12 bytes, which means in one page, if we have 2 power 12 bytes, if I have to identify one among these 2 power 12 bytes, then how many bits are required? 12 bits. Got it? Fine. So let's leave it here and let's extend this. Now we know that in this case, we know that physical address is m bits, isn't it? So why physical address is m bits? Because size of the physical address space, this entire size is actually 2 power m bytes, right? Or 2 power m words. So don't get confused. Words are the ones which we are worried about, and even if the question is given in bytes, we are going to convert it into words. So if the total physical address is 2 power m words, right, and then the physical address is going to be small m bits, right, and now you could divide, actually it is divided into various frames, right, in such a way that frame size is equal to page size is equal to p words, isn't it? So page size equal to frame size equal to p words, which means each page size here, this one, or each frame in this case is going to be p words, right? Then how many pages are there and how many words are present in each page? Now what I will do is 2 power m words are there, and each page is going to contain p words, right? So let me write this p in terms of something which I could divide. Okay, p bits here I have, right? So page size is going to be, or frame size is going to be 2 power p bits, right? And total physical address is going to be, physical address space is actually 2 power small m words. I think this is also 2 power m words, right? So are you following this? Each frame is 2 power p bits, and small p is nothing but I have derived small p from this, from page size only, right? Frame size is going to be 2 power p words, and physical address space is going to be 2 power m words, right? Then my question is, how many frames are present in this entire physical address space? So if you want to find the number of frames, right, then you divide the physical address space by the number of frames. So what is physical address space? 2 power m divided by what is the frame size? 2 power p. Then how many frames will be present? 2 power m minus p. Got it? So it is actually divided into 2 power m minus p frames in such a way that each frame is 2 power p, right? This is the division. Are you understanding this? The entire physical address space is divided in such a way that each the total total memory is divided into 2 power m minus p pages or frames, and each frame size is 2 power p words, right? So dividing it like this is meaningful in such a way that the most significant m minus p bits will identify what is the frame, and the least significant p bits is going to identify the page frame offset. Therefore, if you have to reach any byte within one page, what you should do is, using this frame number, this is what I call it as frame number, right? And this is what I call as frame offset. So first, using this number, go into the frame, that particular frame, and then using this number, go into that particular word. Getting this, right? So that is how you can divide it. So now physical address is divided into frame number and then frame offset. Understood this? Similarly, you can divide the logical address space also. If you watch it, what is the logical address space? Logical address space is capital L words, and which requires small l bits. Therefore, I can write the logical address as 2 power L words, isn't it? And what is the page size? Page size is 2 power P words, isn't it? What does it mean? Your process whose size is 2 power L bits, L words, is divided into many pages in such a way that each page size is 2 power p words. Now, can you tell me how many pages are present? Then the number of pages will be logical address divided by word size. Then how much is this? 2 power L divided by 2 power p, which is nothing but 2 power L minus p. Now you can write this entire address space as 2 power L minus p pages are present in such a way that each page size is 2 power p. Therefore, this is the total number of words possible. Are you understanding this one? Okay, then how can you divide the address? If you think that, each address is going to contain L bits, right? If address is going to contain L bits, now that L bits can be divided into two parts. One part will contain L minus p most significant bits, which will give us the page number. This one I call it as page number, and least significant p bits is nothing but the page offset. Got it? So in order to get into a word in a process, first you go into that particular page, and after you get into the page, you use the page offset and go into that particular word, right? So that is how you are going to divide the main memory address, this physical address, and logical address. I think you got how to divide the addresses, right? So let me just extend this concept. Hope that you have taken down this. Now you understood one thing. Even though I have m bits in the physical address space, it is going to be divided into two parts. One is frame number and other is frame offset. And even though we have L bits in the logical address space, it is also divided into two parts. One is page number and the page offset, like this. Physical address, which is equal to m bits in total. In total it is equal to m bits, is divided into two parts. One part is frame number, right, and the other part is frame offset. So I think you understood now. Frame number is used to go into particular frame in the main memory, and then frame offset is going to go into the frame into that particular word. Got it? And now how many bits are here? So the number of bits required here will be m minus p, and the number of bits required will be p bits. Got it? And similarly, logical address space is going to contain two parts, right? So even though it is going to contain logical address is going to be split up like this. So logical address, which is equal to L bits, logical address is equal to L bits, and it contains two parts. One part is page number and other part is page offset, right? And how much is page number? Now page number will be equal to L minus p bits, and it is going to be p. Now if you observe it, either frame offset or page offset is always going to be same. Why? Because either it is a frame or a page, both sizes are same, right? And therefore the number of bits required to identify a word within a page or frame are going to be equal, isn't it? Therefore these two are going to be equal. Now the entire part of memory manager here, or memory management unit, is how are you going to take the most significant m minus p bits and convert it into L minus p bits. This is the entire part, right? Now how is that done is, we are going to use something called as page table. Page table. Page table. How does this page table operate is, see, now you found out that your logical address space or your process is divided into 2 power L minus p pages. See, if these many bits are there in the page number, then how many pages will be present? 2 power L minus p pages, isn't it? So now your page table is going to contain, the total number of pages will be 2 power L minus p pages, right? So for every page present in the process, there will be an entry in the page table. Okay, so try to understand this. For every page present in the process, there will be an entry in the page table. I already told you with an example, right? Therefore number of entries in the page table, number of entries in the page table will be equal to number of pages in the process, right? So if you have more number of pages in the process, then the number of entries in the page table will be more, isn't it? So what you could understand here is, therefore the total number of entries present in this page table will be equal to number of pages. And how many pages are there? 2 power L minus p. We just calculated it, right? Therefore the number of entries in the page table is going to be 2 power L minus p. And now assume that each entry size, which means this part, if each entry size is e bytes, then what will be page table size? Page table size, the size of the page table, which is very important because it is going to affect many things. I'll show you what it is going to affect later, but anyway you have to calculate the page table size. Now page table size is going to be, how many pages are there, which means how many entries are there? 2 power L minus p entries are there, and each entry is of size how much? E bytes. Therefore, this is the total size of the page table. The total size of the page table is going to be number of entries multiplied with number of bytes for each entry. Now, in the question, if they give you this page table entry size, then it is fine. If they don't mention anything about the page table entry size, then what you should be doing is this thing. Understand this? Sometimes they are going to say that page table entry size is some bytes. That is fine. But sometimes they are not going to say what the page table entry size is. Then what you should do is you are supposed to calculate it. How can you calculate it is, watch it. What will be present in the page table entry? The page table entry will contain the frame number in which this particular page is going to be present. See, for example, page table entry will be like this. Page table entry will contain 0, 1, 2, 3, 4, 5. So these numbers which will not be present inside the page table because it is just like an array. These are the indices of the page table and each index represents the page number. So it represents that page number 0 is present in so and so frame, page number 1 is present in so and so frame, page number 2 of this process is present in so and so frame, right? And now therefore each entry of the page table actually contains the frame number in which that particular page is present, right? So for example, if this page table, if this page of the process is present in frame number 10, then it is going to contain page number 0 is going to be present in the frame number 10. Why do you need it? Because not to convert the logical address into physical address, we have to take the page number and go to that particular page and then take the frame number and put it there. Then we are going to, using this address we can go to the memory and get the word. And these bits they don't vary, right? Okay. Now if they don't give you anything about this, then you can understand that the main entry that has to be present inside this entry is, in the page table is the frame number. Then how many bits are required in the page to represent a frame number? If you watch it, the number of bits required to represent the frame number is m minus p, right? So in case if e is not given, then page table size will be number of entries is nothing but 2 power L minus P, which is equal to the number of pages into the actual information that is present inside each cell of the page table is the frame number, right? And how many bits are required to represent the frame number? M minus P. Got it? So if they don't say anything about the entry size, right, then you can take this as the page table size. But the problem is, this is not actually true. In the sense, in most practical cases, we don't just save the frame number inside the page table. Along with the frame number in which the page is present, we save even more information about the page itself, like whether the page is modified or not, whether the page is referenced or not, or what is the history of the page, everything. We can save even the permissions like read, write, execute, everything we can save it, right? So what I mean to say is, in case if they don't mention anything about the page table entry, you go with this number, right? And this is going to give you the page table size. If they mention it, you go with this, right? In any way, at practice, your page table entry size will be much bigger than this one. See, we have seen various things about paging. Especially the size of the page is going to determine how big the page table is going to be. Let's take one example. See, let us say virtual address space is 4 GB and page size is let us say 4 KB. Then how many pages will be there in the page table? The number of pages will be equal to virtual address space divided by page size. So virtual address space is 4 GB divided by 4 KB, which is nothing but 1 MB, right? So 1 MB of the 1 million pages, sorry, not 1 MB, 1 million pages are present. Therefore, how big will be the page table? The page table has to contain 1 million entries, right? So that big will be the page table. In case if the page size is going to be let us say 4 MB instead of 4 GB, 4 KB, if the page size is 4 MB for the same virtual address space, then What about the number of pages? Number of pages equal to virtual address space divided by page size. So virtual address space is 4 GB divided by 4 MB, so which is nothing but 1000 pages, right? So see the difference. The number of pages, they are getting affected by the page size. If I increase the page size, the number of pages are going to be decreased, and therefore the page table size is going to decrease, right? So depending on the page size, the overhead depends. What is the overhead? Page table. Page table is obviously an overhead, right? What is that we wanted to execute? Process. We don't want to execute the page table, right? In order to execute the process, page table is going to be helpful. And now the size of the page table itself is depending on the size of the pages, right? So you can understand about one thing. If the page size is big, right, then page table size is small. So these two are inversely proportional, isn't it? Now, so it says that you go for big page sizes so that the page table size is going to be small and the overhead is going to be small. But then, there is one more problem. The problem is this: on average, because of paging, half of the page will get wasted. How is it possible? Watch it. Let us say a process is like this. This is the process, and now it is divided into pages, many pages like this, and the last page, and let us say these are all pages, and the last page, this is the last page, has got only a part of the process, right? So in best case, what happens is, let us say one page size is 1 KB, right? Then in best case, what happens is, a process size or the virtual address space, might be exactly the multiples of this page size, which means if process size is 10 KB or the virtual address space is 10 KB, then how many pages are required? Exactly 10 pages are required, and therefore there is no wastage of the page at all, or there is no wastage is there. But sometimes what happens is, if the page size is 1 KB, right, and if virtual address space is, let us say 10 KB plus 1 byte, all this 10 KB can be fit in 10 pages because each page size is 1 KB, and this extra 1 byte, in order to put that 1 byte, we have to dedicate 1 page, right? In that case, even though the page size is 1 KB, only 1 byte will be occupied by the process and the entire page will be wasted, right? Which means nearly here the wastage is 1 page. In this case, the wastage is 0 bytes, and in this case the wastage is 1 page completely, nearly 1 page, right? Because only 1 byte is occupied, so 1 page is completely wasted. So on average, we get a mix of the process, which means some processes might not waste anything and some processes might waste a complete page. On average, we get a mix of it. Therefore, on average, what is the wastage? Half of the page, right? So this is the overhead or the wastage. Therefore, whenever we try to design the page size, or whenever we try to come up with deciding the page sizes, we have to keep we have to think about what is the overhead if I have such so and so page size. Let's see how to come up with a suitable page size. So generally researchers, what they do is they use these parameters. Let us assume that page size is p bytes, okay, and page table entry size is e bytes, right? And on average, virtual address space is, I'm just assuming this, okay, on average the virtual address space is, let us say, s bytes. This is the size of the process on average, right? Virtual address space means size of the each process, right? Then if this is the case, then how much memory will be wasted on average? On average, half of the page will be wasted. I'm talking about overhead, okay? What are the overheads? One overhead is when we divide the process into pages, some at least the last page might not be completely full. In that case, what happens is overhead is going to be the last page size, one page divided by 2. I just told you the reason. Half of the page is going to be wasted on average, which is p by 2, which means these many bytes are going to be wasted. Plus even the page table is also a overhead. How many bytes is page table going to take? If the size of the process is s bytes, right, and p is the size of the page, then how many pages will be there? The total number of pages is going to be s by p, isn't it? And what is the page table size? Page table size is equal to the number of pages into page table entry. So page table entry size is e. So this is the overhead, right? So the overhead is some part of the memory is going to be wasted. Why is this wasted? This is wasted because this part has to be wasted because of the lost 1 byte, or the extra. See, this part is wasted because when we go for paging, the last page might not be completely filled with the process, and now this is wasted because of the page table size. Therefore the total overhead is this one plus this one, right? If this is the overhead, now the question is what is the suitable page size? Then we should try to minimize this overhead. In order to minimize this overhead, what I try to do is I'll differentiate it with respect to p and I equate it to 0. If I differentiate the overhead with respect to p, let us say O is the overhead. If I differentiate with respect to p and equate it to 0, then what do I get? 1 by 2 plus 1 by 2 p by 2 d by dp of p by 2 is 1 by 2 minus s by p square into e, right, and equate it to 0. And this one you can learn it in minima, maxima and minima topic. If I have to find out the maximum value or minimum value of some function, then you are supposed to differentiate it and then equate it to 0. Then what do we get? We get that if I solve it, we get that p equal to square root of 2 into s into e. Yeah, p equal to square root of 2 into s into e, where s is the average process size and e is the page table entry. Now let's talk about the virtual memory. Till now I have been talking about virtual memory, but not in a I didn't show you any practicality about this. But let's now talk about the virtual memory in complete. So the main advantage of virtual memory is whenever the process size is very much big than main memory, it will let the operating system help us in running such a process. So what is the advantage? A user will get the illusion that it is just an illusion. A user will get the illusion that the main memory is available to load his complete memory, or when the user is writing the program, he will never think about what will be the size of the main memory on which this particular program will be executing. He will write the process in such a way that it will fit in the secondary memory. So if the hard disk is, let us say, 1 terabyte, he can go up to 1 terabyte of program. That is not actually possible. These big programs are not actually possible, but still a user can think that there is lot of memory at his disposal, and the memory, that main memory, is equal to the secondary memory. That is illusion operating system will create. So how does it exactly work? This way, watch it. So generally whenever you create a process, let's say the process is initially residing in the secondary memory, right? Therefore your virtual address space is limited by the secondary memory space, and secondary memory is generally cheaper. The hard disk is cheap, right? Terabytes of hard disk is quite common these days. Therefore your process can be very big and they can reside in the gigabytes or anything. They can reside in the secondary memory. Let us assume that there are two processes, P1 and P2. Now without the concept of virtual memory, what people used to do is they used to completely load a process in the main memory and then they used to run it. But now with the introduction of virtual memory, you need not completely load the process in the main memory. You can load only a part of the process in the main memory and you can run it. What is the advantage? One thing is the size of the process itself is greater than the size of the main memory. Second thing is I am actually conserving the main memory, which means by not filling up the main memory with one process, I am just letting this space be there so that I can put many processes. Using this, the degree of multi-programming can be increased. What is degree of multi-programming? At any time, the number of processes which will be residing in the main memory and that will be available for running is degree of multi-programming. Now when I put only a part of the process, I can put many processes in the main memory. That is how the degree of multi-programming can be increased. And I already told you that with the degree of multi-programming increased, CPU utilization will increase. Therefore, virtual memory not only helps us in running the bigger programs. That is the initial advantage number one, or the main purpose of the virtual memory is to run program which is bigger than main memory. But then later it got converted in such a way that using the virtual memory we are able to increase the degree of multi-programming, and so the CPU utilization is also going to be increased, right? So now virtual memory has these many advantages. So almost every operating system these days is using virtual memory only. Even every device is using virtual memory, which means no one is actually loading everything onto the main memory, and no one is going to put a lot of burden on the main memory. They are going to load a part of the process which is required into the main memory and run it, and then replace it with the other pages as required. Got it? So let's see this example. There are two processes P1 and P2, and we are not going to load the entire part into the main memory because main memory will not be sufficient for that. And this is the main memory. Process are divided into pages. Here it has 8 pages, process P1, and process P2 has 8 pages. And now the main memory has frames, and 16 frames are there, in such a way that page size is equal to frame size. And in the main memory, the top 3 frames are given away for the operating system. So operating system is always going to be resident in the main memory. Therefore, we have to dedicate it some space, and in the remaining space, and remember this, loader should always be there in the operating system. Should always be there in the main memory, because loader is used to load many other things, right? Therefore, loader is always supposed to be there. Okay, if loader is not there, we cannot load any other things. Okay, and now once the operating system has decided about the boundary, that this is the system space and this is user space, in the user area the processes are going to be loaded. Now watch it. Now frame number 3 is loaded with page number 1 of process 1. P1 means capital P means the process, small p means the page. Therefore frame number 3 is loaded with page number 1 of process 1, and frame number 4 is loaded with page number 2 of process 1, and frame number 5 is loaded with page number 3 of process 2, right? So if you observe it, it is not only that only a part of the process is present in the main memory, even these parts are present non-contiguously, which means there is no contiguity in the in the process arrangement. So that is one more advantage. What is the main advantage of letting a process be at any place? External fragmentation will be 0, right? But still internal fragmentation is there. I told you in the previous question, right? Internal fragmentation is there, and that will be roughly equal to half of the page size, right? Okay, now watch it. Now if you watch it, process P1 is present at 4 places: process P1, process P1, process P1, and process P1. And if you watch it, page number 1, page number 2, page number 3, this is process P2, page number 3 and page number 4. Page number 1, 2, 3, 4 of process 1 are present in the main memory, and the other pages of process 1 are not present. And if you watch the process 2, page number 1, page number 3, and page number 7 and page number 6, which means 1, 3, 6, 7 are present in the main memory and others are not present, right? So accordingly, your page table, and every process will have a page table. Since there are 2 processes, there will be 2 page tables, and page table 1 represents what are the pages of process 1 which are present in the memory, and what are the pages of process 1 which are not present in the memory. Now if you watch it, this is the page table of the process 1. This entire thing is the page table of the process 1. How many pages are present in the process 1? 8 pages are present. Therefore page table will contain 8 entries representing each page. Now if you see this, if you look at this process 1, one more thing, whatever I am showing you here is a snapshot, which means the system is running these processes, and at some point of time this is what has happened. It doesn't mean that the process started out with this, or the system started out with this. I mean, initially there are various cases. There is no need, or there is no necessity that there has to be at least few pages of a process present in the main memory to start it, right? No need. And whatever I'm showing you here is a snapshot of the system at some point of time, right? Okay, now if you watch it, this page table 1 of process will say which pages are present in which frames. Now it is saying that page number 1 is present in frame number 3 of process 1. Page number 1 is present in frame number 3, isn't it? Frame number 3 contains page number 1, and similarly it is saying that page number 2 is present in frame number 4. So go to frame number 4, page number 2 is present. Similarly, page number 3 is present in frame number 8. Page number 3 is present in frame number 8. Page number 4 is present in frame number 10, right? Now, whenever you are searching for a page, first thing is, in virtual memory, you should be you should first think about whether the whatever page you are looking for is present in the main memory or not, because the chances are that it might not be present. So in order to differentiate whether a page is present in the main memory or not, we are going to use one bit to differentiate it, and that bit is valid invalid bit. So valid invalid bit is going to say whether the page that you are looking for is present in the main memory or not. Now if you watch it, page number 1, 2, 3, 4 valid bits are 1, which means these pages are present in the main memory, and for all the other one, valid bit is 0, which means these pages are not present in the memory. So whenever you try to refer to a page, if it is already present in the main memory, you will go to the main memory and do it, take it. If it is not present in the memory, that is called as page fault. Page fault is whenever the page you are looking for is not present in the main memory, then you are supposed to get it from the secondary memory, right? How can you get it from the secondary memory? We go for a page fault. So whenever we declare a page fault, then the operating system is going to get that page and load it in the memory and again restart the process. Got it? So valid invalid bits are used for knowing whether it is page is present or not. And next one is dirty, this D bit. So there are various entries which are present in the page table other than this frame number, and the next important thing is D bit. D means dirty bit. So dirty bit, or it is also sometimes called as modified bit. This D bit says, or this D bit will say whether the page after getting loaded into the main memory has been modified or not. Why should we know it? In case, let us say D bit of this one is 1 and 0 0 1 0 0 0 0. If this is the scenario, then it means that the page number 1, which is present in frame number 3, has been modified at some point of time. Therefore, now since it has been modified, it has to get reflected in the secondary memory as well. So whenever we try to replace the page number 1 of process P1, we are not just supposed to overwrite on that, we have to write it back, right? That is called as write back. Write back means when we have various levels of memory, and whenever anything gets modified in the higher level, which means in this case main memory, it has to get reflected in the lower level, which means the secondary memory. That is called as write back. And when do we do write back? The best time is not always, right? Whenever we try to replace it, whenever we try to write something over it, whenever we try to overwrite something on that frame, it is better you write it back and then get the new page. So in case if this page 1 of this process is has to be replaced, then we are going to write it back first and then load the new one. That is why dirty bit is going to be used. And next one is referenced. So reference will this is called reference bit. Reference bit will just say in the last clock cycle what are the pages that are referred, right? Which means this bit will keep on changing. In the last clock cycle, if some bit has been referred, it will be marked as 1. If it has not been referred, it will be marked as 0, right? So every clock cycle, reference bits are going to change depending on what are the pages that have been referred in the last. Why is this important is once we know what are the pages which have been referred, then it is very easy to replace them. So generally most of the algorithms will say that if a page has not been referred in the last clock cycle, or it has been not referred for a long time, the chances are that it might not be referred in the future, right? I mean, that is the assumption. So many of the algorithms will do page replacement. What is page replacement? If I have only few number of frames to run my process, and if I already loaded with all the pages, and if I need a new page, then one of the existing pages have to be replaced, which means in this case, the total number of frames that are given to this process P1 is 3, 4, 8, 10. These frames are dedicated to process P1 as of now, right? Then most of the algorithms, they'll try to use these dedicated frames in order to run the process. Then what happens is, when we have 3 frames, 3, 4, 8, 10, and right now they are holding the process pages, page 1, page 2, and page 3 and page 4. And if I need a new page, page number 5, then one of these pages have to be replaced, right? Then which one is more suitable? There are various versions and various arguments about it, and one particular argument is pull out the page which has not been referred in the last clock cycle. So just to differentiate whether a page has been referred in the last clock cycle or not, we are going to use this R bit. So R bit is going to say which process are referred, which means let us say this is 1100, and all the others anyway are going to be 0. They are not present in the page table, I mean in the main memory. How will they be referred? So it means that in the last clock cycle 3 and 4 are referred, and 8 and 10 are not referred. Therefore if you try to replace any of the pages, then the better options will be page number 3 and 4, because they are not referred, right? And the last one is protection bit. P bit means protection bit. What does protection bit indicate? Whether you have rights to do some kind of access. Sometimes what happens is, I told you there are 3 kinds of sections. One is data section, and other is code section, and other is stack section. And if you are in the code section, you are not supposed to modify the code, right? So whenever you are trying to access the main memory, and whenever you are trying to write something on the code, then this protection will catch you. Which means if the CPU has got an instruction to modify a page which is actually a code, right, then the protection section will catch you. So this protection will contain various bits like read, write, execute, right? Generally code section will be read and execute permissions, data section will be read and write, stack will be read and write, right? So if you try to access these sections using any other type of access, then your there will be a page, there will be a trap means you are not supposed to do any other kind of actions other than which are permitted on that page. So generally a page will have some permissions. If it is a code page, you have to only read and execute. If it is a data page, read and write, stack, read and write. So that is how various other informations are going to be useful. And one interesting thing is, even this page table whatever I have shown you, see, the process is present in secondary memory, fine, and now a part of process is present in main memory, fine, and the information about which part is present in main memory is present in the page table, and now even this page table has to be in the main memory, which means even this entire page table is again going to be present in the main memory, right? So I am assuming that in this case we are lucky that the page table is fitting in one frame. In that case I need only one level of paging. So in this one level of paging, this page table is present in the frame number 11. So process has to be present in the main memory, along with that its page table also has to be present in the main memory. Yes, it is present in the main memory. And now where is the page table? That CPU should know it. So even though CPU does not know anything about where the process is present, it is fine, but at least CPU should know where the page table of the process is, so that it will start searching for page table first, and then it will start searching for the page first, page number, and then the frame, right? So now since this is present in frame number 11, in case if process P1 is executing in CPU, watch it, CPU is going to have like this. CPU is going to have a register which is going to say what is the page table base address. Page table base address means where is this page table loaded. So it is containing frame number 11, which means CPU now knows that page table is present in frame number 11. So inside this frame number 11, this entire page table is present. Now what is the advantage of this? Now whenever any CPU generates logical address, I told you logical address is of two parts. One is page number and other is page offset, right? Now we take the base of the page table. This will tell us where the page table is loaded, and then we take the page number and then we add it. Then we can exactly go into that particular page number of the page table. So using these two, I can get into the page table of the required page. Let us say the page number required is 3, right, and the offset required is some x. Okay, now I went into this page number 3 entry of the page table. Now it is saying that valid bit is 1. Valid bit is 1 means yes, it is present in the main memory, and if the valid bit is 1, then only I am going to look at the frame. Along with that, I am going to even see the permission. Let us say I want to read the memory, and now I'll check whether I have reading permissions or not. Generally reading permissions will be enabled for all the pages, right? Therefore now I'll observe that page number 3 is present in frame number 8. So I'll take this frame number, right? I'll take this frame number 8, and then I'll do this page offset as it is, and it is called as physical address. Using this physical address, now I can access the main memory. In the main memory, I'll go into the frame number 8 and I'll get the corresponding word. Understood this? So one thing you should notice, even the process is present in the main memory, as well as page table also has to be present in main memory. In case if page table is too big that it cannot fit in one page, we have already seen it, that is called as multi-paging. In multi-paging, we are going to go till the level so that the last level will contain a page table which can fit in one page, right? Okay. Similarly, the same thing is true with the page process 2 also. Process 2 is loaded in frame number 3, the page table of process 2, and I didn't show you all the bits. You can fill them up, right? What are the main entries are? Watch it. Process 2 page number 3 is present in frame number 5, which means page number 3 of process 2 is present in frame number 5. And again process 2 page number 1 is present in frame number 6, right? And again process 2 page number 6 is present in frame number 7. And process 2 page number 7 is present in frame number 9. Got it? So this is how the page table will be filled up, and you will have valid bits as 1 1 1 1 and then 0 0 0 0. So whenever we switch the context from P1 to P2, which means we stop running P1 and we have to start running P2, then this page table base will now be loaded with the base address of this page number 2, which means it will now get loaded with 13, and all the other registers will also be changed appropriately. Got it? So this is what happens in the virtual memory. In virtual memory, we are not going to have entire process in the main memory. We are going to have only a part of it. And how can we keep track of which part is present? Using the page table, using the valid bits. Along with this, there are various bits, right? Whenever valid bit is 1, it means the page is present. If the valid bit is 0, it means the page is not present, and that will lead to page fault. What is page fault? If the page is not present, then we are going to block the process and put it in the block state, and we ask the main memory, the secondary memory, to load that particular page into the main memory, and then we start running it. Therefore, whenever there is a page fault, the time taken is going to be very high. The entire concept of paging and the page table has been invented, proposed just to solve one problem, to decrease the wastage of memory because of external fragmentation, right? So you know this. So the entire concept of external fragmentation is, since the process has to be contiguous, the rule that was introducing external fragmentation because of the holes that in the dynamic memory allocation, right? And now if the process can be present at any place, that can solve the external fragmentation. So in order to have that flexibility, that we can load the process anywhere by breaking it into pieces, we got paging into picture. Now the paging's main purpose is to save the memory or conserve the memory or decrease the external fragmentation or decrease the wastage of memory. But then paging has got its own overhead. So what is it? Page table, and the page table size could be very big. So see this example. Let us assume that virtual address space virtual address space or the size of the process is 4 GB and the page size is assume that 4 KB. Then how many pages will be present? 1 million pages will be present, right? And for each for 1 million pages, if I have to represent one entry, that the page table itself is going to be very big. And now in order to run this process, before running that, you have to load the page table entirely, right? And now what is the problem with that? If I load the entire page table, that itself is going to eat up the memory which you are trying to solve, save it from the external fragmentation. Then there have been various efforts done in order to save the time, right? So in order to save the space. So in order to save this space, what people did is instead of loading the entire page table into main memory, they are using the concept of locality of reference. Locality of reference says that over the lifetime of a process, at any particular instance of time, it will be referring to only small number of pages, right? So most of the references will be to a small number of pages at any point of time, but then the small number of pages might vary from time to time. That is locality of reference. So locality of reference says that in order to run a process, you need not run the entire, you need not load the entire process. You just load only few pages, and therefore you can even load only the page table entries which are concerning to those pages, right? And now that is called locality of reference, right? So now what I mean to say is, in order to save the space or stop the wastage of space from the page table, what people did is they have used this multi-level paging. So using multi-level paging, they divided the page table into small parts, and they are loading only the part which is required at that particular moment. If it is not required now, we are not going to load it, right? So that concept is fine, but then it is again going to see, it is like this. I'll just tell you what I'm trying to say. See, there is external fragmentation. What is external fragmentation? Some of the memory is going to be wasted because of the holes in the memory, right? And now in order to solve it, compaction was one solution, and the other solution was don't save the process contiguously, save it at different parts. That is fine. And now in order to solve this external fragmentation, paging was introduced. Right? And now paging was initially thought to solve this external fragmentation, but later paging concept has introduced the page table. Now what is the problem with page table? The page table itself is becoming so big that it is going to take up that is going to eat up the space which you are trying to save from external fragmentation. Then in order to save this space, right, so it is going to take large space, right? Most of the cases large space. So how can I save this space, or how can I decrease the page table size? So one way to decrease the page table size is increase the page size, right? So I think you know this. If I increase the page size, if it increases, then what happens to page table size? Page table size decreases. How? If I increase the page size, the overall number of pages will decrease, and therefore the page table size will decrease, because page table size depends on number of pages into size of each page table entry, right? Therefore if I increase the page size, right, and now I can decrease the page table size, but then it is going to introduce one more problem. I told you, on average every process is going to waste half of the page size for internal fragmentation, right? See, initially external fragmentation was there. In order to solve it, paging was introduced. Because of paging we got page tables. Page tables were very large. Now in order to decrease the size of the page table, you might try to increase the size of the page, but if I increase the size of the page, right, then the number of pages will decrease, fine, and therefore page table size will decrease, fine, but that will introduce the internal fragmentation, right? So what happens if the page sizes are too big? It might actually become the same as static partitioning. If page sizes are too large, then they are called partitions, and entire process can go and sit in one partition, and again the internal fragmentation will come into picture. Or even if the entire process cannot fit in one page, what happens is, on average half of the page is going to be wasted by every process, right? Then what happens if the page size increases? Then the internal fragmentation is half of the page, right, which means internal fragmentation will increase. So what is the solution then? Then the other solution is we have used the page table is again divided into multi-level paging, right? So what is the advantage of multi-level paging? If I have various levels of paging, I'm not going to load the entire page table. I'm just going to load the page table which is required at that moment, which is very small, right? Fine. But then by using the multi-level page table, right, the overall time required is going to be increased. How? Watch it, anyway using page table, time is also going to be increased. So there is page table in the main memory, and then there is process in the main memory, right? Now whenever the CPU wants to get a word from the process, it has to first go into the page table and access the main memory once. Let us say main memory access time is m. It has to access it once, and then using that physical address conversion, which means, see, after I go to the page table, then only I can convert the virtual address to physical address. Now I can take the physical address and then I can go to the process and again access the required concerned word. Therefore one more memory access time is required. Without page table, earlier only one memory access time was required. Now because of the page table, I require two memory accesses, right? Which means effective effective memory access time is going to be 2 into memory access time. What is small m? The time taken to read a word from the main memory. Got it? And now anyway it is going to be increased because of the paging. If there is no page table at all, then this would just be small m, right? And now by using multi-level page table, we are even making the situation worse. How? If by using multi-level page table, there will be outer page table, inner page table, like this we can have many levels, and finally process somewhere here, isn't it? Now if CPU has to access a word from the process, it has to go through various page tables. It has to go through this page table and again this page table and again this page table and then this one, right? So obviously if every access is going to take m time, so it is going to take, so the number of levels into m plus one more m, right? So anyway, this space, if you try to save this space by using multi-level paging, okay, how does multi-level paging save this space? Because even though we have these many levels of page tables, at every level I'll have only one page. Even though the page table is going to be very big, at every level, at any time, you need only one page. You need not load the entire page table. Got it? That is how you can save this space. But the problem is the time is going to be increasing, right? So when you are trying to decrease the size of the page table, it is not very easy, right? Then what people thought is, if we don't want to have, they thought this initially. If you want to decrease the memory access time, see, time is the major concern rather than memory. Time is the major concern here, right? See, now in this, let us assume that we have only one level page table, and now there is a process. This is page table and this is the process, right? So now in this page table, what is happening is we are going through two levels of access, or two memory accesses. Now what people thought is, in order to cut down these two memory accesses, why don't we load the entire page table into the registers? This is what they thought. But then the problem was, the registers are very costly, that they might not have that much space to hold the entire page table. Yes, if you load the entire page table into registers, maybe accessing the process, or maybe program execution will become faster, because obviously we are cutting down the time in order to read something from the main memory. But the problem here is, the registers are costly and the registers are smaller, and even if we assume that, let us assume that page table size is very small and the page table can completely fit in register. But the problem with this is, we have to load the entire page table into registers whenever we start a process or whenever we switch the context. Every context switching time has to set all the registers, and it is going to take a lot of time. So if I put the page table in the registers, it is going to take hell a lot of time for context switching. That is why what people did is, they have loaded the page table at some point in the main memory, and then they have just loaded the base address of the page table in one register, right? So that is called as page table base. So by loading only one register, the context switching is going to be faster. What is context switching? Whenever you try to run a process, you have to do some groundwork, like you have to set up all the registers, and maybe you have to initialize some few variables and all, right? And now by using this only one register to load the base of the page table, context switching time will be lesser. So storing the page table inside the registers is never a solution. The reason is, one thing is, page table is going to be very big, and the number of registers are going to be very costly, and the second thing is the context switching time is going to be very high. Then what is the other solution remaining? So then people have finally invented a solution where we will not use main memory, or we will not use registers. We will use some kind of memory which is faster compared to main memory but cheaper compared to registers. That is called as cache, right? So people thought that we will not load this page table into registers. We'll introduce one more kind of memory which is faster than main memory and cheaper than registers. That is called as cache, right? Cache memory. And now using cache, the advantage is we can store more memory, more elements compared to what we could store on registers, and it is cheaper compared to registers and faster compared to main memory. And this concept is also called as TLB, translation look aside buffer. Translation look aside buffer, right? So what is the advantage of translation look aside buffer is, whenever we try to access any page table entry, we'll try to see if that page table entry is present. Okay, let me introduce it in a detailed manner. See, so I told you about the locality of reference. Locality of reference means generally a process will access only few pages for a long time, and then these few pages will keep on changing, but at any point of time a process will not access a CPU, and a process doesn't need the entire all the pages to be available. It requires only few pages, right? Then the concept is, whenever you need any page, then that particular page table entry will be referred, and whenever any particular page table entry is referred for the first time, we are going to load that page table entry inside our TLB. So like this. Now if you have CPU, right, then I'll have TLB. TLB is also called as associative memory. So what is the specialty of associative memory is, every element of this memory will have something called as tag element. Okay, and now using this tag, if you present any item, or if you present any key means some value, if you present any key, right, to this associative memory, it can search the entire associative memory with the key, and it can produce it can say whether the key is present or not. And in case if this key matches with any of the tags, it will take out that entry and give it to you. It will take out that page number and give it to you. Okay, how does it work is this way. Let's watch it. Let us say this is TLB, right? How does it work is, now if there is page table, this is page table and this is process. Okay, now CPU is generating the logical address. Logical address has two parts. One is page number and other is page offset, right? And actually we should go into the page table and we should get the frame number corresponding to that particular page number. That is the concept, isn't it? But then CPU, before going to the page table, what it will try to do is, it will try to give this page number to all the tags present in the associative memory or TLB. Now if this page number matches with any of these tags, it will immediately give the frame number, and you need not go to the page table which is present in main memory. Got it? So how does it help? Since the TLB is faster compared to main memory, you can directly convert the virtual address to physical address here, and then you can go into the main memory and get that particular word, right? So it is going to be faster this way. I'll just take an example and I'll tell you. See this. So some important points to note here is TLB is going to be very small size. I mean, it is bigger than registers but smaller than main memory. Therefore, TLB might not be able to hold the entire page table. It will just hold the frequently used page table entries, which means if an entry has been used recently, that entry will be present in the page table, this TLB. Therefore, whenever you try to load the page table entry for the first time, you might have to go to the main memory. But then from then on, if this entry is present in the TLB, then you need not go to the main memory at all. I'll just take an example and explain you. See this. Let us say this is CPU, and the TLB access times is denoted by small t, 20 nanoseconds, which means in order to access TLB and decide whether a page table entry is present in this or not, the time taken is 20 nanoseconds, right? And now assume that the time taken to access the main memory, right, which means the page table which is present in main memory, time taken to access it is main memory access time, let me call it as M, which is 100 nanoseconds. Therefore, accessing TLB is faster compared to accessing the main memory, right? And now, in case if the page which you are searching for is already present in the TLB, then you need not go to the page table to get it, right? You can directly get the frame number in just 20 nanoseconds, isn't it? And now after you get the frame number from this TLB, you can directly convert your virtual address to physical address and then get to the process which is present in the main memory, and then you can get the particular concerned word in 100 nanoseconds. So in case if you can find the entry inside the TLB, the time taken is just 120 nanoseconds, right? But what happens if you don't find the entry in the TLB? Then in order to know that the entry is not present in the TLB, again the time taken will be 20 nanoseconds. Let us say the entry which you are looking for is not present in TLB because TLB size is small compared to the page table, therefore all the entries will not be there, okay? Or recently a page has never been referred and therefore it is never brought into the TLB. Then what we do is, in that case, first we have to search whatever it is, we have to search TLB first. So in order to search the TLB, time taken is 20 nanoseconds, and then you decided that the concerned element is not present in TLB. Then what we should do is, we should go into the page table and then get it. So in order to go into the page table and get that particular page table entry, the time taken will be 100 nanoseconds, which is used to access the main memory. And after this time, then only we can convert the virtual address to physical address. And after converting the virtual address to physical address, now you exactly know where in the process you should get the word, right? For that the time taken will be 100 nanoseconds. Got it? So in case if your TLB contains the entry, then the time taken is just 120 nanoseconds. If the TLB doesn't contain the entry, then first you have to check it and then go here and go here, as well as parallelly what happens is you might have to even write down that new entry in one of the slots available here, which means if you are recently referred a page table entry which is not present in the TLB, it is not just enough that you get the entry from the page table in the main memory. You should even make sure that that new entry is recorded in the TLB so that your future references, it will be helpful. Then what happens is, in case if there is a slot available, we are going to write that there. In case if there is no slot available, then what happens is the entire one of them has to be searched. Either we use some page replacement policies, or we use some random method, or we do something and we just replace one of the existing page table entries with the new one. Got it? So now whenever we find the required page table entry in the TLB, that is called as TLB hit. TLB hit means the entry which you are searching for is present in the TLB, that is called as TLB hit. Let us say the TLB hit rate is 80%. So what does it mean? 80% of the time you can find whatever you are looking for in the TLB, that is called as TLB hit. I am talking about TLB hit. TLB hit or any hit, it means that whatever you are looking for is present in this. 80% of the time, let us say it is whatever you are looking for is present in TLB. And what happens the 20% of the time? 20% of the time it will not be present. That one I call it as TLB miss, right? Then what happens to the effective memory access time here? Effective memory access time is 80% of the time it is present here, therefore 80% of the time this one happens, plus 20% of the time it is not present here, therefore I will put 0.2 here, right? It is not present, then it is going to take this much time. Then what is the total time? I think if you compute it, it will come down to around, I think, 120 nanoseconds, right? You please do it, you please do the math, or if you want me to do it, I will do it for you. Okay, you please do the math. So it is going to be 120 nanoseconds or 140 nanoseconds, I am not sure. I think it is 140 nanoseconds. Okay, so you please check the math. So anyway, what I mean to say is, if I don't have the TLB concept at all, then I have to go through main memory 2 times in order to get any word. In that case, how much time will it take? 200 nanoseconds. But by using the TLB concept, I have actually reduced the time taken to access the memory, right? So on average, the time taken will be 140 nanoseconds, which is close to 100, which is not close to 200. In case if you increase the hit rate, which means if you see that almost all the references which you make to the page table are present in the TLB, then it will even come down to very less number. As you increase the hit rate, you can find out that the time taken to access the main the effective memory access time will get reduced. So what is the formula here? The formula is, let us say TLB hit rate is H and TLB miss rate is 1 minus H, or let us say TLB hit rate is P. Then in case if it is hit in the TLB, then how much time will it take for me to access a word from the process? The time taken will be, I have to access the TLB first. So let us say T is the access time, or the T is the comparison time for T, and then after that, once I access this TLB, then I have to get the watch it. So P plus T, which is nothing but the TLB access time, plus M. So what does it mean? So whenever there is a hit and hit probability is P, then the time taken will be, first you access the TLB and then you get the memory address and access the memory, plus in case if there is a miss, then 1 minus P into, if it is not present in the TLB, then you are supposed to take the entry from the process table, which is page table, which is present in the main memory, and then go to the main memory and get the word, right? So in this case, you have to check that it is not present first, and then you have to go to the this page table once, and then finally to the process and get it, right? So just be warned here. One thing is, this entire concept is applicable when for a single level page table, and this can be extended even for multi-level page table. How? Whatever levels of page tables there are, if it is present in the TLB, the required page table entry, then you need not look at the page tables at all. You can directly go to the process and you can get that. That is one thing. And in case if there are various levels of page tables, then what happens is, if it is present in TLB, nothing will change. If it is not present in TLB, then you have to find out that it is not present in TLB, for which time taken is T, and then if there are 2 levels, then you have to go through 2 memory accesses to get to the actual entry of the page table, right? Therefore, if I put K here, right? So what is K? K is the number of levels in the page table. So in case if k equal to 1, it means that one level page table is used. In the exam, if they didn't mention anything about the page number of levels, then don't go for it. In case if they mention it like it is 2 level, 3 level, then you can put k equal to so and so number. Got it? So this is the formula you can use. So how does it work? See, I'll just take an example and I'll explain you. Initially, let us say the page number produced is 10, right? And initially there will be nothing in the page this TLB, because let us say we have just started now and there is nothing, and the page number produced is 10, right? Then what happens? Then CPU will search in the entire tags and it will not be present, and then it gives up, and then it will go to the main memory and take the entry who's for the 10, and now it will go to the main memory and it will get the concerned word by converting this page number into frame number. That is all over. And also it will update this this part here. In one of the entries it will update it and will say that page number 10 is now present and its frame number is so and so. Therefore from next time it will be a hit, right? And then I am not actually discussing how much will be the time taken to update this. So actually the time taken to update this is negligible, and this could be done in parallel when we are actually trying to access the main memory, right? So I'm not going to see how much time is going to be taken to update this. I'm just assuming that time will be negligible. And many times what happens is main memory access time will be so big that this factor will become very small, and sometimes in the questions they might neglect it. Anyway, you can have it and still do it, and you will get a close answer to the some number to the solution. Okay. We use a concept called as demand paging with virtual memory. Demand paging. Okay. Let me write it here. So what is virtual memory? Only a part of the process is going to be present in the main memory, which means only few pages are going to be present in the main memory at any time. Now, which pages are going to be those few pages? That is the main question. So here the problem is we don't know what the future is, isn't it? We don't know what the process might require in future. So what we do is we are never going to load the page until it is required. That is called demand paging, which means don't load any page. Loading means into the main memory. Don't load any page until required. So if it is not required, we'll never load it, right? That is called as demand paging. Now what is the problem with this? The problem is whenever any page is referred for the first time, the chances are that page will not be present in the main memory, and later maybe for the second reference, third reference it might be available or might not be, but that is okay. But for the first time it will not be available, right? That is called as page fault. Page fault means we are trying to refer to a page which is not present in the memory, right? So what happens is, see, CPU is going to generate this one logical address, and then logical address is going to contain page number and page offset, isn't it? Now if I take this page number and if I get into the page table, now page table contains this frame number and one more bit. Oh, I told you that in the earlier case there is a bit called as valid invalid bit, which is going to say whether the process is present in whether the page is present in the main memory or not. Please correct it. It is not valid invalid. I told you in the previous one, it is not valid invalid. It is present or absent bit. Actual bit is present or absent. Valid invalid bit has a different meaning. Valid invalid bit says that whether the address generated is valid or not. Sometimes what happens is, even though your virtual address space is 32 bits, which means CPU is generating 32-bit address, the process might not have a size of 2 power 32, right? That is a different case. Okay, so instead of valid invalid bit, you please make it as present or absent bit. Now using the page number, if I get into the page table, then the present or absent bit is going to say whether the page is present or not. In case if the page is present, yes, we can get into the main memory, and then we can get into that particular frame, and we can get the particular word, right? If this page is present in the main memory, if this particular page is present in the main memory. But then what happens if it is not present? So if valid invalid bit says, if present or absent bit says that it is not present, it is absent, right? Then this scenario is called as page fault. Page fault. Okay, don't get confused. The earlier concept where TLB was stored in the page table, page table was stored in TLB, and when the page table entry is not present in TLB, that scenario was called as TLB miss, right? And here it is called as page miss, or it is also called as page fault. Page fault means the page which you wanted is not present in the main memory. Then what is the problem with this? Then if the page is not present, then the time is going to be increased in order to get the page into the main memory. What are the actions that happens here is, so whenever the hardware generates a trap, hardware generating a trap means the page which you are actually trying to refer is not present in the main memory, then that will lead to hardware trap, which will lead to interrupt. Then the operating system will be woken up. Now operating system will take control, and then there will be a context switching. A user process is running. Now user process has to stop and the operating system will start running. Operating system is also a process, right? And therefore there has to be a context switch. Now operating system, what it will do is, it will find out what is the page which was trying to create the trap, and then it will try to go to the main that secondary disk, hard disk, and then it will try to read the page. So operating system will initiate the read request, and once the page becomes available in the main memory, again operating system will schedule this process where it has stopped. Let us say instruction I of some process has generated the trap, which means it tried to access a page which is not present in the main memory. Then what happens? Then exactly at that instruction I, this particular process will be stopped, and operating system will take over. That is where there is a context switch, and now operating system will get the required page into the main memory, and once the required page is available in main memory, again it will schedule the process with again instruction I. Then what happens? Again now instruction I will behave as if it has never happened before, right? Which means it will again get back the context of the process in such a way that process acts as if nothing has happened, and again it will restart the instruction I, and now at this point the page will be present in the memory and it will be accessed, right? But anyway there has to be a context switch. Let us say, see, if everything is fine, which means if the page is already present in the main memory, then the time taken will be around nanoseconds, just the memory access time, right? Main memory access time. Now in case, let us say this memory access time is in nanoseconds, alright? Now in case of page fault, what happens is there has to be a context switch. So for the context switch, what is context switch? Now the process which is doing this page fault has to call the operating system, right? Now operating system has to run, therefore there has to be a context switch. Now for this context switch, the time taken will be in microseconds. Microseconds means 1000 times this one. Why is this so? Is we have to execute some few instructions in the operating system code which might take microseconds, right? And now after the operating system has start running, then operating system will place the request for memory reading from secondary disk into the main memory, right? And for that movement, let us say for the copying, what is that we are trying to copy? A page from hard disk to the main memory, right? For that copying, the time taken is going to be milliseconds, right? And then again there has to be a context switch from operating system to the user process, right? So all these activities, right? So again there will be interrupt, and then interrupt service routine, everything will be there. I'll talk about interrupts later anyway, okay? So now anyway it is a lot of time consuming activity, isn't it? So if there is no page fault, then the process is actually going to run very fast and smooth. Now if there is a page fault, process is going to take a lot of time, right? Now what happens if there are lots of page faults? what happens if every reference is a page fault, right? Then the effective memory access time will become effective memory access time to access the secondary disk, right? So if there are lots of page faults, then the time taken to execute the program is going to increase because of the lot of paging activity, which means we are going to move a page from secondary disk to the main one, and then the other way, right? So that is called as trashing. So trashing is when there are lots of page faults, or in fact if number of page faults is equal to number of memory references, which means almost for every reference of the memory, let us say page fault is 50%, which means out of every 2 references, one reference is going to create a page fault. If that is the case, then most of the time is spent just reading the page from the hard disk into the main memory, right? Then this particular scenario, it is called as trashing. Now what we should do in order to eliminate this trashing is come up with better algorithms, right, which will be able to guess what is the requirement in the future. But it is impossible, right? See, if we know the future, we always take the better decisions. It is never possible. We wish we could, but then it is never possible, right? Then come up with the better algorithms in such a way that which will closely approximate the best algorithm available. Okay, what I mean to say is okay, see this. Now let us say there are various things here. So let us say a process has got only 4 frames allocated to this, even though the main memory contains many frames. In order to keep the degree of multi-programming high, what we try to do is we try to assign some fixed number of frames, or it is done, or some assignment is going to happen. There are various algorithms which are going to assign. Anyway, what happens is when the page numbers P1, P2, P3, P4 are already present in the frames, and now if I want the page number 5, then one of them has to be replaced with the new page, right? That is called as page replacement. For that we have algorithms. If you could do some better kind of page replacement algorithms, then maybe we could reduce the page fault rate. It is very important that we reduce the page fault rate, because the more the page fault is, the more the time required for memory access, and the slower the process execution is going to be, right? So how slower is it going to be? Now watch it. Now the effective memory access time in case of page fault is, if there is a page fault, let us say page fault rate is P, right? Then the effective memory access time is going to be P into service time. So service time is, or it is also called as page fault time, service time or page fault time. So this is the time taken in order to get a page and again restart the process in case of a page fault. In case there is no page fault, right? If there is no page fault, you have to directly get it from the main memory, right? Then it will be just memory access time. So this is the effective memory access time in the light of page fault. So actually what happens is, if there is a page fault, then I have to do a lot of work, and which will be very high compared to the memory access time. Yes, in fact, after doing all this work, again I have to fetch the instruction or whatever the word is from the main memory. Therefore I have to again add page fault time plus main memory access. Okay, are you following it? I'm not sure. Let me just take the example and explain you. What I mean to say is like this. Assume that there is a process. And now the process has got many pages, right? And assume that there is main memory. Then with the concept of demand paging, what happens is we'll start the process even without loading any page in the main memory, right? Then CPU, whenever it generates the logical address, right, it will contain two things. One is page number and other is page offset. So whenever it generates the first address, it will find out that this page number is not present in the main memory. How will it find out? Through the page table, right? In the page table, present or absent bit is going to specify it. then what happens is the required page, it has to be loaded into the main memory, right? And then again the same instruction will start, which will generate the same logical address for this entire time. To stop the process and then copy the page from the secondary memory to the main memory and again start the process. This is called as page fault time or service time. Now this is going to be very high compared to directly accessing the main memory, right? So in case if there is a page fault, then the effective access time is going to be the page fault time, the page fault rate into page fault time. In case if there is no page fault, then it is going to be simply MA. But in any way, even after loading the required page, again you are supposed to read the concerned word from that page. Therefore, I am even supposed to add MA even in the case of service time, but then we need not add MA because generally the page service time will be very high and the page memory access time will be very low. In this sense, it will be in milliseconds and it will be in nanoseconds, which means it will be 1/1,000,000th of the part. So if this is 1,000,000 seconds, 1,000,000 milliseconds, then it will be 1 millisecond, something like this. If it is if it is in 1 millisecond, in million milliseconds, it will be in nanoseconds. Therefore, we generally don't worry about adding this factor, right? So now this is going to be even more complex when we combine the concept of TLB with the page fault. Now first thing is, whenever we try to refer to a page entry, then that page entry, the page table entry, might not be present in the TLB. That is called as TLB miss. And next, whenever you try to refer to the concerned page, the page might not be present in the main memory. That is called as page fault. Now there is some probability of this TLB miss and TLB hit, and some probability of this page fault rate and page fault hit and page fault miss. Let's look at some of the popularly used page replacement algorithms. There are various algorithms which are currently being used, but there are mainly a few popular versions, and of these popular algorithms there are various versions. So let's see the main things now, and then we shall see about the other algorithms also. So page replacement algorithm, the first one is, which has been proposed but which will not be practical to implement, is this optimal page replacement algorithm. So what does it optimal page replacement algorithm mean is, so the page which will not be referred for the longest will be replaced. Optimal says that replace the page which will not be referred for longest, which means you are going to see which one will not be referred for a long time and we are going to replace it. That is called optimal algorithm, right? And then the next one is LRU, least recently used. So LRU says that replace the page which is least recently used. So which means replace the page which has not been referred for a long time. Okay, and the other important one is FIFO, first in first out. The name itself says the first one which has been which has been added into the main memory, that is the first one to go, right? So FIFO means the first one has to go out first. That is called FIFO. So anyway, optimal algorithm says that you look into the requests and you just see which one will not be used for a longest time, then you are going to replace it. With examples it will be clear. I don't think that with theory it will be clear. I'll take examples and explain you, but anyway, optimal says this. Okay, maybe let us say there is a supermarket. In supermarket, let us assume that there is a rack space. which means a supervisor has to choose what are the items that he could put in this space, right? Let us say one item is there is some notebook, and then there are pens, and then there are textbooks, right? So now he has to introduce a new item, right? And now by adding that new item, if he has to add the new item, one of them has to be replaced, right? Then optimal says that you see in the future, see which one will not be bought for a long time. Let us say in future, if you are sure that no one is going to buy the pens, then you can replace the pens. Or if you can see that no one is going to buy notebooks for a long time, then you can replace the notebook. Whichever is not going to be bought for a long time, you are going to replace it. But what is the problem with such a method? We can never expect what the future is. It is like this: you take some decision now based on what the future will be, right? We could never do that, isn't it? In real life also, how could we do that? If you don't know what is happening in the future, how could you make a decision now so that your future will be safe? It is never possible, right? So that is why optimal algorithm has been proposed, but it is never implemented, and it is impossible to implement practically. It is impossible, you cannot implement it, okay? Then why is optimal used is, optimal algorithm, in case if it could be implemented, will give you the least number of page faults. So whenever anyone proposes any new page replacement algorithm, what they do is they will measure its performance against this optimal algorithm, right? So optimal algorithm is used for benchmarking, which means the people will say it is 90% close to optimal, it is 70% close to optimal. So if you come up with any new or any good algorithm, or if you propose any algorithm, and if you have to prove that your algorithm is good, then you run the same simulations on your algorithm as well as on the optimal algorithm. If your algorithm is close to optimal, then people can go ahead and implement it. So it is used for benchmarking, not for implementation. And the next one is least recently used. This is very easy. So you need not look into the future, you look into the past. If someone has not been buying a good, something for a long time, then maybe you replace it. For example, if you look into the past, and 1 day ago someone bought the notebook, and 2 days ago someone bought the pens, and 3 days ago someone bought the textbooks, and after that there are no buyings. So this is 1 day ago, 2 days ago, 3 days ago, right? Then which one are you going to replace? This textbook, right? Because it has been not bought for a long time, in the past, not in the future. So it is practical and it can be implemented. There are various variations of least recently used. We shall see them also, okay, the various variations. But anyway, from gate point of view, variations are not important, only the main algorithms are important, and even implementations are also not important. Let's see the problems, you'll understand it. And next one is FIFO. First in first out says that you just see the order in which you have placed them, which means maybe in the supermarket notebooks were introduced first, and then pens were introduced, and then textbooks. Then whichever has been introduced first, that one has to go out first. So which will go out now? Notebooks will go out. Why? Because notebooks were the first one to enter into the rack in supermarket, right? So this is how we can implement these algorithms. Paging is very popular in many of the operating systems, but along with this there is one more concept called as segmentation. Segmentation is like this. Even though paging is dividing the process into pages, the problem is when we divide them into pages, sometimes what happens is two related pages might two related segments. Okay, what I can say is, I should not use the word segment as of now. So two related parts of a program might fall in two different pages. Let us say you have a function f, okay, and now using this function f, if you have written this in many lines, then if you apply paging concept, it might so happen that the function might get divided into two parts, right? And now it might so happen that these two parts might map to only a single frame, which means in order to load these two parts, only one single frame might be allocated, right? Then what happens? In order to run this, first you load the first part, and then once you cross this boundary, you have to load the second part, right? So dividing the program or the process into pages might sometimes lead to division which might not be meaningful, which means you might try to cross the boundaries, or your paging boundaries might try to divide the process in such a way that some useful things might fall in different places, different pages which are supposed to be together, which is not meaningful. So in order to match the process to how we visualize it, to how we perceive it, to how it is called as user's view. See, user's view is different from the operating system's view. Operating system can directly see the process as pages and it can load it, but a user will always have a different kind of view, in which when we talk about a program, we generally talk about the functions in the program, isn't it? We say that it is main function, it is function f, it is function g, something like this, right? We don't talk in terms of the pages. So for users, to be meaningful for the users, we are going to divide the process into segments. So segments is actually close to what the users will think of a program, like this. So what this concept says is, the entire process will actually be divided into not the pages, it will be divided into segments. For example, one segment can be the main segment, which contains the main program, and then other segment can be some user defined function, something like this, and other segment can be some library function, right? And other segment can be data part, and other segment can be stack, right? Then what happens is, we load these segments in the main memory as a whole. So when we load this main, this segment called main, we load this entirely in the main memory. And when we load this entirely in the main memory. We are not going to divide this into any smaller parts, right? So now, what is the advantage of having such a kind of segmentation is, or how to implement it is, once we are running some function, we need not worry about whether the rest of it is present in it or not. So if you generally call a function f, it so happens that we run it till the completion. Therefore, when you are running it entirely, it will be loaded into the main memory, and you need not worry about the page faults in the middle. And moreover, it will be meaningful for the user also. Then what we do is, whenever we try to load this, just like pages, we load the segments onto the main memory like this. Let us say this is the memory, physical memory in which main is loaded, right? And then this is called the base. Base means what is the starting point where you have loaded it, and this entire part is called as limit, or sometimes called as size. Okay, so base and limit are the two parameters which are associated with the segment. So every segment is going to be loaded at some point in the memory, and the base of that segment will say where it is starting from, and the limit will say till what part it is running, right? And for example, if we have the function f, if it is loaded from here, then we can say that this is the base and this is the limit or size. Okay, and now like this, in the main memory we are going to load all these segments. Then how to manage it, how to given a logical address, how can I convert into physical address? That is called memory management unit, right? Now here memory management unit will contain one table called as, just like page table, there will be a table called as segment table. And now this segment table will contain one entry for each segment present in this, and each page table, this segment table entry will contain, basically it will contain many parts, but the most important part is what is the base and what is the limit, right? So for example, now whenever CPU generates any logical address, it can be divided into two parts. One is what is the segment number that the CPU wants to access, and within that segment what is the offset, which means once you reach the segment, where do you want to, what word we want to access it, right? So CPU generates the logical address, and now logical address contains two parts. One is segment number and other is the offset, which means within that segment where we have to go and get the word from, right? Now by using this segment number, right, we go into that particular segment. For example, if you want segment, this is segment 0, this is segment 1, segment 2, segment 3, segment 4, segment 5, right? By using this segment number, we go into that particular segment and we get the base of it. Okay. Once we get the base of the limit, if the segment size is, let us say, 100 bytes, you should not ask for 1000 bytes. Depending on the limit of the segment or size of the segment, your offset should always be less than that. So we even perform a checking here, right? We take the offset and we perform a checking. So the limit, the offset of the word has to be less than the limit. Then only we are going to take the base and then add the offset, and we are going to get the actual whatever word we have, and we are going to get it, right? So that is how it is going to be acted. And now CPU, whenever it generates this logical address, it should even know where the segment table is stored. Just like page table, segment table will also be loaded in one particular page, right? So segment table will be loaded in one particular at one particular segment, not the page, at one particular point in the main memory, and that will be present in the starting address will be present in a register. This register is called as segment pointer, or segment table base. Let's not call it segment pointer, that has separate meaning in various operating systems. Let's call it segment table base. Now the segment table base will point to the starting address of the segment table, and now the segment number is nothing but from that starting address which entry you want to get into. And once you get into that entry, then you can get the base of it. This base will point to the starting address of some segment. For example, if this one might point to this, right? And then you can take the offset and get into that segment and get that particular word, and that is how the physical address is converted to logical address is converted to physical address. So here, how are you doing it? Given a logical address, we are going to present it to the memory management unit. In this case, memory management unit is nothing but segment table, right? Now logical address contains segment number and the segment offset, and this one will be given to the segment table, and from the segment table we get out the base, and then and from the logical address we take the offset and we are going to add it, and this will be physical address. This one will be given to the main memory and we get the required word. That is how the segmentation is implemented. And segmentation is not very popular. In the sense, pure segmentation is not very popular, but then some of the operating systems, some of the platforms, they support a combination of segmentation with paging. That will be interesting. We shall see what that is. Okay. Anyway, this is how segmentation is done. So what is the main advantage of segmentation? A user can look at the program in terms of the segments, not in terms of the pages, because looking at a program in terms of the pages is not logical for a user. User point of view is different and the system point of view is different, and segmentation is close to the user point of view and paging is close to the system point of view. Now let's combine the concept of segmentation with paging. It is slightly difficult, but then if you can follow it, it is very simple. It will be just like paging, only with just one extra step. If you understood everything about the multi-level paging, all the questions in this memory management will be very easy. Only that you should understand that multi-level paging very well. So this is just an extension to that. A kind of multi-level paging. I'll just show you what it is. First of all, the process is initially divided into something called as segments. Okay, so let us assume that a process containing segments like this. These are all the segments. Okay, and next they're all the segments, and they need not be of same size. Even though the diagram looks like they're all of same size, they need not be of same size. And next thing is, I'm going to divide these segments into equal sized pages. Now these segments will be divided into pages. Okay, and the same concept, main memory will be divided into, right? So let us say this is main memory, and now main memory will be divided into something called as frames, right? And in such a way that these pages will be equal to frames. So now these segments have nothing to do with the loading the main memory with the pages. So segments are closer to the user point of view and paging is closer to the implementation point of view. So that is the benefit of this. So segmentation with paging is actually beneficial in two ways. One is user can still look at the program as a collection of segments, but the operating system will look at it as just like pages and frames, right? And see, the first most popular method is paging, simple paging or virtual memory with paging. And the next popular method is segmentation with paging, and pure segmentation is rarely used. Okay, so anyway, the final point is whenever CPU generates the address, the logical address, how can we know that how to convert it into physical address? Which means if CPU is asking for a word, then how can you get into the main memory and then get that word? That is the main question, right? So in order to answer that, again there is memory management unit. The entire purpose of memory management unit is to convert logical address to physical address. Whatever address is generated by CPU, it has to convert it into physical address so that we can get into the main memory and get it, right? Now to implement this, what happened is, what we do is, first of all, for every segment we are having various pages, right? So for every segment we will have one page table. So this is page table 1, this belongs to the segment 1, or this will talk about what are all the pages in this segment S1. Let us say this is segment S2, this is segment S3, and this is segment S4, right? So now page table 1 will talk about what are all the pages present in S1 and where they are. Either they are in the main memory. If they are in main memory, what is the frame they are present in, or if they are in the not in the main memory, it will say it is not present and you have to load it, some kind of it. So depending on virtual memory is implemented or not. Anyway, every segment is associated with one page table. So remember this, earlier what happened, the entire process used to have one single page table, but here every segment will have a page table, right? And similarly there will be one more page table for the segment 2, and one more page table for the segment 3, and one more page table for segment 4, right? Now these page tables will contain entries for the pages in the segments like this. These page tables will contain the entries for the pages in the segments. Got it? So if there are 10 pages here, then how many entries will be present in this page table? 10. If there are 20 pages here, how many entries will be present here? 20. Got it? So each entry will contain something about the page present there, right? So what should be present initially? So every page table should contain the frame number or the frame base in which this particular page is loaded. For example, let us say this frame number is F1, F2, F3, F4, F5, F6, F7, F8, like this. And let us say this particular page number is let's say it is starting with 0. There is 0 also. This page number is 0, 1, 2, 3. In case if the page number 0 of S1 is loaded in, let us say, frame number 7 of the main memory, then here in the page table, the corresponding entry of page number 0, it will say that page number 0 is loaded in frame number 7. That is what it contains. Therefore, what should every page table contain? Every page table is supposed to contain the frame number in which that particular page is present in. Got it? And now one more thing is, since we are using the paging, even these page tables should also be present in the pages. So if you are going with one level of paging, that is what we do in the segmentation with paging, we have only one level of paging, then we can even extend it, but most of the implementations they follow only one level of paging. Therefore what we carefully design is, we design this paging scheme in such a way that one page table of every segment, or the page table of every segment is going to fit in one particular page. So all the page tables, they should fit in one page each. Therefore if you have 4 page tables, how many pages you should use? We should use 4 pages, or in fact I know we are talking about the frames. We should use 4 frames, and these 4 page tables have to be loaded in 4 frames. And now we should even keep track of which frames contain these page tables. Earlier when we had only one page table, CPU used to have a register which contains the base of the page table, isn't it? But now we have 4 page tables. Now CPU has to maintain the list of all the frame numbers in which these page tables are loaded. Otherwise the mapping forward is not possible, isn't it? That is why in order to keep track of that, we have one more table that is called as segment table. For the entire process we have only one segment table. This is called as a segment table, right? Now what will the segment table contain? The segment table will contain pointers to the page tables, which means each, if there are 4 page tables, then it will contain, this is the first page table, this is the second page table, this is the third page table, this is the fourth page table. See, even though I am talking about directly pointing to the page table, actually what this means is page table, this PT1 is in one of the frame in the main memory, and now we are pointing to the frame. Therefore, even the segment table entries should also be containing the frame numbers in which that particular page table is present, and page tables will contain the frame numbers in which that particular page is present. Are you following it? See, it might look difficult, but once you practice it, it's going to be very, very easy. Okay. And now even this segment table should also be present in a frame, isn't it? Yes, it will be present in a frame. And what happens is CPU will contain, whenever it is trying to run this process, CPU in its one of the registers, it will contain what is the base of segment table. Base of the segment table. Therefore, this particular entry will point to this one, right? And all the entries will point to this, and these will point to the pages, like where the pages are present. So if you want to put together everything and see what is really happening, let's see this. Now CPU will generate something called as logical address. Logical address can be viewed like this. One is, logical address will contain what is the segment number, right? And then what is the page number, and then finally what is the page offset. This is what logical address will contain. Now using the segment table base, we can get into the segment table. Now using the segment number that we want to access, then we get into the corresponding segment. Let us say I want to access the segment number 1. Then to the base I'll add that, and I'll get into the segment number 1. Let us say this is segment 0. We shall always start with zeros only, it will be better. Segment 1, segment 2, segment 3, and page table 0, page table 1, page table 2, page table 3, right? And let us say the segment number is segment number 2. Then what happens is, this is segment number 0, this is segment number 1, segment number 2. To the base, when I add this number, I get into the corresponding entry, and this entry will contain the base of the frame, or the frame number in which the corresponding page table of the segment 2 is loaded, which means this entry will point to the starting of a page table, right? Let us say in that page table again we want page number 3. Then what we do is, we go to this base of the page table and then we add 3, then we go into the corresponding entry, right? Page number 0, page number 1, page number 2, page number 3. Let us say this is the entry, right? And now this entry will contain the frame number base in which that particular page is loaded, right? Let us say that particular page is loaded somewhere here. Okay, now we go into this, and then finally the page offset will say, let us say the page offset is saying 10, which means I want the 10th word in that page. So we can go into that and we can get that word. That is how it operates. Understood this? So what is it? The entire process is divided into various segments, and for every segment we are again dividing into pages, and for every segment there is a page table. It is contrary to the other one. In pure paging, for the entire process we had only one page table, but here for every segment we have to maintain various page tables. What will these page tables contain? The frame number in which that particular page is present. Therefore, what will be the size of page table entry? That depends on what is the frame number size, and that you know that these questions we have already done in paging, right? And then all these page tables are going to point to some of the frames, right? And these page tables also have to be kept track so that we can do the mapping. For that reason we use one more table called as segmentation table. For the entire process, there will be only one segment table, right? And this segment table or these page tables, everything should be in the main memory, and all of them should fit in one frame. I mean, not all of them, each one taken has to go into one frame, which means segmentation table should go into one frame, and all these page tables should go into one frame each, right? And now we should have what is that frame number in which all these are present. Now we should at least have what is the frame number in which the outermost segment table is present. For that, CPU will be loaded with this segment table base. Who will load it? That context switching. During that context switching, the scheduler, whenever it is doing the context switching, right, it is going to load it with this. Got it? Load the CPU register with this particular the base of the segment table. Now the base of the segment table will point to the frame in which the segment table is present. Now using that, you can use this logical address, and we can convert it that way. How? Now we go into the segment table, and using this segment number we can go into the page table. Now after going to the page table, using the page number, we can go into that particular entry. Now after fetching that, we can get into the frame in which that particular entry is present, right? That particular page is present, and after getting into that frame, we can take the page offset, and then we can get into that word. Got it? That is how logical address is converted to physical address. So if you didn't understand this, I'll just tell you how it is converted. See this. Just to make it clear how the logical address is converted to physical address, observe this. Now CPU should at least know what is the base of the segment table, and that will be loaded when you are loading the context of the process. For every process, when you are trying to do the context switching, or when you are trying to start, when you try to start running the context switching, start a process, then along with the other registers, one of the main important register is either the page table base or the segment table base, depending on whether you are using paging or segmentation, right? That is going to be loaded in that register. Now CPU knows where the segment table base is present, which means what is the address in which that particular frame is present, right? And now to this segment table base, if we add this segment number, it is going to give you a new number, right? So what is it? This is nothing but the entry in the segment table in which that particular in the segment table entry in which that particular page table is pointed to. So this number is nothing but the page table base. This number, whatever you get, is nothing but the page table base of the particular segment. Are you following this? Which particular segment? That particular segment depends on what is it you are asking. So here, if you are asking for segment number 2, this will contain the page table base of the segment number 2, right? And now this number, when it is added with the page number, right? When you add this with the page number, then you are going to see, actually this one is going to the page table base, right? Which means using this number you are going to enter into the page table, right? And now when I add this page number, I can get into the page table to the particular entry which points to this particular page in the memory, right? So which means this one will give you the number, whatever we get. This one is going to give you the frame number or the frame base. The frame base of the frame, which contains the required page, right? Which contains the required page. Got it? And now finally we have got the frame base, and to that frame base, when we add this page offset, finally what we get is address of the word, which is nothing but the physical address in which our required word is present. From there you can read the word into the data bus. Now this when physical address, when this is given to the main memory, it will take it, right? Therefore this entire procedure is followed in order to convert logical address into physical address. So what are the various tables involved in this? One table is segment table, and other table is page table. So in segmented paging, memory management unit contains of two tables. One is segment table, other is page table. Using these two tables, we convert the logical address to physical address. File system is the most important part of the operating system. In the sense, without file system it will be very difficult for us to access the information in the computer. So I'll just take an example. See, let us say you have a video, right? And whenever you want to save this video on the computer, you have this hard disk. Okay, first of all, why do you have to save this information? Is any information in general is because your main memory is volatile, which means if you switch off your computer, you know that main memory doesn't last longer. So that is why we try to save everything on the hard disk, and later when we need them we have to fetch them. And the way hard disk is organized is very much different from the way you think the file is organized. In the sense, let us say, take a video. If it is 4 MB, 4 MB video has to be organized across the disk, hard disk. But then the hard disk will not be having a contiguous size of 4 MB available for you. Therefore, you have to divide the information which you want to store into various parts, which is called as blocks, and then map these logical blocks onto the physical blocks, right? What are physical blocks? I'll talk about it later. The hard disk is actually partitioned into something called as blocks, right? Which means like this. If you have a hard disk, even though I'm going to talk about it later, I'll just give you a brief overview, right? Hard disk or any storage device will have small units or chunks of memory which is going to be accessed all at once, either to read it or to write it. So whenever you want to access the smallest information which is present in the hard disk, you are supposed to take the block, right? And now let us say your file is in such a way that it needs 10 blocks to save that file. Let us say a video file. Now if you try to find all the 10 blocks which are contiguous, you may not be able to find it. Or even if you are able to find it, later when you want to fetch it and do it on your own, it will be tedious without the support of operating system. Therefore, operating system just abstracts it out, which means operating system will just leave out the details about how your hard disk is actually structured. It will provide an abstract data structure which is called as a file. So using a file, what we can do is we can provide to the operating system the logical file, and now the logical file will be taken by the operating system and it will store it physically on the hard disk. This entire thing is done by the file system. The entire code which is required to do this process, which is used to create a file, store the file, fetch the file, everything. I'll tell you what we can do on the files, but the entire code which is required is going to be present in the operating system, and it is the most important thing. And what I mean to say is, whatever you try to save on the computer is going to be saved as a file, right? To operating system, everything is a file. Either it is a video, or it is executable file, or it is a text file, or it is even some collection of records of the database. So what we generally do is we collect all the what can I say, logically related information into a file. So if you want to see how the concept has arrived, we have some information, and then we collect the information which is logically related, like let us say maybe all the employee records of a company. These all, they are all related, right? We collect all the related information and we put them into files, right? And then these files are going to be stored in our computer, and if you look at the number of files in your computer, they are going to be very large number of files are going to be there, huge number of files are going to be there. And now in order to manage these many files, it is sometimes going to be difficult. Therefore, we even group the collection of files which are logically related into something called as directory, okay? And then we even group the directories which are logically related into something called as file system. Therefore, file system can be viewed as the software which will manage and create all the directories, which in turn will contain all the files, which in turn will contain the information, right? This is the way it is going to be, okay? And now what will our file system of the operating system perform is, it will perform various operations, and it will give you the code, the executable code, in order to perform various actions. We shall see all of them. Okay, so for now understand that. Later we shall again see in the hard disk about how the file is actually stored on the hard disk, but now let's look at only the logical view of the file part. Okay, so now file is a abstract data structure which is going to have some attributes like in the data structure. Okay, so now let's see the file attributes. So first thing is, every file is supposed to have a name. You know this, we definitely name every file, otherwise it will be difficult for us to take it back, right, when required. So every file is going to have a name, right? And what type of name it is? Generally human readable. Along with the name, it is not compulsory, some of the systems will use it. You are supposed to provide an extension which will help the operating system in choosing the application in order to use a file. For example, if you see .exe, then when you click on the file, operating system will try to execute the file because it is executable. .exe means executable. If you save the file as doc, right, maybe in Microsoft, then it is going to open the Office, MS Office, in order to open the doc, right? So these extensions are going to be kind of hint provided to the operating system, and it is not mandatory. If you provide it, it is good. Okay, in some of the systems it is mandatory, and recently all the operating systems made it optional. We need not provide it with any extension. It is automatically going to add the extension in case if it finds out the type. Otherwise it is going to leave it as it is. Later when you try to open it, you are supposed to even specify what application you want to open that file with. Okay, and now maybe if it is a video, if you save it as .mov, maybe a video player will open it if you click on that, right? So these are all hints, right? And the next one is type. So the type of the file specifies what is the information which is present inside the file. There are various types of information, types of files you can save on a computer, like, you know, executable file, video file, audio file, and maybe text file, or a collection of records, or a sequence of bytes. So whatever, you are going to have the type of the file also. So you know, this is also going to be an attribute. So this particular type of the field, generally some operating systems are going to provide you when you try to save a file. It will even ask you what is the type of it. As if you provide it, it will be better for it to search and open the applications which are related to that when you try to open the file. And the next one is location. Sometimes what happens is, a computer might have more than one storage device connected to that. Maybe you might have external hard disk, and maybe you might have internal hard disk in your computer, and then some of the files might be on the internal hard disk, and some of them might be on the external hard disk. Therefore this location gives the hint to the operating system about where this particular file is located. So it is nothing but a kind of pointer which points to the physical location in which this file is present, right? And the size says what is the total size of the this file in bytes. So why is size useful is, okay, later we shall see it. Okay, I'll tell you, we shall do some problems on it, like if you have a file of size so and so, and the block size of the hard disk is so and so, then how many blocks is it going to take? Then what is internal fragmentation? We shall see that questions later. So size is going to be an important attribute to a file. And the next one is protection. So you are not, sometimes what happens is, you don't want anyone or everyone to run all the files on your computer. You want to give some access, some types of access to some types of users. Maybe to ordinary users who are not admins, you don't want them to run a program which is used to remove remove a file from a directory, right? So like that, you can specify that these are the class of users or the group of users who can perform these actions on this file. Sometimes you can say that some people can only read a file but they cannot delete it. Some people can only write a file, they cannot execute it. So likewise, protection is used to just save the files which are to be saved or which should not be given access to everyone, right? And the next one is time and date. So this indicates what is the time and what is the date you have created a file. It will be useful in some cases. Let us say you have a source file and a compiled version of it. You have a source file and a compiled version of the file .exe. Okay, and now you can develop an application in such a way that whenever someone clicks on the .exe, your application should search the source file which is related to that, and in case if the source file is modified after this exe is created, that executable file is created, you can ask your you can write the application in such a way that it should compile the source file again into the new exe file and replace the new exe file, old exe file with the new exe file, and then run it. So in this case, maybe having this time and date of creation and time and date of lost modified may be useful. For example, let us say here it is .exe file is lost modified or created on May 5th, right? And then source is modified, let us say May 10th, and today is, let us assume that it is May 15th, and if you are trying to execute this file, then it is better that you check if the source file is modified. Yes, the source file is modified. It has executable file is created on May 5th, and then the source file is modified on May 10th, and now you are trying to execute it. Therefore it is better that you compile it again and then get the latest copy of the .exe file and then execute it, right? So in such cases this attribute will be useful. Okay, and next, apart from these attributes, see what is the need of this attribute is, I told you that a file is nothing but an abstract data type, and every data type is going to have some properties. These properties are nothing but the attributes. Now these attributes are just like the metadata about the file. So once you read this entire information, you got everything that is required about the file. It will be easy for you to open the file, read the file, write the file, whatever you want to do. This information is going to be useful first, right? And then there are some operations which you can do on the file. What are the general operations that you do? You must be aware of it, right? You must be knowing most of the operations. I'll tell you what they are. So one is creating. So file operations are nothing but the most important operation is we keep on creating the files, isn't it? So we have to create it, and then after creating we generally write. So whenever we create, what happens is some space will be allocated for the file on the hard disk, and then when you try to write some information, then we are going to add some bytes to that space, right? Now here one thing should be important. In order to see, your file will be growing, right? And let us say this entire space is allocated for your file, and maybe you have written it till here, and next time again when you try to write onto the file, you should again start writing from this point where you have previously left writing, isn't it? Therefore, in order to understand where to start writing, if the file has already been created and if something has already been written, we are going to have a pointer. Let us say write pointer. So operating system is going to maintain a pointer with every file which is going to indicate till what part it has been written, so that you can continue writing from there on, right? And similarly, when you are reading, you read a file sequentially in most of the cases, right? Other than these database applications, generally we do sequential writing. So whenever you are reading, you are going to read sequentially. Therefore, you should even remember what is the last byte that has been read, so that you can read the next byte. Therefore, it is often useful to save a pointer which is called as read pointer, right? So most of the operating systems, in order to avoid using these two pointers, I hope that you understood why these two pointers are required, because a file is going to be a huge space, and now you can either read or write anywhere, and in order to keep track of where you have been writing and where you have been reading from, it is always better that you mark some pointers, right? So that is why we are going to use pointers. Now read pointer and write pointer are two variables which have to be maintained by the operating system, because generally what you do is, whenever you want to read or write something from the operating system, something from a file, you ask the operating system. Therefore it is the responsibility of the operating system to save it, right, to save the pointers. So what operating system is, many operating systems are trying to do is, instead of using two pointers, this read and write, they are generally using a pointer, because it is based on the assumption that we either you open a file to read or to write, and we don't generally do both of it simultaneously. Therefore one pointer is going to act as either read pointer or write pointer depending on how you opened it. If you are opening it for read, then it is going to act as read pointer. If you are going to open it as write, then it is going to act as write pointer. Therefore having that marking, maybe you can think of it like a bookmark, right? When you are reading a book, if you close it later, if you want to open it and read it, it is better that you place a bookmark in that, isn't it? So this is the kind of pointer, is kind of bookmark, and it is going to be useful. I'll tell you later where it is going to be useful. And the next thing is repositioning. Repositioning is, if your read pointer or write pointer is somewhere here, and maybe if you want to skip some part and go to the next part, right, then you are going to use repositioning. There are various commands like seek. Not important, commands are not important, we should not get into that. Let's get only these terms. Okay, so repositioning means just moving the pointers here and there, wherever you want to move them, sometimes if you want to skip it, right? And next one is deleting. So deleting is nothing but you want to delete this space allocated to the file, as well as the information about the file itself, which means even this entire information has to be deleted. It is not just the space allocated to the file. See, as I said, file means it is not actually one thing, it is complex thing, it is a data structure, right? It is actually the space allocated to the file. Along with that, even the metadata means the attributes, right? And deleting a file is deleting the space, freeing up the space allocated to that and giving it to some other uses, the space. Along with that, deleting the attributes also, right? And now truncating the file. So truncating means we would like to free up the space which is given to the file, but then keep the attributes. It is just like this. We don't want the data in the file. We want to again redo the complete file. We want to replace the complete information with some other information. Then what we do is, first you free up the space, and then again you create the file. But then you need not create the complete file. The attributes are going to be there. So only some few things are going to be changed in the attribute, like this size. So you can think of it like this. How can I explain this truncating is, I'm not getting any real-time application. So see, what I'm trying to say is, you are just going to delete the space allocated. The information, everything will be gone, but the name and everything will be there. All the attributes will be there. Later you can add the information freshly, right? Truncating means just the space which is allocated to that will be freed up and everything will be there. The attributes will still be there. Okay, fine. Whenever a process tries to access a file, like if it wants to read or write onto the file, then operating system has to do many things. Like it has to search for the file and get the information about the file, about where it is located and all. And also it has to see what is the last time access made by the process. For example, if you are trying to read something from the file, let us say if you already read it and now again you are trying to read it, then the next information from where you have left has to be shown to you, right? And how can the operating system keep track of all this information? It is going to be hectic because many processes will try to open many files, and operating system has to, anytime whenever any process asks it for a file, it has to go through all the directories to search about the file, to search about the information and then get the information. So instead of going through all this painful process, what operating system will try to do is, it will try to maintain some tables, right? In these tables it will just keep the frequently asked information or the open files like this. If some information is going to be used very frequently, it is very useful that you keep it in a place where you can fetch it easily, right? So the same concept has been used in the page tables, if you remember it. The frequently used entries in the page table are actually kept in a special memory, right, the cache. So similarly here also we can do the same thing. So here whenever a file is open, whenever you want to access a file, if you have the intention to access a file or either for reading or writing any process, it is supposed to open it. So the first rule is every process is supposed to open the file before it reads it. Then whenever you open a file, operating system is going to create a table. Okay, so let us say you have a process P1. Let's say I'm just writing some few processes P1, P2, P3, right? So whenever P1 tries to open a file, then operating system will create a per process file table. Per process file table. In this per process file table, it will maintain information about what is the file that this particular process wants to open. So whenever this one calls open, then it is going to maintain what is the file that it is going to maintain, right? Let us say the file is ravi.c, okay, something like this. Now this file is going to be opened, so it is going to maintain some more information about the file. So what are the most important information is it has to maintain a pointer, right, file pointer. So this file pointer is going to point into the file about where did we leave reading or writing last time. So again, if you have to access the file, we can resume the operation from the point where you have left it, right? And then along with that, it will even locate the access rights, right? So access rights says whether this process can execute it or only read it or only write it, or can it execute it, read, write, execute. So this information is going to be placed in the per process table. Along with this per process table, which the operating system maintains per process, for every process there is going to be a table like this. Along with this, operating system will also maintain a global table, right? It is open file table. This is global, which means for all the files which are open, it is going to maintain a global table, and for all the files which are opened by a process, it is going to maintain a per process table. So per process table will contain the information which is relevant for a process in order to access the file, and the global file table will contain the information which is relevant for every process in order to access a file, right? Now let us say there is one more process P2 which also wants to open the same file ravi.c. Let us say it is also opening the same file ravi.c. Then it will also maintain in its per process table what is the file pointer, because these two file pointers will be different, right? So the file pointer which is used by P2 might be pointing to a different location, and file pointer which is used by P1 might be pointing to a different location. This depends on which part of the file this one is reading at present and which part of the file this one is reading at present. Both of them cannot use the same pointer because both of them are not going to read at the same time synchronously, right? And along with that, both the process might have different access rights, right? This information will be provided here. Now in order to open this file, operating system needs some more information like where the file is located, and the file location does not depend on the process which is opening it, isn't it? That is why the file location information will be located in the global table, right? So let us say this is the entry for ravi.c file, and then file location is going to be present here, and along with that, okay, now file location is going to be present here. So whenever this process wants to read something from this, operating system will first consult the local entry per process page table, and then it will see from which pointer it should continue reading, and then it will see whether it has the access permission to access that, and in case if it is true, then there will be a pointer in this entry which is pointing to this entry. Therefore operating system will go from here into this entry and then get the location of the file and get into the hard disk using the location, right? and then in the hard disk it knows the location and the file pointer, and then it will get the information whichever you are looking for. Got it? So this particular file table is going to grow depending on the number of files which are currently open, and whenever the file has been closed, you are supposed to delete the entry so that you can make space for other entries, other files, right? But then how can you understand whether everyone has closed it? Let us say if a file is opened by only one process, then of course if it closes it, then you are going to delete the entry here, right? And then can I delete the entry here also? That depends on whether all the other files, all the other processes which have opened this file have closed it or not. So just to make sure that all the processes which have opened a file have closed it, we are going to make a counter, right? So this counter is known as file open count. This is nothing but number of processes which have opened a particular file. Why is it important? Because when all the processes which have opened a file have closed it, then only we are supposed to delete that entry from the global file table and then delete it completely, isn't it? Therefore we are going to have one more entry here which is called as file open count. So this file open count is going to show us how many files, how many processes have currently opened the file. Initially it will be 2 because 2 of them have opened it. In case if some other process also opens it, then it will be incremented by 3, and whenever any process closes it, this record will be deleted and it will be decremented. Initially it was 2, now it is 1, and later if this process also closes the file, this record will be deleted. Along with that, this will be decremented to 0, and whenever this decrement it gets to 0, it means that no process is actually opening this file, is using this file. All the process have closed it, right? Even if you don't close it, whenever a process terminates, obviously all this is going to be freed up, and even the count is going to be decremented here. So once this count reaches 0, this particular entry will be deleted. The usefulness of this maintaining these tables, open file tables, is just to save time. If you don't have these tables, then every time any process performs an operation on the file, you are supposed to get into the directories and search the entire information, and then search the pointers and maybe access rights and then the file location. It is going to be tedious because you have to get into the hard disk to get that information. If you can store it in terms of some tables in the main memory, it will be faster. Got it? So this is how we save this information on the main memory to make it easier or faster or efficient. Got it? Okay. Very often, even in your personal computers, the laptops or the computers that you use at home, even in those personal computers also, you would like to have more than one file system. So what are the various reasons we want to have more than one file system is, sometimes we want to differentiate the types of files. Sometimes the files related to some work are very much related or very much closely related, that we want to separate them completely from the other types of file systems and put it separately. So there are various reasons why we want to separate the files completely. In that case, what we want to do is, in the same computer we would like to have more than one file system. One file system will contain completely different types of files, and the other file system will contain completely different types of files. This type of dividing has been used long back, but recently the reason why we are going for more than one file system in the same computer is because we want to use more than one operating system. And when you are using more than one operating systems, the Windows operating system might not understand the files which are created by Linux, and the Linux might not understand the format of the files which are created by Windows, right? So when you have various operating systems working on the same computer, then you might have to use different file systems in such a way that that particular operating system will be able to understand it. So how is this particular concept implemented is, see, the practical part that varies from hardware to hardware, but here we are only looking at the theory. So whatever we discuss here in this course is only theoretical perspective. We are not going to take any case. So let us just put it to theory. Now if you assume that this is our hard disk Now this hard disk, you can think of it as a continuous array of bytes. So you can partition it. So the most common terminology used here is partitioning. So what we do is we partition the hard disk into various partitions depending on how many operating systems or how many file systems you would like to have. For example, if you want to have 2 file systems, then you can make it into 2 partitions. You can also tell your hardware how much space you want to allocate for the first partition and how much space you want to allocate for the second partition. See, there are various terminologies used here. Some people use partitions and some people use the name volumes and some people use the name mini disk. So whatever the name used, the concept is dividing the hard disk or the available memory in the hard disk into various parts and then allocating each part to a file system, right? Now this particular part can be allocated to one file system and the other part can be allocated to other file system. Now when you are trying to access this file system, how do you know how many files are there and what are the names of the files and where are these files located? For example, you can have a file 1 here, right, and then file 2 here and then file 3 here. So how do you know that this is the starting of the file and this is the ending of the file? You are supposed to save all this information, right? So for that reason, every partition is supposed to have at least one special type of file which is called as directory. So the beginning of the starting of the file system will be dedicated to something called as directory. Now what is a directory is, the simple way you can assume it is, a directory is a kind of translation table which translates the file name into all the information required to access it. For example, we remember only the file names. Let us say I want to see a picture which is called ravi.jpg, right? So let us say it is a picture. Now if you want to see that picture, you are supposed to know where it is present, the location, and what is the size of it, till what part it is present, so that you can retrieve it and then look at it, right? So the entire data related to this file will also be kept in the entry called as the directory entry. Are you getting it? If you want to observe it, see this. Now let us say this is the hard disk, and now we are dividing the hard disk into various partitions, right? And now each partition will have a different file system. For example, this is the file system which is related to Windows, and this is the file system which is related to Linux. Therefore, when you use Windows operating system while booting up, then it will use this part of the hard disk, and when you use Linux, it will use this part of the hard disk, because the operating system code, or every operating system will have its own code to access the file system, and it will be different from implementation to implementation. Therefore, you cannot have a simple or a single file system and have various operating systems. Got it? Now every file system is supposed to have at least one file called as the directory. Now this directory is also a special type of file which will contain information about the files. You can think of it as the metadata. The data about the data is metadata, isn't it? Now the files are present here, all the files are present here. The information about these files is present in the directory, in simple words, isn't it? Now these directories are going to contain the entries, right? And each entry is going to say what is the file name and then what is its location. Let us say it is located in some block, let us say block number 100. I hope you know about the blocks. In case if you don't know, later we shall see what about the blocks. And then what is the size of it. Let us say the size of it is 1024 something. All the when is it created, who created it, what are the access rights, everything will be present here. Got it? So directory is in simple sense a file which will contain information about all the files, and every file system is supposed to have at least one directory, otherwise it will be very difficult for us to access the files. Now what are the operations that a directory should support? So what do you want to do on this directory is simple. First thing is you might want to search whether a file is present or not, and the second thing is you might want to create a file, or third thing is you might want to delete a file. Fourth thing is you might want to see what are all the files that are present in this directory, or in case if there is only one directory in the file system, you can say that what are all the files that are present in this file system. You might want to look at it. In that case you might want to write something called as list all the files that are present in this directory. And what is the other thing that you might have to do? Let us say you want to traverse. So traversing is something which will be required when you have more than one level of directory, right? So these are the basic operations you might want to. Okay, one more operation is also there, something called as renaming the file, right? So there are various operations you might want to do on the directory. These are all the operations. And now the directory itself can sometimes become too big. In case if you have millions of files or billions of files in a file system, then it might be very difficult for you to save all the names of the files and information about them in one single file, right? In that case the best thing is to go for levels. If you have only one directory and all the other files, it is called as single level directory, right? Single level directory. If you have various levels, then it is called as multi-level directory. In simplest form, you can have a two-level directory or a tree type directory. So I'll tell you about all these things in detail. I'm just telling you what are the various types of directory structures that exist. One is you can have a single level directory, and the other one is you can have multi-levels. Multi-levels means there will be the root directory, and then there will be many directories, subdirectories in it, and finally there will be files, or even there can be many directories, right? If you have only two levels of directories, then it is called as two level directory. If you have multi levels of directories, it is called as tree level directory. And sometimes in a tree you try to avoid the cycles, and you might have to sometimes create a graph without a cycle. That is called as acyclic graph. Acyclic graph directories. I'm just listing down the names, and exact details about all these directories we shall see about it. And other one is graph. Now let's see these first two types of implementations of directories. One is single level and the other one is two level. So single level directory and the other one is two level directory. So what is single level directory is entire file system will contain only one directory, and this particular directory is supposed to mention all the files which are present in the file system. Now what is the advantage of this and what is the disadvantage of this? See, this is nothing but the directory, and these are all the files, right? Now the directory is containing one entry for each file in the directory, right? So each entry is representing one file 1, file 2, like this. Now the problem with this method is the number of files themselves might be very large that they might not fit in, or even if you try to fit in one directory, this searching may be difficult. But the advantage is, okay, let's talk about the advantages first. What is the advantage of this organization? Implementation is very simple, isn't it? And also, in case if the number of files are very small, searching is very simple. Creating a file is very simple because you have only one directory, and also searching a file is very simple because there is only one place to search, and implementation is very simple. But what are the various disadvantages is, now when you have to put all the files in the same directory, then naming of the files might be difficult. Sometimes you might have to, or you might accidentally or intentionally want to name two files with the same name, right? So most often you might see the names like test.c. if you are writing a test program, you just write test.c, right? And now with this kind of, and you might want that name to be there for two files. Now if you have the same name for these two files, it will be very difficult to distinguish these two files, right? And this is one scenario. And the other scenario is, assume a setting where in your laboratory, in your lab, you have many people using the same system. Then many users will be using the same system, and all of them are supposed to use the same directory in this setting. You don't have different directory for different users, right? Now when you have those many people using the same directory, the problem will arise at various levels. One problem is, as I told you, the naming problem, and the other problem is, it is not just about the names. Other problem is accessing. You might want to, a user who has created this file might want it to be at a different security level. He doesn't want anyone else to access it, and since all the files are in the same directory, some other user, when he logs in, since there is no way we can distinguish him, he might try to use that or access that file. Therefore, having one directory, even though it is a one level directory, single level directory, even though it is easy to implement, it has got various disadvantages associated with it. So one disadvantage is we cannot separate the users, and the other disadvantage is naming is also an issue. And moreover, the earlier operating systems like MS-DOS, it allowed only 11 characters, and using only 11 characters, it will be very difficult for you to come up with unique names as the number of files increases, right? Therefore, and Unix has increased it. Unix, in Unix it is 255 characters. So Unix has somehow solved the problem, but still having multiple users use the same system under this condition is really not advisable, right? And the next solution is the two-level directory. In two-level directory, what happens is, you will have something called as master directory or master file directory, and this master file directory will contain information about all the users who will be using this system. Now let us say there are 4 people using this system: user 1, user 2, user 3, user 4. Now for each user there will be a different directory, that is in the second level, and the first level directory, the main file directory or the master file directory, will contain information about who that user is. For example, if you try to log in onto the system, now you will have a separate credentials like username and password. Now once you give your username and password and you log in onto the system, system will recognize you that you are some certain user type. Let us say the system has recognized that you are user number 1. Then system will automatically access or let you access only the directory which is dedicated for you, and it will be in the second level, right? And now this directory which is dedicated to user 1 will contain all the files which are created by user number 1, and so he can access all those files without using any special permissions like this. Are you getting this? Now user 1, so these are all the files created by user 1, and this is the directory which belongs to user 1. And now similarly there will be one more directory for user 2 like this, and there will be files which are created by user 2. They are all the files which are created by user 2. And now once any user logs in as user 1, then the operating system will remember that he is the user 1 by using some variable. In some of the operating systems, or I'm just taking it as an example, see, we are not going into the case studies like whether it is Unix or Linux or Windows, we are not going into that, but all the operating systems, they generally remember or have a variable in which it will store the username. For example, it will use something called as present working directory, that is the variable, and the this variable will contain what is the directory that this particular user can access, right? For example, if the user logs in as user1, then the present working directory might contain the directory name of user1. And now as long as this particular user is using the system, whenever he specifies any file, then that file will be searched from this particular directory and not from the other directory. This is how we can distinguish the users on the same system. Now what is the advantage of this? The advantage is simple. Now you can have different directories contain the same file name. In sense, here there can be a file which is called as test.c. At the same time, the other user can also have the file test.c without any confusion, because when this particular user logs in user1, then when he tries to use the name test.c, operating system will start searching from his present working directory, which is nothing but this one, which starts at this point, and later in some other multi-level directories you can change the present working directory, right? So let's not use this present working directory, this might create some problem. There will be some variable using which our operating system will remember which directory you are legally allowed to access. Okay, now that is how you can have the same file name for different files, and also you can separate the files which are created by different users, and so even by accidentally also a user will not be able to access the files which are created by the other user. For example, this user will not be allowed to use the files created by this user. Is it an advantage or a disadvantage? In most of the cases it is an advantage, as long as the projects on which the users are working are different. But in some cases it might be a disadvantage in case if if two users wants to share a file, right? And how to share the file, this concept we shall see later. Okay, sometimes we might want to share the files, but the main problem here arises with the system files. There will be something called as system files, which are nothing but the executable files. For example, if you want to create a file, then you are supposed to run a file which will contain the code to create the file, isn't it? Or remove a file or something like that. These are called as system files. For example, compiler is a system file. So when these system files have to be accessed, there will be a problem. The problem is that the system files will not be present in all the user directories. Therefore, when you try to run a system file, when operating system will search in your directory, and if it doesn't find it in your directory, then it will say that you can't run that file. To solve this problem, there are two solutions. One solution is copy all the system files in all the user directories or in all the users space. But the problem with that is, if you go on copying the same system files in all the directories, it is going to take a lot of space, isn't it? It is just a waste of space. That is why some operating systems have used a different method. The different method is, there will be one more special directory, user level directory created, which will contain only the system files. This is a special directory which does not belong to any user, but all the users can use it, and it is called as system. It contains all the system level files or system files. Now all the system files will be present here. Whenever a user tries to give a command which requires that a system file, then initially his own directory, let us say user1 is trying to give a command, then his own directory will be searched to find the find the file. If the file with that name is not present in his directory, then the operating system will go to this particular directory which contains all the system files and then search it. Right? Using that, we can solve the problem of sharing the system level files. But then sharing the user level files, it requires some more detail. We shall see that later. So anyway, the main difference between single level directory and two level directory is, in single level directory we cannot have multiple users, but here we can have multiple users. Here it is simple to implement, but here it is somewhat difficult to implement. right? And most of the systems, they are using multi-level directories. We shall see about it. Now we have seen that files are the most important parts in the operating system, right, or in a computer, because everything in a computer is generally considered as a file. Even if you look at IO device, it is considered as a file, or if you look at any piece of code, that is also stored as a file. Therefore, managing all these files is the most crucial thing, and the file system is the part of the operating system, which is the code which will be responsible for managing the files, right? So files is a separate entity, and file system is the software which is going to manage all these files. And since files is going to form the major part of the computers, file system has to form the major part of the operating system, right? So let's see what exactly the file system deals with. Okay, first thing is, file system provides a mechanism for online storage and access to file contents, including data and programs. So either it is a data or programs, or some operating systems even consider IO devices also as files, right? Therefore everything is a file, and file system is the only means by which you can access a file. Now file system deals with the following issues. The first one is file structure. So we have seen what a file structure is. So there are various data structures associated with managing the file. So everything will be taken care by the file system, right? Everything will be managed, created, deleted, everything will be done by the file system. And the next one is to allocate disk space. Now the main thing while creating a file is where you are going to store it. Generally you are going to store it in the disk. Now if you are going to store it in the disk, the problem is how are you going to store it and how are you going to retrieve it. So you have to manage everything, especially the disk space. So allocating disk space will also be done by the file system. Whenever you create a file, disk space has to be allocated. That will be done by file system. And the next one is recovering the freed space. So if this is the disk, now some file will be allocated now, and later it will be deleted, right? And again some file will be allocated. Let's say many files are allocated and they are given some space. Whenever you delete a file, that space is going to be freely available for the next allocation. Therefore you are supposed to manage this free space. That is nothing but recovering the freed space. You have to recover it and use it later. And the next one is to track the locations of data. Sometimes what happens is the disk will be divided into blocks, and a file need not be stored in one block. You might store the file in many blocks, and all these blocks need not be contiguous. In that case, a file may be present in many blocks which are not contiguous, and you need to track what is the, where did you store that file on the disk. So you have to maintain a record of that. That is also done by the file system. And the next one is interface other parts of the operating system to the secondary storage. So whenever you want to access the secondary storage, even though secondary storage is an IO device, it is completely controlled by file system, because everything that you store on the secondary storage will be in the form of files, and all the files are being managed by the file system. Therefore if you want to access the secondary storage, you have to go through the file system. So file system is going to form a kind of interface between the operating system and the hard disk or the secondary storage in general. Okay, so these are all the issues which have to be dealt by our file systems. Let's see how file system deals with all of these one by one. Okay, fine. And generally while designing any big software, we use layering approach, which means we are going to divide all the tasks into various groups, and some group of tasks will be assigned for some layer to implement, right? So why do we use this is we want to have some kind of abstraction. Whenever you have many layers of software, later when you try to modify one layer, you need not modify the code in the other layer, right? So changing the functionality later will be easy. So most of the operating systems, they follow this layering approach, coming to all the parts including file system. So in file system we are going to have various layers. Now every layer is responsible for some activity. I'll show you with example how or what will happen exactly when a user asks for a file, okay, or any operation on the file, whether to create a new file or read from it or append to it. I'll tell you what happens exactly. Okay, so let's see this. So file systems provide efficient and convenient access to the disk by allowing data to be stored, located and retrieved easily. So its main purpose is to store the data and then locate the data and then retrieve the data. So when you try to create a file, we should be able to store it on the disk, and later we should be able to locate where it has been stored, and later we should be able to retrieve it. This is the main thing. Now how it is being done, we shall see it. Okay, now let us say this is the flow which we are going to follow, right? So our file system is going to be classified into various layers, and each layer is also named, and each layer has specific responsibilities. First thing is, when an application program asks for a file, whether to create a file or to delete a file or to append to it or read from it, whatever the operation, it is going to ask, and the first request will be directed to the logical file system. Now the logical file system is going to have the metadata. Metadata means data about the data. Already file contains the data, and if you maintain the data about the file, that is called the metadata, like who is the owner, when it is created, and what are the permissions on the file. Let us say some user is trying to execute a file, and if he is not having the execute permission on that file, then at this level only we are going to give an error saying that you don't have the permission to retrieve the file or execute the file. Got it? And directory structure also is going to be managed by the logical file system. So what is the directory structure? You know this, it is a kind of tree, right? So you are going to have various directories listed, and finally every directory is going to have even more directories, and finally somewhere you are going to have files, right? So this is the kind of directory structure we are talking about. Now whenever you have a directory structure, right, whenever you ask for a file, you should be able to locate which file you are actually requesting, right? Sometimes you may not actually specify the absolute name. Absolute name means absolute path. You need not say the entire path where the file is. You may sometimes use a shorthand notation, right, like symbolic names, or you might use the current directory, and from the current directory you might try to access a file. Therefore, whatever name you specify, finally you have to identify which file you are going to ask in the directory structure, and this entire directory structure is being maintained by the logical file system. So it will try to find out which file you are actually asking for in the directory, and once you specify the file, next thing is, a file is actually divided into blocks, and each block is numbered. Let us say this is file 1 you are talking about, and this is block 0, block 1, block 2, block 3, right? Even though the blocks are numbered like 0, 1, 2, 3, these are all the logical numbers. Physically, when you store a file, it will be stored on a disk, right? And a disk will have many tracks, isn't it? And a track, and then many sectors, and each logical block may be actually located onto some physical block, right? So there has to be some mapping. Even though you are asking for file number 1 is a collection of blocks, and all these blocks are present on the hard disk, and you have to map them. So what does it mean by block number 0 of F1? It might mean that we are actually asking for maybe block number 10 of the hard disk, and sometimes there will even be something called as cylinders, right? So you might have a cylinder, and within a cylinder you might have tracks, and again within a surface. So there are many things going to be there. So you have to map the logical block into physical block. So that is being done by the file organization module. Now this is going to have logical block to physical block mapping, right? And let us say you want to create a new file. In that case, you have to find out what are all the free blocks available on the disk, and let us say there is a free block, right? Then you are supposed to get it, and into that you are supposed to write some data. Now even that free space management is also being done by file organization module. Got it? Okay. Now once you have decided about what are all the the memory blocks that you need, or the hard disk physical blocks that you need, you pass this information to the basic file structure. Now the basic file system, it is going to issue the commands to the IO control in order to fetch those blocks. Getting this? Now let us say this is the block you want from the hard disk. Now you are supposed to fetch this block from the hard disk. Now when you fetch this block, you are supposed to save it in the memory, main memory, for the CPU to access, right? So that you can open it, you can read it or write it, whatever you want to do. So for that reason you need to have some buffers in the main memory, right? So that is called as buffer. Buffer means some temporary storage or temporary space into which you have to store this, right? The temporary space is also being managed by the basic file system. Now basic file system will issue the commands to the IO control. Now IO control will contain the code using which it can access the hard disk, right? They are called as device drivers. So device drivers will be helpful in accessing the secondary disk, this one. So from this, in order to get it, you are supposed to issue the commands. Those commands will be given by the basic file system. Using those commands, the device drivers are going to get the data, and then after getting the data you are supposed to put it in some buffers, and that is being done by this one only, basic file system. Got it? And then you have to even manage the interrupts, and the interrupts are being managed by the interrupt handlers. So why do we need interrupts? About this we have discussed about this in CO. So what is an interrupt? The speed of hard disk is going to be very less compared to the speed of the CPU. So while the data is being fetched, you need not look at the data, or you can do some other work. So once the data is completely available, then only you are going to look at the hard disk, right? So for that reason we are going to use something called as interrupts. So interrupts are a way by which the CPU will get disturbed once the work is done by the secondary hard disk, which is slow, right? About this we had spoken about this in CO. We discussed about this in detail there. Okay. And finally IO control is going to access the device. Got it? So the data whatever is present here in the devices will be first buffered by this, and from this you are going to get it. Got it? So this is how the entire file system is layered. So this layered organization is going to help us in further modifications. For example, if you want to change some, let us say some module in this, right, it will not affect either the code present here or the code present here. That is why we go for the layered organization. Okay, fine. Now the data structures which are used by a file system will vary from file system to file system. For example, if you take the file system which is used by Unix UFS, it is going to use a different structure, and the file system used by, let's say, Windows, right, NTFS or FAT or EXT. So all these depending on the type of file system, each file system is going to use different data structures. And an operating system, if it is implementing that particular file system, then that operating system is going to implement the file system structures which are used by that file system, right? Therefore we are not going to get into exact details about which file system is using what data types. Instead of that, we shall discuss about the general principles which will help you in implementing any file system. So whatever we are going to discuss here is the generic topic, and we are not going to get into any case study, like we will not be discussing in particular about Unix or in particular about Windows. So we just say a generic what is the generic way in which file system is going to be implemented. Okay, so in the previous video I told you that there is a master boot record which is going to have the partition table, which means the entire hard disk can be divided into various partitions, and in each partition we can have a separate operating system and a separate file system corresponding to that operating system, right? Now let's see within each partition what could be there. Okay, and again when I am saying about this within each partition, I am not talking about any particular operating system, it could be any generic operating system. Okay, now let's see this. Several in-memory and on-disk structures are used to implement, so this word is implement, are used to implement a file system. So which means while implementing a file system we are going to use various data structures. Some data structures are going to be in the memory, and some data structures are going to be in the hard disk, right? So whatever it is, they are going to be used. Okay, these structures vary depending on the operating system and the file system, right? But the general principles apply. So what I mean to say by this is, for example, Windows may use either FAT or NTFS or EXT. Now depending on what is the file system operating system is implementing, these structures are also going to change. But then we are not exactly talking about a particular operating system, and so we talk about only general concepts here. Okay, now the first one is block control, boot control block. So in the earlier video I have shown you that there is something called as boot control block. So in every partition or a volume we are going to have one operating system, and whenever you start your computer, your BIOS is going to go to the MBR, that master boot record, and it is going to execute the code, and then out of this MBR is going to provide you about the partition table. From the partition table you are going to get into a partition, and now you are supposed to load the operating system code which is present in that partition. So in order to find out where that operating system code is, this block is going to be helpful. In every partition, the first block is going to contain boot control block. Now it will give you information about where the operating system code is present and how to load it, and what is the most important code you have to load into the memory in order to start with your operating system, right? Now see this, it contains information needed by the system to boot an operating system from that volume. So volume is also a partition. So every partition or volume is going to contain, you can assume that it is going to contain a separate operating system. It is not the case always, but if you can take, if you assume that every partition is going to contain a operating system, then the first block is called as boot control block. Now it will give you the information to load that particular operating system from the volume. Now this particular block is called with different names in different operating systems and file systems. In Unix file system it is called as boot block. That boot control block is a generic name, and the specific name coming to the Unix is boot block. And in NTFS means new technology file system, it is called the partition boot sector. Got it? So the names are changing but the concept is same. Anyway, all the operating systems are going to have, any operating system is going to have the first block dedicated, which is going to say where to load the operating system from, right? Otherwise, if an operating system is not going to have this block, it is supposed to leave out some space for further implementation. Every operating system is supposed to have this. And the next one is volume control block. See, main purpose of any file system is to keep track of which file is mapped to which blocks in the hard disk, right? And what are the free blocks. So all these information have to be stored by the file system. That is the main purpose of the file system. Therefore this volume control block will know exactly about how many blocks are available in this partition to be allocated for the files, right? Now see this, it contains the volume details such as the number of blocks in the partition, size of each block. So this information will be maintained by the volume control block. So following this boot control block, the next block will be volume control block. In this volume control block you will find out exactly how many blocks are there in the partition, right, and what is the size of each block. Depending on that, whenever you get a request for a file allocation, you will choose how many blocks to allocate and how many blocks are required. Okay. And in the UFS, which means Unix file system, this one is called as the super block. So again, that is the generic name, volume control block, and the specific name coming to UFS is super block. And in NTFS, which means Windows file system, this information stored in master file table. The same information will be stored in something called as master file table, right? So after knowing about how to load the operating system and where the operating system is, and after finding out how many blocks are there, you need to keep track of how many blocks are empty, isn't it? So that you can know where to allocate which file. So let's see the next one. Now the next one is directory structure per file system. It is used to organize the files. So this is the block which is going to give you about everything about the files, how the files are organized. So what are the directories you have and under what directory you are going to have a file. The entire directory structure is going to be stored in this block. And the next one is called as file control block. It is going to give you all the details regarding a file. So for every file you are going to have something called as file control block, and in the file control block you are going to have all these details present, right? So what are all the details? See this, for every file you are going to maintain this. Now what are the file permissions? File permissions means who can read, who can write, who can execute, all those things. And when is it created, when is it accessed, when is it written, all the details, that is file dates. And file owner, so what is the owner group and who are all the owners of the file, everything will be here. And the file size, the size of the file in terms of the bytes. And file data blocks or pointers to the file data blocks. So it means that whenever you are going to have a file, that file will be containing many blocks, and all these logical blocks have to be mapped onto the physical blocks, right? Now let us say a file is containing block number 0, block number 1, block number 2, block number 3 and 4. Now this block may be mapped to block number 500 in this volume or the partition, right? Similarly, this may be mapped to 502, 505, something like this, right? Then entire mapping has to be present in this structure, right? See this, file data blocks or pointers to file data blocks, right? Now a typical file control block. So this is how a typical file control block will look like. Now let's see how the disk is actually partitioned. So sometimes what happens is, in a single computer you might want to run more than one file system or more than one operating system. In that case, we take the entire hard disk and we divide into something called as partitions or volumes. Okay, so let us assume that these are the various partitions we have divided the entire a hard disk into. Now after finding out all these, after doing all these partitions, in every partition we might load one operating system. For example, here I might load Windows and here I might load Linux, something like this. Then now the main challenge is, how will we know where the code related to Windows is in the hard disk and where is the code related to Linux is, and which one to use. So for that reason we are going to have BIOS, basic input output system. So this is a small piece of code which will be present on the ROM. See, whenever you turn on your computer for the first time, you are not going to have anything in the main memory because it is volatile, and unless you have anything in the main memory, your CPU cannot execute any instructions. For that reason, in order to break this loop, we are going to have some piece of code which is going to be present on the ROM, and this piece of code is called as BIOS, right? Now this BIOS is going to fetch the first block, which is nothing but the 0th block from the hard disk. Always it is going to get the 0th block, the first block in the hard disk, right? Now generally the first block in the hard disk is MBR, master boot record, right? There are various names given to this, but the most generic name is master boot record. Now this BIOS is going to load the 0th block from the hard disk into the main memory. Now from that main memory, wherever it is loaded, our CPU will start executing from the first instruction of MBR, right? Now it will check whether this MBR is valid or not. So generally MBR always starts with a standard number, some magic number, using which you will know whether it is a right MBR or not, which means whether the disk is formatted or not. Okay, now once you are sure that this is right, then the MBR will tell you, or whenever you are booting up the system, you will sometimes get the message like this: which operating system you want to load, Windows or Linux or whatever. Now all those messages, the related code will be present in the MBR. Now MBR will also contain something called as the partition table, right? Now in this particular block we are going to have something called as partition table. Now partition table is going to tell you where each partition is going to begin, whether this one and then the second one is going to begin from here, like that. So every entry in the partition table is going to tell you where each partition is going to begin, and also it contains information about how many partitions are there. Now in case if you represent one of the partition as the active partition, then always it will directly go to that particular partition and start executing. For example, if you say that this is the active partition that you always use, then the operating system, your computer will load the first block of this one, and the first block of every partition is going to be boot block. Now this boot block will know where the operating system code is present and how to load that code. So all these entries we shall see later. So in this diagram, what I want you to understand in this video is that BIOS is going to load MBR, and MBR is going to contain all the information about how many partitions there are and what is the starting address of each partition, right? And also it can show you a menu about which partition you want to choose and work, which means either you want to load Windows or Linux or whatever operating system you have. And then it will also give you where it is going to start and how many partitions are there. That's it. And then coming to the each partition or the volume, the structure of it depends on the type of file system you are going to use. Depending on the type of file system, all these blocks will be defined. Now till now we have seen what happens with the data structures, or what are the data structures required on the hard disk, right? So what are the blocks required and what are they containing. Now we shall see, in order to implement the file system, what are the data structures that are required in memory. Now why do you want to maintain some data structures in the memory as well? Because if you store some information in the main memory, it will be faster to access instead of always going into the hard disk and getting the information. If you can buffer it in the main memory, it will be faster sometimes to get the information, right? It will improve the performance. Now let's see what are all the in-memory data structures we are going to use in file system implementation. Now the in-memory data structure is used for both the file system management and the performance improvement via caching. So we are going to maintain some data which will be helpful in managing the file system, and also it is going to give us performance improvement. So how is performance going to be improved? If we have something in the main memory, it will always be easy for us to get it compared to the information which is present in the hard disk. This data loaded at mount time. This data is loaded at the mount time and discarded at the dismount. So whatever data I am telling you, it is going to be loaded at whenever you are going to mount the file system, and whenever you unmount it or dismount it, you are going to delete the data. So what is mounting and dismounting is whenever you connect a new hard disk or let's say a new partition or a new volume to just even a pen drive. If you connect it to the computer, it is called as mounting. And whenever you mount anything like that, you have to get all the information which is present in that particular device into the main memory. So what is information that you need, like what are the files present in that, what is the directory structure, all such information, right? Now let's see what we get here. Now inside the memory we are going to have something called as in-memory mount table. So this table is going to tell us about what are all the hard disks or the partitions or the devices, memory devices which are connected to the computer, right? Now it contains the information about each mounted volume. So either it is a pen drive or a hard disk or a DVD, whatever it is, whenever you connect it, we are going to see that in the table, right? That is called as in-memory mount table. And the next one is in-memory directory structure cache. It holds the directory information of the recently accessed directory. So whatever directory you have recently accessed, that information will be present in this one. So why should it be present? Because if you have recently accessed a directory, it means that you might have got that directory structure block from the hard disk or that particular volume into the main memory. If you have used it now, there are chances that you might again use it, so you can save it for some more time. That is why it is going to save it for some more time. That is why it is called as cache. Cache means it is going to save it temporarily for some more time. And the next one is system wide open file table. Now in the entire system you might have opened some files from various devices, right? Now what are all the open files? That list will be maintained in this, right? System wide open file table. This is going to contain the information about all the files which are being opened by the operating system currently. It contains the FCB of each open file, right? What is FCB? File control block. It gives the information about the entire file. If a file is already open, you should know about it and you should know the status of it, because if you want to access it again by some other process, you have to look at it, okay? And the next one is per process open file table. So I told you that every process is going to maintain something called as open file table. So every process is going to open some files, and entire information about the files that particular process has opened is going to be present in this one. So for every process there is going to be one open file table. Now if you observe this, already we have system wise open file table. It is going to contain all the files which are open, and this one is going to give us which process have opened those files. Therefore the information is same, but just the organization is different. Here all the files will be listed out, and here only the files which are opened by a process will be listed out in each file. So that is why what we can do is we can maintain some pointers. I'll show you what. It contains the pointer to the appropriate entry in the system wide open file table. So what it means is, let us assume that the system wise open file table is going to say that file number 1 is open, file number 10 is open, file number 21 is open, file number 30 is open, file number 31 is open, and file number 41 is open. Right? Now these are nothing but the file control blocks of these particular files. Now if there is a process P1, and if the process P1 has opened the files, let's say F1 and F10, now it need not contain again the file control block, isn't it? If a process P1 has opened F1 and F10, it need not again replicate that file control block of F1 and F10 again. Since it is already present in this table, it can just have a pointer to this. That is what the meaning of it. Right? Now this is the system wide open files. This is per process open files. Anyway, when a process has opened a file, that information is going to be present here. Therefore, instead of replicating it again here, we can directly point to this. Now let's see the implementation of the directory. Directory can be implemented in two ways. Now either you can maintain it as every directory as if it is a list of files, and that list could be a simple linked list, or you can maintain a hash table. So I'll tell you what is the advantage and disadvantage. Anyway, the main thing that you should be considering while choosing a data structure is what is the performance and what is its reliability. Right? So let's see this. The selection of the directory allocation and directory management algorithms significantly affects the performance and the reliability of the file system. So what type of algorithm you are going to use, that depends on what type of data structure you are going to use. Depending on the data structure, your algorithm is going to give you performance. Right? Now one simple way of implementing the directories is you can maintain all the files in a directory as a list. If you are going to maintain all the files as a list, a simple implementation is shown here. Right? Let us say we are maintaining all the files in a linked list, single linked list. Now in this case we are going to have a file name, and what are all the data blocks which are assigned to it. As I told you, every file is going to be allocated some data blocks, isn't it, within the volume. Now if it is having, let's say, 4 blocks, this file is having 4 blocks. Now all those 4 logical blocks have to be assigned 4 physical blocks, and the information about the 4 physical blocks is present here, and this is the pointer to the next file. Now like this, if you maintain all the files within a directory as a list, then what is the problem with this one is, if you have to create a new file, you might have to search the entire list to know whether the current the new file name already exists or not. In case if it doesn't exist, we can create it at the end or at the beginning. That's not an issue, but anyway you have to search it. Now second thing is, if you have to open a file, then again you might have to search the entire list, right? Or if you have to delete a file, then again you might have to do a search. The search operation is going to take a lot of time if you are going to implement it in purely as a linked list, right? So what is the other alternative is, have this linked list, along with that you can have a hash table. Right? Now by maintaining the hash table, let us say you are maintaining a hash table like this. Now it can have key and value pairs. Key and value. Now based on the file name you can form the key, right? So based on the file name, if you apply hash function on the file name, then you are going to get the key, and you are going to save the key there, and the value for that may be the file to which you have a node there in the linked list. Got it? Now by using this hash table, the advantage is search will be faster. If you are trying to create a file, then you can directly search in the hash table in order of one time whether that file is existing or not. If you want to open a file, you can directly go and open it. If you want to delete a file, you can delete it, right? So that is how hashing will be better compared to this, but still hashing is going to have some disadvantages, like it is going to be in fixed size. So every time you have to increase the size, the number of files are going to be increased. And also the other problem is there might be some collisions. So whenever you have to have collisions, then you might have to use open hashing or chaining or whatever techniques we have discussed in algorithms. Therefore both of them are having advantages and disadvantages, and whatever you want to use, that is up to you, up to the implementers, right? And even the directories are also implemented in the form of lists only, right? And sometimes you can even use B trees and B plus trees. If your number of files and directories are very large, then you can go with B trees and B plus trees, which we have discussed in DBMS. Okay, so anyway, these are the two popular methods which are currently under use. Okay, now let's see the implementation of the directory. Directory can be implemented in two ways. Now either you can maintain it as every directory as if it is a list of files, and that list could be a simple linked list, or you can maintain a hash table. So I'll tell you what is the advantage and disadvantage. Anyway, the main thing that you should be considering while choosing a data structure is what is the performance and what is its reliability, right? So let's see this. The selection of the directory allocation and directory management algorithms significantly affects the performance and the reliability of the file system. So what type of algorithm you are going to use, that depends on what type of data structure you are going to use. Depending on the data structure, your algorithm is going to give you performance, right? Now one simple way of implementing the directories is you can maintain all the files in a directory as a list. If you are going to maintain all the files as a list, a simple implementation is shown here, right? Let us say we are maintaining all the files in a linked list, single linked list. Now in this case, we are going to have a file name and what are all the data blocks which are assigned to it. As I told you, every file is going to be allocated some data blocks, isn't it, within the volume. Now if it is having, let's say, 4 blocks, this file is having 4 blocks. Now all those 4 logical blocks have to be assigned 4 physical blocks, and the information about the 4 physical blocks is present here, and this is the pointer to the next file. Now like this, if you maintain all the files within a directory as a list, then what is the problem with this one is, if you have to create a new file, you might have to search the entire list to know whether the current the new file name already exists or not. In case if it doesn't exist, we can create it at the end or at the beginning. That's not an issue, but anyway you have to search it. Now second thing is, if you have to open a file, then again you might have to search the entire list, right? Or if you have to delete a file, then again you might have to do a search. The search operation is going to take a lot of time if you are going to implement it in purely as a linked list, right? So what is the other alternative is, have this linked list, along with that you can have a hash table, right? Now by maintaining the hash table, let us say you are maintaining a hash table like this. Now it can have key and value pairs, key and value. Now based on the file name, you can form the key, right? So based on the file name, if you apply hash function on the file name, then you are going to get the key and you are going to save the key there, and the value for that may be the file to which you have a node there in the linked list. Got it? Now by using this hash table, the advantage is search will be faster. If you are trying to create a file, then you can directly search in the hash table in order of one time whether that file is existing or not. If you want to open a file, you can directly go and open it. If you want to delete a file, you can delete it, right? So that is how hashing will be better compared to this, but still hashing is going to have some disadvantages, like it is going to be in fixed size. So every time you have to increase the size, the number of files are going to be increased. And also the other problem is there might be some collisions. So whenever you have to have collisions, then you might have to use open hashing or chaining or whatever techniques we have discussed in algorithms. Therefore both of them are having advantages and disadvantages, and whatever you want to use, that is up to you, up to the implementers, right? And even the directories are also implemented in the form of lists only, right? And sometimes you can even use B trees and B plus trees. If your number of files and directories are very large, then you can go with B trees and B plus trees, which we have discussed in DBMS. Okay, so anyway, these are the two popular methods which are currently under use. Okay, now as I told you, the main responsibility of the file system is to allocate the blocks to the file blocks. If a file has let's say data which can be kept in 4 blocks, then what are the physical blocks in the hard disk that you are going to put these file blocks in, and how do you put it and how do you retrieve it whenever it is required, right? That is the main thing, and that is called as allocation. So we have various allocation methods. Now depending on what type of allocation you are going to use, the performance is going to vary, right? Now let's see this, how to allocate this space to the files so that this space is utilized efficiently and the files can be accessed quickly. So this is what is we are going to discuss. Now the first method is contiguous allocation. So contiguous allocation means, let us say this is the hard disk you have, and you have all the blocks 0, 1 to 11. 0 to 11 blocks are there. Now if you are going to allocate the blocks in such a way that a file is going to get contiguous blocks, then that is called as contiguous allocation, right? So for example, I'll just take some example and show you. Let us assume that this is the directory which is containing 3 files. One is temp, other is tr, and other is list. Now the temp is the name of the file and the starting block of the file is 0. It means that we are going to start here. We are going to start in the 0 block. So temp is the name of the file which is going to start in 0, and the size is, or length is 2. Length is 2 means it is going to occupy 2 blocks, which means 0 and 1 are the blocks in which the file temp is going to be mapped to. Got it? So if you want to see, what I mean to say is, if the temp is having the data which is sufficient to fill at least 2 blocks, right, like this. Let us say this is block 0 and block 1. Now the first block is going to be placed in the 0 block of the hard disk, and the second block of the file is going to be placed on the 1th block in the hard disk. Now if you look at this one, the next one is file tr. It is having the starting block as 5 and the length as 4. So what it means is, I am going to start at 5 and I am going to go for 4 blocks, right? So 5, 6, 7, 8. And if you look at list, it is going to start at 10 and the length is 2. So list is going to start at 10 and the length is 2, right? Which means these two are going to be given to that particular file, right? So but if you look at it, anywhere we are always using the contiguous, right? Contiguous allocation, isn't it? Contiguous. Now what is the problem with that? So advantage is, it is very simple and the read performance is excellent. So why is read performance excellent is, since the blocks are not randomly distributed, all the blocks are having a sequential order. So what I mean to say is, in the hard disk if you see it, let us say they are all the blocks, right? Block number 0 is here, block number 2, block number 3, so on like this. Now if I have to read the entire file, I just have to go to one particular block, and once I reach that particular block, I just have to rotate the disk so that the entire file can be read in that entire sequence, right? Therefore I need not move the read write head to the other track. So once I go to the track spending one seek time, that is enough. I need not go to the other track at all. I can just stand there and let the disk rotate in order to get the entire file. And in most of the cases, we are going to read the file from starting to the ending. Therefore, by putting them in contiguous blocks, it will be beneficial for us if we are going to read the complete file. And it is going to take less time in case of contiguous allocation. Got it? And coming to the disadvantages, the disadvantage is the disk becomes fragmented. So if you remember, while talking about the memory management, we have talked about the contiguous allocation of memory. In contiguous allocation of memory, there was a problem of fragmentation. So what is fragmentation is, whenever you are going to allocate the files and then pull out the files. Let us say initially you have allocated 0, 1 to some file, and let us say 2, 3, 4 is allocated to some other file, right? And later let us assume that 2, 3, 4 is emptied, which means that particular file is deleted, which means 2, 3 and 4 will now become the files, the blocks 2, 3 and 4 will now become free, right? Later if I get some other file which has to be allocated, which needs 4 blocks, right? Let us say one block is here, other block is here, other block is here, all these 3 are free, and this one is also free. So 4 free blocks are available, and a new file requires only 4 blocks, but since they are all not contiguous, I will not be able to allocate it. That problem is called as external fragmentation, right? Now what is internal fragmentation? If a file requires a space which is equivalent to 2.5 blocks, still I have to allocate it 3 blocks. Now in the last block, half of the block is being wasted. That is internal fragmentation. Got it? So both external fragmentation is possible and internal fragmentation is possible, but anyway internal fragmentation cannot be avoided by any methods, isn't it? If a file requires 2.5 blocks, whatever method you go with, always you are going to allocate 3 blocks for it, right? Therefore that cannot be avoided, but then this external fragmentation can be avoided by going for non-contiguous allocation. Are you getting this? So we got the external fragmentation problem, so which can be avoided by using the non-contiguous methods. Okay, now let's see one of the non-contiguous method, which is linked list implementation, right? Now what is linked list allocation is, you need not have the file blocks, we need not give the file blocks contiguous memory blocks or the hard disk blocks. For example, you can give, let us say there is a file A, and the 0th block of the file A is given to the physical block number 4, and first block of the file A is given to the physical block number 7, and second block is given to 12, and third block is given to 10. Now if you observe this, these are all not contiguous, isn't it? Now this non-contiguous method of allocation can be allowed or is allowed in this type of linked list implementation. Now what happens in this implementation is, every file will contain what is the starting physical block in which its first block is stored, right? Now block number 0 is stored in the physical block number 4. Now once you go to the physical block number 4, at the end or at some point, beginning or the end, it is going to tell you where is the next block, right? Best thing is to put it in the beginning, right? Why? Random access may be easy instead of going till the end and then finding it out. Okay, wherever you are supposed to maintain a small pointer which is going to give us where the next file block can be located in the hard disk. Now this is clearly showing that you need to go here, which means in this part you are going to have 7. What is the meaning of it? The second file block or the next file block is present in the physical block number 7. Got it? And here it will be 12. So what does it mean? The next file block is present in the physical block number 12, and here you are going to have 10, right? By having this kind of allocation, you need not have contiguous blocks allocated to a file. You can even go for non-contiguous allocation, right? Now what is the main advantage? External fragmentation can be avoided. So what is external fragmentation? If a file needs 4 blocks and all the 4 blocks are not available contiguously but they are randomly available, still I can allocate the files this way. Got it? So that is why this is having the advantage. Unlike contiguous allocation, every disk block can be used. So here we are not going to leave any block unused because it is present in the middle of some other blocks. Got it? No space is lost due to disk fragmentation except for internal fragmentation in the last block of each file. This one we can't do anything. If a file wants only 2.5 blocks, you have to go with 3 blocks. Either you go with the normal allocation or with the linked list allocation, right? Now what is the disadvantage is, the random access is very slow. Now if you observe this, here it is not like you can seek to one of the track and stay there, isn't it? In the earlier method, we are going to one of the track using a seek time, and once we reach that track, we are going to stay there till the end, right? Till we complete the entire file reading. But then here in this case, if you have to read a file, you have to go to the track which is containing physical block 4, and again you might have to go to other track which is containing physical block number 7 in case if 7 is not in the same track. That is why you might have to move the read write head, and so it is going to take some delay, and so it is very slow. And the next one is, pointer is going to take few bytes. So you are going to maintain pointers here unnecessarily. I mean they are necessary here, but compared to the other method, in the other method the pointers were not there, but here the pointers are there, which is a disadvantage, right? They are going to take up few bytes. Now how can we solve this one is, in the next method we shall try to eliminate these disadvantages. Got it? Okay. Now we have seen that one of the disadvantages of the linked list implementation is if you have to access randomly. So let us say I want to access block number 2 of the file. Even if I have to access the block number 2 of file A, I'll have to go and access block number 0 in order to get the pointer which is pointing to the second block, which is nothing but block number 1. And now I have to go to block number 1, and from that I can find out where the block number 2 is present in the hard disk, right? Therefore it is very difficult for me to do the random access. Even if I have to do the random access, I'll have to access all the blocks in the file, right? So that is why this is the disadvantage, right? Random access. Now just to correct it, what we could do it is, how the implementation have changed is, the solution is like this. We are going to allocate an array, we are going to create an array, and in this array, for every disk block in the hard disk, we are going to maintain one entry. For example, if you have 15 blocks, 15 physical blocks, for all the 15 physical blocks, one entry is maintained in this array, right? Now this particular array is going to show us where the next block of the file is present in, right? For example, if you see about the same file A, how it will be implemented is, file A is first is starting with 4, isn't it? File A's first physical block is at 4, right? Okay, it is pointing to 4. Now when you go to the entry 4, here you can clearly see that the second block is 7, isn't it? The second block of the file is present in the physical block number 7. That is what is given there. Now if you go to the second block, which is 7, in this array, it will give you where the third block of the file is present. It is saying that the third block of the file is present in block number 12, isn't it? The third block of the file is present in the block number 12, right? And now if you go to block number 12, it is going to show you where the fourth block of the file is present in. It is showing 10, isn't it? It is present in 10. Now if you go to the 10th block, it is showing -1. What does it mean? It means that the file has ended in the block number 10. Got it? Therefore, by using this table, we will be able to randomly access any block of the file. For example, if I have to access the third block of the file, I know that this is where the first block is, and this is where the second block is, and this is where the third block is. Therefore I can go to the block number 12 directly. Therefore random access is possible, right? I mean, compared to the earlier implementation, this implementation is better, but still it will also have some disadvantage. Okay, this table is called as file allocation table. This is the table which is file allocation table. Now the disadvantage is, see, advantage is random access is easier. Now the disadvantage of this table is the size of it may be very large, right? The size of this one might be too big, that it will consume lot of memory. For example, I'll just give you a scenario. Let us say a hard disk is having a capacity of 20 GB, right? And assume that we are going to have each block of size 1 MB, right? Or let me say 1 KB. 1 KB is the size of each block, right? Now what happens is, if this is the size of each block, then the total number of blocks which are present in this hard disk is going to be 20 million. So 20 million blocks are going to be present in the hard disk. Now if you have to maintain one entry for every block, then you will have to maintain 20 million entries, right? Now assuming that each entry is going to occupy a space of 4 bytes, right? It is going to take up a space of 20 million into 4 bytes, which is nothing but 80 MB. So 80 MB space is wasted only to maintain this, right? And as you grow the capacity of the hard disk, it is going to be even bigger, isn't it? As the number of blocks are going to be increasing, the entry size will also increase, right? Therefore it is cumulatively going to be a very big thing. Got it? So that is the disadvantage of this method. Even though random access is there, that is a disadvantage. Got it? Now the main responsibility of the file system is to allocate blocks to each file and then to keep track of it. That is one responsibility. And the second responsibility is it has to even know how many blocks are freely available for the next allocation. Let us say you have to allocate a file, and then you have to find out how many blocks are free, and from those free blocks you have to give some blocks to the file, right? So how are you going to keep track of the available free blocks? That is the main issue. So various methods are used, but here we are going to discuss the main methods which are popularly used. Okay, so one method is bit vector. So in bit vector it says that for every block we are going to maintain a bit, right? One bit only, not a byte. For every block we are going to maintain a bit, and if the bit is 1, we consider that it is free. Otherwise it is, if it is occupied or if it is taken away by some file, it is made 0, right? What I mean to say is, let us say you have 10 blocks totally. So 10 blocks is too small. Just for the sake of example I am telling you. Now 1 bit will be given to each block. Let us say block number 0, block number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we have 10 blocks, okay, 0 to 9, 0 to 10 is 11 blocks there. Okay, if we have 11 blocks, then each block will be given 1 bit. Initially all the blocks will be free, right? Now whenever you allocate any block to a file, let's say you have allocated block number 1, 3 and 4, then you are going to make them 0. So it is allocated to a file, it is allocated to a file, and it is allocated to a file, right? Now whatever is again, if you want to find out how many free blocks are there, or if you want to allocate free blocks to a new file, then you just scan through this list. It is called as bit vector. Vector means an array, bit vector means an array of bits, right? Just scan through this and you can easily find out which are the free blocks. Then you can choose some of them and allocate to the other file, right? Now in this case each block is represented by 1 bit, right? If the block is free, then it is 1, otherwise it is 0. So this is one approach, and the other approach is linked list method. So linked list method you have already seen. Now let us say this is the disk, this is the hard disk, and you are having many blocks inside it. Now what we can do is we can point from one block in the disk to the other block, other free block. Let us say this one is free and the next one is this one. Then you point from here to this one, showing that this is free and this is the next free block. And if the next free block is here, point to that. If the next free block is here, point to that, right? So like that you are going to point. So this is how you are going to implement in the linked list, right? It is also called as free list. Now see this, another approach of free space management is to link together the free disk blocks, keeping a pointer to the first free block in a special location on the disk and caching it in the memory. So in order to get all the free lists, you have to just store the first free list, right? So first free block, if you can save its location somewhere, if you can get the pointer to that, using that you can find out what are all the free blocks available. Got it? So these are the two approaches which are popularly used in free space management. Okay. Now as you know, a process generally have two types of tasks. One is the burst time, which means it uses CPU for most of the time, and then at any point in time a process will want to do IO. IO means it want to read something or it want to write something, right? And most of the times IO will be done from the hard disk. So hard disk means the secondary memory. So any process generally will have, one is a need for CPU time, and second thing is a need for IO. Now if you generally schedule a process, it will go to the CPU and start executing, and the CPU will be very fast, that it will be finishing its burst time very quickly, and as and when a process requires an IO, it is going to block it, right? Therefore your process is going to get blocked whenever it needs the IO, let's say hard disk. Now what happens is, gradually as the time goes on, many processes will need the IO, and since the hard disk is very slow, the requests will pile up at the hard disk. Now at a hard disk, the queue of waiting systems or the queue of waiting process which require to read some data from the hard disk or to write some data into the hard disk are going to pile up. Now the main issue here is how are you going to process the request. The reason why I am saying this is the order in which you process the request is important is, now depending on the way you service a request, the overall time taken by the hard disk to process all the requests is going to vary. For example, if you want to, if a process wants, let us say track number, let us say sector number 10, a process wants it. Now if you are going to provide it with sector number 10, and next if any other process wants sector number 11, if you provide the service to that particular process, you will not be wasting any time. Otherwise, let us say there is 10 in one track and 100 in other track. Now if you have to move the read write disk from the track containing 10 to track containing 100, it is going to take some time. Therefore, based on the way you service the requests, the overall time taken by the hard disk to service all the requests is going to change. Now the main purpose of the operating system here, whenever operating system comes into picture here, its main purpose here is to see that it does all these requests in an optimum way. Optimum way means reduce the time as much as possible. Now when you go to the hard disk, there are various times. We have seen it in CO also, we have seen it, that there is something called as seek time. Seek time is moving the read write head to the appropriate cylinder or the track is called as seek time, right? In case if you have many disks, then we call it as a cylinder, right? If you have only one disk, we call it as a track. Now if you have to move the read write head, there is going to be seek time involved. Now if you have to decrease the seek time, then you better process or provide service to all the process which have all these requests in a closer proximity, which means let us say one process requires some data from cylinder 1 and other process requires from cylinder 2. Better you do it one after the other. Instead of going from cylinder 1 to cylinder 100, go from 1 to 2. That is how you are going to save some time, right? So your operating system has to look into all these details. Yes, one thing is for sure, hard disks are going to be very slow. The reason is the basic bandwidth or the rate at which you can read the data from the hard disk is going to be fixed. We can't do anything about it. Only way we can save time is by reducing the seek time, right? Now how we reduce the seek time, that depends on the algorithms which operating system is going to use in order to provide the service, right? So let's see all the algorithms one by one, and we shall see with examples that once we go with some algorithm, the time taken will be something, and if you go with some other algorithm, the time taken will be some other thing, right? So let's see this part. This is called as disk scheduling. So what is disk scheduling is, if there is a hard disk and a queue of requests waiting to be served, then which request you are going to serve next, that is called as disk scheduling. Okay, now let me read it out for you, the theory. File systems must be accessed in an efficient manner, especially with hard disks, which are slowest part of the computer. So as you know, every file is going to be stored on the hard disk, and hard disk is the slowest part of the computer, and so you have to do the access in an efficient manner. As a computer deals with multiple processes over a period of time, a list of requests to access the disk build up. For efficiency purposes, all the requests from all the processes are aggregated together. So whenever all the processes are getting blocked in order to get the service from the hard disk, all of them will be in a queue, right? Now all of them have to be considered together, and you have to decide about which one you should process next, right? That is called as aggregation here, right? So all the requests are considered together, and you are going to provide the access to all of them at once, right? Now the technique that the operating system uses to determine which request to satisfy next is called as disk scheduling. So the technique is nothing but the algorithm which we are going to use. Let's now talk about system calls. Actually this is not in the syllabus, GATE syllabus, it is not mentioned, but then finishing operating systems without talking about system calls it doesn't feel good. So I'll just finish it off, and it will not take more than 2 hours or so. It is a very small topic. Even though it might not be asked in GATE, just try to watch it, it will give you some more insight into this subject, okay? So let's say this is the main memory, okay? and assume that some part of the main memory is being occupied by operating systems, and whether this contains the total operating system or it contains only part of it, that is system dependent. Some operating systems feel that only kernel should be present in the main memory, and whenever required other modules should be loaded into the main memory on demand. That is what some systems feel. But just to simplify the things and keep it easy, I want to assume that entire operating system is present in this part. Okay, and say a process is running, a program is loaded and a process is created, and a process P1 is loaded here and it is executing. Now as again, if you see this, it is also an assumption that I am using the contiguous allocation and the entire process is loaded here. So I didn't use any paging or anything. Just to keep it simple, I am using the contiguous block allocation. Okay, now in general what happens is every process will be allowed to access only certain range of memory, and it is not allowed to access other parts. So why is this so? We wanted to provide the protection. So a process running should never ever access any memory other than what is actually allocated to this. So this process should only access these memory locations. It should not access this memory location, or let's say some other process here, some other process here. It should never access that. Okay, but then if this is so, every user process will be having very limited powers, which means a user process will not be able to do much if this is the case. The reason is most of the things in the system are actually maintained by or managed by operating system. For example, if your program wants to read something from the keyboard is under the control of operating system, right? And in order to read something from the keyboard, the actual code that has to be executed will be present inside the operating system somewhere. Similarly, if you want to write something onto the monitor after processing, this process wants to write something onto the monitor. Again, the monitor will also be controlled by operating system, and so you have to invoke or execute some part of the code which is present in the operating system in order to execute that, in order to accomplish that thing. Either you want to read or write a file, right? Or you want to have a hard disk access. Everything, almost everything will be present in the operating system code itself, and you have only limited power as a user, right? So what you should be doing is, if you need anything, you are supposed to call that particular module which is present in the operating system. Now whenever you want to go into the operating system and execute that particular module which is required, we call this one as system call, raising a system call. System call is exactly same as the function call, but then in system call you will be trying to call the function which is present in the operating system. In general, a function call can be anything. Either you can call a function which is present in your computer, in your process. Let us say this is a user defined function, right? If you are trying to call this, that is also a function call. But when you are trying to call a function or a module which is present in the operating system, that is generally called as system call. Now various systems, they have different methods of implementing the system calls. Some systems have given the control directly to the program or higher level program, and you can write the instructions in the higher level program and you can directly call that particular system. For example, in Linux, if you are writing a C program, you have the function calls write, and you have the function calls read, and you have the function calls open, close, right? So all these function calls are directly implemented in the higher level language. If you include these lines in your higher level language program, you can directly call them. Similarly, some systems, they use an indirect way of calling the systems, these functions which are provided by operating systems. So what they do is, they will have a system library or the local library, and the library function call or is going to implement the system call. For example, in C programming you might have seen printf, right? So when you execute printf is a library function, right? And the code related to this printf will be loaded along with your process into your process. Therefore you are not going to write the code of the printf, it is provided as a part of the library function, and now this library function will be loaded when your process is loaded, right? And whenever you call this printf internally it will call write. Okay, so this is how a user will call a library function, and now the library function will make the system call. Got it? So there are various ways. Some people say, some systems use assembly language instructions. For example, if you try to call, let us say this is the higher level system call, when you compile it, a assembly level language code will be generated, and that code will cause the operating system to be invocated, right? And also that whatever you are running as a process, you run this in the user mode, and whenever you want to execute the code in the operating system, it will be run in the super mode, right? A super user mode. Okay, so anyway that mode changing is there, and then context switching will be made. So what are the things that you should be remembering here is, whenever a process needs something from the operating system, the only way it can get it is through system calls. And how to make the system calls? There are various methods. Sometimes again this is depending on the system implementation, therefore there is no standard way. From system to system it changes. Some systems they use assembly language instructions, therefore you are supposed to include those instructions and automatically it will be called. And some higher level languages have the facility of including the higher level language instructions, which will lead to a system call. And some higher level languages in C we can directly write and read, or you can directly call printf, right, or scanf, something like this. And some of the languages they wrap the system calls inside a library function, and so user will be calling the library function and the library function will call the system call. Got it? And anyway, just like the way a process switch is happening, just like the context switch, here also a context switch has to happen. So which means when you are trying to call a function here, your entire status, right? So the state of the process will be saved somewhere for the later restoring. So you go there, you do the complete execution, and again you come back and execute from where you left. Similarly, one more issue that has to be answered here is parameter passing. For example, if you are trying to write into some file, say you want to write into some file in Linux, in a system like Linux, everything is a file. A monitor is a file, a keyboard is a file. If you have to write something onto the monitor, you are supposed to use the system called write, and for this write you are supposed to send the parameters like what is the file you want to write and where you want to write and what is the size of the message and what is the message, like that. Some parameters have to be passed, isn't it? If you are trying to write something, some parameters have to be passed for the function, right? See, from here if you are calling write, the parameters have to be passed. And how are we going to pass the parameters? Again, it varies from system to system, and there are various ways of calling it. So one way of passing the parameters is by using registers, which means this method says that whatever parameter you want to pass from the user program to this program which is present in the operating system, you place them all the parameters in the registers, so that when this particular instruction gets executed, starts execution from here, they will automatically fetch the operands that are being passed, parameters that are being passed from the registers. But the problem with this method is, as you know, sometimes our parameters may be bigger or the number of parameters may be more compared to the number of registers available. Therefore, this is not widely popular method. This has been used initially, but later people are not using it. And the second way is you can pass the parameter by storing it in a block of memory, right? So you can use memory, which means as we have seen in maybe CO or some other places, we are going to store certain values in certain memory locations, fixed memory locations. For example, a system may say that we are going to save all the parameters that are being passed at address number 0. Right, let us say some space is allocated to this, and let us assume that this space is allocated in such a way that there will be no overflow, a kind of stack kind of implement. Let's not talk it as stack. Some memory location is some memory is fixed and allocated to that. Now when you want to pass the parameters, you store all the parameters there and say that this part is available for you to access. You just save it there, and then you call the system, right, operating system, and it will take care of it. And some other implementations say that we are going to use this stack. So stack implementation is same as how you do the function calls. So what we do is, in this stack we are going to write all the parameters in some place and then call the system, and after the operating system has used up all the parameters, it will just free up the space and get back to you. Got it? So we are going to call the operating system, and also we are going to pass the parameters. Now what will the operating system do? It will perform the act, whatever you are trying to do, it will just finish it off, and after finishing it, it will again come back. Control will be returned to the process. So anyway, there is certain overhead here. You are supposed to do context switching because you are in some user mode executing a process, and everything that is being done has to be stopped, and the entire context of the process, you know what a context is, we discussed it many times. So the context of the process has to be saved somewhere, and you have to go into the system mode, and again you have to change the mode. So from the user mode you have to change to system mode, and again after finishing it, you are again supposed to restore the context, right? So which means you have to restore the process by loading the context, all the registers and everything, program counter and all, and again you are supposed to do this. Therefore a context switching is involved, and also we are going to go from user mode to system mode. So there is of course a overhead, right? In case if this particular function is being provided as a part of the process itself, there is no need of context. That is the main difference between a system call and a normal function call. If you talk about a normal function call, your function will be present in the same address space to which your process is given permission to access. In that case, you need not switch the context. You need not go from user mode to system mode. You can simply start executing it. But here, in case if this, since it is present in the operating system, you have to perform all this. But then why this headache? Why don't you directly give every process the access to operating system, so that whenever required it will go there, execute it and come back. The problem is such a thing is, we don't want every user to access and modify the code of operating system. It will raise lot of protection issues, right? So there will be security and protection required. So that is why we want to go into this system mode and do it in a protected manner, right? And also, since this code is shared by many processes, we want to have some mutual exclusion. Even if you keep it in the read mode, we want to have some mutual exclusion, and there are various things there. Okay, so after doing a lot of experiments, they found out that this is the best way to provide the access to resources for a user process. If you want any resource, go through the system call. Okay, so before talking about the threads, if you have to understand why threads are so useful mechanism, you should actually understand why we cannot do certain things in an efficient manner without using threads. Okay, I don't want to confuse you, just try to understand this. See, I'm going to explain you threads in the next video, but if you have to understand why threads are required, you should understand what happens or what are the disadvantages if you are not going to use the threads. So for that reason, even though we don't have this particular system call in the syllabus, I want to discuss about these two system calls. Okay, so actually nothing is mentioned in the syllabus about this fork and execute system calls, but then I think once or twice I have seen some question about it. Probably Earlier maybe that was in the syllabus, but currently it is not there in the syllabus, so you need not by heart it for the exam. But if you can understand this, I can make the threads concept simple. Otherwise you will not be able to appreciate why threads are required. Okay, so let's talk about this system call. Two system calls, fork and execute. Okay, execve, these are the two system calls, and these two system calls are available in many versions of many flavors of Unix and also in Linux. And those who have already worked on Unix and Linux, it will be easy to understand, and anyway for others I'll try to explain. So the main advantage of using a fork is like this: if any program, any process, if it is executing and if it suddenly calls the fork system call, let us say this is a process, and if it suddenly calls the fork system call, suddenly it will create a new process. This will be called as a parent, the one which has executed the fork system call, and this will be called as a child process, right? Parent process and child process. Now what is the advantage of having parent process and child process? So let's say, in order to explain it clearly, okay, let's see what is happening here. Assume that this is the main memory, okay, and somewhere here there is a process P1. Let's call it as process P1. Process P1 is executing, and what will be associated with a process? Instructions will be there. Let's call this section as instructions, right? Or .exe code, which means executable code, .exe. Okay, and what will be the other parts? Static variables or global variables will be there. And what will be the remaining things? We'll have one is stack and other is heap, right? As the process is executing, it will be using many variables, and it will be executing some instruction, right? At the end, program counter will say what instruction it is executing, and this is the image of the process in the memory. And whenever it executes fork system call, let us say one of the instruction in the execution sequence is a fork system call. Whenever it calls the system call fork, then automatically we will get into the operating system function, right, which is fork, and this particular function, it will create a new process, let's call it as P2, right? And this new process is going to be a child of this one, and this entire thing will be copied here, right? So what will be copied? The entire memory image completely, whatever is in the stack, whatever is in the heap, whatever are in the static or global variables, and whatever is in the instructions, completely everything will be copied here. A Xerox copy of this will come here, right? Now why is it useful? You can think of it this way. Let us say there is a process which is a server, okay, a server, and let us say it is a web server, okay, and what is its main purpose? Whenever any client approaches this web server, it is supposed to send the web pages, okay. So if it can handle only one client, isn't it? So whenever someone approaches it, it can send the HTML, and while it is sending the HTML files, if some other client approaches it, then what should it do is it can create an image of the same thing using fork, right? And good thing about the fork is, if you are having fork written somewhere, let us say fork is written somewhere, once this instruction is executed, we are going to create two process, and both the process will execute from the next line. Now this one can handle this client, and the new client request, whichever it got, that will be redirected to this, and this one can perform the provide this service to the client. This is how you can solve the problem of handling many requests at the same time, right? But then there is a problem with this. The problem with this particular approach is simple. The problem with this particular approach, if you can see, is you have to call the operating system, and now operating system has to create you an identical copy, isn't it? And then both of them will be executing parallelly, right? So now this is a process and this is another process, and both of them can execute parallelly and provide the same service to different clients. Got it? So how can they provide same service to different clients? I'll get back to you. So how to identify which one is child and which one is the parent? I'll tell you that. But try to understand one thing. Now creating a new process using the fork system call will actually require a context switch, and you have to change from user mode to system mode, isn't it? Initially you are executing in the user mode, now you have to go to system mode and execute a different code. Then because of this context switch, there has to be a lot of instructions which have to save the context, and these instructions have to be executed, which is a overhead, isn't it? Yes, you are getting two processes, but what is the penalty you are paying? There is an overhead here, clearly, right? So that is why creating two processes to provide us some service is actually a overhead, or we have to go through some penalty. So this is why we are not going to use it. Got it? So that is why we need a mechanism called as threads. That is the reason why we need threads. Now let's come back to the fork system call again and see what are the other ways fork is being used. Now whenever you call fork, generally fork instruction will be called like this. In a program or a process, the fork system call will be called like this, something like this: int I equal to fork. Okay. Now by executing this line, fork is going to return some value into I, right? So after this you are going to write like this: if I equal to 0, then you are going to write something here, and if I is not equal to 0, we are going to write something here. This is how generally the structure of a program which is using fork look like. Now I told you that fork is going to create two processes, one is parent and other is child. Actually it will create only one more process. Already one process is existing, one more process will be created. Now since both of them are identical twins, they should know who is parent and who is child. That is why the fork returns. So fork is going to return I equal to 0, fork is going to return a value 0 for the child process. Therefore if I put I equal to 0, the process which will execute this code will be child process, right? And the process which will execute this code will be parent process, right? See, in case if you are not understanding it, don't worry about it. This question will not be asked in GATE, but if you can understand this, it will make my threads topic easy. That's it. Even if you don't understand it also, you can listen to threads, that is fine, but it is interesting. Just see how it is being done. Okay, so now see this. So what is being done here? I have called the fork, and fork has created a new process. Now how can I distinguish which is parent and which is child? Because fork is going to return a value of 0 to the child process and is going to return a value of non-zero, right, to the parent. So what parent is going to get is process ID of child will be returned to the parent, and the child will be getting 0, right? Now whatever code you execute here, you write here, it will be executed by the child process, and whatever code you write here, it will be executed by the parent process. Generally what people will do is, here they will write the code in such a way that this entire body of the child will be replaced by some other program, and we will start executing that program, right? So for that purpose we are going to use one more system call, which is called as execve. This is the system call. If you are going to call this system call with a program, with some binary binary file, then this entire image is going to be replaced. Actually, a new program will be loaded into this area, and that new program will start executing, which means initially when child is created, that child will get the copy of the parent. But if you don't want the same thing to be done again, just like in case of this, if your program is not like a web server, then if you want to execute something else, then you can completely replace this process with some other thing, and then you can start executing it. Got it? So in general, how people will make use of this system is, if you want to perform if you want to execute something, then a parent will create a child, and this child code will be replaced by that particular program. And once this child is execution is over, it will write exit at the end. It will write exit, which means the child is over, and it will write exit, and it will return to the parent. Right? Now what parent will do is, till the child process is executing, in general it will try to wait for it. So it will try to wait on I. So where I is the process ID of the child. So this is in general what happens, how people make use of it. You need not see, it is not a compulsion that always when you create a child you have to run a different program, but in general most people use it for that things. For example, those who have used this Unix, those who have attended this Unix course in your college, you must be aware of this concept called as shell. C shell, Bourne shell, Conch shell, all these are shells developed by various people, right? So what is the main importance of the shell? When you start executing a shell, when you start running it, you are going to see a command prompt, isn't it? And when you type something on the command prompt, then that particular instruction is getting executed. For example, you might try to write cat, right? Or you might try to use the instruction ls, right? List all the files in the directory -l, something like this. Now these are the commands which you are going to give to the shell, right? First you will start executing the shell, and then you are going to type something in the command prompt, and that particular instruction will be executed. What is the concept behind it? Simple. So initially your shell will be running as a process, and whenever you give a new command at the shell, our shell internally will call the function, the system call fork, which will create a new process, and that will actually be containing the same thing as the shell, but then it will use the execute instruction in the child code by like this here, right? It will use the execute instruction in the child code, and then it will execute this one, right? And parent will wait for child, and child will actually execute this binary code ls-l, and the binary code for this ls has to be present in the default directory where you can go and search it. Got it? And after everything is done by the child will exit, which means it will display all the results and it will exit, and then your parent will continue. Got it? So okay, whatever I told you, I just wanted to give you a brief overview. Actually, talking about Unix and Linux is actually a course in itself. Like, it is a very big course, just like operating systems, but we don't have that course in the syllabus. Maybe I'll do it as a separate course later if possible, but I'm not going to promise you anything. Later, if I have time, I'll do that. But for now, you try to understand all this. Everything I discussed here is to make one point clear. If you want to perform parallel execution of the same thing, using the fork and execute, or using the fork call, is actually not very useful. The reason is, yes, it is useful, but it is going to incur some penalty. What is it? Whenever you want to create a new process, you are supposed to execute the fork system call, and that involves context switching as well as change from the user mode to system mode. And whenever we go into that system mode or super user mode, then it is obviously going to be costly, right? So we need an alternative in which we don't actually change the mode from user mode to system mode, right? But then we want our work done efficiently. So that is where threads are going to be very useful. Okay, in the next video we are going to discuss about the threads. Okay, fine. Now before discussing about threads, let's see what has happened with these processes. Okay, so when we have seen that, one thing is clear. Whenever you want this parallelism, we are going to go for multi-programming. So multi-programming is a concept in which we have only one CPU, but then we'll be able to perform many tasks at the same time. I mean, it appears as if many tasks are being performed at the same time because we are having many processes and all these processes will be switched. So one process will execute for some time and then next one and then next one in a round robin fashion, right? So till now only type of parallelism we are able to get is through the use of multi-programming, right? But then the multi-programming has got some disadvantages. The disadvantage is like whenever you want to switch from one process to the other process, because you have only one CPU, it is going to incur some cost because of the context switch. Therefore multi-programming is an expensive task, right? But then multi-programming has an advantage that each process can perform something individually. But what if our need is we don't want to perform some independent tasks, we want to perform the same task over and again. For example, we have seen something called web server. In web server, everyone will ask for the same web page, right? Therefore the code required to service a client is actually the same, even if it is client 1, client 2 or client 1000, right? So in that case, going with multi-programming, right, is a disadvantage because we don't have different tasks, we have the same task and the same code. If you are going for multi-programming by using various processes to service various clients, then you have to create a process in which the same code will be there. Okay, listen to this, I'll just show you here. Now assume that there is a web server running, okay, and this web server is a process, and if you look at this process in the memory, it will have all this, right? So one is the code and other is the data, right? And we know the other parts, one is stack, other is heap. So apart from this is what will be present, these are all will be present in the memory. Apart from this, the process will also get, in case if it is opening any files, it will also get something called as file descriptors. So what is a file descriptor? It is a programming language terminology. Generally file descriptors are used to access a file. So once you open a file, then you are going to get the file descriptor. Generally every process will have certain files open, right? And then apart from this, apart from whatever I have shown here, you are going to have something called as resources which will be allocated while it is running at the CPU. So one such resource you can think of it as register files, right? Register file means the register set that you are going to get. Got it? So everything is applicable for one process. Now when we are going to create and also we are going to have program counter, isn't it? So these two are something which will be allocated for a process, and these will be used while running. If the process is not running, these things will be saved in something called as context of the process. And if you want to run a process, you are supposed to load these things into the CPU registers as well as CPU program counter. That is what we know about the context switching. We already discussed about it, right? So whenever a process is running, the next instruction will be pointed by the program counter, and whatever registers it is using, they all will be present in the register file, right? In case if it is not running, you are supposed to save all this at some place so that later we can get it and run. Got it? So anyway, these are also associated with the process. Got it? When it is running. Now let us say this is a web server whose purpose is to service a client whenever he needs some web page. Let us say it is currently processing one request, which means it is sending the web page to a client. At the same time, if some other client comes and asks for this service, then it will not be able to provide this service. Then what are the various alternatives we have? One good alternative is create a child process and then assign the work to the child process, right? Therefore, if this web server uses fork system call in order to create a child process, the child process will also be exactly same as the web server, but this is a parent and this is the child, right? Both will be having different process IDs. Now whenever you create it, exactly the same memory image will be created as I told you earlier, right? So what will the memory image contain? One is the code, right? And the other one is the data, and the other one is stack and heap, right? And the other one is whatever files are open here, you are going to get the same files, and associated with this will be register set and the program counter, right? And the program counter initially when it is created, both will be having the same value, right? And also register files will also be having the same value. Now if you observe it, if you clearly observe it, this part is same, isn't it? The data and the code section are exactly the same. Now if we want to execute the same code, why do you want to have two copies? And second thing is, whenever you want to switch between these two processes, context switching is required, which is very expensive. Got it? So what are the disadvantages of this? If you are looking at this multi-programming using processes by creating new process for any new request, the problem is that it is expensive because of the context switching, and then resources are also wasted. See this, same files are opened, same file descriptors will be again copied, and even the same data, same code will be present, and these will also be same, but later they will change anyway, but initially they will be same. So everything is exactly the same. So one thing is, CPU wise it is expensive because context switching is required, and memory wise it is expensive because memory is unnecessarily wasted to store the same code and same data two times, right? So this problem is being solved by using the threads. Now let's discuss about the threads. So whenever we talk about a thread, instead of using the name process, we use the name task. A task is nothing but certain amount of work that we want to achieve, and we are trying to achieve it using multiple threads. Okay, so this is probably the first time you are talking about or you are listening about threads, so just be careful. I'll discuss what it is. Now initially when you start a task, it will have only one thread. Okay, now let us say this is a web server task. So if someone has to be served, if a client has to be served, then what is that we are going to do is, we will be running one thread, and this thread will be servicing this client. Now exactly like a process, this will have the same thing. One is code and other is data, and the other thing is we have the heap data as well. Okay, but then what happens is, every thread will have its own copy of stack, right? And also data as well as heap will be there, which will be shared. So this code and data section will only be once, right? So it will have its own copy of the stack and its own copy of the register set and its own copy of the program counter. Now suddenly if someone else asks for a new request, then instead of creating a new process like in that method, we'll try to create a new thread. Now the advantage of this, let us say we are talking about user level threads. So there are two types of threads. One is user level threads and the other one is kernel level threads. We shall discuss about the difference between user level threads and kernel level threads later. But for now, let us discuss about the difference between the processes and the threads first. In this case, we are talking about user level threads. Now what happens is, if we get suddenly, see, one request is currently being processed. We got a request and that is being processed by a thread. Okay, what is a thread? A thread is nothing but a sequence of execution, right? So you can consider a process, in this case this process, as a task with a single thread. Got it? So what is a thread? A thread is nothing but a sequence of execution. That's it. And sometimes thread is also called as lightweight process. Lightweight process means it is not as heavy as a process. Okay, so actually it will contain everything that a process has, but it is not that heavy. That heavy means if you see this, every process will have its own copies, but threads will be sharing it, as I will show you. Now assume that when client 1 is being serviced by this thread, let us say client 1 is being serviced, we got a request from client 2 for the web page. Then in general, if you don't have this threads execution, if you have only web server, right, let us say you have only one web server and we are not even creating the child, then what happens is we have to wait until this entire request gets fulfilled, then only we can take the next request. But in case of multi-threading, the user can create a new thread, right? So mark my words, the user is creating the new thread. That is why it is called as user level threads. In this case, if you have to create a new process, you have to call the system call, and therefore our operating system will create a new process. That is why it is expensive, because operating system is involved. It is cheap because operating system is not involved and user is actually creating the new process, right? Therefore, new thread. So one more new thread will be created, and it will have its own stack, it will have its own register set, and it will have its own program counter. Now having two different program counters will enable the thread to remember where it has stopped earlier, right? Now what we do is, for some time this process will run this thread. Let's call it as a task. For some time this task will run this thread, and then it will switch to the next thread. Now again, for creating the thread, we are not calling the operating system, and also from switching from one thread to the next thread, we are not calling the operating system. Therefore it is very inexpensive. So just like a process, a thread will have all the states, right? So new state, ready state, running state, block state, as well as terminated state. Everything is same as a process, but only thing is all the resources are shared. So data will not be unnecessarily copied two times. Code will not be unnecessarily copied two times. You can create any number of threads and all of them will be sharing everything, including files and signals. Files will also be shared, right? So that is the advantage of the threads. So what is the main difference between the process and user level threads is, you can think of it like this. Let us say we are using the processes using fork call, right? So instead of, whenever we want to do multi programming, we are going to use this, right? So if you want to achieve the parallelism using the processes, we are going to use fork, right? And the other one is threads. So in this case we are talking about user level threads, right? So what is the main difference between these two? We shall see it. So one difference is clear. So in this case, system calls are involved. So system calls are involved for creating a process, isn't it? fork is involved, and in this case no system call, right? And in this case, if you have to switch from one process to the other process, context switching is required, right? So in this case, no context switching is required. So simply register set switch. So register set switch. So in most of the cases, even this register set is going to contain the program counter as well. That is why I am not saying program counter switch also. If you change the registers, program counter is also a register which is a part of the register set file. You can include it there. And now register set will contain something called as stack pointer, which will point to a new stack. Therefore you need not switch the stacks explicitly. Once you switch the registers, automatically stack will change and program counter will change, right? Therefore it is cheaper, isn't it? So what can you say about this? This is expensive, this is cheap, and this is expensive, and this is cheaper. Got it? And if you see it, even at the memory level, right? So different copies, of code and data section are required here, right? But here we have same copies of code and data, right? So now we are having only the same copy of code and data here, right? But then here we are having different copies of code and data. But then there is a problem here, right? So it is not a problem, you can think of it this way. See, here whenever all the threads are executing or using the same address space, then what happens is every thread will have the access to other threads stack as well as to the data as well as to the code. Therefore we might get some synchronization issues. So in threads, if you have to share some data, or if you want to use the same code, then we might have to use something called as critical section, isn't it, or locks. So critical section or locks are required in case if your threads are going to share it. But in this case, if you want to share information, if you want to enable inter-process communication, here also we don't have any other option. We have to use critical section and the locks. That is why I am not writing it as a difference, because either in threads or in processes, both the critical section and locks concepts will be required if they want to communicate. But then one advantage you have in having different processes, one process will not be able to change the stack of the other process. Both are completely independent, there will be no interference at all. But then here if you observe it, one thread can access the stack of the other thread, right? It looks like it is a problem, but then it is not a problem, because we don't have to provide any protection, because both these threads are actually created by the same user, and the user is going to have control over how a thread is going to execute. Why will a user, when he created two threads, will write the code in such a way that one thread will corrupt the other? Therefore no protection is required here. Therefore it is not at all an issue. So if you see anything, there will be only advantages in threads compared to the processes, right? So this is why we need threads compared to the processes. So there are some disadvantages as well. So when you look at this user level threads, there is a disadvantage. Sometimes what happens is, let us say this particular thread wants the hard disk, and so it has called the operating system, some system call related to hard disk, and then that system call has blocked this thread, right? See, now for a operating system, it doesn't know that it is a task and it is having these many threads right? So all these threads are being created by the user library at the user level. Therefore our operating system, the kernel, is unaware of this threads concept because it is implemented at the user level. Now for a operating system, this entire thread might look like, this entire task containing many threads might look like a single process, right? And assume that this particular thread, it wants some service from the operating system. Let us say in this case it is asking for the hard disk. Then this thread will make a request for the system call, through system call to the operating system, asking for the hard disk. Let us say hard disk is not available now. Then operating system will block this particular thread till hard disk becomes available, right? But the problem is, whenever this particular thread is blocked, according to operating system, it is not a thread, this is the entire process. So even when one thread gets blocked in the user level threads, the entire process will get blocked. But if you look at these two processes, if one process gets blocked, the other process can execute, because to the operating system they are two different processes. Therefore it can schedule the other process even if one process is blocked. But here to the operating system it is a single process, it is unaware of the threads, right? And so what happens is, as I told you, one thread, if it gets blocked, the entire process will get blocked. That is a disadvantage. Therefore the parallelism may be affected in case of threads sometimes whenever there is a blocking system call, and this one can be rectified by using kernel level threads, right? So what is kernel level thread is, instead of asking a user to create the threads and then switch between the threads, we'll ask the operating system to create the thread and switch between the threads. But then it is going to introduce its own set of problems. What is it? For every creation we have to again call the operating system, right? Okay, so that is called as kernel level thread. And also if you see, when you are having three different threads executing, if the operating system sees it as a single process, it will not give it 3 time slots. It will give it the same time as the time given for a process, right? Let us say one process is having 100 threads and other process is a simple process which is having only one thread. Now if these are user level threads, then according to the kernel, it will treat both of them equally and it will give the same time for executing this one as well as this one, right? In case of user level threads, that is why we know there is a concept called as kernel level threads, in which these problems have been eliminated. Now we shall see what that kernel level thread is and what is the difference between user level and kernel level thread. Okay, we have seen that there are two problems with user level threads. So one problem is, let's say problems or disadvantages. Okay, problems, there are two problems with this user level threads. So what are the problems? Blocking system calls. So what is blocking system call? If you make a call, let us say if you want a hard disk and if the hard disk is currently being used by someone else, then you have to be blocked until that hard disk is going to be available. So in order to access the hard disk, you are going to make a system call, and therefore that particular system call is going to block you, right? So a process will be blocked because of the system call in case if the service that you requested is not available. Once it gets available, you will be unblocked, right? So blocking system calls in case of user level threads will block the whole task. So what is the meaning of this? Let us say we have a task, and in this task let us assume that we have many threads going on. Now even if one thread asks for a system call, if this leads to blocking, right, actually only this thread has to be blocked, but what happens is the entire task will get blocked. That is the problem with this. Now, because of which you can clearly see that even though the other threads have no problem, they also are going to suffer because of this particular block, right? That is the disadvantage of user level thread. That is one disadvantage. And the other disadvantage is unfair scheduling. So let us say there is a task which is having 100 threads, and there is one more task which is having only one thread. Now if you use user level threads, our operating system will not know how many threads are executing in your process. For the operating system, it is just a process and it is just another process, right? So it will give 1 millisecond for this process, and I'm just assuming it, okay? In case if you are using a time quantum of 1 millisecond in round robin, then this process will get 1 millisecond and the other process will also get 1 millisecond, right? But the fair thing to do would be giving 100 milliseconds for this and 1 millisecond for this. That is the fair thing to do. But then without knowing it, our operating system will just give 1 millisecond for this and 1 millisecond for this. Now this 1 milliseconds have to be shared between 100 threads. Then first time this one will get the chance, and again this one will get the chance. Second time this one will get the chance, and again this one will get the chance, which means by the time each thread here gets a chance, this thread will be getting 100 times the chance to execute, right? Which means this thread will be getting 100 times faster and these will be slow, right? So in order to overcome from this disadvantage, the only solution is to let the kernel know that we are having threads, and to let the kernel know that it is only one thread which is getting blocked and you can schedule the other threads. So for this reason, we are going to use this solution called as kernel level threads. So in kernel level threads, what happens is whenever a process, generally the task, whenever it starts, it is going to start with one thread, and whenever it wants to create the next thread, right, this thread has to make a system call, and this system call is used to create the next thread. Therefore, exactly like how we create a new process, a new thread will be created. Got it? A new thread will be created by whom? By the kernel, right? Therefore, kernel is actually involved in the thread creation, and so kernel knows what is the thread that is created, and so kernel knows how many threads are there in the task, right? So now what happens is, assume that later at some point of time this particular thread makes a system call and then it gets blocked. Now even though this thread gets blocked, you are not going to block the entire task. You are going to block only this thread, and this one will be scheduled, right? Therefore, it is easy in this case to attain parallelism. We are letting know the kernel that we are having multiple threads. Got it? And so this problem has been fixed. What is the problem? Blocking system calls will block the whole task. Okay. But here, one blocking system call will block only single thread, not the whole task. And also the second problem can be solved. So what is the second problem? Unfair scheduling. Now if the kernel has created the threads, and if it knows that there are 100 threads in this task and only one thread in this task, then kernel will appropriately schedule the thread. Instead of scheduling the process like in this case, it will schedule the threads, which means each thread will now get equal amount of time. For example, this one will get 1 millisecond, 1 millisecond, 1 millisecond, and this one will get 1 millisecond. Therefore, as a whole, a task which is having 100 threads will get 100 milliseconds, and this one will get 1 millisecond. Therefore, it is a fair scheduling, right? But then what is the disadvantage of this method? So what are the problems in kernel level threads? Problems in kernel level threads. So it is very clear that while creating a thread, we are actually involving a system call. Therefore, it is expensive compared to user level thread, isn't it? Expensive compared to user level thread, but then it is slightly lower expense, right? Its expensive slightly lower compared to the creation of the process. So if you see a creation of the process, when you are trying to create a new process, let us say this is one process, and if you are trying to create a new process, you have to actually create everything, right? Therefore it is more expensive. But if you are trying to create a new thread, you are not actually creating everything, you are just sharing most of the things. Therefore if you look at the expense, creating processes is more expensive compared to creating kernel level threads, and creating kernel level threads is more expensive compared to creating user level threads, because user level threads are created by the user library without any system calls. Both of these are going to get system calls, but this is a heavyweight process, it is a lightweight process, therefore the cost is less here compared to this. Got it? So expensive compared to user level threads for creation, isn't it? And what is the second problem? The second problem is switching is not done without a system call. So switching a thread here requires context switch, right? So switching a thread, kernel level thread, requires system call again, right? Now what happens is, just like the switching the processes, when we switch the thread, you have to call the operating system. So operating system call has to be required, system call has to be required. Then what happens is, your kernel will get into the picture and it will try to change the context. But anyway, the context switching is very simple, because only registers have to be changed, everything is similar, right? So anyway, again, switching is also expensive compared to user level threads, but comparatively less expensive, when you compare it with the process switching, right? So both the approaches, user level threads as well as kernel level threads, are having some disadvantages, but they are better compared to using multi-programming or more processes for doing the same task, right? See, overall threads are performing well compared to the process if you have to do only one particular task like web server, right? But then the problem with the threads is, there are certain problems like this, right? And both the types of threads, either the kernel level threads or user level threads, are having these problems. And so many some of the operating systems, they go with a hybrid threads, which means they are combining the concepts of kernel level thread and the user level thread, and they are calling it as the hybrid threads. We shall see about the hybrid threads example now. Okay, fine.